Hello friend, this is Said Mohammad Wakas. Today I'm going to discuss about MEP design calculation. So first of all, I'm going to discuss about firefighting system design calculation, then plumbing design calculation, and then HVAC design calculation. So it's going to be a very long training session, about 13 hours. So first of all, I'm going to discuss about firefighting system design calculation. So these two topics will be covered in this video, and the last three topics, foam system design calculation, head loss calculation for fire hydrant system, and fire pump head calculation will be covered in the future. So after that we have plumbing design calculation, and if you see here there are total 11 topics covered in this video, and the remaining 3 topics will be covered in the future. And then we have HVAC design calculation. You can see here there are total 27 topics. Among that, 25 topics will be covered in this video, and remaining 2 topics, that is swimming pool dehumidification calculation using spreadsheet and smoke management system, these topics will be covered in the future. So if you continue with the videos, you will see there will be a lot of spreadsheets and softwares I have used in the training session. If any one of you interested in buying those spreadsheet softwares, you can simply join the channel membership and get access to those spreadsheets, drawings, and there are other materials available like MEP general notes, drawings, MEP work method statements, MEP books. So all you need to do, you have to go to the channel, you just have to click this join button. So once you click this join button, you can see there are total 5 levels here on the membership. For membership, first is MEP design calculation, then MEP drawings and work method statement, then MEP design softwares, and MEP design Excel sheets, and then you have complete MEP material. So once you click this each level, you can see the detail of each level, like what you will get at that particular level. In some countries this YouTube channel membership is not available. In that case, you just have to send an email on the mentioned email address here. If you go to the about section, and you will see the email, so you have to send an email on this address if you don't have the join channel button, because in some countries the YouTube channel membership is not available. So let's get started. Hello guys, this is Sayyid Mohammad Wakas. The topic which I am going to discuss today is related to the sprinkler system hydraulic calculation. So as you can see that there I have prepared an Excel sheet for sprinkler system hydraulic calculation. And so this is the drawing which I am going to use for sprinkler system hydraulic calculation. And here are the tables and charts which I am going to use during calculation. So first of all, you have to understand the drawing, and then we can start the hydraulic calculation. As you can see that this is the dining room area drawing which I have in here. You can see that we have total 8 sprinklers in here. The blue dots representing the sprinklers, 1 2 3 4 5 6 7 8. So we are gonna perform the hydraulic calculation for this dining room area. So you can see the distance between the sprinklers is mentioned in here, and these are the branch lines, and this one is the cross main in here. So we have to calculate up till this point. So I'm going to do hydraulics up till this point. So you can see that I have divided drawing into different sections, that is 101, 102, 3, 4, 1T and 3T. So you can see the different sections on the drawing. Just for easiness, we have divided this drawing into different sections. So let's move back to our calculation sheet. So you can see that I have write the sections in here: nozzle identification and location, and then we have a flow rate column, pipe size column, and pipe fitting summary, then equivalent length, pressure loss in psi and bar, then we required pressure, and then the formula which we used in here. So first of all, whenever you are performing the hydraulic calculation, you have to check the space So what kind of space is this? According to that, you have to select the fire hazard occupancy. So the space in here in the drawing is the dining room. So it's covered in the light hazard occupancy. So I have used the light hazard occupancy as per NAFPA 13 standard. You have to select the occupancy hazard, whether it is light hazard, it is ordinary or extra hazard. You can see here in the chart light hazard, ordinary or extra hazard group. So according to that you have to select. So I have select this light hazard. So first of all you have to do is you have to calculate the flow rate across each sprinkler. You can see in here. So how did I get this flow rate across each sprinkler, that is 15.5 GPM. So first of all you have to get the area covered by each sprinkler. For light hazard occupancy, the area covered by each sprinkler you have to check from NAFPA 13 standard. So I took 155 square feet as per NAFPA 13 standard per sprinkler. This is the coverage area, and this point 1 is the density. So you need to multiply area with the density to get the flow rate across each sprinkler. So how did I get this 0.1 density? Let's move back to our chart. This is the density chart. On x-axis you can see that density is in GPM per square feet. Y-axis we have area of the sprinkler operation in a square feet. So since we said that we have ordinary hazard group, so you can see that the minimum area of sprinkler operation is 1500 square feet. At this minimum area we have minimum density is 0.1 GPM per square feet for this ordinary hazard group. So that's how we have selected 0.1 GPM per square feet. So we have used 0.1 GPM per square feet multiply with 155 is the area covered by each sprinkler. So total flow rate across each sprinkler is 15.5 GPM. This is basically our small q which we have to use in here. So what is small q and what is capital Q? Small q is basically the flow rate across each sprinkler, and capital Q is basically the total flow rate. So at this point we have small q and capital Q both are equal because we are starting from this point. So one more thing, first of all you have to select the most remote hydraulically sprinkler, or the sprinkler that is farthest away from the source of supply, the most remote outlet from the source of supply. So we are going to start our calculation from this point. So at this point small q and capital Q both are equal, that we already calculated 15.5 GPM. So we have to use here 15.5 GPM. Small q and capital Q already applied the conversion factor, so it's converted this into liters per minute flow rate. So this Q I have used 15.5. This is the flow rate across each sprinkler, and this is nozzle identification and location from 102 to 101. You can see that from this 102 to 101 we have one sprinkler in here. So we can go in here and write the GPM, and then we have to write the pipe size. So nominal diameter of in the drawing, if you see that it's 1 inches. So we have write nominal diameter 1 inches, but we have to write the actual internal diameter over here. So for 1 inch pipe size, actual internal diameter is 1.049. So we have to write actual internal diameter because when we are using the equation we have to use the actual internal diameter instead of this nominal diameter. So fittings, as you can see, this is a straight pipe. There are no fittings included in this one from 102 to 101, so it's not applicable. So now we have to write the length, straight pipe length. If you want to check, you can check in here. So one thing over here, the distance between the sprinklers on the branch line, this is the branch line, distance between the sprinklers is not as per NAFPA 13 standard. So let me write this as per NAFPA 13 standard. If you remember my video on how to place the sprinklers in Revit as per NAFPA 13 standard, there I have used S and L rule to show you how you can place sprinklers as per NEPA 13 standard. So I'm going to apply the same rule to get the distance between the sprinklers on the branch lines. So as you can see that this 35 feet 11 into 1 by 2 inches is the width of this dining room. So let me convert this into feet. So 11 1 by 2 means 23 divided by 2, 11.5 inches. If you want to convert this into feet, that is 0.95 feet plus 35. So width is 35.95 feet. So what is NEPA 13 standard says, we have to keep this distance between sprinklers is 2 times compared to the distance from the wall to the first sprinkler. So that means we have to keep this distance 2 times, this distance 2 times, this is 2 times, this is 1, and this is 1. So total 2, 4, 6, 7 and 8. So we need to divide this figure by 8. That means each uh, dimension will be 4.5 feet. So since we said that we need to keep this distance twice between the sprinklers, and this distance is half from the wall to the first sprinkler, this distance should be half of the distance between two sprinklers. This is SL rule. So if you see that this is one dimension, you need to multiply with 2. That means 8.99 feet is the distance between this sprinkler to this, then 8.99 between these two, and 8.99 between these two. So I'm gonna write the distance for this section 102 to 101, that is 8.99 feet. 8.99 feet. So 2.74 meter. If I convert this into meter, it will be 2.74 meters. Already applied the conversion factor in here. So since we don't have any fittings in here, you can see that this is just a straight piece of pipe. So this is 0, and total equivalent length will be the sum of straight and fittings. So we can write equal to sum, or instead of this we can write equal to this plus this. So total equivalent length is 8.99 feet and 2.74 meters. So now we have to calculate the pressure across that sprinkler. But before that I have to go back in here and let's define the distances as per NEPA 13 standards. So you can see that this distance is 8.98, this is 8.98, this is 8.98. So we need to multiply with 3, that is 26.96, and we know that total width of the room is 35.95. So we will minus this one. So we are left with 8.98. So we are left with 8.98 means 1 time this distance and 1 time this distance divided by 2. That means 4.5 feet. 4.5 feet is the distance from the wall to the first sprinkler. So we can write directly the distance between the sprinkler. This is 103 to 102 is 8.9 straight pipe. This is again 8.95. Then 1T to 104, that is 4.5 feet. This is just calculated here, 4.5. So now we are going to calculate the required pressure across that sprinkler having 15.5 GPM. So this is the formula which we are going to use. PT is equal to Q divided by K whole square. So here Q is 15.5 and K is basically our constant factor for the sprinkler. And how you will gonna get this value? This value you have to get from the supplier, the one who supplied you the sprinklers. So you have to check their technical data sheets, their manuals to get this value. So it depends on supplier to supplier. So let's say we got 5.3 sprinkler K value. So I'm gonna use 5.3 in here, and C is basically the pipe roughness. It depends on material to material. So since we have used galvanized steel pipe in here, so its roughness is 120. So there I have a hydraulic calculator. You can see that C value of the different material is given in here. You can see that this is for galvanized steel, this is for mild steel, this is for copper is 140, mild steel is 120, stainless steel is 140. So since we have used galvanized steel, I'm going to select galvanized steel in here, and C factor is 120. You can see, so that's how I select C is 120. So now I'm going to put the values. Q is 15.5 and K is 5.3. So 15.5 divided by 5.3, if we take the square of this one, that is 8.55 or 8.56 psi. So this is psi, 8.56 psi, 8.56 psi. If you want to convert this into bar, you just need to multiply this 8.56 with 0.068, 0.0689. You will get this value in bar, 0.59 bar, 0.59 bar. So now this is a calculated pressure across sprinkler. So we have to write in here, it's 0.59 bar. Already applied the conversion factor, so we get this value in psi. You can see that 8.56, 8.56. Since there is no change in elevation at this point, PE is basically pressure loss due to change in elevation. There is no change in elevation at this point, so we can write this one 0 bar, that means 0 psi. And PF is basically the pressure loss due to the pipe friction. So this is the hydraulic calculator which I'm gonna use. As you can see that this is the Hazen-Williams equation which I'm gonna use in here to calculate this PF, friction loss or pressure loss. So what is the size in here? Pipe size is 1.049. We have to use actual internal diameter. So 1.49 means in mm it will be 26.64 mm. 26.64 mm. And the flow rate, if you see that total flow rate is 15.5. C factor is already selected, and the length which we used in here, total equivalent length is 2.74 meter. You can see here this one, 2.74 meters, 2.74 meters. So just calculate and it will give you the total pressure loss is 0.005 bar. Sorry, one thing, this flow rate is in liters per minute, and this one we have used in GPM, so this is the liter per minute, 58.7. So 58.7 we have to use in here and then calculate. 2.74 is there. So you can see that total pressure loss is 0.049 bar, 0.049 bar. So we have to write in here 0.049 bar. So this is already calculated into psi. So this is the total pressure, and if we have to calculate the bar per meter pressure loss, so it is very simple. You just need to divide this total pressure in a bar divided by total length. You will get in bar per meter. Same way you need to divide this if you getting in psi per foot. So you need to divide this required pressure divided by the total length in a feet. You will get psi per foot for this one. So now we are moving to the second section, 103 to 102. You can see that 103 to 102 we have this sprinkler in here, and pipe size, if you see that this is 1/4. Pipe size is 1/4 over here. So we have pipe size 1/4 in here. So 1/4 means if you check the internal diameter of this that is 1.38. If go back to our tables and charts, so 1/4 for schedule 40 pipe, normally inside diameter, if you check that, it is 1.38 inches, 1.38 inches. So we have to write 1.38 inches in here, and there is no fitting in here. It's a straight piece of pipe, so no fitting. So now we have to get the value of the Q first. How we will get this Q value? You have to use this formula. Q is equal to K square root of P. So K, we know that 5.3 is the sprinkler constant, and then square root of P we have to use in here, and P is the total we have to use, that is 9.27. 9.27, and this is basically sum of these three in psi. If you want to get this in bar, same thing you have to do, equal to sum. So you will get 0.64 bar, and total pressure is 9.27 at this point. So we use 9.27 pressure and 5.3 GPM. So let's check. 9.27 square root into 5.3, we'll get 16.14 GPM. 16.14 GPM. The same Q we have to use in here, 16.14. And then how we'll get the capital Q? Capital Q is nothing but sum of these two, the previous one plus the one which we calculated now. So that means flow rate at this point is 31.6 GPM. 31.6 GPM means 119.8 liters per minute. So straight length pipe we already get, this is 8.99 feet. There is no fitting, so it's 0. Total equivalent length equal to straight pipe plus fitting, that is 8.99. So again there is no change in elevation, so we're gonna make it 0. And again we have to apply the Hazen-Williams equation by using this hydraulic calculator. So this time we have 1/4 diameter. So if you want to convert this into inches, that is internal diameter of 1.38 inches into mm, it will be 35.05 mm. So 35.05 mm. Flow rate is how much? Flow rate is 119.8 liters per minute. 119.8 liters per minute. And if you see that total equivalent length is same, 2.74, calculate. So total pressure loss is 0.049 bar. Again 0.049 bar. It will automatically convert to psi, then you can divide per unit length to get into psi per foot or bar per meter. So let's move back. Let's move to the third section, that is 104 to 103. If we move back to drawing, that is 104 to 103. So again we have length is 8.99 feet. Convert this into meter, and pipe size is again same, that is 1/4. So 104 to 103 we have this sprinkler, this one, and size is 1/4, that is equal to 1.38 inches internal diameter, and again no fittings, so 0. Total equivalent length equal to this one plus straight pipe plus fittings, 8.99. So again we have to calculate the Q first. So how you get this value is, again this is the sum of these three. So we'll do for the bar again, equal to sum these three. So you will get 0.69 bar total pressure in here and 9.98 psi. So Q is equal to K square root of P. To calculate the Q value, again K is 5.3. 5.3 cross square root of P. Total pressure you can see this is 9.98. So 9.98. So check this one is how much? 9.98 square root multiply 5.3, 16.74 GPM. 16.74 GPM. So you can write in here 16.74 GPM. So how you will get total Q again is equal to previous one plus the one which we calculated now. So capital Q is 48.4 GPM. So that means the flow at this point is 48.4 GPM. So now the flow rate is done. Since there is no change in elevation at this point, so we're gonna make it 0. There is no pressure loss due to change in elevation, that's why it's 0. Again we have to use this hydraulic calculator for Hazen-Williams formula, and this time we have again 1.38 inch means 135.05 mm, and flow rate is 183.1. C factor is constant for galvanized steel, and you can see that the length, total equivalent length is 8.99 feet, that means 2.74 meters. So 2.74 meters, calculate. So total pressure loss is 0.110 bar. 0.110 bar. So it will convert into PSI by using this conversion factor, and then again you have to divide this factor, this pressure in a bar, divided by total length in a meter to get the bar per meter, and you need to divide this required pressure in PSI with total length in a feet to get PSI per foot. So let's move further to section 1T to 104. So you can see that this point is 1T and this is 104. So again we have one sprinkler at this point. This is the fourth sprinkler. From 1T to 104 we have this sprinkler, and this distance we already write from this is there we have a T also. You can see that there's a T connection in here, and this distance we already know 4 feet and 5 inches. We already 4.5 feet we already write in here. So since we have 1T in here, that's why we write 1T in here. Pipe size is again 1/4. You can see in here pipe size is 1/4. So we write 1/4 in here, that is 1.38 inches internal diameter. And we have 1T in here, so we have to write the equivalent length for this T. So move back to our tables chart. This is the equivalent length for C equal to 120, the galvanized steel pipe, schedule 40. So you can see that 1/4 inches in here and T is here. So for T, 1/4 inch, this one, equivalent length is 6 feet. So we can write in here 6 feet. So it will automatically convert into meters, and then total equivalent length equal to this one plus straight pipe plus fitting, that is 10.5 feet or 3.2 meters. So now what we have to do is we have to calculate the Q again. Q is equal to K into square root of P. So K, we know that it's sprinkler constant 5.3 cross square root of P. So total pressure is again at this point is 11.57. So let's calculate this one. 11.57 square root multiply 5.3. So its GPM is 18.03 GPM. 18.03 GPM. So we have to write in here 18.03, and capital Q is again this previous one plus the one which we calculated now. So Q at this point 1T to 104, Q at this point is 66.4 GPM or 251.4 LPM, that is liters per minute. So we know that pipe size is 1.38 inches. So we can now we have to calculate the pressure in here. Just sum up this one to get the total pressure, equal to sum. So we have a change in elevation at this point. This is the cross main, and this is the branch line, and we have a change in elevation of 3 feet between the cross main and the branch line. There's a 3 feet change in elevation, so we have to write in here. So we know that if we want to convert this into head, so 1 psi is equal to 2.31 feet. So we can write if there's a 3 feet change in elevation, so 2.31 into 3, so head loss will be 6.93. So we can write there's a pressure loss due to the change in elevation of 3 feet is 6.93 psi. So if you want to convert this into bar, you just need to multiply with 0.0689 equal to this one into 0.0689. So that means 0.48 bar. So now we will calculate the last one, that is PF, using this hydraulic calculator. You can see size is again 1/4, okay, that is 35.05 mm, and flow rate is 251.4, and you can see the length, total equivalent length is 10.5 feet or 3.2 meters, 3.2 meter, and then calculate. Total pressure loss is 0.227 bar, 0.227 bar. 0.227 bar. So, or you can check one thing here directly. This is the pressure loss per meter of the pipe, that is 0.071, or you can just convert it and then calculate it accordingly. So this one is done. So next, total pressure will be the sum of these three. As you can see that the first one is 11.57, second is negative 6.93 plus 3.29. So total pressure at this point is 7.93 or 7.94. This is calculated in here, and this one is in the bar. We can just apply the formula to get the total pressure at this point, that is 0.55 bar. And at this point, so now we are at the second point of 3T to 1T. This is 3T and this is 1T. There is no change in elevation, so pressure loss due to the elevation is 0, so we can write 0 in here. And how we'll get the total pressure due to the pipe friction? As you can see that this point pipe diameter is 2 inches. You can see the pipe diameter is 2 inches in here in the drawing, and the distance between the branch lines, this is the branch line, this is the branch line, distance between branch line is 14 feet 11 inches. This is mentioned in here, and 2-inch pipe size, 14 feet 11 inches distance between branch lines. So 14 feet and 11 inches. If you want to convert this into feet, 11 inches means plus 14. That means 14.92 straight feet of pipe, 14.92. And then again we have T at this point again. From there to here we have a T again, this point. So we have to write T in here, this one, and the T for 2-inch diameter. Just check the tables and charts and check the equivalent length for T, 2 inches diameter. So T is 2 inches, 2 inches, T, that is 10 feet equivalent length. So we have to write 10 feet in here, and total equivalent length equal to this one plus straight 5 plus fitting equal to 24.92. So Last thing remaining in here is we have to calculate the PF, but before that we have to calculate the Q at this point. Since there is no sprinkler at this point, just a straight piece of pipe, as you can see that from 3T to 1T there is no sprinkler, so K factor is 0 at this point, so Q is equal to 0. So we can write small q 0 and capital Q will be same as this one, equal to this one, or we can write like this, equal to this one plus small q is 0. So 66.4 GPM or 251.4. So we have to calculate PF, that is the pressure loss due to the pipe friction, using this hydraulic calculator. At this point we have 2 inches, internal diameter is 2.067 into 25.4 to convert this into mm, so 52.5 mm. 52.5 mm, and you can see that GPM is flow rate is in 251.4, it's same, and equivalent length in the meters is 7.60 meters. 7.60 meters, just calculate. So total pressure loss is 0.076 bar. 0.076 bar. That means 1.1 psi. So again you just need to divide this by total length, you will get bar per meter, or you need to divide this psi divided by total feet, that is 24.92, get in psi per feet. So the last one remaining is here. So let's say our source of supply is far away from here, and I'm just writing a length which we don't know in here, so I'm gonna write 150 feet from the source of supply, straight pipe, and let's say we have this is 5T point and this is 3T point. We are talking about this one. So at this point we have to check the pressure also. So we are going to use this equation, we have to adjust the flow. So we are going to use this equation, Q adjust equal to QL into PH divided by PL, where QL is the flow across low pressure line, PH is the flow across high pressure line, and PH is the pressure across high pressure line, and PL is the pressure across low pressure line. And why are we doing this one? Because we did not accommodate the flow rate across these sprinklers. There must be some pressure, more pressure at this point due to these sprinklers, so we are adjusting the pressure at this point. So that's why we are using this formula. So Q adjust is equal to QL. QL, as I told you, is the flow across low pressure line. So this is the flow across low pressure line, this is for low pressure line, and this is for high pressure line. So flow across low pressure line 66.4, square root of flow, this is the pressure across high pressure line, and this is the pressure across low pressure line. So high pressure line, you can see the pressure is this one, this is the high pressure, say 9.04, 9.04, and PL is the pressure across low pressure line, is this one, this is the low pressure line, 7.94 psi, 7.94. So we'll just use this formula, 9.04 divided by 7.94, take square root of this one, multiply with 66.4, so you will get 70.85 GPM. 70.85 GPM. So you have to write small q is 70.85 and capital Q is equal to this one plus the one which we calculated now. So total GPM is 137.3 GPM and 519.6 liters per minute. So again the pipe size is 2 inches in here, so we have used 2-inch pipe size. So we don't know exactly how many elbows and T's up to the point of source of supply. So we just write it roughly that let's say we have 5 elbows and 3 T's from this point to the source of supply. So 3 T's and 5 elbows, and straight pipe length, let's say we got from this point to the source of supply is 150 feet. So we write 150 feet in here. So fittings length we have to write, we see that 2-inch we have 5 elbow and 3 T's. Let's go to table and charts. 2-inch 90-degree standard elbow or long turn elbow. I'm gonna use this 90-degree standard elbow, 2-inch, and its equivalent length is 5. So we have 5 elbows, means 5 into 5, 25 feet is for the elbows. And for T, if you see that 2-inch T is 10. So we have 3 T means 30 is for T's and 25 for elbows, 5 elbows. So total 55 feet. So total equivalent length equal to straight pipe length plus fittings length. Total equivalent length is 205 feet or 62.48 meters. So now we are going to calculate the PT in a bar. It's same as I calculated above, sum of these three values, and then there's no change in elevation, so I'm gonna write 0. And now I'm gonna use again hydraulic calculator or Hazen-Williams formula. So this is 2-inch again, 2.067 means 52.5 mm, and flow rate is how much? 519.6 lpm, 519.6 liters per minute. And length, if you see that total equivalent length is 62.48 meters, 62.48 meters. Calculate. So total pressure loss is 2.374 bar, 2.374 bar, 374 bar. So this one is in PSI, just apply the conversion in here. So again you just need to divide this pressure loss in a bar divided by equivalent length, you will get bar per meter. So for PSI is again same thing, you just need to divide PSI per foot, you have to divide this required pressure divided by total equivalent length in a feet to get PSI per foot. So if you see that the total pressure here is 3 bar, total pressure here is 3 bar or 43.47 psi, which we calculated in here, and total flow rate you can see that 137 GPM or 519.6 LPM, or you can say that 520 LPM. So this is how you can perform the sprinkler system hydraulic calculation. I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Don't forget to press the bell icon. Thank you. Bye bye. Hello friends, this is Syed Mohammad Waqas. The topic which I'm going to discuss today is related to FM200 system design calculation, and this is the Excel sheet which I'm going to use for FM200 system design calculation. So this is in the IP units and this is in the SI units. So what we do basically, we will calculate the weight of the FM200 gas required for this protected area. And the second thing, we will calculate the number of nozzles. You can see the discharge nozzles, number of nozzles required for this protected area. So we'll calculate this one by one. But before proceeding towards design calculation, let me explain you about FM200 system. like typical installation arrangement and how FM200 system works. So you can see the typical installation arrangement of FM200 system here. These are the cylinders installed here, in which FM200 gas is stored, and then we have extinguishing control panel in here, and then we have a alarm bell in here, and then we have a distribution piping. As you can see in here, this is the distribution piping, and these are the smoke detectors. You can see in here smoke detectors, and these are the discharge nozzles through which FM200 will be discharged. Now these discharge nozzle could be 1 port, 2 port, 4 port, 6 port, depending on the supplier or manufacturer. There are three different type of nozzles, discharge nozzles, which we can use here for FM200 system discharge. I will tell you later about this type of nozzles. So how FM200 system works: so each zone has their own smoke detector. As you can see here, we have smoke detector here and here and here, three smoke detectors. So basically we divide this into three zones. So this is the first zone, this is the second zone, this is the third zone. Each zone has their own smoke detector, and as per code requirement, maximum coverage area for each smoke detector is 250 square feet. That means this smoke detector coverage area is 250 square feet, and this one also 250 square feet. So in a case of fire, the smoke detector will detect the smoke and send the signal to the extinguishing control panel. So what will happen next is alarm will start ringing in case of fire, and then it will send a signal to the actuator, and but before sending a signal to the actuator, this ventilation system will be shut down, because ventilation system is interlocked with the fire system. Ventilation system will be shut down, and then a signal from extinguishing control panel will send to actuator, and it will discharge the FM200 into the protected area. So this is basically the protected area of IT server room, in which we are going to place this FM200 system. So I'm gonna use this Excel sheet for FM200 system design calculation, as well as this software or FM200 calculator for FM design calculation. So I'm gonna use Excel sheet as well as this software. So before proceeding towards the design calculation, I want to talk about the channel membership. So if you guys take the channel membership, you can avail the Excel sheets, MEP softwares, MEP books, drawings. So all you have to do is you have to just click this join button. So once you click this join button, you will have 5 perk levels. As you can see that this is the Excel sheets, this one is for the softwares, but includes 2 perks like MEP softwares and Excel. So after joining, you can see the instruction tab in order to get the Excel sheet or softwares. So level 3 has 3 perks, as you can see here: carry air conditioning system design handbook, MEP drawings, general notes, or MEP Excel sheets and software. So you can select whatever you need from that perks, and you can even see the more about these perks, or you can see the instruction tab for details. So same, we have level 4 and level 5. So you can select whatever level material you need, and for in order to get the access to the material, you just go to instruction tab to get the access to the material, or you can go to the about of this channel and you can send an email on that address to get access to the particular material. So let's proceed towards the design calculation. So let's proceed towards the design calculation of FM200 system. So first let me explain you the design basics, like which code we are going to follow for FM200 system design calculation. So basically we are following this NAFPA code 2001 for FM200 system design calculation, which is a standard on clean agent fire extinguishing system. This code we are going to follow. So first of all, you have to understand the fire classes before proceeding towards the calculation. So fire is divided into basically 3 classes: class A, class B, and class C. So class A, what we have, what material is included in class A? Materials like wood, cloth, paper, rubber and plastics, these are included in class A fire. Now class B fire, what materials are included? These include like liquids and gases, like fire inflammable liquids like oil, grease, tars, oil-based paints and flammable gases. These are included in class B fire. Now the class C fire, that involves energized electrical equipment like IT server rooms, electrical rooms, these are included in class C. So we are talking about this class C. We have this IT server room in which we are going to place this FM200 system. Now we have to check the design concentration of each fire hazard class. So as you can see in this formula, W is equal to V by S into C by 100 minus C, where C is FM200 agent volumetric design concentration. So it depends on fire hazard class. So design concentration for fire hazard class, which includes cloth, paper, rubber, plastic and wood, has C value of 6.7, and class B, which includes flammable liquids and flammable gases, has design concentration C value is represented by 8.97, and design concentration for class C, which includes energized electrical equipment like IT server rooms, has a design concentration of 7.2. So now we have to apply some safety factor for design concentration of each fire hazard class. So class A recommended safety factor is 1.2, which we have to apply here on design concentration in order to get the final design concentration. Class B safety factor is 1.3 and class C safety factor is 1.2. So now this is the main formula which we are going to use. So amount of the FM200 required to achieve the design concentration at specific temperature can be calculated by using this formula. W is equal to V by S into C by 100 minus C, where W is FM200 weight in lbs. Since we are using the IP unit, so it is in lbs. If you go in the other one, this one is in kgs. So V is basically the protected space volume in cubic feet. So this is the volume which we are going to protect by using FM200 system. So this is our protected volume, that is length into width divided by height, length into width into height. So we'll get the volume. So C is FM200 volumetric design concentration percentage by volume, which I already explained here, depends on the fire hazard class. And S is basically specific vapor volume in cubic feet per pounds, and S is calculated by formula S equal to 1.885 plus 0.0046 into T, where T is the minimum anticipated temperature of protected volume. So it is the minimum temperature we are going to use here in this space. So since this is IT server room, and minimum temperature which we are going to use over here is 70 degrees Fahrenheit, which we will use here later in calculation. So let's start the calculation. First of all, we have to calculate the volume of the protected space. So net volume of the protected space is calculated by length into width into height in cubic feet. So let's say we have length of this protected space IT server room is 35 and width is 28 and height is 13. So length into width into height will get the net volume of the protected space, which is equal to 12,740 cubic feet. So now we have to specify the hazard classification, what kind of fire hazard of this space. Since I said that this is an IT server room, so there's an electrical equipment installed in here. So if we go and see that class C is basically involving the energized electrical equipment, so we have to select class C over here because it involves the electrical equipments IT server room. So we have to select the hazard classification as class C. Now we have to specify the design concentration. Now we have to specify the design concentration for this fire hazard class. So design concentration for fire hazard class C is 7.2, which we have to select in here. So we'll specify here design concentration. So just select this one, 7.2. And safety factor for fire hazard class C is 1.2, which we already know here. So we have to apply safety factor 1.2. So the final design concentration, you need to multiply this design concentration with safety factor. You will get the final design concentration is 8.64. Basically this design concentration is varying from 7 to 15. So this is as per code requirement. So now we know design concentration. Now we have to specify the temperature. Since I said that we have to maintain the minimum temperature in the IT server room is 70 degrees Fahrenheit. So I'm going to use 70 degrees Fahrenheit here, and this specific vapor volume will be calculated by using this formula which I have shown here. So as soon as I put the 70 degrees Fahrenheit, the specific volume is calculated by using this formula, which is equal to 2.207 cubic feet per lb. So we know everything in this formula to calculate the weight of FM200 gas. So in order to put all the values in the formula, we will get the FM200 weight in lb. So by putting all the values in this formula, we calculate FM200 weight is 546 lbs. So now we know the weight of FM200 required for this protected space IT server room. So now we have to calculate the number of nozzles. How many number of nozzles we have to discharge nozzle we have to place in that protected area. So number of nozzles is calculated by formula protected area divided by coverage area per nozzle. So protected area is length into width. So length into width will get the area, protected area. So let's say the length is 35 and width is 28. So the protected area which is calculated 980 square feet. So now we know the protected area. Now we have to understand the coverage area per nozzle. So there are three type of nozzles which basically we use for discharge of FM200. First is 90 degree corner nozzle, second is 180 degree sidewall nozzle, and third is 360 degree radial nozzle. So you have to understand the coverage area per nozzle. So let me explain you the coverage area per nozzle. As you can see in here, this is our 90 degree corner nozzle, and there's only one port, discharge port, for discharge of FM200. And you can see that coverage area is 32 by 32. So 90 degree corner nozzle coverage area is 32 by 32, that is 1024 square feet, which is equal to 95 square meters. So you can see that coverage area for 90 degree is 1024. And these number of ports, it varies from supply to supply. Some suppliers has one port, some has two ports, some has three ports, depends on supply to supply. So now the second one, you see that 180 degree sidewall nozzle, it has two ports, and you can see the coverage area is 64 feet by 32 feet, which is equal to 2048 square feet, and in meters it will be 190 square meters coverage area. So you can see the coverage area for 180 degree sidewall nozzle is 2048, and coverage area for 360 degree radial nozzle, you can see in here 360 degree radial nozzle having a 4 port. Again, the number of ports depends on supplier to supplier. It could be 6 ports, could be 8 ports, depends on supplier to supplier. And the coverage area you can see here is 64 by 64 feet, that is equal to 4096 square feet, which is equal to 381 square meters. So this is how we get the coverage area for each nozzle. Since the nozzle which we are going to use in the IT server room is 90 degree corner nozzle, so we're going to follow this coverage area. So number of nozzle, I said you can calculate by formula protected area divided by coverage area per nozzle. So we know the protected area is 980 and coverage area for 90 degree corner nozzle is 1024. So number of nozzle required is 1. So this is how you can calculate the FM200 weight required for protected area and number of nozzles required for your protected area. So this is the sheet in SI units, you can see in here. Also we are going to use a software for this purpose as well. So this is the software which I'm going to use for the same FM200 gas quantity calculation. So since the So you can see the units in here. SI unit, IP unit, both are available. So I'm gonna calculate in IP unit format. We said that width is 28 feet, and we said that the length is 35 feet, and the height we said that it's 13 feet. So volume will be calculated. And then fire hazard class, we said that it's an IT server room. So IT server room is covered in electrical room. So if you go here, you can see the fire hazard classes, which I have already explained in here. So class C involves energized electrical equipment. So this is an energized electrical room, so we have to select class C in here. And FM200 design concentration percentage is 9. So this software accept minimum as 9. It will not accept less than 9. Since I said you that design concentration varies from 9 to 15 percentage, so it accept minimum 9. So minimum 9, and temperature we said that going to maintain is 70 degrees Fahrenheit. So the quantity of FM200 calculated is 699 lbs. So the one which we calculated in here is 546, because design concentration is 7.2. If I change this to 9 design concentration, then quantity of FM200 calculated is 699 lbs, which is same as calculated here through the software. So if you want to select the cylinder, number of cylinder, you can also select from supplier. It will give you a catalog like this, and based on your requirement you can select the cylinders in here. So this is how you can perform the design calculation for FM200 system. I hope you guys learned something from this video. For more videos, keep watching my channel, and don't forget to subscribe, and don't forget to press the bell icon. Thank you. Hello friends, this is Saeed Mohammad Wakas. The topic which I'm going to discuss today is related to hot water heater capacity calculation and selection. So the first sheet here is related to the individual hot water heater capacity calculation selection, and the second spreadsheet here is related to the central hot water heater capacity calculation and selection. You can see here. So individual hot water heater supplying hot water to single or multiple spaces without any recirculation system. But here we have a central hot water heater which is supplying hot water to multiple spaces within the building and have large capacity, and we have a hot water recirculation system as well. So therefore in this central hot water heating system, we will calculate the central hot water heater capacity, storage and capacity, as well as we will calculate the circulation pump flow as well as head. So the source of heat in the central hot water heating system could be solar, boiler, or heat pumps. So primary source of heat are these three which I mentioned here. Of course there will be a secondary source of heat would be attached to the storage tank, and that is electric power heater that is attached to the hot water storage tank. In case primary power is failed, there will be a secondary source of power will be there for hot water system, and that will be electric backup power heater. So let's get started with the first spreadsheet, that is individual hot water heater capacity calculation and selection. So as you can see here that the calculation will be according to the type of building and fixture unit method. So it is very important to select the type of the building here, because this table here, the demand mentioned here as well as demand factor and storage capacity factor, all of these are depending on type of the building which you select from here. There are several type of the building you can see here: apartment, club, gym, hotel, hospital, industrial, office building, private, residential, and many more in here. So it depends on what type of building you will select. If I select the gym, the demand will be changed, demand factor will be changed. You can see here demand factor, storage capacity, everything will be changed. Like if I select industrial, it will be changed as well, and if I select the private residential, it will be changed as well. So let's say I'm going to select individual hot water heater for an apartment here, apartment in the building. So first and this table is extracted from AHU Application Handbook Chapter 45 Table 9, this table. So this table means the demand, all of the demand mentioned here, the demand factor and storage capacity factors. So it depends on type of the building which you select here. So first step, you have to go to the drawing and you have to count the number of fixture needed hot water in your space. So you have to go and count the number of fixture need hot water. Let's say the fixture type and number of fixtures here. So let's say the lavatory which are private in the apartment. So the private lavatory we have two, and you have to check this from the drawing. So you have to check the bathtub. Let's say it's 1, dishwasher 1, foot basin 1, kitchen sink 1, laundry 1, and shower 2. So all you need to do is you have to put the values here in the quantity, and it will calculate the total gallons per hour GPH. So private lavatory, you can see here we have 2, and then we have bathtub 1, then we have dishwasher 1, foot basin 1, and then kitchen sink we have 1, laundry we have 1, and shower we have 2. So once I put all the values in here, it will calculate the gallons per hour for each fixture. So total is calculated in here, which is the sum of all the fixtures here. So total GPH is calculated 132 gallons per hour. So now we have to apply the demand factor in here. As I told you, this demand factor is depend on type of the building which you have selected in here. So for apartment it's 0.3, so you just need to multiply this demand with 0.3 demand factor and you will get probable maximum demand is 39.6. so heater recoil capacity is same as probable maximum demand, which is calculated in here, that is 39.6. now the storage capacity factor, this again depends on type of the building which you have selected here. Storage capacity factor, so storage tank capacity in the gallons we need to calculate in here. We simply multiply this probable maximum demand with this storage capacity factor. Here you can see that, and we will calculate the storage tank capacity in gallons. So needed storage tank capacity in gallons is 27.72 gallons. So if you need in liter, you simply need to apply the conversion factor and you will get the storage tank capacity in liters. So now we know the storage hot water heater storage tank capacity in liters, so we can select the hot water heater from the suppliers catalog. So you just have to go to the approved suppliers catalog, and then you will, let's say I have one here, that is Zenith water heater catalog. Let's say this is the approved catalog, which approved supplier catalog which I have in here. So I will select from this one. So as you can see here, these are the horizontal wall ceiling mount hot water heater, and these are the capacities you can see here. So we have 100, we have 100, 120. So these are available in the standard capacities, and the one which we calculated here is 105. So 120 is there, so we are going to select 120 liters capacity in here, and the standard power, if you see, is 2 kilowatt. So we'll select 120 liter capacity with 2 kilowatt power. So we have to write in here 120, which we select, and power is 2 kilowatt. So as I write in here, so water heater selection is done here. So selected hot heater storage capacity in liters is 120 and power is 2 kilowatt. So this is how you can do for the individual hot water heater system. So let's go to the central hot water heater calculation here. So same calculation will be made according to the type of the building and fixture unit methods. Here you have three things. First is the type of the building, second is the type of the pipe will be used, and the type of the means insulation, it's insulated or not insulated, you have to write here, and the type of the pipe. So again it depends on type of the building. These table values, this demand factors, and this capacity factor depends on type of the building which you select from here. So there are a lot of available here. If you select a hotel, this demand will be changed, as well as demand factor and storage capacity factor will be changed. So same for school, if you select the school or hospital, it will be changed as well. So let's say I'm going to select for office building, and pipe I'm going to use the hot water pipes is insulated or not insulated. This is very important to select in here, because this table, which is extracted from ASPE code, so here the values heat loss per foot of the pipe, it depends if you have pipes insulated or uninsulated. Insulated, if you have like fiberglass insulation, half-inch fiberglass insulation, you can select here the insulated. As I select insulated, the values will be changed. Depend on the if I have selected the insulated or non-insulated pipe. So let's say I am selected the non-insulated pipe. I don't apply any insulation. If you have insulation, you can select insulated pipe, and these table values will be changed accordingly. So again, you have a type of pipe used. So there are different pipes available here: schedule 40 steel, brass, and type K copper. So again, these values Q loss per foot of the pipe depends on the material which you select from the top. So it is important to select the correct material from here. So let's say I'm going to select for type K copper here, office building, non-insulated pipe. So if you have insulated pipe, you don't have to worry about if I have insulated pipe here, I don't have to worry about the type of the pipe which I'm going to use here. So let's move to the next step. Again, same thing. First of all, you have to write the number of fixture. You have to count the fixture from the drawing, and then you have to write the quantities in here. It will calculate the demand in gallons per hour. So let's say I have laboratories in the office building that are 15. Let's make this non-insulated. And laboratories, we have 15 in the office building, and we have a kitchen sink 10, we have pantries 10, and service sinks 10. So let's write the quantities here in the table. Again, the source is same, AHU Application Handbook for this table, chapter 45, table 9. So let's write the laboratories. For public laboratories, 15 laboratories we have. Then we have kitchen sink, we have 10, pantry sink we have 10, and service sink we have 10. So once I write all the quantities in here based on my drawing, so I will calculate the gallons per hour here, which is the sum of all the fixtures. So 590 here. So in order to get the probable maximum demand, I need to multiply this demand factor with this gallons per hour demand. So I will multiply 590 with 0.3. I will get the probable maximum demand is 177. So heat or coil capacity is same as the probable maximum demand, that is 177. Now the storage capacity factor is 2 for this office building. So storage capacity factor is 2. So storage tank capacity in gallons will be, you simply need to multiply this probable maximum demand with this storage capacity factor. You will get 354 gallons storage capacity for this office building. If you need to convert this into liters, simply apply the conversion factor. You will get the capacity in liters. So again, you have to go to the approved supplier catalogs and select this storage tank, hot water heater storage tank. So next step is I have to calculate the pump flow and the head for recirculation system, hot water recirculation system. So as I told you, this table is extracted from ASPE code table 17-1. It is important to compute the values to proceed for pump head and capacity calculation for recirculation system. So I have write all the pipes from the drawings in here, whatever I have used in the project for hot water system. So I have write in here. So piping length I have write in here from the drawing as well. Now this Q loss, that the heat loss per foot of the pipe, it depends on this pipe material is insulated or not, or type of the pipe which you have selected in here. So now we have to calculate the heat loss in BTUs per hour. Since this value is in meters, we need to convert this into foot, so that's why we have multiplied this with 3.28 in here in order to convert from meter to feet. And we just need to multiply this 80 into 3.28 into 15. We'll get the total loss in BTUs per hour. So same way you have to do for all the piping you have used in your project. So, and you have to calculate the heat loss in BTUs per hour for each piping length. So once you calculate for all the pipings in your project, you have to write total loss in BTUs per hour in here for hot water network, which is the sum from top to the bottom. See, that is, so we got total 67,174 BTUs per hour heat loss. So for each 10,000 BTUs per hour need 1 GPM. So we need to add 1 GPM for each 10,000 BTUs per hour. So we calculate here is 67,174 BTUs per hour. So required GPM for heat loss makeup pump will be total heat loss in the system, that is this value 67,174 divided by 10,000. So required GPM for the heat loss makeup pump will be 6.7 GPM. So this is the capacity. So now we have to calculate the pump head as well. For in order to calculate the pump head, we have to check the furthest pipe length for supply as well as return to get the pump head. And since we have a loss in the straight pipe length as well as the fitting, so we have to compute the loss for the straight pipe length as well as fittings to get the pump head. So in order to get the pump head, you need to 1.5 into uniform friction head loss, uniform friction loss into total piping length. Why I multiply this with 1.5? Let me tell you first uniform friction loss first, and then I will tell you 1.5 why I multiply with 1.5. It is recommended to use 4 foot per 100 foot to 6 foot per 100 foot uniform friction head loss. It is recommended. So if you have seen my previous videos, I have used the 4 foot per 100 foot uniform friction head loss. So same I have used in here, 4 foot per 100 foot of the uniform friction loss. And why I multiply this 1.5 to compute the losses for the straight pipe length and fittings. So if you don't know the friction loss for the fittings, it is a thumb rule to add 50% of the straight piping length of friction losses for the fittings. So 50% and 1, it will be 1.5 total. So that's why I multiply with 1.5. So 1.5 into 4 by 100 into total pipe length. So total pipe length, as I told you, it is the furthest pipe length supply and return from the source of supply to the furthest outlet. So from the drawing you have to check the furthest pipe length, and you have to write in here. I have write 70 and convert this into feet here as well. So pump head is equal to, calculated in here by adding or putting all the values in here, 1.5 into 4 divided by 100 into pipe length is 229.61. So after putting all the values, you get the pump head 13.8 feet head. If you want to convert this into PSI, just multiply with 0.433, you will get the pump head in PSI, that is 5.97 PSI. So now we can now we know the storage tank capacity for central hot water heater system is 354 gallons storage tank is needed. And hot water circulation pump selection is also done. The flow which we calculate here is 6.7 GPM, and the head which we have calculated here is 5.97 PSI. So this is how you can do the hot water heater capacity calculation, storage tank capacity calculation and selection. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe. Thank you. Hello guys, this is Said Mohammad Wakas. The topic which I'm going to discuss today is related to LPG tank sizing calculation and selection. So this is the spreadsheet which I'm going to use for this purpose. So first of all you have to go to the drawing. So as per drawing you have to write the area. So let's say we have a main kitchen area and we have to write the main kitchen here and dishwashing area and pastry area. So whatever the area in the drawing you have to write in here, and then you have the description of the equipment, like what equipment is installed in that particular area. So let's say in the main kitchen we have this boiling pans, we have this great combi ovens, and then we have griddles, so range with the 4 burners. So whatever the equipment, kitchen equipment is installed in that main kitchen area, as per drawing you have to write in here. Same with this dishwashing area and same with this one, and you have to write the equipment. And this is the quantity column. So let's say in the main kitchen you have 2 boiling pans, so you have to write 2 in here, and then you have to write the capacity of each equipment that's serving in that area. So where did you get this capacities of this equipment? You need to get this from the supplier, the one who supplied this kitchen equipments. You need to get the value from that supplier, so he will provide you these values in BTUs per hour. This is just a conversion for kilowatt and CFH. So, and this is the total capacity of that equipment. So since we have two boiling pans in here in the main kitchen, so we need to multiply this with 2 in order to get the total capacity of the boiling pans in the main kitchen. So one by one you have to write for all the equipments you have in your area. So you need to, in the end you have to sum up all of these capacities here. So before proceeding towards the total capacity of the equipments which we have in here, let me tell you one thing. The LPG which we are using here is 100% propane. So all the values which I have used in here, which is heating value of the LPG, which is propane, and 1 gallons of LPG propane and specific gravity of propane. So LPG, it could be a mixture of propane and butane, or it could be 100% propane. So it totally depends on country to country. So every country is using different mixture. So sometime it's like LPG is a mixture of propane and butane with the ratio of 70% propane and 30% butane, or it could be 50% propane or 50% butane. So according to the ratio you have to write these values. As I told you, this is 100% propane, so these values are based on 100% propane. So as you can see here, 1 gallon of LPG propane is 91,740 BTUs per hour. This is basically the heating value of propane. And 1 gallon of LPG propane is weight is about 4.23 lbs, and specific gravity of propane at 15.6 degrees Celsius is 0.508 in liquid state. So these values we are going to use when we do the calculation. So as I told you, we need to sum up all the capacities which we have in here or here. So I have sum up all the capacities here, which is approximately equal to that much, 2826192 BTUs per hour. Before proceeding towards the calculation, let me just tell you about the channel membership and the benefits which you will get if you will join YouTube channel membership on MEP engineering tutorials. If you guys can join the channel membership, you will get access. If you just have to go to the channel, click this join button. So you have to select the level on which you want to take the material. Like you can select different levels here. So based on your level you will get the required material. If you have any query related to membership, you can just send an email to saidmohammadw@gmail.com, or you can find that email here as well. Go to the about section, you can see the email here. Or even after taking the membership, you have to send an email on the same address to get access to the material. You just have to send an inquiry email and you will get access to the material. So grand total is that much in BTUs per hour, kilowatt and CFH. Now we are going to apply the diversity factor on this total capacity. So it's not a there's a probability that they are not going to use all of the equipment at the same time at 100%. Obviously some are running at some time and some are off, so we are going to use some diversity factor in here. So we are going to use normally we keep 80 to 85% diversity factor, because not all of them going to be used at the same time. So let's change this to 85. We keep diversity 85. So since I change this to 85, this value will be multiplied with 0.85, and this is the capacity which we got in here in BTUs per hour, kilowatt and CFH. Now we have to write the number of hours the daily operation for all of these equipment. Let's say this is these all equipments are going to be operate 10 hours. So you need to multiply this capacity with 10. You will get total capacity for 10 hours. So total capacity for 10 hours. And next thing we have to write here is the storage, like how many days we are going to store this LPG. So I'm going to store the LPG for 7 days. So it could be 15 days, 30 days, it's entirely up to you how you want to do the calculation. But one thing you need to keep in mind, that if you are increasing the number of days, that means you are increasing the tank size, or you are increasing the number of tanks in which you are going to store the LPG. So other thing, there are two factors. One is that you are increasing the size, and second factor, if transportation charges are less for you, then you can keep this storage days less, so that would be more economical. If transportation charges are high, so you can increase the number of days for the storage. So it's entirely up to you, whatever is economical you can do that. So I'm going to write 7 days in here. Storage, as I told you, the propane heating value is 91,740 BTUs per hour. So required LPG volume we will calculate in here. So we just need to divide this total storage for 7 days and operation for 10 hours with this value, propane heating value. So you need to divide this value with 91,740, which is the heating value of the propane. So required volume you will get here is 1,833 gallons, which is approximately equal to 7 cubic meter. So now we will get the how much weight of the LPG which we are going to store in here. As I told you, 1 gallon of LPG propane is 4.23 lbs. Let me just remind you one more time, this is for propane LPG. If you have a mixture of propane and butane, so this value will be changed. So this is 100% propane, so it's 4.23. So resulting weight will be how much? We got 1 gallon of propane equal to 4.23, and we got total volume of 1,833. You just need to multiply 1,833 with 4.23. You will get the total weight will be 7,754 lbs, which is equal to 3,525 kgs. So this is for 7 days. If you need to get it for per day, you just need to divide this with 7, because we keep the storage for 7 days. So per day it will be 503 kg per day, and for per hour it will be 50.4 kg, because we kept 10 hours daily operation. So 50.4 kg per hour is the requirement for the LPG. Now next important thing over here is we need to select the tank water capacity. Since the LPG tanks are coming in the water capacity form. So what is basically the water capacity? So water capacity is basically representing the capacity or size of the LPG tanks if it was filled with the water. So if you see here in the drawing, this is the LPG storage tank which we have in here. This is just an example to show you. This is the schedule you can see in here, LPG tank schedule, and you can see the nominal LPG capacity in kgs is 1000 and water capacity is 2250 liters. So it's coming in the form of water capacity. So this is just an example to show you. So let's say we are going to select, so according to the catalog you have to select the so from the approved suppliers catalog you can select this tank water capacity. So I'm going to select 1300 gallons for this one. So according to that, now I have to calculate the maximum allowable gallons of LPG that can be stored in the above selected tank. So this is the formula which I'm going to use. V is equal to D into C divided by 100 into G into F. So D is basically the filling density in here, LPG filling density. C is basically representing the container water capacity, which we have selected here is 1300 gallons, and G is basically representing the specific gravity of LPG propane at 60 degrees Fahrenheit, and F is basically the correction factor if LPG is stored at temperature other than 60 degrees Fahrenheit. So if we know all the values we're going to put in here. Since I told you D is the filling density, so filling density for the LPG tanks which we normally keep is 80%. We're not filling 100%, we are keeping 100%. 80% is the filling density for the LPG, so we're going to use 80 in here, and C is the tank water capacity which we selected here is 1300 and 100, and then we have G is the specific gravity. As I told you, specific gravity of propane is 0.508 at 60 degrees Fahrenheit, and F is the correction factor which is 1 because it's stored at 60 degrees Fahrenheit. So now we can calculate the fuel allowed per tank. How much is the fuel allowed per tank? So put all the values and you will get 2048 gallons per tank is the fuel allowed, which is equal to 7.8 cubic meter. If you see the required LPG volume is 1833, which is less than our allowed fuel allowed per tanks. So how we will get the number of tanks? You will get the number of tanks if you will divide your required volume divided by allowed volume per tank. So you will get 0.9 in here. That means we need one tank for the storage in here. So if you change the tank capacity, you can change this one and you will get maybe more tanks in here. So if I'm going to change this to according to the catalog, so you have to change. Let's say I have this catalog and I'm going to select from here. Let's say I'm going to select 865 gallons in here. So 865 gallons, if I select, you can see that the required volume, we see that here is 1833 and allowed is less, so that's why tank is 1.4. so if you see that required fuel storage capacity is not met because we need 1.4 tanks, so we have to change this to 2. So that means we need 2 tanks of 865 gallons water capacity to store that much gallons of LPG, which weigh around 3535 kgs. So so whatever the value you will select in here, you will get the number of tanks here accordingly. So this is how you can do the LPG tank sizing calculation, and you can select the number of tanks accordingly. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe. Thank you. Bye bye. Hi guys, this is Saeed Mohammad Waqas. The topic which I'm going to discuss today is related to chilled drinking water system design calculation, and this is the spreadsheet which I'm going to use for this designing of chilled drinking water system. So let's get started. Before starting the design calculation, let me just tell you about the spreadsheet. I have used the different colors just to differentiate. So this basically green color are the input values from the user. Green text is basically the input values from the user, and the red color values depending on the type, depending on the selection which you made from the top 4 rows. So as you can see here, green and the red color. So first of all, you have to determine the type of the building in which you are going to place this chilled drinking water system. So you have to select from here the type of the building. So based on the type of the building, if you select the restaurant, you can see the gallons per person is 0.1 gallon per person. So this value will be changed based on the type of the building. So if I select the hospital, this value will be changed. So let's say I'm going to perform the calculation for school building. So if I change this to school, you can see that gallons per outlet per hour is 5 gallons. Now the second thing over here is the water inlet temperature. So you have to check this water inlet temperature from the local authorities of your area. So let's say I'm going to use 75 degrees Fahrenheit of water inlet temperature. If I change this to 75 degrees Fahrenheit, you can see that this value will be changed. The BTUs per hour per gallon will be changed. So this value, BTUs per hour per gallon, depend on your water inlet temperature. So if I change this to 90, this value will be changed to 374 BTUs per gallon. So here I'm going to use water inlet temperature at my area is 75 degrees Fahrenheit. So I'm going to use 75 degrees Fahrenheit. And this design of drinking chilled water, it's on 45 degrees Fahrenheit supply temperature. So we are going to supply 45 degrees Fahrenheit supply temperature at the drinking fountain, and the water inlet temperature is 75 degrees Fahrenheit. And next thing come over here is the room temperature. Room temperature where we are going to place the fountains. So drinking fountain area temperature which I have selected here is there are total 3 temperatures, 70, 80 and 90 degrees Fahrenheit. So normally we are placing at the corridors area, so I'm going to use 80 degrees Fahrenheit is the room temperature here. So this 80 degrees Fahrenheit, if you select here, so these values comes up. If I change this to 70 from here, room temperature, if I change this to 70, then these values will be changed accordingly. These circulation losses in the pipes as well as for the circulation pump capacity calculation. Later I will tell you about this. So I'm going to select 80 degrees Fahrenheit here. So next thing over here is the pump horsepower. So how in this we have to assume over here, it's if you see here we have pumps from 1/4 to 2 horsepower. So we are going to assume the pump horsepower of 3/4. So based on this selection, your heat load will be calculated for your pump. So if I use 3/4, you can see that this circulation pump heat will come here, which is 1908 BTUs per hour. If I change this to, let's say, 2 horsepower, then this value will be changed to 5090. So circulation pump heat input depends on the horsepower of the pump which you assumed in here. So here I'm going to assume the horsepower of 3/4. So next thing, you have to count the number of outlet. As I told you, green color is the input from the user. So you have to go to the drawing, count the number of outlets and use in here. Let's say the number of outlets check from the drawing is 60, and these values, as I told you, depending on the selection which you made here. So now we have to calculate the load due to the above usage here. So simply multiply these three values and you will get the load, that is 75,000 BTUs per hour. So next we have to calculate the losses, circulation losses in the pipes, this one. But before that we have to write all the piping lengths which we have used in our project. So you have to write all the pipes in here, whatever you have used in your project. Then you have to go to the drawing and write the length in here. You have to check the length of each pipe segment and add it in here. So after checking the lengths in the drawing of each pipe segment, I have right in here, let's say these are the lengths which I have right here, and we need to convert this into feet. So I just need to multiply this value with 3.28 to get this length in feet. So you have to write in here everything, and then you have to proceed towards the circulation losses in the pipes. So now I have to calculate the circulation losses in the pipe. So I have write the pipe lengths in here, which is the same as here, and these values in BTUs per hour per 100 foot of the pipe. So these values depending on the room temperature which you selected in here, 80 degrees Fahrenheit. If I change this to 90, the values will be changed. These values will be changed accordingly. So I have selected 80, so these values are in here. So simply you need to multiply length with this one. You will get the circulation losses in the pipe in BTUs per hour. Since this value is in per 100 foot of the pipe, so you need to multiply them and divide by 100 to get in BTUs per hour per foot of the pipe. So total losses you calculate here is 4,650 BTUs per hour. So now the third thing which we have to calculate here is the circulation pump heat input. So as I told you, it depends on the horsepower which you assumed in here. So 3/4 horsepower which we assumed here, the circulation pump heat input is 1908 BTUs per hour. So now we have to add all of these load which we calculated, that is 75,000, 4,650 and 1908. After adding all these values, we get the total BTUs per hour, 81,558 BTUs per hour. Now we are going to use 15% as safety factor. So 15% of this will be added into 81,558. So total BTUs per hour calculated here is 93,792 BTUs per hour. So load is done. Now we proceed towards the circulation pump calculation. So in circulation pump calculation, we will calculate the circulation pump capacity in GPM, as well as we'll calculate the circulation pump head. So I have write all the pipes which I have used in this project, and again these are the lengths, the same which I computed here above, and these values in the red color are again the same depending on the room temperature which you selected in here, 80 degrees Fahrenheit. So these values in gallons per hour per 100 foot of the pipe. So again you need to multiply this 600 with 14.6 and you need to divide by 100 because this value is in per 100 foot of the pipe. So we'll get the value of 88 gallons per hour for 1 inch pipe. So same way you have to write for 1/4 and 1.5 inch pipe, and you get the total gallons per hour, that is the sum of all of the above. So it is 135 gallons per hour. So again we have to add 20% as a safety factor. So after adding 20% safety factor, we will get total 162 gallons per hour. So if I want to convert into GPM, divide by 60, divide this value by 60, I will get 2.7 GPM. But this is not it is not decided that we are going to use 2.7 GPM for this circulation pump. we need to check one more thing and then we decide we are going to use or not. So minimum we use 3 GPM per circuit in designing of the drinking chill water system. So number of circuits we have to check. So we have to go to the drawing and check number of circuits. So let's say we are going to use 5 circuits and we say that minimum 3 GPM is required for each circuit. So total value which we calculate here for circulation pump is 3 into 5, which is 15 GPM. Now we have to decide, so whichever value is greater here, so we have to use as circulation pump capacity. Now this one we calculated is 2.7 GPM, and this value which we calculated here is 15 GPM. 15 is greater, so we're going to use 15 GPM is the circulation pump capacity. So you have to decide based on which our value is greater. So I'm going to use circulation pump capacity of 15 GPM. So now I'm going to calculate the circulation pump head. As you know that for the head calculation we have to check the furthest pipe length for supply and return. And to calculate the head we have total two type of losses which we have to compute. One is the straight pipe length loss and fittings and component losses. So here I am going to assume 50% of straight pipe length losses to be used for fittings and components. So that's why I multiply this with 1.5 here to get the pump head. So we need to multiply uniform friction head loss with 1.5 to get the circulation pump head. As I told you in the previous videos as well, uniform friction loss we normally use is 4 to 6 per 100 foot of the pipe. So here I am going to use 4 foot per 100 foot of the pipe as the uniform friction loss. So 1.5 into, you need to multiply this with the total piping length. So we have uniform friction head loss. As I told you, I have used 4 foot per 100 foot. So 4 divided by 100 into total piping length. So again you have to go to the drawing and you have to check the furthest piping length. That means from the source of supply, which in that case is circulation pump. So from circulation pump to the furthest outlet in the drinking chill water system, you have to check the length. Let's say it's 100 meter, which is equal to 328 foot. So you have to use this value in here. So circulation pump head will be 1.5 into 4 divided by 100 into 328. So head calculated here is 19.7 feet. If you want to convert this into PSI, just multiply this with 0.433. You will get the head loss of circulation pump in PSI. Now the one last thing you have to calculate here is the gallons to be cooled. That means storage capacity we have to calculate here now. So in order to calculate the storage capacity, first thing I have to do here, I have to use this formula. BTU is equal to gallons to be cooled into delta T into 8.3. So this formula I'm going to use in here. So gallons to be cooled, I know that the BTUs, total BTUs I have calculated here is 93,792, which I have written here. So gallons to be cooled is equal to this value divided by delta T into 8.3. Now delta T, as I told you, the water inlet temperature is 75 degrees Fahrenheit here, and the supply and the chilled drinking water system temperature which we selected here is 45 degrees Fahrenheit. So 75 minus 45 equal to 30. So we have to write 30 in here. 75 equal minus 45 equal to 30. So gallons to be cooled calculated here is 377 gallons. Now we assume that 50% of the water will return back to the chiller and 50% will be consumed. So that 50% will come from the makeup water. So now we're going to calculate the storage capacity. So if we calculate the storage capacity, since we said that 50% of the water will return back to chiller and 50% will come from the makeup water, so we just need to multiply this gallons to be cooled with 0.5 to get the storage capacity. So now we got all the values. As you can see here, chiller cooling load which we calculated is 93,792 BTUs per hour, this one. And storage capacity which we calculated here is 188 gallons based on 50% of the water returned back to the chiller. And number of pumps we are going to use here is 2, one duty and one standby. And circulation pump capacity which we calculate here is 15 GPM based on the assumption of 3 GPM per circuit. And circulation pump head which we calculated here is 8.52 psi. So this is how you can do the calculation for chilled drinking water system. I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe. Thank you. Hello guys, this is Syed Mohammad Waqas. The topic which I am gonna discuss today is related to the pump head calculation using Pipe Flow Expert software. As you can see that there I have opened Pipe Flow Expert software. Before starting drawing the pipes on the grid, let me tell you something about this software. As you can see that this is the drawing grid area on which we are going to draw the pipes and placing pumps, flow control valves and tanks. And this is the area where you can see the pipes, tanks and their properties. And this is the toolbar at the top. You can see that there you can add fittings, components, pipes, add demand pressure, add demand flow, everything you can add from here. So let's start drawing the pipes and we'll discuss these things one by one. So first of all, I'm gonna take the tank from here. I'm gonna place one tank here, and second tank I'm gonna place in here, and third one I'm gonna place in here. So what I'm gonna do basically is I'm gonna draw the pipes, and we have to pump the water from this tank to this one and this one. So first of all, you have to select the tank, and then you can see in here the surface pressure. So I'm gonna keep this open to the atmosphere, so I will keep this surface pressure 0. And liquid level, we have to write the liquid level, how much is the liquid level in this tank. So let me change the units. So you can change the units also by just going to the units and change from imperial to metric or metric to imperial. So I'm gonna change this to imperial. So I'm gonna give the level, liquid level to 30 feet in this tank, and bottom elevation I will give 0 for this tank 1, and this is the tank 2 and this is tank 3. So tank 2 I'm gonna place this one at same 0. I will keep surface pressure, and liquid level I will keep for tank 2 is 15 feet, and bottom elevation for this tank 2 I'm gonna keep this, let's say 50 feet, and same for the third tank. You have to give the surface pressure open to the atmosphere, so I'll keep 0. And liquid level, let's say the liquid level in this tank is 25 feet, and the bottom elevation of this tank 3, let's say it's 70 feet. So I am done with the elevations and everything. So let's draw the pipe. Here you can see that add pipes, you can draw the pipes from there. So I'm gonna draw a pipe from this tank. So once you draw the pipe, first pipe segment, then it will ask that by default it's scheduled 40 pipe, and length is that much, diameter is that much, and roughness is that. But if you want to change these values, you can just select yes now, or you can change the pipe values. Or if you want to change it later, you can do it also later by just selecting no. So I'm gonna change it now. so I will select yes. So here you can change the pipe material, diameter, length, everything in here. So let's if you want to change the pipe material, you just go to the material, and here you see that all the materials are already there in this software. The best thing about this software is you can find all the materials, fittings, their K values in this software, and it will calculate automatically the pump head. So right now schedule 40 pipe is selected in here, steel. So I'm gonna keep the same, and pipe size selected is 4 inches. So instead of 4 inches, so I'm gonna change this to 2.5 inches. So it depends, whatever the pipe size you have calculated, according to that you have to select the pipe size in pump head calculation. So I will keep the same material, and I will change the diameter from here. This is for steel schedule 40, you can see in here. And I will change the pipe size to, let's say, 2.5 inches. If you just select this use selected size, it will be changed, and you have to save to the pipe, and then okay. Also, if you want to change the length of this segment, you can change the length. You can see that this is represented by P1. You can change the length from here. So let's say we keep this to 10 feet, and you can see the pipe diameter. We already changed this one to 2.5 inches. So let's draw more pipes. Now I will connect this pipe with the third tank over here. So as you can see that I have draw the pipe segments in here. So what we basically doing in here is we are supplying water from this tank, first tank, to the second tank and to the third tank. So we're gonna place one pump in here that will supply the water from this tank to the tank 2 and tank 3. So now I'm gonna add pump and the fittings. So let's say we calculate the total demand for these two tanks is 200 GPM. So what I'm gonna do is I'm gonna let's say, and we got 80 GPM for this tank, and we got 120 GPM for this tank. So in order to control the flow at this tank, 80 GPM and 120 GPM for this one, I'm gonna use one flow control valve either here or here to control the flow across these lines, so that I will get total if we have a total 200 GPM in here, 80 will flow here and 120 GPM will flow there. So first of all, I'm gonna place pump of 200 GPM. So you just select the pump from here, and just click the pipe here, and you can place the pump in here. So if you want to change the by default data, you can change in here also. Just yes, it will open this dialog box, so you can check this one. The pump is in here. There are three types of pump which you can select in here. You can select this one, fixed flow rate set to that much, and fixed head increase or fixed speed. So if I know the demand, total demand for these two tanks, let's say it's 200 GPM, so I'm gonna use this fixed flow rate. So pump will produce 200 GPM fixed flow rate. So as per demand, I'm gonna select this fixed flow rate set to, I will change the unit to US gallons per minute. Let's say it's 200. So I will select this one, and it's saved to the pipe. And then what you have to do, let's change the elevation also at these nodes. So we know that this elevation is 0, same as this one. This one, let's say, change the elevation. Just select the node and change the elevation from here, elevation of the joint. So let's say this one is 50 feet. So this tank elevation, this one also I will keep the same, 50, and this one also 50. So also this tank is placed at 70 feet elevation, so I will keep this joint 70 feet. And if you want to change the length also of this pipe segment, you can change the length also. So just select the pipe. Let's say we'll change this one to 40 feet. and change this one to, let's say, 30 feet, and this one, let's say, I will change to 20 feet, this one 10 feet. Okay, let's keep this one 10 feet. So now I'm gonna place the fittings like elbows, T's, everything in there. So how we can place them, just go select the pipe segment and go to add fittings, just select this one and select the pipe segment in here. You can place the fitting in here. So as you can see that this pipe segment, we will have I will keep one gate valve in here. So you can see that this is 1 inch size in here. So we have selected 2.5 inches. So this is 2.5 inches. Steel schedule 40 pipe you can see in here. So I'm gonna place one gate valve in here. So there I have a gate valve, this one 2.5 inches. Just select this one, add to the pipe section, and after that there will be an elbow at this point, at this node. So I'm gonna place one elbow also, that is standard bend 2.5 inches. There's a K value 0.54. K value is also in here, you can see. Just add to the pipe segment, then standard bend will be added, that is elbow. And one more thing I will add in here is pipe entry sharp edged, this one from tank to the pipe. This fitting I'm gonna add. So just add to the pipe, and you can see that total K value for these three fittings is 1.18. After that just save it. So you can see that the fittings are available in here. So after that I'm gonna add 1T at this point. You can see that there's a T connection in here, so I'm gonna add a T in here. So just select the pipe, 2.5 inches, pipe size is same. There's a branch T connection, you can see that there's a branch T connection in here. So I'm gonna select a branch T in here, 2.5 inches, and you can see that this is the through T and this is the branch T. So I'm gonna select the branch T, 2.5 inches, add to the pipe. K value is 1.08. Just save it. Then again we have to, there is no fitting away here, so I'm gonna add some fittings here also. So just select the add fittings, select the pipe segment. Here I'm gonna add one gate valve here, 2.5 inch gate valve. So just select 2.5 inch gate valve, add to the pipe, and there's one more fitting which I'm gonna add in here, pipe exit to the container, so, or tank. So I'm gonna select this fitting at this point. So just select this one and add to the pipe, save it. So you can see that the fitting is added in here. And one more fitting we have to add in here, that is elbow at this node. So there will be an elbow, so I'm gonna add one elbow in here also. So just select the fittings again, select this pipe segment and select standard bend, this one. You select this one, add to the pipe, save it. So these fittings are already added in there. So now I'm gonna add fittings here also. So I'm gonna select this pipe, I'm gonna add the fittings in here. So just select the add fittings here, select the pipe segment. Here I'm gonna add one gate valve here. Also if you see, I will add some elbows, like one elbow at this point and one elbow at this point. So total 2 elbows I will add, 2.5 inches. So standard bend, add to the pipe and change the quantity to 2. And gate valve, 2.5 inch, add to the pipe. So one gate valve in here. And one more thing, we have to add the pipe exit to the container at this point. There will be a fitting, pipe exit to the tank, this one. So I will add this one also, add to the pipe. Total K value is 2.22. Just save it. Have to add the flow control valve for this one. We said that total demand, let's say we got total demand is 200 GPM at for this pump. So you can see that So and we, let's say we calculated the 80 GPM for this tank 2 and 120 GPM for tank 3. So we have to place a flow control valve so that 80 GPM will flow to this path and 120 GPM will flow to this path. So I'm gonna add some component in here. So you can see that add control valve. So just select this one and select the pipe segment where you want to place the flow control valve. Select this one and give it a name of FCV, that is flow control valve. And the flow which we are going to limit in here is 80 GPM. Just select OK. So that means 80 GPM will flow this way and 120 GPM will flow this way. This is a constant pump flow, so it will gonna give 80 here and 120 here. So we are almost done with placing the pipes, components, everything. So what we have to do next is we have to just in order to generate the results or in order to calculate the pump head, you can see that calculate button in here. You just have to press calculate and it will generate the results. There's a dialog box will appear. You can see that the network was solved successfully and solution values are displayed on the drawing. Or you can see that in here pump head is 91.257 feet calculated, and low pressure at any node is this much, and highest pressure at any node is this much. Close this one and view the drawings, view the results on this drawing area. You can, if you hover your pointer to any of the pipe segment, you can check the results like flow and velocity, length, diameter, start elevation, end elevation, start pressure, end pressure, everything you can see in here. Even at the tank you can see that liquid level, elevation, pressure, everything is shown in here. Also on the drawing, if you see that this is representing in red color, this is representing in dark green, and this one is in light green, and you can see the color of the pipe flow rate in US GPM. Red means 200 GPM, so this is 200 GPM coming from this way. Then dark green is like 80 GPM this way, and this is the flow control valve that is supplying 80 GPM to this tank 2. And in the middle you see that light green color that's flowing this way, that means around 120 GPM this way. Or you can see that this is F means flow 120 GPM, this is 120 GPM, this is F means 80 GPM, and this F is 200 GPM. So you can also go back to your log. You can view the results in Excel sheet also by clicking this one, or you can also create a PDF report. Just click this one, and whatever the data you need you can select and check the PDF report. So you can also change the company name, whatever your company name is you can write in here. You can write the project name, and you can choose whatever the data you want to check in the pipe, whatever the data you want to check in the node, and you want to check in the energy data. So let's say I will remove the mass flow and let me check the friction loss in here. So after selection is done, just click the create PDF report. It will generate the report of your results. So this is the drawing, you can see that, and this is the fluid data. You can see in here we have used H2O water, 68 degrees Fahrenheit. So you can also change the fluid by just going back in here, go to redesign, go to the fluid, and you can change the fluid in here. You can see that a lot of fluids are available in here like ammonia, butane, and propane, water. By just clicking the all fluid, it will show the gases also in here, all the gases, everything in there. If you just click the liquids, it will give you only liquids in here. So you can see that we have selected water, 68 degrees Fahrenheit temperature. So by default we have selected the water. So let's move back to our report, PDF report. and you can see that the pump data is available in here. You can see that pump in and outflow which we have selected is 200 GPM, velocity is 13.402 at the main pipe, and suction pressure you can see that 12.6 psi, and discharge pressure is 52.08 psi, and pump head you can see that 91.257 feet head is the pump head for our system. This system pump head calculated is 91 feet head, and net positive suction head required is not known. You have to check this one when you will select the pump from the supplier, and net positive suction head available calculated is 62.29 feet. So you can also check the pipe data. This is the pipe segments. You can see pipe 1 2 3 4 5 6 7, and the material which we use 2.5 inch steel schedule 40 pipe. Internal diameter is shown in here, pipe roughness is shown, total length of the each pipe segment is shown in here, total K value, friction loss coefficient values for each pipe segment is shown in here. So whatever the fittings and you have used in your pipe segments, its K value, loss coefficients are shown in here. The best thing about this software is you can have all the fittings K values for all the materials is available in here. So you can just select the material accordingly. You have to select your pipe fittings and it will automatically take the friction loss coefficient K values. So you can see the velocity also in each pipe segment. You can check the entry pressure, exit pressure, and friction loss. So this is how you can read your pump head data. So it's very easy to calculate the pump head using this pipe flow expert software. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello friends, today I'm going to discuss the water distribution system design using booster pump as a source of supply, and this is the Excel sheet which I'm going to use for that purpose. You can see here, and there are other tables which I'm going to use in here. You can see the hydraulic tables also, and this is the example which we are going to cover in this session. So as you can see that we have a water service main line, and this is from the street main. If you see that the building information, it's a 16-story building, so I have write 16-story in here, and the street pressure we need to write here. So this street pressure, how you will get this one? You need to get this from the local authority of your area. Normally they are keeping the record how much is the street pressure, so you need to write in here. So let's say the local authority reported the street pressure is 45 psi in our area. So now the next thing over here, if you see here, this is the street main, and this is the piping which we took from the street main, that is water service line, and then we have a booster pump in here, and this is the suction of the booster pump, this is the discharge of the booster pump, and then from here this point we have taken the hot water heater supply, and this one is supplying hot water, and then this one is supplying cold water. And you can see that we have risers, different risers here. This is the riser 1 represented at section H, and riser 3 represented by section B, riser 4 represented by section C, and riser 5 represented by A, riser 2 is represented by F. So I just divided the each riser and section by sections. You can see here, this is A section, this is B, C section, this is B, and then this is section E, this is section D, this is section G, and then this is section I. I have divided this into different section in order, because we need to calculate the pipe sizes for each section, and we need to calculate the demand for each section. So the next thing we have to check here is the highest fixture outlet. So highest fixture outlet is 180 feet above the pump level. So we need to write this one in here, because later we have to calculate the static pressure for the highest outlet. That's why we have write this thing here. So next thing is you have to check the highest outlet pressure requirement. Since the highest outlet which we use is the water closet and it's a flush valve operated water closet, so based on this we have to write the highest outlet pressure requirement. If you see the note in here, that is system, if the system is a flush tank operated, 8 to 15 psi we have to use the operating pressure, and if the system is a flush valve operated we have to use 15 to 25 psi. Since our case we said that water closet is a flush valve operated, so we have used 20 psi. This second case, 15 to 25 psi we can use, so we have used 20 psi in here. If you can join the channel membership, you can get access to the Excel sheet, MEP softwares, MEP books. You can see the channel membership link is given in the video description. You can click join button to get access to Excel sheet. Whatever the level you select, you will get material accordingly. If you have any thing you want to know before taking the membership, you can contact on the email address given in the video description. Even after taking the membership, you can ask things on the same email address mentioned in the video description. So if you join the channel membership, you can get access to Excel sheets, softwares, MEP books, depending on what level you have selected for the membership. So next thing, we have to check the length of run to the farthest and highest fixture. So we need to write that length in here. So you have to go to your drawing and you have to mark the lengths of each section, riser and everything. So since we know that our water closet is the highest and the farthest outlet, so up to that outlet we have to check the length and we have to write in here. Let's say we got 350 feet is the length of run to the furthest, and the highest fixture is 350 feet. We have to write in here. This is called DLR, that is developed length of run. DLR. Then material, this is also very important. So based on material, these hydraulic tables are prepared. You can see here from table 14-1 through 14-12. There are total 12 tables I have used here for sizing. So material for water service into the building, that is a copper K tubing. So if you see here, this is water service, this is the street main, and this one we are talking about, this is of type K copper tubing, material for water service into the building, this copper K. And if you see the other one, material for the water distribution system within the building, is type L copper tubing. So from pump discharge within the building, the piping is of type L copper tubing. So next thing we have here is uniform friction head loss. So we are going to use uniform friction head loss in order to calculate the hot and cold water pipe sizing, and we need to keep two things in mind while we do the sizing of the cold water and hot water pipe sizing. That one is one is the uniform friction head loss, which we set over here, this one, uniform friction head loss, and the second is the velocity. Velocity has a very prime importance for domestic hot and cold water supply system design. So if you see the note over here, maximum recommended velocity for domestic cold water supply pipe sizing is 8 feet per second. And for the hot water supply, maximum recommended velocity is 4 to 5 feet per second. So we are going to use 5 feet per second limitation in a case of hot water supply pipe sizing, and 8 feet per second in a case of cold water supply pipe sizing. So if you are going for higher velocities, if you are going to design your system on higher velocities, which is not recommended, you will have problems of noise, water hammer, cavitation. So that's why you need to follow this velocity recommendation, because we don't want to create any noise issue, cavitation and water hammer. So we need to keep these velocities in mind. So we are talking about uniform friction head loss. Uniform friction head loss, normally we are taking 4 psi per 100 foot to 10 psi per 100 foot. So we have taken 6 psi per 100 foot over here, which is like most economical design is like 5 to 6 psi per 100 foot. So we have used 6 psi per 100 foot. So as you are changing this uniform friction head loss, if you move to 10 psi per 100 foot, then your pipe sizes will be smaller. That means less insulation will be used, smaller pipe insulation will be used. That means you are saving the cost on the piping and insulation as well, but you are increasing the pump head will be increased if you increase the friction head loss. So let's say if I'm going to change this to 10 psi per 100 foot, you will see that pump head loss will be changed. There will be more pump head loss. Let's say this change is to 10 and pump head loss is increased. There is 115.4 psi. So more power will be used by the pump. So let's change back to 6 psi per 100 foot. Now the next thing which we have to use over here is PRV installed at the pump side. So there we have a PRV installed at the pump side. So obviously there will be a lot of fittings over here also, like maybe there will be some drain cock or something, and there will be a water meter here. So you need to add these values in here also. I added only PRV over here, and this PRV pressure loss or head loss, I got this from manufacturer or supplier of this PRV. So I need to add this value here, 5 psi. If we have water meter over here, we need to add the water meter head loss here also. So next thing we have to add here is the static pressure for the highest outlet. So since we know that our highest outlet is 180 feet above the pump level, so now we need to calculate the static pressure for the highest outlet. We know that 1 feet is equal to 0.433 psi. So static pressure for the highest outlet is equal to 180 feet into 0.433. In order to convert this into psi, it will be 77.94 psi. Now next thing is the equivalent length of run. Equivalent length of run for this system. Equivalent length of run, it will be the sum of straight piping length, which you can see here, straight piping length, plus valves and the fittings used in this system. So since we don't know the sizes of the pipe, so what we do, we use this note. We are going to use a thumb rule, that is 50% of developed length will be considered as a friction loss for the fittings and the valve. This is a thumb rule. So we know that total developed length for the straight pipe of the fitting is 350 feet. We are going to add 50% of this 350 as a friction loss for the valves and the fittings. So how much our equivalent length of run will be? 350 into 1.5. So total 525 feet is the equivalent length of run. Now the last one over here is the friction head loss. How did we get this friction head loss? Friction head loss you have to get just simply multiplying your equivalent length of run with the uniform friction head loss. Uniform friction head loss is 6 psi per 100 foot, and equivalent length of run is 525 feet. So if you multiply 525 with 0.06, you will get 31.5 psi friction head loss. And what is this friction head loss? This friction head loss is due to the straight pipe length plus fittings and the valves in your system here. So the friction head loss is 31.5 psi. Now the total initial pressure, it will be the sum of A, B, C and D. I have write A here, this one, B, C and D. So we need to sum up all these to get the total initial pressure requirement. So total initial required pressure is 134.4 psi. So now we know that street pressure reported is 45 psi. But in a case of peak demand, you will not get this 45 psi, maybe 5 to 10 psi less. So it is a good practice to take 5 to 10 psi less than reported pressure by the local authority. So I'm going to subtract 5 psi from this reported street pressure in a case of peak demand. So here it will be 40 psi. Now we can easily calculate the pump head, how much the pump head will be. So how we'll get the pump head? We need to this total required initial pressure minus suction pressure at the street main. So if you subtract the suction pressure from the street main to the initial pressure requirement, you will get the pump head. So that means pump head is 94.4 psi, and if you want to convert this into feet, so you will get 218 feet is the pump head here. So if you see over here, the total water supply fixture units which we calculated here, which I will tell you later. Let me just calculate the pump head and total capacity. So the total water supply fixture unit which we calculated here is 4840 fixture unit at this point. 4840 you can see here. So 4840 fixture unit, we need to calculate the pump capacity. We calculated the head, but we need to calculate the demand GPM for this one. So 4840 fixture units. So 4840 fixture units, I will go to this table. If you see the conversion of fixture unit to equivalent GPM, this is for the flush tank, this is for the flush valves. So if you note that after 1000 fixture units, values are same for flush tank and the flush valves. So our case, we have to check for 4840 fixture units. So if you go for 4000 we have and 5000 we have, so we will apply the interpolation formula to get the exact value of the GPM at 4840. So this is the interpolation table which I have. This is a formula which I am going to use, interpolation formula, to get the exact value. So we have 4000 fixture units and we have 5000 fixture unit, and we need to calculate GPM at 4840. So as I'm applying all the values, you will see the GPM calculated here. So we know that for how much GPM we have at 4000 and how much GPM we have at 5000. So go here, 4000 how much GPM, 525, and 5000 we have 593. So 525 and 593. So 525 and 593, it will calculate at 4840. So how much GPM calculated at 4840? 582 GPM. That's how I write 582 GPM, and reference table is 13-4 which I use here, this one. So this is how you can calculate the booster pump head as well as demand. So now we will proceed towards the hot and cold water demand. So after demand, we have to calculate the pipe sizes for the hot water as well as cold water. So here I used only water supply demand calculation for riser 4, which is represented by section C. So in the same way which I'm telling you now, you have to calculate the water supply demand for other risers and other sections of the building. So this is the riser 4 which I'm going to calculate right now, demand calculation. So in riser 4, I got there's a flush, there's a water closet of flush valve types, and urinals we have, and the lavatory we have. So we have to write all the fixtures for each riser and section one by one, and then we have to go for number of fixtures. So how many water closet I have? 55 water closets, 15 urinals wall hung, and 42 lavatories. So now we have to calculate the hot water fixture unit and total hot water fixture unit. Now we have to calculate cold water fixture unit and total cold water fixture units, and then combined hot and cold water fixture units. So number of fixtures, I write 55 here. Now I have to get the value of each water closet. So I'll go to this table, demand weight of fixtures in fixture units. So we have a water closet now, and 16-story office building, and this we considered as and we know that it's a flush valve operated water closet. So occupancy is public, flush valve operated, and you see that cold there is no cold water connection on water closets, that's why there is no value in here. So hot, there is no connection of hot water, so that's why no value here. So we have only cold water point in the water closet, so value of fixture unit is 10 in a case of water closet with a flush valve, and total fixture unit value is 10. So we are going to write for cold water fixture unit is 10 value, and combined it's also 10. Combined water supply fixture unit value is also 10. So how we will get the total cold water fixture unit? We just need to multiply number of fixture with each fixture unit value. So we'll get the total cold water fixture unit value. So in the same way you have to go for urinals, and how we will get the total water supply fixture unit. We know that 10 value we have calculated here. 10 value, you can see that combined for a total value of fixture unit is 10. So we have write 10 here. So it's the same, 10 into 55, that is 550 total fixture units. So now I'm going to show you for the laboratory as well. Total 42 laboratories we have, and each total 42 laboratories we have here. And in the laboratory we have both hot water as well as cold water connection, so we need to write value for the hot and cold water. So we'll go here in our table 13-3. now we have to check for laboratory. So laboratory, if you see here, this one is the laboratory, but this is a private, and this laboratory is public, so we are going to use this one, public laboratory. So if you see here, the hot water is 1.5, cold water is 1.5, and total fixture unit value is 2. So we will write here hot is 1.5 fixture unit, cold each fixture unit is 1.5, and combined is 2. So 1.5 into 42, you will get the total hot water fixture unit, that is 63, and 42 into 1.5, that is cold water fixture unit. 42 number of fixture unit into each cold water fixture unit is 1.5, so total is 63 also as well. And if you see the combined, we have 2, so 42 into 2, you will get 84 total fixture units. The reason is, so if you see the total hot water fixture unit at riser 4 section C is 63, and total cold water fixture unit at riser 4 is 688 fixture units. So same, if we have right here hot water 63 fixture unit, cold water fixture units are 688 fixture units at riser 4 or section C. And the reason why I have calculated the total water supply fixture unit, because when we do the sizing for this section, that is from pump discharge up till this point where the connection is taken off to the hot water heater, so this line and the water service main will be sized based on total water supply fixture unit values. That is, this is only for riser 4. You need to calculate for every riser and sum up. You need to calculate for every riser this for total water supply fixture unit value, and write in here it is, that is 4840 fixture unit. So you need to size this piping and water service main based on this total water supply fixture unit value, that is 4840 fixture unit. And from this point you have to do the sizing for each section and riser based on the fixture units. That is, cold water fixture unit is the total cold water fixture unit at this point is 4730, and total hot water fixture units are 345. So if you see here, if you sum up the water supply fixture units up till this point, let's check the cold water fixture units. So this riser 5 or section A is 1376, plus we have 688 here, and 430 cold water fixture units here, that is 2494 at this point, and then we have to some cold water 860 here. 860 plus 2494, that is 3354. So we have 3354 cold water fixture unit at this point. Now the last one is riser 1, that is 1376 fixture unit plus 1376. So total cold water supply fixture units are 4730 fixture unit, you can see here up till this point. Same way you have to calculate the hot water, it will be 345 fixture units. But as I told you, from this point you have to calculate the pipe sizes and GPM demand based on total GPA, total water supply fixture unit. Just like we calculate for riser 4, you have to calculate for riser 3, 2, 1 and then sum up, and it will be 4840 fixture units. So now next step is we have to go for the cold and hot water pipe sizing, and I'm going to use the hydraulic tables to calculate the cold and hot water pipe sizing. You can see that these hydraulic tables, there are total 12 hydraulic tables which I'm going to use. So let's go to the calculation sheet and let me show you for any riser to calculate the pipe size. So let's check for riser 5, which is represented by section A. You can see that riser 5 represented by section A, and how many cold water supply fixture units we have here? 1376. I'm not going to calculate for all risers demand. The way I have shown you for riser 4 represented by section C, same way you have to calculate the demand for each riser and each section. Otherwise video will be much longer, that's why you have to calculate. This is just a procedure to show you how you can calculate. So riser 5A fixture units, cold water supply fixture units are 1376. Now we need to calculate the demand at this point. So as I told you how we need to convert this fixture unit into demand GPM. So how we'll get this one? I have used the interpolation table as I shown you before. So 1376, this is a cold water, so 1376. So we have 1250 and we have 1500. So this one is for the flush tank and this is for the flush valve. So our this riser contain the flush this water closets with the flush valve system operated. So we are going to follow this column, the flush valve. So 1250 demand is 240 GPM and 1500 demand is 267 GPM. So 240 and 267. We have to write here GPM, and this one is 1250 and this one is 1500, and we need to check fixture unit value at 1376. So fixture unit value we have 1376, we need to check the demand. So how much is the calculated demand at 1376 fixture unit? This is the interpolation formula, so which I have used here to get the exact value of the demand, that is 254 GPM. So now we know the demand at 1376 fixture unit. So now we need to calculate the pipe size. So now I have to check the pipe size. So the table which I have used here is 14-9 as a reference table to calculate this pipe size of 4 inches. Now I will tell you how did I get this pipe size of 4 inches. So demand calculated here is 254 GPM. 254 GPM. If you see here 254 GPM. So since if you remember that in the beginning I said that material for water service into the building is copper K and distribution system inside the building is L. So we have to check this L copper tubing. 254 GPM. So this is the L copper tubing and 254 GPM. If you see that 240 GPM we have 260 GPM, we don't have 254 GPM, so we will interpolate the value for 254 GPM. If you see that 240 GPM value is this is the velocity column and this is the head loss column for copper L tubing. So 240 GPM velocity is 6.42 and 260 GPM velocity is 6.95. So we will use interpolation formula to get the value at 254. So 240 and 260 we have 6.42 velocity and 6.95. 6.42 and 6.95 at 240 GPM, and 260 GPM we need to calculate at 254 GPM. So how much is the velocity calculated at 254 GPM? That is 6.79 feet per second. 6.79 feet per second, as you can see here. So since this 6.79 feet per second is less than 8 feet per second, which we said here in the beginning, so the pipe size which we selected 4 inches here is okay. We can use 4 inches pipe size. Now we have to calculate the head loss also. We use the uniform head loss of 6 psi per 100 foot. So now we need to calculate the head loss also at this pipe segment or riser 5, which is represented by section A. See, same way we have to calculate the head loss. So we will just write the GPM here, interpolation table, and we calculate the head loss. We'll go here and now we'll calculate the head loss. 240 and 260. 240 copper L tubing. How much is the head loss? 1.9 psi per 100 foot, and 260 head loss is 2.1. So 1.9 and 2.1. 1.9 and 2.1. So calculated head loss is 2.04 psi per 100 foot. So 2.04 psi per 100 foot. So this is how you have to use hydraulic table to get the pipe size for cold water pipe sizing. So let's go for another riser. Let's check for this riser 3 plus 4 plus 5, which is represented by E, as you can see here in the drawing. This pipe segment which we are going to calculate now, this is riser 5A, this is 4, and this is 3. So at this point it will be the sum of section A, B, and C, which is represented by, and also as well as D. So D is basically the sum of D is basically the sum of this riser 3 and 4 is represented by D. So if you see that total fixture units at this point section E, it will be, so if you see the sum of 3 and 4 riser is cold water supply fixture unit 430 and 688. That is 1118, which is written here, 1118 represented by D. And then we have to add this 5A, cold water supply fixture unit 1376 plus 1376, so 2494. So total for cold water supply fixture unit at section E is 2494. So we need to calculate demand first, 2494, in order to get the pipe size at this section, which is represented by E. So you can see here, I just sum up this and in order to get the value. So 3 plus 4 is represented by D. So and we get the value of total fixture unit is 2494. Now we need to convert this into demand GPM. So how we'll do this one? So we will I will use the interpolation table again. 2494, and if we go here and we will check, we have 2250 and 2500. So 2250 fixture unit, 2500 fixture unit. The value is 348 and 375. 348 and 375. So 2250 we have 348 and 2500 we have 375. So how much is the GPM calculated if we have a fixture unit of 2494? GPM calculated is using interpolation formula 374 GPM. So we have right here 374 GPM. So demand is done. Now we have to calculate the pipe size again, and then velocity, and then head loss. We need to confirm the velocity should be less than 8 feet per second. So now we need to calculate the pipe size first for 374 GPM. Reference table we use is 14-10. So this is the 14-10 table, and how much GPM we set? 374 GPM. So 374 GPM. So one thing I need to tell you first, if you see that 374 GPM is also available in here, but if you move to the copper L tubing and check the velocity is 9.36 at 350 and 10.70 at 400. So 374 is also available in here, but if you see the velocity is higher than recommended velocity, it exceeds the limit. That's why we are not using this 4-inch pipe size. Head loss, although the head loss is okay, but velocity is exceeding, so we are not going to select 4-inch pipe size. That's why we have selected 5-inch pipe size, table 14-10. So if we go here and we check 350 and 400, so we need to check at 374 GPM. So 350 copper L, type L copper, velocity is 6.01, and 400 6.87. 6.01, 6.87. This one is at 350, this one is at 400, and we need to check at 374. So 374, if we check the velocity calculated is 6.42 feet per second using the interpolation formula. So we have right here 6.42 feet per second. Now we need to calculate the head loss as well. Same way, we go to 14-10 table. 350 head loss is 1.3, 400 head loss is 1.7. 1.3 and 1.7. Head loss is 1.49 psi per 100 foot at 374 GPM. So 1.49 psi per 100 foot at, so if you notice that the velocity 6.42 is less than 8 feet per second, and the head loss is 1.49 psi per 100 foot. So both values are less than our recommended values which we said in the beginning. So the 5-inch pipe size selected for 374 GPM is correct here. So now in the same way you have to calculate the pipe sizes for other sections. Now let's check for the hot water pipe sizing, how you will calculate the hot water supply pipe size. Let's take one example for this one. So we are going to calculate the hot water pipe size for section G. So if you see that this is the section G, and hot water supply fixture units at section G are 249 fixture units. So we have 249 fixture units over here. Now we need to calculate the GPM for this hot water supply pipe sizing. So how we'll get the GPM for this one? So same, we have to use 13-4 table to get the GPM. This table we have to use for fixture unit to GPM. So fixture unit over here are 249. This is for the flush tank, this is for the flush valves. 249. So 225 and 250 over here. But at this point, for hot water pipe sizing, you have to use the flush tanks, not the flush valves column, because we don't have a water closet and urinals included in the hot water piping system. So we have to use flush tank over here this time for the hot water pipe sizing. So we have 225 and 250, that is 70 and 75 GPM. 70 and 75. $225 and 250. 225 70 GPM, 250, we have 75 GPM. We need to check at 249 fixture unit how much the GPM value. So it's same 75 GPM, so we are going to use 75 GPM here as well. So here we have used 74 GPM, so 74, 75, so we will change this to 75 GPM. So we are going to use 75 GPM here. Now we need to check the pipe size at this GPM demand. So how much pipe size, hot pipe size will be. So table which I have used here is reference 14-7. So I'm going to use this table. Demand is 75 GPM. So we have a demand of 70 GPM here, and copper L, type L copper. If you see 70, we have 4.70, and the 80 we have 5.37. 70 we have 4.70 velocity, and 80 we have 5.37. Four point 5.37. And 80, and we need to check at how much GPM, 75 GPM. So velocity is 5.04 GPM, 5.04 feet per second, sorry, 5.04 feet per second. So recommended velocity is 5 feet per second for hot water system. As we said, it is 5.04, is almost 5 feet per second. So we can change the size to 3 inches, but it's okay to use 2.5 inches because it's almost 5 feet per second. So that's why we have used 2.5 inches pipe size in here. So in the same way, you have to calculate the pipe sizes for all other sections. You have to calculate the pipe sizes for the sections, as I have written here in the table. So the last thing I have to tell you over here is you have to calculate the pipe size for this section from booster pump discharge up to the point where connection is taken off to the hot water heater. So this will be sized based on total water supply fixture unit, as I mentioned you earlier. So total water supply fixture units over here are 4840 fixture units. So I need to do the pipe sizing for 4840 fixture units. So let's go to the calculation sheet. We calculated the total water supply fixture units are 4840. We already know the demand at this point is 582 GPM. So let's get the size. Let's get the size of this pipe size. Let's get the pipe size for this demand. So this time I'm going to check the table, hydraulic table. Over here it's 5-inch table, and 5-inch table, if you check the demand here is 550 and 600. So 550, we have 550. If we check the velocity is copper L tubing, since this is again inside the building, this so we have to use copper type L copper. So 550, the velocity is 9.45 feet per second, and 600 velocity is 10.3 feet per second. So again this velocity is higher than recommended 8 feet per second, so we are not going to use 5-inch pipe size. So we'll go to the next table, 6 inches, and then check the demand 550 and 600. 550 and 600, type L copper, velocity is 6.57 at 550 and 7.17 at 600. So 6.57, and let's interpolate and get the exact value at 582. So 6.57 and 7.17. 7.17. This is at 550 GPM fixed units. Sorry, this value we have to check the velocity. So 550 we have 6.57 velocity, and 600 we have 7.17 velocity. We need to check at 582 GPM. So how much it will be? So velocity calculated at 582 GPM is 6.95. So 6.95 is the velocity calculated in here, feet per second. So the velocity calculated here is 6.95 feet per second at 4840 fixture unit, and with the pipe size of, how much is the pipe size we selected here is 6 inches. So 6-inch pipe size. So 6 inches pipe size. So this pipe segment from discharge, booster pump discharge up to this point, it will be 6 inches. So same water supply fixture unit you will have here, 4840 fixture unit. So same pipe size we can use in here. So this is how you can design your water supply system using a booster pump as a source of supply. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe and don't forget to press the bell icon. And one more thing before ending this video session, if you can join the channel membership, you can get access to the Excel sheet, MEP softwares, MEP books. You can see the channel membership link is given in the video description. You can click join button to get access to Excel sheet. Whatever the level you select, you will get material accordingly. If you have any thing you want to know before taking the membership, you can contact on the email address given in the video description. Even after taking the membership, you can ask things on the same email address mentioned in the video description. So if you join the channel membership, you can get access to Excel sheets, softwares, MEP books, depending on what level you have selected for the membership. So this is the end of this session. Hello guys, this is Syed Mohammad Waqas. The topic which I am going to discuss today is related to the total water supply demand calculation for a building. If you remember, about 1 month ago I made a video related to hot water and cold water pipe sizing. In that video I did not explain how you can calculate the water supply demand. So in this video I am going to show you how you can do that by using a water supply fixture unit method, that is WSFU, and by using International Plumbing Code IPC and UPC, that is Uniform Plumbing Code. But before proceeding towards the calculation, I want to tell you one more thing. In my next video I'm gonna discuss about the water distribution pipe sizing with one more complicated example. As you can see that we have risers in here also. In the previous example for water supply and hot water and cold water pipe sizing, it was not complicated. So in my next video I'm going to use this complicated example. You can see the risers are also included in here, so you will learn more in this video. And we're going to do the pipe sizing for the main service lines, and we're going to do for water supply distribution piping, and we're going to go for risers also. So let's move back to our main topic. So let's say we have an office building, and we have a number of fixtures are described in here. Like water closet, we have flush type, and 60 water closets are in there. And urinals, we have a wall hung type, and a flush valve type is used in there. So 12 urinals, and lavatory we have 40. So it depends on number of fixtures which you have in your drawing. You have to write the total number of fixtures in here. So second thing, you have to, since we are using water supply fixture unit method, so we have to write the fixture unit value associated with each fixture. So here are the tables and charts which I'm gonna use. So first fixture is water closet and number of fixtures are 60. So there is no hot water required for this one, so we'll go for cold water fixture units and total water fixture units. So if you see over here, and the occupancy is also matters, since this is an office building, so we're gonna select this public space instead of this private space. And type of supply, we know that this is a flush valve instead of flush tank. So water closet, public type, flush valve. You see the cold water fixture unit required are 10 and total water supply fixture units are also 10. So move back here to our Excel sheet and write cold water fixture units are 10 and combined water supply fixture units are also 10. So since we know that one fixture unit requires 10, so 60 fixture unit you need to multiply 60 into 10, that is 600. Again same thing, 60 fixture units in here and combined water supply fixture unit value is 10, so 600 is the total water supply fixture unit. And urinals we have 12. This is a wall hung flush valve type. Move back to our chart and tables. So here you can find stall or wall urinals and stall or wall urinals, one with the flush valve, another with the flush tank. So since we have used the flush valve type, so we are gonna use this value. So cold water required is 5 fixture units and total is also 5. So same way we have to write cold 5 and total is also 5. Again you need to multiply this number of fixture with cold water fixture unit to get the total water supply fixture unit here for cold water, and total water supply fixture units are also 5 by 12, that is 60. And the last fixture we have here is the lavatory, and lavatory required both hot and cold water. So move back to our tables and charts and find the lavatory in here, and you can see that this lavatory is private and we are looking for public. So you can see that this is lavatory. Since we have an office building, that's why I'm going to use public occupancy. So lavatory, public, faucet type, you can see the hot water fixture unit is 1.5, cold is also 1.5, and total fixture unit required are 2. So hot and cold are 1.5 and total are 2. So we can write hot water fixture units are 1.5 and cold water is also 1.5 and total 2. So simply you need to multiply this fixture unit with number of fixtures, this fixture unit with number of fixtures, and this fixture unit with number of fixtures to get this total cold water fixture unit, total water supply fixture units, and total hot water fixture units. So this is the demand which we calculated here is the intermittent demand, that is a non-continuous demand. It's not used all the times, its frequency of use is different, it's not used as continuous demand. This is a non-continuous demand. We need to add the continuous demand to the non-continuous demand if continuous demand is available. But before that we need to convert our fixture unit values into the GPM. So since we know that total hot water fixture unit is 60, so we have write 60 in here, and total cold water fixture unit, it is a sum of these three, that is 720 fixture units, and combined water supply fixture unit we have in here is 740 fixture units, that is the sum of this one. Now we have to convert this fixture unit value into GPM, so we are gonna use the table in here. So this is the table, you can use this chart as well as this table to convert this fixture unit to equivalent GPM. So first is a hot water, that is 60 fixture units. So hot water 60 fixture units for the lavatory, So we are gonna use this. There we have two columns, flush tanks and flush valves. So we have 60 fixture unit. For flush tank it's 32 GPM. 60 fixture unit is 32 GPM. So we're gonna write 32 GPM in here, and then we have to get the value for cold water fixture unit and combined fixture units value also. So total water supply fixture unit are 720 in here. So we have to go back, but cold water, if you see that we have a flush valve type for this one, so we are going to use flush valve column in here. Whatever the valve you are using in there, you have to follow that column. So 720 fixture units. So we don't have 720, we have 500 and 750. So if you go for the second column, this is flush valve. So we have 720, so I'm gonna write approximate value in here, that is 100. Let's say we are gonna write 174 value in between them, and we check for total water supply fixture unit value or combined water supply fixture unit is 740. So 740, if you go in there and let's say approximate value, we will get between 500 and 750 is fixed. Let's say we get the GPM of 177 GPM. You can do interpolation to get the exact value. So right now I'm just writing the approximate value, that is 177 GPM. So this is our intermittent demand which we calculated in here. So now we have to add this demand with the continuous demand. If you have any continuous demand, you have to add this with intermittent demand. So let's say we have two hose babes there, and we have to go back to our tables and chart to get the fixture unit value for this hose babe. So as you can see that demand at individual fixtures and required pressure. If you see, this one is the flow rate GPM, this is the fixture, and this is the pressure. So this is the hose babe as you can see over here, and the GPM required is 5 GPM. So we have 5 GPM required in here. So two hose babes, it will be 10 GPM. And the second continuous demand is air conditioning makeup water. So this value you have to get from the HVAC design engineer. So how much is the required GPM for the air conditioning water makeup? So let's say we get this value 30 GPM. So we just need to add these two values to get the total continuous demand. So TCD is the total continuous demand, that is 10 plus 30 equal to 40 GPM. And then you can see that hot water demand here, hot water demand we already calculated, that is 32 GPM in here. And the cold water demand, you need to add this continuous demand also in the cold water demand, because this water supplied here for the continuous demand is also normal or cold water. There is no hot water required in here. That's why we did not add any continuous demand to our hot water demand. It's simply 32 GPM. But for cold water demand, we need to add this continuous demand also, because this also required normal or cold water, hose babes and air conditioning water makeup equipments. So total cold water demand will be, that is cold water demand we calculated here 174, for intermediate demand, and continuous is 40. So 174 plus 40 equal to 214 GPM. And total water demand required here is 217, that is 177 is the total water demand here, plus continuous demand, that is 40. So total water demand required is 217 GPM. So reason why we have calculated hot water demand, cold water demand and total water demand, because if you move back to this example which we are going to discuss in the next video, So here if you see, this is our service main. So we are gonna this service main pipe sizing based on our total water demand required. So we have to do sizing based on total water supply demand required, that is this value. So if you go from here, this is our pump, that is a booster pump, this is the suction, and this is the discharge. So from service main to the point of connection to the, this is our hot water heater. From service main to the point of connection to the hot water heater, we have to do the sizing of this water supply piping based on this GPM. This is just an example to show you that's why we have calculated this total water supply demand. But after that you have this hot water piping in here. So you have to do this hot water piping based on this hot water demand, because here you have hot water supply, this is hot water supply, and then this is your cold water supply. After this point of connection you have this cold water supply. So you have to do the sizing of this cold water supply piping based on this cold water demand. That's why we have calculated this hot water demand, cold water demand, and total water demand. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Syed Mohammad Waqas. The topic which I am going to discuss today is related to the drainage pipe sizing. So there I have prepared an Excel sheet. As you can see over here, there's a lot of tables which I'm going to use to calculate the drainage pipe size. And this is the drawing for the 9-story building. As you can see over here, it's given here, and we are going to calculate the pipe size for each branch. As you can see, the sections are given as A, B, C, D, E, F, G, H, I, and then stack J, and then run out K, and then we have run out again M. So this is the drawing which we are going to use and to calculate the drainage pipe size. Before starting calculation, I want to give one small message to you guys. If any one of you interested in PhD from Canada, then you guys should visit this channel, Vagabond TV. This channel is related to the PhD in Canada. There you find a lot of videos related to PhD in Canada. So this is really helpful for you guys if you are interested in PhD from Canada. So please subscribe this channel. So let's move back to our topic. So as you can see that there I have a drawing for 9-story buildings, and we have divided each branch. We have given the name of each branch as section A, B, C, D, E, F, G, H, and I. And this vertical stack is represented by J, this runout is represented by K, or offset is represented by K, and then again this vertical stack is represented by L, and this runout is represented by M. So as you can see that I have prepared this table. In branch A, how many fixture unit we have? As you can see over here, we have 70 fixture units. So you have to understand first what is the fixture unit. Fixture unit, if you remember that we have used the fixture unit in water supply pipe sizing. That time it was called water supply fixture unit, and here we are going to do for drainage system. That's why it's called drainage fixture units. So fixture unit basically depends on 3 factors, that is rate of discharge, time of operation, and frequency of use of fixture. So based on these factors, these tables prepared by ASPE, that is American Society of Plumbing Engineers, IPC International Plumbing Code, and UPC Uniform Plumbing Codes. So based on these factors, these tables developed by these IPC, UPC, and ASPE. So I took this table from ASPE, that is American Society of Plumbing Engineers. So based on this table, I'm gonna do the sizing of drainage piping. And as you can see that we have horizontal branch sections given as A, B, C, D is mentioned here in the Excel sheet, and we are going to calculate the pipe diameter. And then we have a vertical stack, that is J, and this vertical stack is represented by L, vertical stack J and L. And then we have offset or run out, that is represented by K and represented by M, K and M. And the list of the fixtures in each branch section is given over here. So for example, branch A, we have water closet, urinal, lavatory, kitchen sink, shower, domestic, bathtub, laundry, floor drain and bidet. So according to that, we have write the fixture unit value from the table 6.2. So this is the table fixture unit per fixture or the group. So from this fixture we have taken value and we have given it over here. So for example, water closet, you can see the drainage fixture unit value is how much. You can see the water closet over here. So since we are using the valve operated water closet here, so we are going to use this value 6. So water closet drainage fixture unit value is 6. So you can write 6 here. So in the same way, you have to write the drainage fixture unit value for each and every fixture. And then number of fixtures given in branch A for water closet is 5. Urinal we have 2 and lavatory we have 2. So you need to multiply number of fixture with the individual fixture unit drainage fixture unit value, and you will get the total drainage fixture unit value for the water closet in the branch A. So total drainage fixture unit value given for branch A, it will be the sum of all these fixtures. It will be the sum of all these fixtures. So 30 for the water closet, 8 for the urinals. You need to sum up all of these drainage fixture unit value to get the total drainage fixture unit value in the branch A. So total drainage fixture unit value is the sum of all these, that is 70. Same way you have to write the drainage fixture unit values over here in this column for the branch B by seeing the which fixture unit is connected to the branch B. So you have to write the fixture unit values in here and then multiply with the number of fixture unit to get the total drainage fixture unit value. So this is how you have to do for all branches, that is A, B, C, D, E, F, G, H and I up till here. So first we are going to calculate the branch pipe size for branch A, B, C, D, E, F, G, H and I. And second, we are going to calculate this stack pipe size represented by J, and then we calculate the pipe size for this offset run out K, and then again vertical stack pipe L, and then again this offset or run out M. So first we are going to calculate the pipe size for this branch A. Since we have 70 fixture unit connected to this branch A by using, and this table 6.4, we are going 6-4 is going to be used for fixture unit loads for sanitary branches. So we are going to use this table 6-4 to calculate this branch pipe size A for all of these branches. So we have 70 fixture unit over here. So as you can see, the total fixture unit we have 70. 70 is in between 20 and 160 and in between 3 and 4 inches. So we will go for 160 on the higher side. So 160 on the higher side, so we'll get the pipe size is 4 inches. So we'll write 4 inch pipe size. And again branch B, that is 90 fixture units. 90 fixture units again come between same table 6-4 we'll use. It's in between 20 and 160. That is we'll go for the higher value, that is 4 inches. So in the same way you have to calculate for this 120 fixture unit branch C. 120 fixture unit is also between 20 and 160, so we'll go for the higher side, again 4 inches. So D has 90 fixture unit, we already calculated. For B it will be same as D, that is 4 inches. Now we'll calculate for the branch E, has 150 fixture unit load value. It's again less than 160, so we'll go for 160. It is in between 20 and will not go for 20, we'll go for 160, and pipe size is 4 inches. And then you can see the branch F has 180 fixture units. So 180 fixture unit, it is in between 160 and 360. So we'll go for the higher value, 360. 360 we have 5 inch pipe diameter, so we're going to use 5 inch for section F. And then we have section branch G with 190 fixture unit. So in the same way you have to write for G, H and I. G is 190. 190 is also less than 360. We'll go for the higher value, that is 360 is 5 inches. And H is also 160. 160 is in bit 160 is here, 4 inches. And then I, you can see, is 200 fixture units. 200 fixture unit is in between 160 and 360. So 360, that is 5 inches. Now we have to calculate the vertical stack pipe. As you can see over here, this is represented by J. So when you are calculating the vertical stack pipe size, you need to sum up all these branches fixture unit load, that is 70, 90, 120 and 90. That is equal to 370 fixture units. So 370 fixture units load will be on this vertical stack represented by J. Now to calculate the vertical stack pipe size, you need to use this table 6-3, that is maximum permissible fixture unit load for sanitary stacks. So this first column is for the, if we have a 3-story building or less than 3-story building, then we have to use this column. If you have more than 3-story building, then you have to use this third column. Since we have a 9-story building, so we are going to use this third column. So since we have 370 fixture units connected to this vertical stack J, so 370, these are the fixture unit values. 370 fixture unit, that means it is between 60 and 500. So obviously we'll go for the higher value, 500. So if you move to the left side, you will find the stack diameter is 4 inches to the 500 fixture unit value. But you need to check one more thing in the last column, that is total discharge in each branch interval fixture unit is 90. This condition should be satisfied, that total discharge in one branch interval should not exceed 90 fixture unit value. But if you go there, you find that this 70 is okay, 90 is okay, 90 is okay, but here we have 120 fixture unit value. So these branches connected to the stack J is not satisfying the condition of 90 fixture unit value. So this is exceeding with one branch interval. This branch has more than 90 fixture unit value, so we cannot take this value for 4-inch pipe size. So we need to increase the pipe size from 4 to 5 inches. So if you select this 5-inch pipe size, you can see in the last column we have total discharge in one branch interval is 200 fixture units. Since 200 fixture unit is the maximum in each branch interval, if you see over here, we have all branch interval less than 200, that is 70, 90, 120 and 90. So our condition is satisfied, so we can select this 5-inch pipe size for this vertical stack J. So this is 5 inches. And then we have to calculate this offset runout pipe size, and the slope which we used in our project is 1/8 inches per feet. So this K section or runout or offset is going to be sized based on the table 6-5, maximum permissible fixture unit load for sanitary building drains and runout from the stack. So this is a runout from the stacked pipe, or it is also called offset. So how many fixture unit we have here? Same A, B, C, D. You need to sum up all these branches. That is 370 fixture unit over here. So 370 fixture unit with 1/8 inch slope. So 370 fixture units. It is in between 180 and 390. We'll go for the higher value, 390. So for 390 with 1/8 inch slope, you will find 5 inch pipe diameter. Even if you are using 1/4 inch slope, it will also be 370 will also be in between 216 and 480. Obviously we'll go for the higher value, 480. So same 5 inch pipe size. So since we have 1/8, so 5 inch pipe size we are going to use in here for this offset K. And then we have this vertical stack again representing by L. So here if you are calculating the pipe size for this vertical stack L, it will be the sum of all the fixture unit above offset and all the fixture unit below offset. This is the offset. Sum of branches above offset, sum of branches below offset, to get the size of this stack L. So we know that 370 here, and how much is here you can calculate. That is 370 plus branch E is 150, F is 180, and G is 190, H is 160, and I is 200. So total fixture unit value to calculate the size of this stack L is 1250 fixture unit. So as I told you, to calculate the stack pipe size we have to use this 6-3 table. Total fixture unit value for more than 3 story stack, more than 3 stories, we have to use this column because we have a 9-story building. So we have total fixture unit value is 1250. 1250 is in between 1100 and 1900. So obviously we'll go for the higher value, so we'll go for 1900. So for 1900 you can see that 6 inch pipe size. Same time we have to check the total discharge in one branch interval is 300 fixture unit. So each branch interval should not exceed 300 fixture unit value. So let's check and verify the condition. So maximum fixture unit in each branch interval is 200. So it is satisfied, this condition is satisfied that our each branch interval, that is total discharge in our each branch interval, is less than 350 fixture unit. We have a maximum of 200 fixture unit. So this condition is satisfied, so we can use easily this 6 inch pipe size for vertical stack L. And in the end we have to calculate this pipe size for this offset or runout represented by M. So total fixture unit value, it will be the sum of all branches from top to the bottom. We already know that is 1250 fixture unit. So this is runout or offset. As I told you that we have to use table 6-5 to calculate this offset pipe size that is going directly to the manhole, and total fixture unit value is 1250 and slope which we used is 1/8 inches. So 1250 is in between 700 and 1600. So obviously we go for the higher value, 1600. So 1600 you can find the pipe diameter, that is 8 inches. So we can use 8 inch pipe size. Again, if you note over here that 1250 is coming in between them, so we'll go for 1920. If you have a slope of 1/4 inches, still pipe size will be 8 inches. So since in our project we use 1/8 inches, so it's the same, that is 8 inch pipe diameter. That value is coming between 700 and 1600, and our fixture unit value is 1250. So we are going to use 1600 and pipe diameter is 8 inches. So M is 8 inches. So this is how you can calculate your drainage pipe size by using the tables from ASPE, American Society of Plumbing Engineers, IPC and UPC, that is Uniform Plumbing Code. But again, I have to tell you one thing, that you have to follow the local codes of your area. For example, if you are working in India, you have to get the values from the local authorities. These tables you have to get from the local authorities, because every region has its own codes and standards developed by them. For example, if you're working in the Gulf region like UAE and Saudi Arabia, Bahrain, Qatar, you have to follow their standards. This is an international standard which I have discussed in here. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Said Mohammad Hokas. The topic which I'm going to discuss today is related to the drainage vent pipe sizing. So there I have an Excel sheet, as you can see here, and these are the tables which I'm going to use for drainage vent pipe sizing. So I'm going to discuss two examples here. This is the first example and this is the second example. So in the first example, you can see that we have individual vent pipes which will do the sizing, and in the second example, this is the second example, you can see here if you see that we have the vent stacks that is A, B, C and D that are connected to the common vent header. This is our common vent header at the top of the vent stacks and then extended through the roof at one point. So this is the second example. So in first example, if you have noticed that this is the same example which I had used during the drainage soil stack pipe sizing. If you have not seen that video, I will give the link in the description below. You can watch it, because this vent stack pipe size is related to the soil stack pipe size, so you must watch that video. And if you see that here we have vent stack that is represented by section B. Vent stack is represented by section B, and you can see that this is the dashed line representing the vent pipe, and this is our soil stack is represented by A. So this is our second vent pipe, you can see here represented by F in the dash lines, and this E is basically representing the soil stack. So when you are doing the vent pipe sizing, three things should be known. First is the soil stack pipe size, second is the drainage fixture units connected to that soil stack pipe, and third is the developed length. So these three things should be known before doing the vent pipe size calculation or before getting the vent pipe size. So what is developed length in here? So you need to understand the developed length first. So developed length is basically the length of the vent stack is measured from the point of connection to the drainage system at its base point. So this is the base point from here to the point of discharge at the outlet above roof. So from the base point of the drainage system to the point of discharge at the roof level. So this is our high roof level and this is our low roof level. Six story, you can see that we have a low roof level in here. So from this base point of the drainage system to the top of the roof level, this is representing the developed length. Before starting the vent pipe sizing, there is one announcement about the channel membership. If you join my channel membership, you can get access to all Excel sheets, relevant softwares and carrier air conditioning design handbook. So basically the membership on my channel has 3 levels. Membership link I will give in the video description, or you can go to my channel and click the join button. So let's start the pipe sizing with the first example. So this is for the first example, you can see that the section B here As I said that vent stack is represented by section B. So I said that three things should be known to get the vent pipe size. So first is you have to check the soil stack pipe size. So I'm not gonna discuss the soil stack pipe size, how did we get this one. So for that purpose you should go for drainage system design or drainage pipe sizing video. I will give the link in the description below just to save the time. So I will proceed to the next step, that the connected drainage fixture units. So you can see that total connected drainage fixture units is how much: 90, 70, 120 and 50. So we have total 4 branches here, that is 90, 70, 120 and 50, total 330. So up till this point we have 330 fixture units connected here. So we write here 330 fixture units, and the developed length, which I said that from the base point, so we are talking about this vent pipe. So developed length is from the base point to the top of the roof level. So you can see that 10 feet, 10, 20, 30, 40, 50 and 55. So developed length is 55 here. So now we have to check the vent pipe size here. How much is the vent pipe size connected to the vent stack having, connected to the soil stack having size 5 inches. So we know that soil stack pipe size is 5 inches. Developed length is 55 and connected drainage fixture units are 330. So we're gonna use this table 9-1. We said that soil stack pipe size is 5 inches, 5 inches and 330 fixture units. So 330 fixture units is in between 200 and 500. So we'll go for 500 higher value. And so before going this, let me tell you about this table. These pipe sizes, 1/4, 1/2, 2 inches, these are basically vent pipe sizes. These are the connected drainage fixture units, and this is the soil stack pipe size. And in between we have these developed lengths. These are the developed lengths. So we know that 5-inch pipe size, soil stack pipe size, and 330 fixture unit will go for 500. And developed length is how much? 55. So 55 is in between 30 and 70. We'll go for higher value, 70. So 70, you will check the pipe size is 3 inches. So vent stack pipe size is 3 inches. So we got 3-inch pipe size in here. So same way you have to check for the second one, that is second stack pipe is represented by F. You can see in here. So how many branches are connected to this stack F? So we need to include the branches above this run out. We need to add this one also. So 330 plus 160 plus 200 plus 230, and the last one is 170. So total drainage fixture units connected are 1090. 1090 we can write here. So again we have to check the developed length. How much is the developed length? Since this one is connected from the base point of the drainage system to the top of the roof level, this is onto the low roof level. So total developed length is 10 feet, 20, 30, 40, 50 and 55. So again 55 developed length here, and 1090 range fixture units. And again you have to check the connected soil stack pipe size. You can get that one if you see the video, drainage pipe sizing video. So we use the table 9-1 again. 1090 drainage fixture units and soil stack pipe size is 6 inches and 55 is the developed length. So 6 inches with 1090 drainage fixture units, 6 inches and 1090 drainage fixture units. 1090 is between 960 and 1900, so we'll go for 1900. And developed length is 55, again between 20 and 70. We'll go for 70. Higher value, there is no 55, so we'll go for 70 and check the pipe size is 4 inches. Vent stack pipe size is 4 inches. So we have 4 inches here. So now I'm going to discuss the second example here. Here you can see that we have 4 vent stacks represented by A, B, C and D. These are connected to the common vent header. This is a common vent header and then extended to the roof. So we'll start from stack A. You can see here I have divided into different sections. Stack A, you can see that fixture units are 150 and developed length is 180. So 150 fixture units, 180 developed length. So we need to check the soil stack pipe size. So soil stack pipe size, and then we have to check the vent stack pipe size, and then we will check the header pipe size later. So first we check for the stack A, soil stack pipe size and vent stack pipe size for this section A. So first check the soil stack pipe size using the table 6-3. So we have 150 fixture units. 150 fixture units. Since we know that we have more than 3 story, so 150 fixture unit, we have to use this column. 150 is in between 60 and 500, so we'll go for 500 higher value, and we'll check the soil stack pipe size is 4 inches. So 4 inch. So now we have to check the vent stack pipe size. So we know that developed length is 180 feet, and we know that soil stack pipe size is 4 inches, and we know that drainage fixture unit connected are 150. So we use this table 9-1. So 180, 150 fixture units, 180 developed length. 150 fixture units, 4 inch pipe size. 150 fixture units, 100 and 200 is here, so we'll go for 200. And developed length is 180, is in between 90 and 250, so we'll go for the higher value 250 and check the vent pipe size is 3 inches. So vent pipe size is 3 inches. So next is A to B. This is the vent header section A to B. So here we will check the header pipe size now. The developed length is now 180 plus 10 more, that is 190. So developed length is 190, 180 plus 10. This is the 10 feet. Drainage fixture units connected are same, that is 150, same. So 150 fixture units and 190 developed length. So 150 is, again we check the size for the soil stack is again 4 inches. So 4 inch pipe size and 150 fixture units and 190 developed length. 150 fixture units is in between 100 and 200, and 180 is the developed length is in between 190 is the developed length is between 90 and 250. You'll go for 250 again. Pipe size is 3 inches. So header vent pipe size is 3 inches. Section A to B header pipe size is 3 inches vent pipe size. So now we'll go for stack B. 200 fixture units, 290 developed length. 200 fixture units, 290 developed length. Now we'll check for soil stack pipe size and vent stack pipe size. So 200 drainage fixture units. First check the soil stack pipe by using the table 6-3. So again, more than 3 story, 200 fixture unit is in between 60 and 500. So we'll go for higher value 500 and check the pipe size is 4 inches. So pipe size soil stack is 4 inches. Now check for the vent stack pipe size. So we know the soil stack pipe size is 4 inches. We know drainage fixture unit 200 and 290 is the developed length. Now we check the vent stack pipe size. So again we use table 9-1. So 4 inches, 200 fixture units and 290 developed length. So 290 developed length is in between 250 and 900. So we'll go for higher value 900 and check the vent pipe size is 4 inches. So this stack B vent pipe size will be 4 inches, this vent pipe. And then we'll go for header pipe size B to C. Now we'll check for header pipe size B to C, this one. So we know that the drainage fixture unit A to B is 150 and this stack B is 200. So 150 plus 200, it will be 350 for the point B to C. So you can see here 150 plus 200, that is 350 drainage fixture units. So now the developed length we can see here, at point A to B total developed length was 180 plus 10, that is 190, plus 40, 190 plus 40, that is 230. You can see here 190 plus 40, that is 230. So now we check the header pipe size B to C. So we know that drainage fixture unit 350. So first check the soil stack pipe size, how much it would be. So based on this we have to check header pipe size. So 350, if we check the, so again in between this, and we'll go for higher value 500, 4 inches pipe size. So 4 inches we have to check developed length 230 and 350 fixture units. 4 inches 350 fixture units is in between them, so we'll go for the higher value 500, and developed length is 230. 230 is between 180 and 700. We'll go for higher value 700 and check the vent pipe size is 4 inches. So the header vent pipe size B to C is 4 inches. So now I'm gonna skip B to C, C to D. B to C is already done, so I'm gonna skip C to D and stack C just to save the time. So I'll go for the last one, stack D, 500 fixture units and 270 developed length. So 500 fixture units at stack D and 270 developed length. First check the soil stack pipe size for 500 fixture units. So again 6-3 table, 500 fixture units, soil stack pipe size is 4 inches. 4 inches, okay. And then we know that developed length is 270. You can see that here, developed length 270. So soil stack pipe size is 4 inches, 270 developed length and 500 fixture units. So 4 inches, 500 fixture units and 270 developed length is in between 180 and 700. We'll go for high value 700 and check the vent stack pipe size is 4 inches. That is 4 inches, you can see here. So now the last one is from D to the outlet. You can see that from D to the, this is the roof level extended up to the roof. So for total developed length will be how much? That is C to D. C to D it was 260. C to D it was 260 plus 40 plus 10. So 260 plus 40 plus 10, that is 310 total developed length. And fixture units, if you see that here 500 fixture units, here you can see that C to D fixture unit, which we calculated is 550. So 550 plus 500, it will be 1050 fixture units. So we know that developed length, we know that drainage fixture units. So we can calculate the vent header pipe size. So first check the soil stack pipe size, how much it would be on 1050 fixture units using table 6-3. So 1050 fixture unit is in between 500 and 1100. So this value 1100 we will take. So soil stack pipe size will be 5 inches. So 5 inches with 1050 drainage fixture units and 310 developed lengths. Let's check the header pipe size, vent header pipe size. So 5 inches, 1050, that is equal to almost 1100. So 5 inches soil stack pipe size, 1100 drainage fixture units, and developed length is 310. 310. So 310 is in between 200 and 700. So you will go for the higher value 700 and check the vent header pipe size is 5 inches. 5 inches. So you can see that this is the 5 inches. So this is how you can do the drainage vent pipe sizing. If you have the individual vents, or you have the vents that is connected to the common vent header. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Saeed Mohammad Waqas. I'm back with another video. The topic which I'm going to discuss today is related to the hot water recirculation system, and this topic is very important, so please make sure to watch the video all the way till end and don't forget to subscribe my channel. So let's start hot water recirculation system design. So as you can see that there I have prepared an Excel sheet and I have taken an example of 24-story building, and we're gonna design the hot water recirculation system for that 24-story building. So here I have a table also which I'm gonna use. So first thing you have to do here is you have to write your risers, all the risers in here which you have shown here in the figure. So as you can see that I have given the name for each riser, like riser 1, 2, 4, 3 and up till 11, and hot water piping is already shown here in the drawing, as you can see that. So if I will zoom and you guys can see, this is our water heater installed in the basement, and this is the hot water supply piping. This is the hot water supply piping from here, and if you see that this is going all the way up till 24 story, and then there's a recirculation piping, hot water recirculation piping, and this recirculation is going back into the heater. So we are going to design this recirculation lines. So we are going to design the risers and we're going to design the main for recirculation system. And hot water piping sizes are already mentioned in here. So if you remember that I have made a video on domestic hot water pipe sizing. So if you don't know how to do this hot water pipe sizing, you can go back to my channel and you can watch the video about domestic hot water pipe sizing. So I have to write all the risers in here, and main also. This is the risers and this is the main, from risers to one riser to another riser. That means this is the horizontal pipe. You can see that this is the horizontal pipe for recirculation, this one. So first you have to do is you have to write the hot water pipe sizes here, and the second thing you have here is hot water piping BTUs, loss per hour per unit length. So this is you have to write in here, then you have to write the length, and then hot water piping BTUs loss per hour based on this length, and then you have to calculate this hot water recirculation piping BTUs per hour, and in the end you have to calculate this GPM to overcome the heat losses. So first of all I'm gonna take main from heater to the riser 1. So as you can see that this is the heater which we have in here, and this is the hot water supply piping. You can see in here this, and size of this pipe is 4 inches, hot water supply pipe, and sizes for recirculation pipes are unknown, so we are going to calculate. So this hot water supply pipe size, you can see that it's 4 inches up till this point, and this point is riser 1, and then again you go over here and you will see the size is same, 4 inches, 4 inches, 4 inches, you can see here. So from this point 3, riser 3, size is changed to 3 inches, then you have 3 inches up till here, this point 14, riser 14. So after that your size is changed again to 2.5 inches. You can see here 2.5 inches, again 2.5 inches, and then here you have 2 inches. So if you see from main, from heater to riser 1, so heater to riser 1 we have write 4 inches in here. So same way which I have told you, you have to write the sizes from riser 1 to riser 2. That means from riser 1 to riser 2 there's a main pipe in here, and size is 4 inches, you have to write 4 inches. And from, let's say we take another like riser 12 to 14. How we get 3 inches? So this is 12 and this is 14. In between them we have horizontal pipe, the main pipe, and you see that the size is 3 inches. Hot water pipe size is 3 inches. So we have write 3 inches. So in the same way you have to write the pipe sizes here one by one for the hot water. And hot water piping BTUs, how you will get this one? So you have to use a table for this thing. So you go back here and you check the piping heat loss per linear feet for 140 degree Fahrenheit water supply temperature and 70 degree Fahrenheit room temperature. Here if you see that we have bare pipes and insulated pipes. So if you have a bare pipes without insulation, you have to use these values. If you have insulated pipe, you have to use this column values. Since our pipe is insulated, half-inch fiberglass insulation, so this one. So first I have 4-inch pipe size, so I have to write the heat loss value for 4-inch pipe size with insulation. You see that it's 46, so I have to write 46 value in here. So same way you have to write one by one. So let's say 2 inches. 2 inches is how much? 28. So we have BTUs per hour, so we have to write 28 in here. So once this is done, you have to go for the next column, that is length. Length is very simple. You just have to go to your AutoCAD plan and you have to measure the length from one point to another point. So as per the AutoCAD plan, you have to check the lengths and you have to write lengths here. So I already write the lengths here. So if you can see that lengths are already mentioned here, like 20, 10, 10, 10, 20, 20, 30, 20, 20. So according to that I have write all the lengths in here. So you just have to check it from the AutoCAD and write in here one by one. Now the next column is hot water piping total BTUs loss per hour. How you will get this value? Now we know that the length of the pipes and we know that BTUs per hour per unit length. So you just need to multiply these two figures, then you will get the hot water piping total BTUs loss per hour. So one by one you have to just multiply these two, like hot water piping loss per hour per unit length into length, you will get the hot water BTUs per hour. So one by one you have to calculate for all of the piping. So next thing over here is the hot water recirculation. This is the main thing which we are focusing on, because this is the hot water recirculation system design. So if you see in here, hot water recirculation piping BTUs loss per hour, this you have to calculate in here. And how you will get this one? Since we don't know the recirculation pipe size, this is what our case that we want to calculate the sizes for the recirculation system, hot water recirculation system. So we don't know the sizes for hot water recirculation system. So there is an assumption as per IPC, International Plumbing Code, or ASPE, American Society of Plumbing Engineers. But we have to do, there's a standard that we can, if we don't know the sizes, we can take 2 by 3 of this value, which heat loss we calculated here. We can take 2 by 3 of this value. 2 by 3 means 0.67. So you just need to multiply this value with 0.67 and you will get the hot water recirculation piping heat losses. So one by one you have to multiply with 0.67. So this is a standard value, as I told you, as per IPC. So you have to calculate one by one for the hot water recirculation piping heat losses. So next thing you have to calculate here is the GPM, that is gallons per minute, to overcome the heat losses based on 20 degree Fahrenheit temperature difference. As we mentioned earlier that supply temperature from the heater is 140 degree Fahrenheit. So based on our assumption of 20 degree Fahrenheit temperature difference, that means hot water supply temperature is 140 and recirculation is 120. So based on 20 degree Fahrenheit we have to calculate the GPM to overcome the heat losses. So how you will get this one? You just need to add these values, that is for the hot water piping plus hot water recirculation piping divided by 10,000. You will get the GPM. So how did I get this 10,000 value? So I will tell you also how I get this one 10,000. So as we know that 1 gallon of water weigh 8.3 lbs. You can check over the internet that 1 gallon of water weight is 8.3 lbs. so pounds, and 1 BTU is equal to heat necessary to raise 1 degree Fahrenheit, and recirculation for 1 GPM. Since it is based on 20 degree Fahrenheit, so we just need to multiply this 8.3 based on 20 degree Fahrenheit, so you will get 166 BTUs per minute. So if you want to convert into hour instead of minute, you just need to multiply with 60 and you will get 9,960. That is almost equal to 10,000. So this is why I have divided this value with 10,000. So one by one you have to get these values over here in this column. For this one you just need to add hot water piping total BTUs plus recirculation piping BTUs divided by 10,000. You will get the GPM in here for that particular section of the pipe. So that means main from riser 8 to 10. This is our riser 8 and this is 10, and this is the main in here, horizontal pipe. So the GPM over here is 0.13 GPM, which we have right in here. So this is done. After that we'll go for the risers. So if you see that riser 157, I write it combined because the length was same, that's why I write 157 together, and 2414 I write together because of the length. So I have write together all of these just because of the length. So if you go for riser 1, 5 and 7, so 1, 5 and 7, so you have to check their lengths from the AutoCAD plans and you have to write the lengths accordingly. So riser 1, if you see that which pipe do we have in riser 1, hot water piping. I'm talking about the hot water piping, what we have here in riser 1 for the hot water piping. So if you see that in the riser 1 we have 2.5 inches, 2.5 inches, 2 inches, 1.5 inches and 1/4. So we have to write all this pipe there. You can see that 2.5, 2, 1.5 and 1/4. So all of pipe you have to write in here accordingly. And again you have to get this hot water piping BTUs per hour per unit length from the table. So 2.5 inch pipe, how much it is? 32. So 1/4, how much it is? 21. That is 21. So this is how you have to write one by one for each pipe size. So length, again I am telling you have to check from the AutoCAD plan and you have to write it. So I already write the length in here. So 160 feet, 27 feet, 18 feet and 6 feet. And for what you have to do, again you have to multiply in order to get your hot water piping total BTU loss per hour. You just need to multiply the length with per unit length BTUs loss. So you will get the total piping loss in BTUs per hour. So same way you have to do for this one and this one. So once you are done with this, you have to just get the total of this value, total heat loss for the hot water piping. And this one is again same assumption, we have to take 2/3 of this value because we don't know the pipe size for recirculation system. So we are going to take 2/3 value of this one. So if you multiply this with 0.67, that is 2/3 of this value. It is 4,323 BTUs per hour for recirculation piping heat losses. And this thing again you have to calculate sum these two values and divide by 10,000. You will get the GPM, 1.08 GPM. So as you know that this is for one riser which we have calculated, and here if you see that we have 3 risers, that is 1, 5 and 7. So if we have 3 risers, that means you need to multiply this value with 3 and this value with 3. So I already multiplied this with 3 and this with 3. So we got the total BTUs for hot water piping and hot water recirculation piping heat losses for 3 risers. This is for individual riser and this is for 3 risers. So same way you have to other risers 2, 4 and 14. So I'm gonna take one more here just to save the time. I'm not gonna do for all of these. So I'm gonna take one more example here for riser 6. So if you see riser 6, so we will check now, check the pipe sizes in riser 6. So this is riser 6, and if we check the pipe sizes, this is 1.5, This is the hot water pipe sizing again. This is 1.5, this is 1/4, 1/4 and 1 inch. So we have 1.5, 1/4 and 1 inch, three pipe sizes here. So 1.5, 1/4 and 1 inches. That's how we write the pipe sizes in the riser, and we will write the heat loss values for each. Same way, you have to check these values from this table and you have to write in here. And these lengths you have to get from AutoCAD plans and you have to write in here. And hot water piping BTUs per hour, you have to get, just multiply this per unit BTUs per hour loss for hot water with this length. You will get the total hot water heat loss per hour for the hot water piping. So one by one you have to calculate for all pipe sizes and then you have to sum it up in here. And then what you have to do in here is you just have to calculate the second one, that is 2/3 of the total value, 2/3 of the total value. So you just need to multiply this with 2/3, that is we are taking 2/3 of this value, that is 0.67, and you will get the heat loss for the recirculation piping, hot water recirculation piping. So in the same way you have to get the GPM. You just need to sum up hot water piping BTUs per hour loss and recirculation hot water piping and divide by 10,000. You will get the GPM, that is 0.80. So this is how you have to calculate the BTUs and GPM for the remaining risers. So here we have 4 risers, you can see that. So you need to multiply with the 4 to get the total BTUs, and you need to multiply with 4 to get the total heat loss for recirculation and hot water piping. So after that what you have to do is you have to sum up your heat losses for hot water piping and recirculation hot water piping. So if you sum up the hot water piping heat losses, it's around 95,534 BTUs per hour, and if you check for recirculation losses, this one is around 64,000 BTUs per hour. Hot water recirculation piping loss 64,000. So total recirculation rate will be how much? It will be the sum of both hot water piping plus hot water recirculation piping. That is 1,59,542. That means almost 1,60,000 or 160,000 BTUs per hour. So how you will get the required flow rate? Required flow rate, how you will get? You just need to, same way, you just need to divide the sum of these two, that is hot water piping heat loss plus hot water recirculation piping heat loss, divide by 10,000 to get the required flow rate. So required flow rate for our system is, required recirculation flow rate is 15.95 GPM. So 15.95 GPM is required. And if you check in here, the next thing is uniform friction head loss. It is recommended to have a uniform friction head loss of 2 to 4 feet per 100 feet. So here we have taken 3 feet per 100 feet uniform friction head loss, and developed length of the run which we have to calculate, that means from heater to the most remote riser. So this is our heater and most remote riser. If you see that this is our most remote riser, that is 11 at story or floor number 11, floor number 24. We have the most remote riser, that is 11. So from here recirculation piping, if you check that hot water recirculation piping to the heater, this is our developed length total to the most remote riser, that is 11 number riser. So if you check from the AutoCAD plan, you can get these lengths, and according to that you have to write your lengths. So this is for the riser, due to the riser 207, this is from the riser recirculation 207, and this is for the horizontal piping to the main, from main to the heater. So 207 is due to the riser and 275 is the main piping length. So total is 482 feet is the developed length. So how we'll get the equivalent length of run? Since we don't know the sizes for recirculation, so we're gonna apply the general thumb rule for fittings to get the total equivalent length of run. So we know that the total piping length for the straight piece of pipe, but we don't know for the fittings and the valve. So what we're gonna do is we're gonna take 10% of this value to get the equivalent length of run. So you can see that this value plus 10% of this value, so we'll get 530 feet is the total equivalent length of run. So now we know that equivalent length of run, and we know the friction head loss, that is 3 feet per 100 feet. It is recommended value 3 feet per 100 feet, that's why we have used this one. If you increase this value to 5, 8 or 10, you will have more losses. That's why we have selected 3 to have a uniform losses. So if you want to calculate the head required now for recirculation system, so how you will get that? You just need to multiply this uniform head loss with the equivalent length which we have calculated in here divided by 100. You will get the head. So head for recirculation system required is 15.91 feet. That means 16 feet head is required for the recirculation system. And GPM we already calculated, that is 16 GPM. So now the last thing which we have to do here is we have to size the hot water recirculation system. This is very important. So how we did this thing? So basically I have used this formula. For the brass or the copper piping you have to use this equation, and for galvanized or steel pipe you have to use this equation. Since we have a brass or piping, so we have used this formula. So we have the H value, head we know that 16, and length, its per unit length we have calculated here. So if you, and Q we also know that is 16 GPM in here. So if you know all the values in here, so the thing which remaining is D, that is diameter for piping. So you can calculate easily after putting all the values. So based on this thing, there is a formula developed in here. If you change the GPM one by one, you will develop this this thing, that is half inch is equal to 1.8 GPM. So from this equation I got this values: half inch equal to 1.8 GPM, 2 inch equal to 34.6 GPM, and 4 inch equal to 181 GPM. So now we are going to use one by one to calculate the recirculation pipe sizes. So one more thing, if you have to check in here, for all the risers, if you see that GPM is 1.08 for 157, and 2, 4 and 14 GPM is 1.02, and 1.14, 1.80, 1.04, 0.92. So you can see that minimum GPM here is 1.8 GPM, and all the GPM which we have calculated in here for the risers are less than 1.8 GPM. So the minimum size, if you see that here is half inches available, that means our riser will be half inches, all the risers, because their GPM is less than 1.8. So we can use half inch in here, but we will not gonna use half inch. The minimum size recommended is 3/4 inches, 3 by 4 inches. So instead of half inches, we're gonna use risers 3 by 4 inches. The reason why I'm gonna use 3 by 4 inches instead of half inches, because pipe size will be very small, and with the time maybe deposits will be developed inside the pipe and it will gonna block the pipe. So it is better to use 3 by 4 inches pipe size instead of half inches, even if it is 1.8 GPM. So I'm gonna use minimum pipe size is 3 by 4 inches for all the risers. If you see that all GPMs is less than 3.5, so all the riser size for the recirculation hot water, it will be for risers, it will be 3 by 4 inches. So riser size is done, 3 by 4 inches. Now what we're gonna do, we're gonna calculate the size for the main recirculation piping in here, like between 9 to 11 riser, between 6 to 9 riser, between 5 to 7, between 1 to 2. We have to calculate the main horizontal piping. So we'll do one by one. So first is riser 11. So it start from the most remote one. If you see that this is riser 11 in here, and we're gonna get the size for this main pipe, main recirculation pipe in here, which is connected to water heater in here. So we'll go one by one and calculate one by one size to the water heater recirculation pipe sizes. So here you have section 11. This is riser 11. and we are going to get the size for this horizontal pipe in here, this one. So this is we have 11. If you see here, this is riser 11 plus main 9 to 11. First we calculate the GPM, and based on GPM we'll get the sizes. So between 9 to 11, if you see that how much is the GPM we got from main from riser 9 to 11, this one. If you see, the GPM is 0.12 between 9 to 11, between 9 and 11 riser, and 11 riser is how much GPM? Riser 11, this one, remember that 0.12, and riser 11 is 0.92. So 0.92 and 0.12. So 0.92 plus 0.12 is 1.09 GPM total. So if you see that 1.09 GPM, based on the assumption and based on the values applied to this formula, we got this thing. So 1.09 so 1.09 is less than 3.5 GPM. So we can use 3x4 inch pipe size in here. So we're going to use 3x4 inch pipe size for this one. So that means we can use 3x4 inch pipe size up till 3.5 GPM. If we have 3.6 GPM, then we have to increase the pipe size to 1 inches. So I'm gonna take another example in here. So let's take second one also, 1.04. So 0.92 plus 0.12, it is 1.04, sorry. So let's take the second main pipe size. So now we will calculate the size for the second one here, second one. So if you see, the second one is riser is 9. We have to add this value also, which we calculated earlier. This value, first value which we have calculated here, plus riser 9 GPM value, plus between sections riser 6 and 9. So if you check previous value which we'll add, that is 1.04, which we have right in here, plus riser 9 plus main 6 to 9. So if you see that riser 9 GPM is how much? You see here, that is 0.92. So we have to write riser 9 0.92, and the last one here is main 6 to 9. If you check the main from 6 to 9, this one GPM is how much between 6 to 9? So main from riser 6 to 9 GPM is 0.11. So you have to write 0.11 here. So you know all the GPMs now, just add it, total it will be 2.07. Again 2.07 is less than 3.5 GPM, so we can use 3x4 inch pipe size. So we have used 3x4 inch here. So I'm gonna use some other example here now. So let's say I'm going to calculate for this one. So you have to consider the previous one also. Previous one is 11.34 plus riser 3 and main 4 to 3. That is main is this one, riser 3 and main 4 to 3. So if you see that riser 3 is in here and 4 is here, so we have to check GPM for this riser 3 and all the GPM, previous GPMs here, plus riser 3 GPM to get the size for this pipe segment. So what you have to do is GPM for riser 3 and GPM for between riser 3 and 4 and the previous all GPMs. So riser 3 is how much? 1.14, and between 4 to 3 is 1.08. So you can see that riser 3 value is 1.14 and 0.08 is for main between 4 and 3, and this is the previous GPM which we have to add in here to get the size for the next pipe segment. So if you see that total which we calculated here is 12.56 GPM. So 12.56 GPM, if you see here, it's 12.4 GPM. Up till 12.4 GPM you can use 1/4 inch, but since this 12.56 is greater, so we have to increase the size to 1.5 inches. So that's why we have used 1.5 inch for this pipe segment. So you can use 1.5 inches up till 18.3 GPM. You can use this size. After that you have to increase the size again. So one more last item I will tell you here. Same way you have to do for this one also. So last item is riser 1 plus main to heater. So if you see here, so last item we have riser 1 and all the previous GPM which we have calculated to get the size for this pipe segment. To get the size of this pipe segment, you have to add all the GPM which you have calculated in here plus riser 1 GPM, and this main pipe GPM, recirculation main pipe GPM. So from section 1 to the heater. So if you see that from heater to the riser 1, how much is the GPM we calculated? 0.15. And the riser 1 GPM, how much we got in here? That is 1.08. So 0.15 and 1.08. So if you see here, 1.08 for riser 1 and 0.15 is for main to the heater 1. And 14.6 is the previous GPM which we have calculated. So adding all these values, you will get 15.99 GPM total. So 15.99 GPM is less than 18.3 and greater than 12.4. So that means we can use 1.5 inch pipe size in here for that pipe segment. So this is how you can do the hot water recirculation pipe sizing, or you can design your hot water recirculation system. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Thank you. Hello guys, this is Saeed Mohammad Waqas. The topic which I am going to discuss today is related to the combined stormwater and sanitary system design. As you can see that there I have prepared an Excel sheet for this combined stormwater and sanitary systems design. So this is the drawing which I'm gonna use, and I will calculate the pipe size of each segment represented here on the drawing. So these are the tables which I'm gonna use during calculation. So first of all, you can see here we have a pipe mark. You can see that I have divided each pipe segment and give it a name. So here it is represented by a pipe mark, and then we have a fixture unit, then we have a demand, and then equivalent drained area in a square feet. Since this is a combined stormwater and sanitary system, we need to convert this fixture unit represented here on the drawing, because this fixture unit is from the sanitary drainage system. We need to convert this into equivalent drained area and write it here in this column, equivalent drained area. So for stormwater, is you can see that we directly here we have a roof area in here that is going to be drained is 4,000 square feet, and here it is represented 3,500 square feet, but we need to convert these fixture units into the equivalent drained area, and we can write in here. And then you can see the pipe breakdown. That means if you see in here this pipe section C, since the flow is from point A, flow is towards the point C, so flow at point A and point B. So flow at point C, it will be the sum of point A and B. So we're gonna calculate up till point Q, and we'll do the sizing up till point Q. So we're gonna start from this furthest outlet 256 fixture unit stack P2 point. So first thing over here, important thing is here is the location. So where are you going to perform this one, because rainfall rate is different for each city in the country, or different in different countries. So first of all we have to check the location. Since I'm talking about New Delhi, India, so first I have to get the maximum rainfall rate in inches per hour in New Delhi. So there I have table here for 72 different cities in India. So since I'm you can see that rainfall per hour, this is for 1 hour, this is for 3 hours, this is for 6, and this is for 24 hours. Since I'm talking about New Delhi, per hour rainfall rate in centimeter is given here. So as you can see here, its rainfall is per hour is 11.17 centimeter per hour. So if I want to convert this into inches, how much it will be? 11.17 divided by 2.54. That means 4.39 or 4.4 inches per hour. So that's how I write here 4.4 inches per hour for New Delhi. So for different cities, almost 72 cities data is in there. You can choose the cities. So here the procedure for combined stormwater and sanitary drainage system, there's a procedure that which we need to follow as per standard, that if you have less than or equal to 256 fixture units, then equivalent drained area you take is 1000 square feet. Let's say if you have 200 fixture units, then equivalent drained area which you will take as per procedure is 1000 square feet. And if you have more than 256 fixture units, then equivalent drained area, you will get the equivalent drained area 3.51 square feet per fixture unit. That means every increment in the fixture unit after 256 you need 3.51 square feet per fixture unit. And how did you get this value, I will tell you later. So this is the piping slope which we have used in our project, that is 1/8 inch per foot slope which we have used in here. And now I will tell you how did I get this 3.51 square feet per fixture unit. If you have more than 256 fixture units, for every increment in the fixture unit after 256 you have to use 3.51 square feet per fixture unit. This depends on the rainfall. So since we know that 1 GPM is equal to 60 gallons per hour, so if you want to convert this gallons per hour to cubic feet per hour, you need to divide 60 divided by 7.5. You will get 1 GPM is equal to 8 cubic feet per hour. And we know the rainfall rate in New Delhi is 4.4 inches per hour. If you want to convert this inches to feet, so simply you need to divide 4.4 divided by 12, you will get in a feet, that is 0.37 feet per hour. So now we want to get the how much GPM will be conveyed from the surface, because here if you see that we have a GPM also, so how much GPM will be conveyed from the surface should be converted to equivalent drained area. So that's why we are converting this one. So how you will get this 21.82 square feet, you just need to divide this 8 cubic feet per hour by 0.37 rainfall rate in New Delhi, India. So you will get 21.82 square feet. Now what does it mean, 21.82 square feet? That means 21.82 square feet of horizontal area is equivalent to 1 GPM that must be conveyed from the surface. Or in other words, the 1 GPM collect on 21.82 square feet of horizontal surface if you have a rainfall rate of 4.4 inches per hour. So now we'll go towards the pipe sizing of this combined stormwater and sanitary system. Before proceeding towards sizing, there's one announcement that if you guys join the channel membership, you will get access to exclusive perks like Excel sheets, softwares, and drawings. Whatever I use in the video or in the future videos, you will get access if you have a membership on the channel. And this channel membership is really cheap, around $2 per month. So if you guys want to join the membership link is given in the description, you can join from there. So before proceeding towards the pipe sizing of the combined storm and sanitary system, you can see that this is a combined system we have in here. This is a sanitary drainage piping line, and this is the stormwater line, and here it's combined together, and same thing over here. And one thing you need to understand about the leader pipe and the sanitary drainage pipe. So let's me go to the piping section and explain you here. So as you can see here, this is the combined stormwater and sanitary drainage system. This is the soil stack pipe, and this is the runout from the stack, and this is the main combined storm, this main combined storm and drainage pipe. And you can see that this is the leader pipe for the storm water, and there we have a trap, and then we have horizontal pipe in here. It is important to understand this thing before proceeding towards the pipe sizing. So you can see that the stormwater connection should be at least 10 feet downstream from any branch of the building drain. As per the code, you have to maintain minimum 10 feet distance between the soil stack and the stormwater pipe. So now proceed towards the sizing of the system. And one more thing you can see in here, that this is the roof over here, and this is the roof drain through which water will be drained down. And this is basically a primary scupper, and here you can also see that we have secondary scuppers. These are the secondary scuppers installed in the parapet wall. These are the parapet walls. In case this drain is blocked or clogged, in that case water will drain down from the secondary scuppers, as you can see in here. And these scuppers are installed normally 2 inches above the roof level. So first we'll start from this point, and we'll go up till point Q. So we're gonna start from this point. You can see that this is the stack P2 over here. This is the stack we're talking about. This is the stack pipe, and this is a horizontal run out from the stack. So there we have a stack with 256 fixture units represented by P2. So pipe P2, 256 fixture units. Since we said in here that 256 fixture units, if we have less than 256 fixture units, then equivalent drained area we get is 1000 square feet as per code. So 1000 square feet we have to use in here. But before that, I forgot to tell you how did you get this 3.51 square feet per fixture unit. So since we know that 1 GPM conveyed to 21.82 square feet of the horizontal surface if you have a rainfall of 4.4 inches per hour. So this 0.161 you need to multiply with this area which we got here is 21.82. And how did we get 0.161? So every fixture unit after 256 required 0.161 GPM. So that's why we write 0.161 into we talk about 1 GPM is 21.82. Once you multiply these two, you will get 3.51 square feet per fixture unit, and this will be used only if you have fixture units more than 256. Then each fixture unit drainage area you will get by 3.51 square feet per fixture unit. If you have less than 256, less than or equal to 256 fixture unit, then you will get by this procedure you have to get 1000 square feet drained area. Since we have 256 fixture unit in here, so we are going to use this 1000 square feet area. You can see that equivalent drained area is 1000 square feet. So now the reference table here which we have to use is 6-3 to get the pipe size. Since this is a stack pipe and we have more than 3-story building, so this is a 6-3 table. There you see 3 columns in here. If you have seen my drainage pipe sizing video or drainage system design, I have used the same table 6-3 and 6-5 for drainage system sizing for the stacks and the runouts. If you have not seen that video, I will give the link in the description below. You can watch it. So since we have more than 3-story building in height, so we have to use this column in here. So how many fixture units we said? 256 fixture unit in here. So 256 fixture units. 256 fixture units is this is 60 and this is 500. So 250 in between them, so we'll go for the higher value 500, and if you will check here is 4 inches. So that's how we got 4 inches pipe size in here. Then move to the section A. Section A is basically the run out from the stack. This is basically a run out from the stack. So we have to use table 6-5 to get the pipe size. We know the fixture unit at point A is also 256. It's same. So this is the run out So we're going to use table 6-5. So this is table 6-5 which I'm going to use. Since we know that the slope which we have used here is 118 inches per foot, and fixture unit is how, so we have to follow this column 18 inch per foot slope, 256 fixture units in between them. So we'll go for the higher value 390. You check the pipe size here is 5 inches. So the pipe size from the stack to the run out to the main pipe is so this section A is 5 inches, this using table 6-5. So now we'll go to this is stormwater pipe having a drained area of 3500 square feet. Surface drained area is 3500 square feet, and then we have a trap in here, as I talked here about the trap. This is a leader pipe, this is a trap, and this is a horizontal pipe. So first we'll talk about the leader L2 before trap. This is the leader L2 having 3500 square feet. You can see in here. So we have to use table 7-1 to get the size for this L2. So I'm gonna use 7-1 table, and since we are talking about the leader drained area, so we're gonna use this column, and we said that 3500 square feet. So 3500 square feet is in between 2200 and 4600 square feet, the leader drained area column. So we'll go for the higher value of 4600. So if you check the pipe size in here is 4 inches diameter, so we have to use 4 inch here. So after the trap, you see the horizontal pipe here. This is represented by B. This is represented by B. So 3500 same equivalent drained area at this point. So we have to get the size from the same table 7-1. But this time we have to use 1/8 inch per foot slope column, because this is the horizontal piping drained area for the various slope. Since we know our piping slope is 1/8 inch per foot, and 3500 is in between these two, 3340 and 5350. So we'll go for the higher value, that is 5350. Then this is basically a fixture units. So if you see over here to the left side, the pipe diameter is 6 inches. So that's how we got 6 inches pipe size in here for section B. Now if you see the section C, it is the sum of the flow from the point A and the B. That's why I have written here is C equal to A plus B. Now if you check the drained area at point A is 1000 square feet. We already converted 256 fixture unit to 1000 square feet, and this one is already in square feet, equivalent drained area in square feet. So total it will be 4500 square feet at point C. How we get this 256 fixture unit equal to 1000 square feet, we already talked in here. So total now here is 4500 fixture unit. It is a combined system for stormwater and sanitary system. So we're going to use 7-1 table to do the pipe sizing for at point C or section C. So C section 4500 square feet, use table 7-1 again. So 4500 square feet is in between these two values, so we're gonna use the higher value 5350 fixture unit and check the pipe size in here. Again, this is horizontal piping, so we are using 1/8 inch per foot slope. So 5350, the pipe diameter is 6 inches, so we have used 6 inches in here. So in the same way you have to do for other pipes in here, like 180 fixture unit, 4000 square feet, and then at point F it will be the sum of D and E. And then how you will get for G, it will be the sum of C plus F. And then same way you have to do for this P4 stack, then horizontal run from the stack represented by H, and then P3 stack, and then horizontal run is represented by I, and then you have J over here, and then at point K it will be the sum of G plus J here, that is G plus J, and then you have to do for this one. And for this GPM you have to use since we talk about 1 GPM conveyed equal to 21.82 square feet, so equivalent drained area you just need to multiply 120 with 21.82, you will get the drained area for this one. So now I'm talking about this last one over here. So I will do the sizing for stack P5 first, having 400 fixture units. P5 400 fixture units. So this is the stack P5, so we're going to use the table 6-3. So more than 3 story we have to use again, and 400 fixture units in between 60 and 500, so we'll go for higher value 500, and we'll check the pipe size is 4 inches. So P5 is 4 inches. Again we have the horizontal run from the stack, that is represented by N. So for horizontal run out from the stack we have to use table 6-5. You can see in here again same fixture units from the stack. So 6-5 maximum per visible fixture unit load for this one you can see in here. The slope for the pipe is 1/8 and 400 fixture units. So we have 390 and 700, so we go for the higher value 700, that is more than 390 fixture unit, and you will check the pipe size here is 6 inches, having 1/8 inch per foot slope. So here you can see that 6-inch pipe size we have used in here. Now next is O, that is coming from the sump having 100 GPM drained from that point. So this is 100 GPM, we know that. So we are going to use 1 GPM required 1 fixture unit over here. So 1 GPM required 1 fixture unit in here, so 100 GPM required 100 fixture unit in here. So we have used 100 fixture unit, and again this is the runout from the sump number 2. So for the runouts we have to use this table having 1/8 inch per foot slope, and 100 fixture units between 20 and 180. So we'll go for the higher value 180, and pipe size is 4 inches. So we have used the pipe size 4 inches here. So next is point P. It will be the sum of point N plus O. P, that is the sum of N O, you can see in here. And if you see the fixture unit which we calculated here is 100, and at this point we have point N is 400, point O is 100, and is 400, you can see in here. So total fixture unit at point P it will be 400 plus 100, that is 500 fixture unit in here. So again this is the horizontal run out here for drainage system. There is no stormwater pipe in here, so we can use table 6-5 to do the sizing for section P. So 6-5, 1/8 inch slope per foot, we have to use this one, and we talk about 500 fixture units. So 390 we have, 700 we have, so we'll go for 700 and check the pipe size because we don't have 500 in here, so we'll use 700. So 700 pipe size is 6 inches. So you can see in here for P section pipe size is 6 inches. Now the last section here is Q. Q, it will be the sum of the flow from point M and P. You can see in here M and P. So M, we know that if we already calculated in here, the equivalent drained area for M is 12397 square feet. And for point P we have fixture units, we don't have the equivalent drained area, so we need to convert this fixture unit into equivalent drained area. So G47 is this value. We directly have the equivalent drained area plus this value. Fixture units are 500. Since we said that if we have fixture unit more than 256, so we require 3.51 square feet per fixture units. So we have 500. So 500 into 3.51, it will be 1755 plus 12397. 12397. Sorry, again. 500 into 3.51 plus 12397. So total here is 14,152 equivalent drained area. You can see in here this equivalent drained area at point Q is 14,153. 14,152 or 14,153 here, which we have calculated here, because we have the equivalent drained area directly in here, but this fixture unit we need to convert this into equivalent drained area. So 500 fixture unit, we know that is 3.51 square feet. Since we have 500, so 500 into 3.51, total 1700 something plus this one. So total fixture unit is 14,153. Since we know the fixture units now, this equivalent drained area in a square feet, so now we can get the pipe size in inches using table 7-1. So again you have to use this is again the horizontal pipe. This one Q is again the horizontal pipe, so we have to use again this horizontal piping 1/8 inch per foot slope, and then you have to check 14,153 fixture units, and 14,153 fixture units you have to check in here, and you will get the pipe size, that is 10 inches. So this is how you can do the combined stormwater sanitary drainage system sizing. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Syed Muhammad Waqas. I am back with another video. In this video, I will tell you guys about water supply pipe sizing, cold water and hot water, both of them pipe sizing. So here you can see that I have a drawing for 2-story factory building equipped with 2 toilet rooms, as you can see over here. First one toilet room and the second toilet room, and the highest fixture you can see from this is the street main over here. So highest fixture is located over here. This is the 8 feet and this is 13 feet. So total height is from street main to highest fixture is 21 feet. So highest fixture is located 21 feet above street main. And over here in the street main we have a 2-inch corporation caulk at street main, 2-inch corporation caulk, and pressure loss through that caulk we can get it from supplier. And minimum pressure available at street, this is the street main, and the minimum pressure available at street main is 55 psi. So this value you can get from local water authorities on your location. And let's move to this tab. So this is the table we are going to use to calculate hot and cold water pipe sizing. As you can see over here, the things which I already mentioned before, like minimum pressure available at street main is 55 psi. This value you can get from the local water authorities on your area. So highest pressure at the fixture is 15 psi. As you can see that this is the highest fixture we have over here, and as explained that the highest fixture group consists of flush valves. So basically you need to understand 2 things first. If you have a highest group of fixture contain flush valves, then the pressure for that group should not be less than 15 psi. This is as per International Plumbing Code IPC. And if your highest group of fixture contain flush tanks, then the pressure for that group should not be less than 8 psi. Since we have flush valve over here, so that's why we took 15 psi as per International Plumbing Code IPC. So that's why we have 15 psi is the pressure loss for this highest pressure required at the fixture. And we have a 2-inch water meter over here, 2-inch water meter. As you can see in the drawing, there we have a water meter over here. It's 2-inch, and the pressure loss to that meter, you can get that from supplier. As you can see that the pressure loss we got from supplier manufacturer is 1.61, and the static head loss is 21 feet. Static head loss is due to the change in elevation. As you can see that from the street main to the highest fixture, we have total height is 8 feet and 21 feet. So elevation difference is 21 feet from street main to the highest fixture. So we got the static head loss is 21 feet. Since we know that 1 is equal to 0.43 psi per feet, so in order to convert this into psi, you need to multiply this with 0.43 psi per feet. So after multiplying this 21 into 0.43, you will get 9.03 psi static head loss. And then we have a special fixture loss like backflow preventer. Since you can see that in the drawing, we have a one backflow preventer over here, and this is 3-inch backflow preventer. We need to get this value, pressure loss value or friction loss value, from the supplier for the backflow preventer. So we get this value from the supplier, that is 9 psi. And if you have any other special fixture loss, like if you have filter or water softeners or anything, you need to mention over here these losses. So as you can see that we have mentioned each and every pressure loss with the different line A, B, C, D, E, F, G, H, I. So we need to add all these losses from point B to point H. So line B to line H, total losses 15, 11, 1.61, 9.03, 9. So total friction loss is 45.64 psi. As you know that we get this minimum pressure at street main from local water authorities is 55 psi. So now we need to subtract this total pressure available at street main minus pressure losses through water meter, taps in the main, static head loss. We need to subtract all these losses. So this is the pressure available to overcome pipe friction. That is line A minus J. A is 55 and J is 45.64. So after subtracting, you will get 9.36 psi. So 9.36 psi is the pressure available to overcome the pipe friction. So now as you can see that we need to divide our into different sections. We have divided the drawing into a different section where major changes in elevation or branches lead to the fixture group. So A to B, this is one section, B to C one section, C to D one section, and D to E one, and then C to F another section. As you can see that how many fixture units we have over here: 288 fixture unit here, then we have 264 fixture unit here, B to C, and then 132 fixture unit here, 132 here, 132 here, and B to C we have 24 fixture unit, and then C to F we have 12 fixture units. And the lengths are given: A to B 54, B to C 8 feet, C to D 13 feet, and D to E 150 feet. So everything is mentioned in the drawing. So let's move back to our table. As you can see that we have a fixture unit for A to B is 288, then B to C we have 264, C to D 132, and C to F 132, and D to E 132. So now we have to get the gallons per minute through each section, because while doing water supply pipe sizing, we have to do it using a fixture unit, water supply fixture unit method. So load values of fixtures must be determined as water supply fixture unit. Then we need to convert them into gallons per minute to determine the peak demand. So we need to convert these fixture units into gallons per minute. So 288 fixture unit, then 264. So let's move to tables and charts over here, and we are going to use this table, this one 103.3. as you can see that this is the load, this is the demand, and this is for flush tanks, and this is the load demand for flush valve. Since we are using the flush valves, so we need to use this columns. So we have 288 fixture water supply fixture units. Since we have 275 here and 300 here, so we are going for the higher value for the safety. So 300 fixture unit, the demand will be 108 GPM. So move back there, 288 108 GPM. Then 264, how many GPM? 264 fixture unit, this is 250 and this is 275. So we don't have 264, we will go for the higher value, that is 275. 275 load, we will get 104.5 GPM load. So 104.5 GPM. So same way you have to check for 132 for each, you will get 77 GPM for each. So now we need to check the length of each section, A to B, B to C, C to D, D to E, and C to F. A to B is 54. As you can see, A to B is 54, B to C is 8, C to D is 13, and D to E is 150, and C to F is 150. So you can see that all the lengths we have mentioned here, 54, 8, 13, 150 and 150. So now the third thing is in this column, column number 5, we have to check the trial pipe size. So the trial pipe size, how to get the trial pipe size? Trial pipe size, there's a formula which we have to use to get the trial pipe size. This is the formula, that is pressure available to overcome pipe friction divided by equivalent length of run to the most remote outlet multiplied by 100. So if we move back to our drawing, you can see that the most remote outlet is here. So total length from street main to the most remote outlet is how much? 54 feet, 8 feet, 13 feet and 150 feet. If you add all of them, how much length you will get? That is 54 plus 8 plus 13 plus 150. So total you will get 225 equivalent length of the straight piping. So we did not add any length for the fittings and the valves. So as a rule of thumb, we can add now 50% of the straight length of the pipe, just for now, as a trial pipe, for the trial pipe size. So 50% will be 112.5 plus 225 equal to 338. So total equivalent length of run is 338 feet. So now we know that the pressure available to overcome pipe friction, that is 9.36, we already calculated. We know that equivalent length of run to the most remote outlet, that is 338 feet, we just calculated now, multiply by 100. So pressure available to overcome pipe friction, as you know that we calculated here, that is 9.36, this value. So 9.36 divided by 338, total equivalent length, multiply by 100. So how much friction loss we get? That is 2.77 psi per 100 feet. This is the average friction loss, that is 2.77 psi per 100 feet. So based on this 2.77 psi per feet as the average friction loss, and demand and the GPM, we already know that this is 108. So 108 GPM is the demand, and we know that average friction loss is 2.77 psi per 100 feet. So now we are going to use one chart. And one more thing, all the piping which we used over here is copper L type piping. So when we go over here, this is the chart for copper K type. Since we use this copper L type in our project, so we need to use this chart, that is 103.3 figure. So as you can see that on x-axis we have pressure drop in PSI per 100 feet, and on the y-axis we have demand in the GPM, gallons per minute. So we know that we know that the demand is 108, and we know that the pressure drop is 2.77 psi per 100 feet. We already calculated here. So 2.77 psi over here and 108 GPM here. So it will be around 2.5 inch pipe size, as you can see over here, 108 GPM and 2.77 psi, that is 2.5 inch pipe size. So that's why we got 2.5 inch pipe size here, A to B section. Then B to C section, again we have how much GPM we have here, 104.5, and pressure loss will be same, 2.77 psi per 100 feet, and GPM is 104. So GPM is 104 over here, and pressure loss will be same, so it's almost same, that is 2.5 inch pipe size. So we have used 2.5 inch pipe size. Now the third one is C to D, C to F and D to E. We have same GPM, that is 77 GPM, and we know that average friction loss is 2.77 psi per 100 feet. So move back to our chart. 77 GPM, this 50, 60, 70, 80. So just over here 77 GPM and 2.77 psi per 100 feet. It will touch somewhere here. So it is in between 2 and 2.5 inches. So for the safe side we are going to select the 2.5 inch instead of 2 inches. So 2.5 inches pipe size for these sections. So now move to the next column, equivalent length of fittings and the helves. A to B, what fittings we have from A to B. So this is the table we have used for the fittings for the cold water pipe section, the hot water pipe sections. So A to B, what fittings do we have? If you move to the drawing, A to B, what fittings do we have? We have 1, 2, 3 gate valves and 1 side branch T. 3 2.5 inch, we already know the size, so that's why 2.5 inches gate valves and 1 2.5 inch side branch T. So this is the side branch T over here, and 3 2.5 inch gate valves. So now we have to get that equivalent length in a feet, pressure loss or equivalent length in a feet for these gate valves, 2.5 inch gate valves. So move back to our tables and charts. This time I'm gonna use 103.3 table. This one. As you can see that this is for the threaded fitting. Since we are using the copper tubing, so we are going to use this table over here. So we know that we have gate valve. You can see that we have a valve, gate valve over here, and 2.5 inch gate valve, and equivalent length is 1 feet. You can see 1 feet, and we have side branch T, 2.5 inch side branch T, and its equivalent length is 12 feet. So since we have 3 gate valves, 1 for each, so 3 gate valves, we have 3 feet. 1 2.5 inch side branch T, that is 12 feet, we already calculated. So now from section B to C, as from B to C we have only a straight run T, only one. So one straight run T, 2.5 inches. Move back to our chart, and this is our straight run T, and 2.5 inches. Straight run T is 0.5, equivalent length is 0.5. you can see over here 0.5, so 0.5 over here. Then C to F, then from C to F we have a side branch T. C to F we have a side branch T over here, and only one 2.5 inch side branch T. Size we already calculated before, trial pipe size, 2.5 inch side branch T. We already calculated 2.5 inch side branch T, that is 12. We can no need to go and check again. So C to D. Now from C to D, what we have here, one elbow over here, size is same 2.5 inches. So 2.5 inch 90-degree elbow. So we need to get its value from the table. You can see that elbow standard 90-degree, 2.5 inch, and its value is 7 feet. Equivalent length is 7 feet over here. You can see. So 7 feet. Then again from D to E, again we have a side branch T. As you can see over here, the most remote outlet we have side branch T, same 2.5 inch size. 2.5 inch side branch you already calculated, that is 12, so we can use 12 over here. So in the same way, the way I have calculated the friction loss for the fittings and the walls for the cold water, you can do for the hot water pipe sizing, and you can write it over here. So I don't want to make video much longer, that's why I will skip this part. If you have any query, you can ask me in the comment section below. So let's move back over here. So equivalent length of the fittings and the walls now we have to write over here. So A to B section, how much is the equivalent length of the fittings and the valves? As you can see that 3 and 12, so total is 15. Then B to C 0.5, C to F 12, C to D 7, and D to E 12. So 15, 0.5, 7, 12 and 12. We have write all the equivalent lengths in a feet. Now move to the next column, 7, total equivalent length. So now we know that the straight pipe length, and we know the equivalent length of the pipes and the fittings, valves and the fittings. So we need to add both of them. Straight pipe length section A to B is 54, and equivalent length of fittings from section A to B is 15. And we need to express this per 100 feet. So 54 plus 15, that is 69, divided by 100, it will be 0.69. So same way from section C to D is, that is 13 is the straight pipe length, 7 is the equivalent length of the valves and the fitting. So 7 plus 13, that is 20, divided by 100, that is 0.2. So in the same way you have to write all the lengths. So now we have to get the friction loss per 100 feet of trial pipe size. Friction loss per 100 feet of the trial pipe size. Since we know that our calculated GPM is 108, and based on our trial pipe size 2.5 inch, we have to write these values. So 108 GPM and 2.5 inch trial pipe size, we have to write the actual friction loss per 100 feet of the trial pipe size. So 108 GPM, 2.5 inch pipe size. So this is copper L, again same. We know that our calculated GPM is 108 and trial pipe size is 2.5 inch. So 108 must be somewhere here and somewhere here, and trial pipe size 2.5 inch, and go below you will find here. So the friction pressure drop per 100 feet is about 3.2 something like this. 3.2 something like this, you can calculate over here, that is 3.2. So we have to write this 3.2 friction loss per 100 feet on this trial pipe size 2.5 inch, based on this trial pipe size. So next we have 104.5 GPM and trial pipe size is 2.5 inch. 104 and trial pipe size is 2.5. It's same, almost same, just 0.1 before 3.2, that is 3.1. let's say 3.1 is the pressure drop, so 3.1 over here. And the next one we have C to D, we have 77 GPM and 2.5 inch trial pipe size. So we need to know what is the friction loss. So 77, 60, 70, 80, so it's over here 2.5 inch, almost here, it's touched 2.5 inch here. If we go below, it's somewhere before 2, maybe 1.85 or 1.9 we can take over here. So 1.9. So same over here, 1.9, 77 GPM, 1.9. So this is the actual friction loss per 100 feet based on our trial pipe size of 2.5 inches. So next column is the friction loss in equivalent length. Friction loss in equivalent length. So now we know that total equivalent length based on our straight length of the pipe and based on our valves and the fittings, and we know that the friction loss per 100 feet based on our trial pipe size. So friction loss in equivalent length will be, we need to multiply column 7 and 8, you will get the friction loss in equivalent length. So 0.69 into 3.2, that is 2.21, and then again we have 0.5. Sorry, this one is by mistake 0.85, it should be 0.085 because we need to add both length, that is 8 plus 0.5, that is 8.5. 8.5 divided by 100, 0.085. So it's by mistake 0.85, it should be 0.085. So equivalent friction loss in equivalent length, there will be 0.085 into 3.1, that is 0.26, and 1.62 into 1.9, 3.078, so 3.08. So this is how you have to write these friction losses in equivalent length for each section. So after that we have to add all these length. So since we know that the length to the most remote outlet is, what are coming in the most remote outlet? A to B, B to C, C to D, and D to E. This is not a part of most remote C to F. So A to B, B to C, C to D, and D to E. We have to add all these lengths. So A to B, that is 2.21, 2.21 plus, then B to C is 0.26, and then C to D is 0.38, and then C to F, no, we have to take D to E to the most remote outlet, that is 3.08. So 5.93. So as you can see that the friction loss in equivalent length is 5.93 over here for the cold water piping, and we know that the pressure available to overcome pipe friction representing by line J is 9.36. So we need to get the value, we need to subtract this pressure available to overcome pipe friction with this value in the column 9, that is friction loss in equivalent length, that is 9.36 minus 5.93 equal to 3.43. So this is the excess pressure available to overcome friction losses. So as you can see that this is the positive answer. Make sure that this value should always be positive. For proper designing of water supply, hot and cold water, this value should always be positive. So the excess pressure available to overcome pipe friction is 3.43 psi. So this value is positive. If this value is negative or not positive, then what you have to do, you need to change your trial pipe size and perform the calculations once again. So you need to balance this one. This should always be positive to make sure that your design is perfect. So the sizes which we have selected over here, 2.5 inches, all are good. So excess pressure available to overcome pipe friction is 3.43. So in the same way you have to do pipe sizing for hot water, and you have to check. You can see that 7.99 psi is equivalent loss, friction loss in equivalent length. So if you minus 9.36 pressure available to overcome pipe friction minus this loss, so excess pressure available to overcome pipe friction is 1.37. This is also positive, so that means our selected diameters for the pipes is correct, that is 2.5 inches, 2 inches, and 1.5 inches for hot water sizing. So this is how you have to do your water supply pipe sizing. This is as per International Plumbing Code IPC. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Thank you. Bye bye. Hello friends, this is Saeed Mohammad Waqas. The topic which I am going to discuss today is related to generator room ventilation calculation. So after selecting the capacity of the standby diesel generator at site, the electrical engineer has decided a capacity of 750 kVA, which is equal to 750 kilowatt as well. So now we are going to design the ventilation system for this generator room. So let's get started. So this is the formula which I'm going to use in here. This is the main formula for ventilation calculation, that is ventilation air in cubic meter per minute is equal to H divided by D into SH into DT plus engine combustion air. So basically we are going to calculate the ventilation air required for this generator room as well as the lower sizing we will do. So these are the tables which I'm going to use, that is air density at different temperatures and specific heat of the air at different temperature while performing the calculation. So let me discuss these parameters one by one. So H is basically the heat rejection to the atmosphere in kilowatt for engine as well as generator. So we need to add the heat rejection capacity for engine and generator here, H. So for this one I need to check this value from the manufacturer technical data sheets. So let's say the generator which was selected here is from Caterpillar generator 750 kVA. So there I have a catalog of standby diesel generator 750 kVA from Caterpillar. So I need to check the heat rejection to the atmosphere by engine. So this is the technical data, as you can see here. You can see here the heat rejection to atmosphere from engine is 96 kilowatt and the heat rejection to the atmosphere from generator is 28.9 kilowatt. We need to add both 96 and 28.9. So I have added in here 96 plus 28.9. So total heat rejection to atmosphere from engine and generator is 125 kilowatt. So now V, as I told you, this is the ventilation air in cubic meter per minute and D is the density of the air in kg per cubic meter. I will tell you later how to get this one because this depends on temperature. Let me discuss the temperatures first. Now SH is the specific heat of the air in kilowatt minute per kg degree Celsius. This also depends on temperature, so let me discuss the temperatures first. And DT is basically the temperature difference, that is T2 minus T1 inside the engine room, generator room. So T1 is the design temperature which was taken at 40 degrees Celsius and T2 is the maximum allowable temperature, that is 50 degrees Celsius. So we need to take the density of the air as well as specific heat of the air at maximum allowable temperature of 50 degrees Celsius. So T2 is calculated as dt is calculated as T2 minus T1, that is 50 minus 40 equal to 10 degrees Celsius. Now I will tell you how did I get the density of the air here. So let me go to air density table. So it should be in kg per cubic meter and we need to check the density of the air at maximum allowable temperature of 50 degrees Celsius. So let's go to air density table. As you can see here we have temperature column represented in degrees Fahrenheit and this is the density in kg per cubic meter. So we said that we need to check density of air at 50 degrees Celsius. So I need to convert this from degrees Celsius to degrees Fahrenheit. So this is the converter I'm going to use. So degrees Celsius, 50 degrees Celsius to 50 degrees Fahrenheit equal to 122 degrees for Fahrenheit. So I have to write 122 in here. So we know that we have 120 and 140 but we don't have 120. So we're going to use this interpolation table to get the exact value at 120 degrees Fahrenheit. So we have temperature 120. We don't know the density at 122. We'll calculate using interpolation table. We have 140. So what is the density at 120? Kg per cubic meter is 1.097. We don't know at 122 and 140. What's the density of the air? 1.06. 1.06. So what is the density calculated at 122 degrees Fahrenheit? That is Y2. So at 50 degrees Celsius, 122 degrees Fahrenheit, density calculated is 1.0933 kg per cubic meter. So this value I get here, 1.0933 kg per cubic meter at 50 degrees Celsius. Now I have to calculate the specific heat of the air in kilowatt minute per kg degrees Celsius. So this also depends on temperature. We need to calculate this at 50 degrees Celsius, that is maximum allowable temperature. So this is the table which I'm going to use, specific heat capacities of the air, and this is the temperature column in kelvins, and this is the specific heat of the air at constant pressure, specific heat of the air at constant volume. So we are taking specific heat of the air at constant pressure. We need to check this column, but first we need to convert the temperature. So 50 degrees Celsius, how many kelvins? So we go here, converter again, and 50 degrees Celsius, if we get the Kelvin, how many kelvins? 323 Kelvin, 50 degrees Celsius. So I will write 323 kelvins here. So again we have temperature 300 and 350. We don't have 323 to get the exact value of the specific heat of the air at 323 degrees Celsius. So 323 kelvins. So I'm gonna use the interpolation again to get the exact value at 323 Kelvin. So we have 300 temperature. We need to check the specific heat of the air at 323 Kelvin, and we have 350. So we have a CP value at 300, that is 1.005. 1.005. We don't know CP value at 323. We'll calculate now. And what is the value of CP at 350 Kelvin? 1.008. 1.008. So what is the exact value of CP we calculated at 323 Kelvin is 1.00638. So this I have right here, 1.00638 kilojoule per kg kilojoule per kg Kelvin. But if you see here the table, the formula, we need to get this value in kilowatt minute per kg degree Celsius. This value is specific heat. So I need to apply some conversion factors here. So there I have an online converter from kilojoule per kg Kelvin to kilojoule per kg degree Celsius. So let me write the value 1 and convert. So 1 kilojoule per kg degree 1 kilojoule per kg Kelvin equal to 1 kilojoule per kg degree Celsius. So I have write in here this conversion factor. So now I have to convert this kilojoule per kg degree Celsius to kilowatt minute per kg degree Celsius. So if you check this converter on the internet as well, you will find 1 kilojoule per kg degree Celsius equal to 0.016667 kilowatt minute per kg degree Celsius. So this is the units we have to use in here for the specific heat. We already converted, and this is for 1 kilojoule per kg, and we have calculated 1.00638. So 1.00638, how much it will be? You just need to multiply this value 1.00638 with this conversion factor. You will get the value of 0.017 kilowatt minute per kg degree Celsius. So this value of specific heat, 0.017 kilowatt minute per kg degree Celsius, we got at 50 degrees Celsius. So this is how I got this 0.017 specific heat in kilowatt minute per kg degree Celsius. So now the only thing remaining is ECA in this formula. ECA is basically the engine combustion air, that is the exhaust gas flow. Again, you need to go to the manufacturer technical data sheet to get this value. So this is basically the exhaust gas flow, engine combustion air. If you go here, technical data sheet, and you will check the exhaust. This is a technical data sheet for 750 kVA Caterpillar generator, and the exhaust system, you check the exhaust gas flow rate, which is 129 cubic meter per minute. Exhaust gas flow rate, that is engine combustion air volume, or exhaust gas flow rate, 129.8 cubic meter per minute. So we'll go back here and we will write the value here, 129.8, that is almost 130 cubic meter per minute. If you want, you can convert this into cubic minute per hour, but we need this in cubic meter per minute. We use this value 130. So now we have all the values. We have H, we have D, we have SH, we have DT, we have engine combustion air, which is exhaust gas flow rate. So what we have to do is we have to put all the values in this ventilation formula. So if we put all the values here, we calculate the ventilation air in cubic meter per minute is 802 cubic meter per minute. If you want to convert this into cubic feet per minute, just apply a conversion factor. You will get this ventilation air in cubic feet per minute. So applying the conversion factor, I got the ventilation air of 28,295 cubic feet per minute. Now I have the ventilation air, I can calculate the intake louver size. So normally the velocity which we consider for generator room ventilation is 1000 fpm, feet per minute. So by using this equation, Q is equal to VA. So we know everything, we don't know the area, so A is equal to Q divided by V. Q, which we calculated here, is 28,295, this here ventilation air, divided by velocity, which we consider is 1000 fpm. So louver area, which is calculated here, is 28.3 square feet. If you want to convert this into square meters, you just need to multiply it with 0.0929. You will get the louver area in square meters. So same way you can do the exhaust louver size as well, considering the velocity of 1000 fpm for exhaust louver as well. So this is how you can do the ventilation calculation for generator room. So before leaving this video, I wanna give one small message about the channel membership. If you guys can join the channel membership, you will get access. If you just have to go to the channel, click this join button. So you have to select the level on which you want to take the material. Like you can select different levels here. So based on your level, you will get the required material. If you have any query related to membership, you can just send an email to saidmohammadw@gmail.com, or you can find that email here as well. Go to the about section, you can see the email here. Or even after taking the membership, you have to send an email on the same address to get access to the material. You just have to send an inquiry email and you will get access to the material. So next time I'm going to discuss about the transformer room ventilation calculation. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe. Thank you. Hello guys, this is Said Mohammad Waqas. The topic which I'm going to discuss today is related to the cold storage room design. So I'm gonna use this software Cool Selector provided by Danfoss for cold storage room design. So first let's move back to our Excel sheet. You can see that this is our cold storage room which we are going to design. This is the length, this is the width, and this is the height. So room dimensions are given in here, and these are the inner dimensions: length 10 meter, width 5 meter, height 4 meter. And panel insulation which we used in here is polyurethane 100 mm thickness, and floor is made of concrete, and there is no insulation we used in here, so it's not insulated floor. And ambient condition is depends on location. So I'm talking about Abu Dhabi, UAE. So Abu Dhabi ambient condition is 46 degrees Celsius, so that means 115 degrees Fahrenheit. So ambient condition of Abu Dhabi is 46 degrees Celsius, that means outside temperature. And the surrounding conditions means the temperature of the spaces adjacent to this cold storage room. So normally we keep temperature 22.5 to 26 degrees Celsius for surroundings. So let's say we keep here is 23 degrees Celsius of the surrounding temperature, surrounding spaces temperature, and humidity we keep for thermal comfort is like 50 to 60%. So here we have taken 55% relative humidity. And below floor temperature is 12 degrees Celsius we kept in here. Normally we keep 10 to 12, so I kept 12 here. And this is the most important thing for cold storage room design, that is goods, what type of goods you are going to store, their storage life and storage temperature. So the goods which we are going to store inside here are the vegetables, and in vegetables we are storing broccoli. In here you can see that broccoli we are going to store inside. And storage life and storage temperature, so where you will get this data, storage life and storage temperature. This is the table: recommended temperature, relative humidity, approximate storage life of the fruits and vegetables is given in here, provided by the agricultural department. You can see that different products are given in here, from arranged alphabetically from A to Z, and their storage temperature is given in here, relative humidity and approximate storage life is given here. So we are talking about broccoli. So you can see this is the broccoli. So you can see that the storage temperature is 0 degrees Celsius, that means 32 degrees Fahrenheit, and relative humidity is 95 to 100, and approximate storage life is like 10 to 14 days, so maximum 2 weeks we can store. So let's move back to our software Cool Selector, which we are going to use to design cold storage room. So first of all, this is the main interface. First of all, you have to go to commercial applications, and here you will find the cold room. So you have to select this cold room. When you select cold room, this screen will pop up. There you find two methods to design the cold room. First one is wizard type and second one is manually defined. So what is the difference between these two methods? Manually defined method is used only when you know all the parameters, then you will use this manually defined cold room. If you don't know some of the parameters, like in our case, we don't know the quantity of the food or mass of the food, how much food will be stored inside. So this is one of the important parameter. So that's why we're going to use this wizard type, because it will help you to estimate some parameters, like you don't know, like quantity of the goods, it is not known, so it is recommended to use this wizard type. So I'm going to use this wizard type. When you select this one, this screen will pop up. You have to give the dimensions. So make sure we have inner dimension, so make sure that inner dimension selected, and you can see in here length is 10 meter, width is 5 and height is 4. So it's 10 meter, this width is 5 and height is 4 meters. So after that you have to give the room surroundings temperature, like we have to give the temperature conditions adjacent to this cold storage room. So as we said that we have maintained 23 degrees Celsius with 55% relative humidity in the surroundings. So we have to change this to 23 degrees Celsius and relative humidity 55%, and temperature below floor we said it's 12 degrees Celsius. So 12 degrees Celsius, and floor is uninsulated, is not insulated, so I'm going to uncheck this one, and after that you have to select next. Now you have to check what kind of goods you want to store in the cold storage room. So here the different types of products are given in here. So in our case we said that we are going to store broccoli vegetables, so we have to select the vegetables from here, vegetables, and the quantity per day, we don't know the quantity. So how we can do that one, we will estimate the mass of the goods from the room volume. We know the room volume, so we can estimate. So estimate mass from the room volume, you have to select this one, and then this screen will pop up, and then you have to give the two things in here: first, percentage of the room used for the goods, and second, percentage of the goods changed each day. So percentage of the goods which will occupy in the room, we don't want to fill up like 80% or 90%. We need to keep two things in mind while giving this percentage of the room used for the goods. We want to keep the space so that person can easily move in between the racks, and he can easily remove the goods, or he can easily place the goods. So we need to keep that thing in mind. Also, we need to keep in mind that we don't want to place goods too much close that there will be no air circulation between the goods. So we want to keep a little space between the goods so that air can easily flow in between the goods. So in order to that, we will keep percentage of the room goods like 60%. So that means 60% of this room volume will be occupied by the goods and 40% will be empty, so that person can easily walk in, and there's a gap between the goods. So percentage of the goods changed each day. Obviously you will gonna put some new foods, and the new food will be replaced by the used food. So you have to, every day you have to replace the food. So percentage of the goods changed each day. We're gonna change this one to, like, let's say 10% of the goods we are changing each day. So we'll change this to 10%. So after that you have to select OK. And one more thing, as you can see that when we estimate it, then total mass in the room is 54,000 kgs, and quantity per day is 5,400 kg. That means we have to replace this quantity every day, 5,400. So here you have to consider one more thing, that is inlet temperature. Inlet temperature by default it's 5.5 degrees Celsius. So how we select the inlet temperature, it depends on the storage temperature. So if storage inlet temperature should be 5 degrees above the storage temperature by default, because the goods are assumed to be pre-cooled before storing in the cold storage room. So we keep 5 degrees inlet temperature 5 degrees above the cold storage temperature. So here cold storage temperature, a cold room storage temperature is 0 degrees Celsius for broccoli. So 5 degrees above, that means we have to keep 5 in here. So after that you have to select next, and the storage temperature, we know that we just checked from the Excel sheet. Broccoli storage is 0 degrees Celsius, so we will change this one to 0 degrees Celsius. And relative humidity is from 95 to 100%, so we'll keep the 95 same. And based on this storage temperature and relative humidity, operating hours will be calculated, that is 12.6 hours. That means our refrigeration system should run 12.6 hours to maintain 0 degrees Celsius storage temperature and 95% relative humidity. If we change the relative humidity from 95 to, let's say, 98%, and then estimate the operating hours again, then operating hours will be changed and it will be reduced. So let's estimate operating hours again, and now operating hours is 11.1 hours. So it depends on storage temperature and relative humidity. So let's change it back to 95 and keep the operating hours 12.6 for this refrigeration system. And we know that the insulation panels which we used in here are polyurethane 100 mm thickness. So we're going to select the same polyurethane, and we are going to select 100 mm thickness. After that you have to select this one, and this screen will pop up. Here you can review your cold room load. You can see, or you can edit the parameters in here. If you want to change, you can change in here. So now air exchange, which we did not define before, let's talk about this one. Temperature, we know that 23 degrees Celsius and 55% relative humidity in the surroundings area. So now talk about the door opening. Since we kept 10% of the goods changed each day, so that means door will be open, you can say that it's regularly. Here we have three options in here: often, regular, and rare. Since we are changing like 10% of the goods, and you know that the mass of the good which we can store is for maximum 2 weeks. It's not a very long period, it's like a short period. If you see that some of them store even for 6 months, 7 to 8 weeks, 4 to 8 weeks, so this is a short storage period. So that means door will open like regularly. It's not, if it is like very long period, then we can keep like door is open rarely. So that because of the long short storage time, we will keep this one like regularly. So if you change this one, you can see that based on this regular and our input parameters, air exchange rate is automatically calculated. You can even change this one if you want, but this is calculated based on our parameters. So if you change this one to, you can see 3.54 it's now. If you change this one to rare, it will decrease 2.12. So in our case it is regular, we're opening the door because of the low storage, less storage time, so it's regular. So after that you have to select the panels. Here you will calculate the heat load or heat transfer. So one is standard option available, other is custom. I'm gonna select the custom panel. The reason I'm selecting custom panel because left side, right side, front side, there we have a conditioned space in the surrounding, but the back side of this cold storage room, it is open, it is like exposed to the sun or exposed to the ambient conditions. So that's why I'm going to select custom panel. So here you can see the front, left, right, back, ceiling and floor. So front will keep, we know that the sounding temperature is 23 degrees Celsius, we talked in the first place. So we're going to change this one to 23. Left is also 23, right is also 23, and the back side we said that is exposed to the sun or exposed to the ambient condition. We know the ambient condition is 46 degrees Celsius in Abu Dhabi, so I'm going to change this to 46. Back side 46, ceiling I'm going to take same 23, and the floor we said that we kept 12, and we said that it is not insulated, so we will uncheck this one. So once you are done with the heat transfer, let's move to our this additional loads. So based on the room area, the lightning load is automatically calculated, that is 400 watt. So how did we get this 400 watt? You know that the length and the width, length is 10 and width is 5. So 10 cross 5, that is 50 square meters. So based on 8 watt per square meter thumb rule, this lightning load is calculated. So 8 watt per square meter means multiply with 8, you will get 400 watts. So 400 watt is calculated automatically in here based on 8 watt per square meters. So instead of using this 8 watt per square meter, I will go more precisely and I will take the electrical load sheet. I will check from there how many lights are used inside the cold storage room. Let's say we have used 8 light bulbs, each with 40 watt. So 40 watt for each and 8 light bulbs, that means 320 watt is the total. So I will change this one to 320 watts. So based on our input parameters, the fan power is automatically calculated, that is almost 500 watt. And number of and then people, how much time people will spend inside this cold storage room. Obviously you have to store the material inside and then you have to remove the goods for the usage. So how much time people will consume inside? So since we said that door opening is regular, so we will keep this same 2 hours per day. If we had kept this one to rare, then we can change this to 1 hour per day. So in the whole day it will be 1 hour per day, but since we said that door opening is regularly, so that's why we keep this 2 hours per day. And you can see that the additional other load, if you have any equipment inside this cold storage room, then you have to add that load also in here. And the last thing here is a defrost. You can see that the defrost heater, this power is basically defrost heater power, and you can see there are two options available in here. One is electric, other is natural. Since natural is not available in here, the reason why it is not available because room temperature, storage temperature which we selected is 0 degrees Celsius. At 0 degrees Celsius natural defrost is not possible. Minimum 4 degrees Celsius temperature is required for natural defrost. Let's say if I change this to 4 degrees Celsius, then you can see that natural option will be available. So if I change this to 4, you can see that natural defrost is available. Since in our case storage temperature is 0, we'll keep it 0, and by default electric heater, defrost heater is selected in here, and automatically we had calculated the power based on the inputs, that is 3571 watt, and the defrost per day we're gonna keep this one 3 by default, because when we open the door, very average amount of humidity it will enter, so we'll keep defrost 3 times per day. So if it was door opening was rare, so we can keep this defrost 1 time per day. So since this is regular, so we can keep defrost 2 to 3 times. We kept 3 times. So after that you have to select next, and then you will select the region of your area. So since I'm talking about the Middle East, UAE, United Arab Emirates, so I'm gonna select Middle East, and then the types of preferred type, I'm gonna prefer like Optima, or whatever your preference, you can select accordingly. So you can select Optima and then select your refrigerant, what type of refrigerant you want to select in here. So I'm gonna select R134A because this is environmental friendly, so just select this one. Next. So once you select this one, you can see that your load summary, total required cooling load is 10.06 kilowatt, and cold room temperature condition which we selected, you can see in here. Operating hours based on storage temperature and relative humidity is 12.6 hours refrigeration system will run. And here are the different types of loads you can see in here: calculated transmission load, infiltration, goods respiration, cooling, light, fan, defrost. Total load is 10.06 kilowatt, and based on our inputs, you can see that the dew point temperature calculated is -8 degrees Celsius, and superheat calculated is 5.2 Kelvin. And after that you have option like thermostatic expansion valve material, what kind of thermostatic expansion valve you want, like stainless steel or brass. So I'm gonna select the brass in here. So after that you have to select, it will generate the equipments for you, best equipments suited for your application. You can see that this is a condensing unit which they have selected for our case based on our load calculation. So you can see that this is the unit which they have selected, OPMGUE148M LA060. So based on the condensing unit, it has also selected the controller for us. So if you select this condensing unit, you can see that the performance in here, you can see that in valve over here, you can see the performance details in here. You can see other information like technical data. If you want to check, you can check technical data. You can check the spare parts, you can check the electrical specifications, like how much is the fan current, is 1 amps, fan power consumption is 500 watt. Or you can select this performance, and you can read the data in here also. R134A refrigerant, total cooling kilowatt is 10.64. Also you can generate a report. You just go to the report, and then you have to go here left side, cold room 1, and whatever you want to include in your report you can select. Like if you want technical data, cooling capacity, power consumption, you want the current, you want the COP. So after that you just update here, and it will update the report. So now it has updated the report, you can read. So you can see the refrigerant, you can see the evaporating pressure, everything is in here. You can see the charts. So even if you want to save it in the PDF, you just go to PDF, and then you have to select OK, and then save it wherever you want. You can just give the location and then save it. I'm gonna save on desktop, save it. Also if you want, you can see the report in here also. Also, if you want to edit in your report, if you want to make some changes, so you just go back to your selection, and then you have to go to edit selection. It will take you back what type of method you want to select, again wizard, or we selected the wizard, so it's just select the wizard, this one, and it will remember the inputs which you put in here, so you don't have to change, you just have to next, and then if you want to make any changes you can make the changes. So this is how you can design your cold storage room based on your information, like what kind of vegetable or fruit you are going to store, and the relative humidity, every data is given in here. So based on this you have to give the input, storage temperature, relative humidities, everything. So I hope you guys learned something from this video. For more videos keep watching my channel, and don't forget to subscribe, and don't forget to press the bell icon. Thank you. Hello guys, this is Syed Mohammed Wakas back with another video. Many guys were requesting about fan static pressure calculation, so most awaited video is going to be released today. So today I'm going to explain you guys about the static pressure calculation of the machine. So as you can see that there I have a drawing. This is a 3D view. Let's go to our floor plan first. So there I have one air handling unit that is supplying air to the office space, as you can see here, to the meeting room and the manager's room. So if you move back to the 3D view, it looks like this. So there I have the air handling unit at the rooftop, and there I have return ducting, as you can see over here in the pink color. This is return ducting, and this blue color is supply ducting, that is supplying conditioned air to the space of the building, and this green color is the fresh air ducting. So basically I'm gonna use this Excel sheet which I have prepared here to calculate the static pressure of the fan. So as you can see that I have divided into three parts: supply side, return side, and the fresh air side. So first I'm gonna calculate for the supply side. As you can see that I have divided each section into and described over here. So move back to our drawing. The reason why I have selected this Revit to show you about 3D view, because in 3D view you can easily visualize each and every fitting that is coming on the way from the machine mouth till our most remote outlet. So as I already selected, first of all you have to select the most remote outlet. So I already selected the most remote outlet. So this is from the machine supply side, it's going from here, so all the way in here. This is our most remote outlet. You have to check the length of each section, and then you have to come up with the most remote outlet. So I already selected this most remote outlet to here. So if move back to our floor plan, ceiling plan, so this is the meeting room. This is our most remote outlet for ESP calculation. So we are going to follow that route all the way from up till here for our ESP calculation. So let's start the ESP calculation. So first of all we have a transition, rectangular transition, as you can see in the 3D view. So first of all we have a rectangular transition on the supply side of the air handling unit. Also I'm gonna use this X-ray fitting database software to calculate the static pressure for different components. The first fitting over here is rectangular transition over here. As you can see, the size of this rectangular transition is 1100 into 950 by 750 by 550. This one we already given here in our Excel sheet. So number of fitting is 1 and the flow rate is 2571 liters per second. So I'm gonna use this X-ray database to calculate the static pressure loss for this rectangular transition. So there I have a AHU duct fitting database software. As you can see that this is the fitting we have used in our drawing, that is SR4-2. so this is from the fan side and this is to the other side of the fan. So fan side is H1 W1 and other side is W0 H0. So as you can see that the fan side is 1100 by 950 and the other side is 750 by 550. So H1 W1 is the fan side and the other is width height is 550 and width is 750 and the fan side is 950 and the width is 1100 and the flow rate we know that is 2571 liters per second and the length we can get from the Revit. As you can see that is 375 mm. 375 mm and then calculate. If you calculate you will get the pressure loss is 1. This is the calculate button, you need to click this and you will get pressure loss is 1 Pascal. So we need to add this pressure loss here in our Excel sheet, that is 1 Pascal in here. And then we have a straight duct piece. As you can see that we have a straight duct and until here our size and flow rate is same, so pressure loss will be same throughout this piece of duct, that is 750 by 550 size, because flow rate and duct size is same, so pressure loss will be same. So what I'm gonna do is I'm gonna add all the lengths, this one, and this piece and this piece. So there we have in between these two pieces we have duct silencer. I'm gonna add this one later. First I'm adding the static pressure loss for the straight piece of duct, that is 750 by 550. If you add all of these duct lengths it will be 4.53. that's already added in here. Or you can check the length of each piece one by one by using on the property palette. If you go there and you will find the length of this piece is 17.92 meters. So you have to add all of these lengths, so it will be total length will be around 24.53, that is 80.46 feet, and flow rate is 2571 liters per second. That's we already know here. For this piece of duct, you know that flow rate is 2571. In the property palette you can see 2571 liters per second. So I'm going to again the AHU database and I will check the rectangular straight duct fitting. This is called CR11-1 fitting. If you want to check your fittings in Revit also, you can check that by clicking the property palette. So we know that duct size is 750 by 550 and the length is 24.53. so go back to our AHU database. We are going to use this CR11-1 fitting. Height is 550 and width is 750. So absolute roughness we keep the same, that is 0.09. Length is 24.53 meters. Okay, and flow rate is 2571 liters per second and density of the air is same. So just calculate and it will give you the pressure loss for that piece of duct, that is 14.3 Pascal. For 550 by 750 duct with 2571 flow rate, it will give you 14.3 Pascal. So 14.3 Pascal over here. This duct silencer over here, basically you need to get this value from the supplier for this duct silencer. Let's say we got this duct silencer from Ruskin, and size of this duct silencer is 750 by 550, and head pressure loss we got is 16.87 Pascal. So you need to get this value from the supplier or manufacturer. So 16.87 directly I will write in the Excel sheet, that is here. And then we have 90-degree rectangular metered elbows, radius 1.5 W. As you can see that we have how many elbows? So straight piece of duct, transition, duct silencer, all of these are done. And then we have one elbow here and second elbow here, and size is same, that is 750 by 550, and the flow rate is again same, that is 2571 liters per second. So we have two elbows here. So as you can see that two elbows in here, 2571 liters per second, size is 750 by 550. Okay, there we go, and we find the smooth radius elbow without veins. This is the elbow which we have used in here, and the size of this elbow is width is 750 and the height is 550. Radius ratio, because we use 1.5 W, so it is by default 1.5, and 90-degree elbow we have, and flow rate is 2571 liters per second. And then calculate. So pressure loss calculated over here is 4 Pascal, and then we have to go back to our Excel sheet, and pressure loss is 4 Pascal. Since we have two elbows, so total is 8 Pascal. And then move back to our drawing, and then since up till here we are done, so after that we have a transition in here. As you can see, we have a transition here. So you need to calculate for transition in the same way as I explained before. So just to save the time, I'm skipping this one. And then we have a straight duct piece, that is 450 by 300, and the flow rate for this piece is 570 liters per second. As you can see over here in the property palette, 450 by 300, 570 liters per second, and length of this piece is, you can see here the length of this piece this one 5.74 meter is the length, 570 liters per second is the flow rate. So move back to our Excel sheet. Rectangular transition you calculate in the same way as I explained before. Then straight duct 450 by 300 with 5.74 meters the length, and 570 liter per second is the flow. This one I already explained before also, straight duct, so same way you have to calculate. And then you have since this is our most remote outlet, so we'll go to the right side. So there we have a T. So this T will be acting, after T we have a reducer, so this T will be acting as elbow T plus reducer T. So we divide this into two parts, that is elbow plus reducer, because we are going to the right side to the most remote outlet. And the flow rate, we can check that how much is the flow rate to that side, that is 269 liters per second. So as you can see in the Excel sheet, we divide this into elbow T and reducer T, elbow T and reducer T. So size is 450 by 300 for the elbow, and reducer size is 450 by 300 to 300 by 250. As you can see that this is the transition reducer we have, that is size is 450 by 300 and 300 by 250. As you can see here in the property palette, that is 450 by 300, 300 by 250. So elbow, as I already explained you for the elbow also. The same way you have to calculate for elbow and for reducer transition. And then again we have a straight piece of duct. Flow rate is 269 liters per second, and length of that piece is 5.14 meters. You can see in the property palette. So go to our Excel sheet, straight piece 300 by 250, 5.14, 269 liters per second. So straight piece of duct is also I explained before, so you need to get in the same way, straight piece. And then we have a rectangular to round transition. If you move back here, so after straight piece is done, you have this rectangular to round transition. Because this is a rectangular piece and then we have a round flexible duct, so we need rectangular to round transition to connect these two pieces. So you can see that rectangular to round transition over here. If you want to check the fitting also, you can just go to property palette and edit and check the fitting, that is SD4-2. This is the fitting which we have used here. So I move back to AHU database, and then I will go to transition and then rectangular to round transition. So if you go there, you find the same fitting SD4-2. So I'm going to use this fitting. You can see that from the fan side, or the flow direction is from this way, and this is to the round side. So this is H1 is the height and W1 is the width, and from the fan side. So this we know that that is 300 by 250. 300 is the width, 250 is the height. You can see there, this is 300 by 250. So this side is 300 by 250 and round side flexible dia is 300 mm. You can see here. So move back there. Then our height is, how much is our height? That is 250. Width is 300 and diameter is also 300 mm, and length of that transition is if you select this transition and check in the property palette, computed length is 60.4 mm, that is 61 we can say. Okay, 61 mm, and flow rate is 269. We already know, we check from Excel sheet and from the drawing, and then calculate. So pressure loss is 0 Pascal. So it has some value, but it's giving 0. So let's move back to our 3D model and check the pressure drop is 0.06 Pascal. It's very small, so we're going to add the same 0.06 Pascal. So rectangular to round transition 0.06 Pascal, only one fitting, so 0.06 Pascal. Then we have VCD, flexible duct and diffuser onto the supplied side. As you can see that VCD here we did not add, so I'm gonna add the VCD also. For this VCD you need to get this value from the supplier. For this VCD, supplier or manufacturer, he will provide you the pressure loss value. So right now I'm gonna keep 20 Pascal pressure drop, but you need to check this value from supplier or manufacturer. So I have used 15, so I'm gonna use 20 here. And flexible duct, I'm gonna use 1 Pascal here. If you move back here, and this is our flexible duct, and check the pressure drop for this flexible duct, that is 0.73 Pascal. So I'm gonna use 1 here. And then diffuser, for the diffuser also you need to check this value from supplier. So this is the most remote outlet diffuser, so you need to check this value also from the supplier, the one who provided you this diffuser. He will give you the value, pressure loss value. So pressure loss which I'm gonna keep here right now is 14 Pascal. 14 Pascal. So we are done with the supply side of the air handling unit. So static pressure loss, it will be the sum of all the duct and fitting losses coming on the way on the supply side to the most remote outlet. The total static pressure loss is 82.97, 15% safety factor we are going to use here. So total external static pressure on the supply side is 95 Pascal. So in the same way you have to calculate for the return side. If you see that the return side rectangular transition we already did, you know that how to calculate. Straight also did. Duct silencer, you need to get this value from the supplier, the one who provide you the duct silencer. And elbow we also finished. So only one thing is different here, that is rectangular wire mesh with insect screen. So if you move back to our, so this side we will have a rectangular wire mesh with insect screen to the return side, because it will suck all the air from this way to the return side and take it over here. So if you see, the size of this duct is same throughout until here. There we have a wire mesh, so its size is 750 by 550. So our duct size is 750 by 550, and the same size of the wire mesh we are going to use here, that is 750 by 550. So move back to our H3 database fittings and let me find the correct fitting. So if you go to rectangular and you will go to obstruction, there you will find screen only. So we will have a screen here onto the return side. Let me zoom it. We will have a screen to the return side to prevent any insect or anything to go inside the duct. So this screen will also compute in the pressure loss. As you can see that N is the free area ratio of the screen, A0 is the area of the duct, A1 is the cross-sectional area of the duct fitting where screen is located. So I'm gonna use same size of the screen as the duct size, same screen size as the duct size, and free ratio we will add like 50%. So our H0, this is our duct size. Duct size is 550 by 750, we already know. 550 is the height, 750 is the width. Area ratio is 1 because same size of the screen I'm using, so that's why it's small. And free area ratio I'm gonna keep here is 50%. That means 50% of the air will be obstructed because of this screen. And the flow rate is on the return side. If you check the flow rate to the screen is 2185 liters per second. So 2185 liters per second. So pressure loss calculated is 28 Pascal. Because of this screen, it's much loss because of the screen. So due to the screen, you can see the pressure loss is 28 Pascal. So in the end, you have to sum up in the same way which you did for supply side. So static pressure loss is 67, 15% safety factor. Total external static pressure for the return side is 77 Pascal. That is 15% safety factor and this. And then in the end we have fresh air side also. Why we are calculating for the fresh air side also? Because sometimes you have fresh air is supplying from the fresh air handling unit. So that time you have to calculate in the other way, but this side we have fresh air supplied directly with the from the sand trap blower with insect screen. So this is supplying directly, so we need to consider the losses for the fresh air also, because there's only one fan working for the supply, return and the fresh air also. That's why we have to compute the loss for this fresh air also. If you see the fresh air, I did not add the sand trap blower fitting, but we will have a fresh air sand trap blower here. So fresh air sand trap blower, then straight piece of duct, and then we have a VCD in here. As you can see that this is the VCD, this is the VCD, and then we have a transition here also. Transition is 1050 into 400 by 600 by 400. So total 4 items. First transition, this one, flow rate is 386 liters per second, and straight duct is 600 by 400, VCD is 600 by 400, and fresh air sand trap blower over here. You need to get these values from the supplier for VCD and the fresh air sand trap blower. And straight duct you already know, rectangular transition you already know, as I already explained how to calculate the. So same way you have to calculate pressure loss for all of these items. So static pressure loss is 38.2 Pascal, safety factor 15%. So sorry, this is fresh air side. So total static pressure on the fresh air side is 43.93 Pascal. In the end you have to sum up all these static pressure loss, that is fresh, supply side, return side, and fresh air. So total will be sum of all these, that is 216 Pascal. So this is the external static pressure, but we need to add the internal static pressure also. So you need to get this value also from the supplier for internal static pressure. Internal static pressure, you will have pressure loss due to the filter, due to the coils. If you have a 4-row coil, if you have a 6-row coil, 8-row coil, you need to get this value from the supplier, because he will provide you the coil losses. If it is 4-row coil, it will be different. 6-row coil, it will be different. And due to the filter, you will also have a losses. So right now I'm gonna consider, let's say I got this 20 Pascal from the supplier due to the filter, and 30 Pascal due to the coils. So total internal static pressure is 50 Pascal. So total fan static pressure loss will be the sum of external plus internal. External is 217 and internal is 250. So total it will be the sum of these two, that is 266.91. So you need to select the machine based on this static pressure loss of 267 or 267 Pascal. So this is how you have to calculate the static pressure loss for your machine. So I hope you guys learned something from this video. For more videos, keep watching my channel. Hello guys, this is Syed Muhammad Waqas. The topic which I am gonna discuss today is the air handling unit fan motor power calculation. If you remember that in my last video I have calculated external static pressure for air handling unit. So I'm gonna continue from the same Excel sheet to calculate the fan motor power of air handling unit. So if you remember that this is the drawing which we used last time to calculate the external static pressure of the air handling unit. So now I'm gonna calculate the fan motor power for this air handling unit. So move back to our Excel sheet. So as you can see that this is the main formula which we are going to calculate the fan motor power of the air handling unit. As you can see that formula is CFM into total static pressure divided by 6356 into efficiency of motor into efficiency of blower. So this formula you can find in the carrier handbook. I took this formula from the carrier handbook. So if you want to calculate the hot power, you need to this formula. So CFM, as we already know that total CFM of the machine is, how much is the total CFM of the machine, we can see from the Revit also, or we can check from our Excel sheet. Total CFM was total airflow was 5445 CFM. So CFM we know that. Total static pressure we already calculated in the last video. Total static pressure was 267 Pascal, as you can see over here, but we have to use the static pressure in inches of water column over here. So we need to convert this into inches of water column. If you divide this figure with the 250, you can get the static pressure loss in inches of water column. So total fan static pressure loss is 1.07 inches of water column. So we are going to use 1.07 here. The total static pressure divided by 6356 is the constant in the formula, and multiply efficiency of motor into efficiency of blower. Efficiency of motor we normally take is 85%, that is 0.85, and efficiency of blower which we normally take is 80%. These are the standard values. which we have used in here. So efficiency of motor is 85%, efficiency of blower is 80%. So if you used all of the values in here, CFM into total static pressure divided by 6356 into efficiency of motor into efficiency of blower. So after that you will get 1.3 horsepower. So you need 1.3 horsepower fan motor in the air handling unit. And if you want to convert this into kilowatt, you simply need to multiply this horsepower value with 0.746. So you will get the fan motor power in kilowatt. We needed 1 kilowatt fan motor power for air handling unit. So this is how you can calculate the fan motor power of the air handling unit. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Saeed Mohammed Bukas. Today I'm going to explain you guys about the expansion tank sizing procedure. So before starting the calculation, I want to explain you guys about expansion tank, what is expansion tank and why we are using expansion tank in our system. So expansion tanks are basically required in a closed loop heating or chill water system to absorb the expanding fluid and limit the pressure within the heating or cooling system. So it is important to properly size your expansion tank, because a properly sized expansion tank will accommodate the expansion of system fluid during the heating or cooling cycle without allowing the system to exceed the critical pressures. Also, expansion tank basically uses the compressor to maintain the system pressure by accepting and expelling the changing volume of water as it heats and cools. So this is the chiller yard drawing I have over here. As you can see, let me zoom it. This is the expansion tank that is connected to our system or pressurization pump set. As you can see that this is expansion tank. So basically today we are going to do the expansion tank sizing, and in the end I will explain you guys about the position or location of the expansion tank where we need to put our expansion tank. So make sure to watch the video till the end to get a better understanding of the expansion tank sizing. So let's start moving to the calculation procedure of the expansion tank. I have made this Excel sheet. First of all, we have this sheet that is related to expansion tank sizing formula. Second one is basically related to system volume calculation, and the third one I have prepared over here for different charts and tables we are going to use during our calculations. So let's start this expansion tank sizing. So this is the formula which we are going to use to calculate the expansion tank size. So what is this formula? Let's look at this. Vt is equal to Vs into V2 divided by V1 minus 1 minus 3 alpha delta T divided by 1 minus P1 by P2. So what are these parameters in this formula? First we need to understand what are these parameters. Only then we are able to calculate the size of expansion tank. So what is Vt? Vt is basically the volume of the expansion tank, which we are going to calculate in gallons or cubic feet or cubic meter. And Vs is the volume of the system. Volume of the system means that all the pipes which we have used in our project, all of the volume occupied by the pipes and equipments, everything. It is the sum of all of the pipes and equipments volume. So we will calculate this one. And V1 is the specific volume of the water at low temperature, and V2 is the specific volume of the water at high temperature. And this P1 is low pressure, and the minimum pressure we took over here is 20 psi, the minimum pressure we can take for our system. And P2 is the higher pressure. Alpha is the linear coefficient of thermal expansion. It depends on material. This alpha value depends on material. Which material you are going to use, you need to put the value over here. So let me go to the third tab, that is tables and chart, to show you the value of alpha, that is linear coefficient of thermal expansion. So as you can see over here, I have a material list for aluminum, carbon steel, cast iron, copper, and this is the thermal expansion coefficient for all the materials. So since we are working on chilled water system and the material which we use over here is carbon steel, so alpha value over here is 6.5 into 10 to the power minus 6 inches per inches degrees Fahrenheit. So this value we are going to use in our calculation because we are using black carbon steel material. So 6.5 into 10 to the power minus 6. So this is the value which I have used over here for the alpha. And delta T is equal to higher temperature minus lower temperature difference, and this is 66 degrees Fahrenheit. T1 is the lower temperature, T2 is the higher temperature. Now what is lower temperature? T1. T1 is basically our chilled water supply temperature, that is 44 degrees Fahrenheit. And T2 is the higher temperature or our ambient temperature on the location which I am working on. Let's say the location ambient temperature is 110 degrees Fahrenheit in which I am working with. So and T1 is the chilled water supply temperature. So delta T is equal to T2 minus T1. So our temperature difference will be delta T equal to this T2 minus T1, ambient temperature minus chilled water supply temperature. That comes out to be 66 degrees Fahrenheit. So now we have to calculate volume P1, specific volume of the water at lower temperature. Now how this value comes out, I will show you. So we know that our lower temperature chilled water supply temperature is 44 degrees Fahrenheit. Now we have to calculate the specific volume of the water at this lower temperature. So let's move back to our tables and charts to get this value. So 44 degrees Fahrenheit. So this table is in degrees Celsius and this one in Fahrenheit. As we know that our temperature is 44 degrees Fahrenheit, since we don't have 44 here, we have 40 and 50, and specific volume is same, 0.01602 at 40 degrees Fahrenheit and 0.01602 at 50 degrees Fahrenheit. So we can take this value at 44 degrees Fahrenheit, that is 0.01602 cubic feet per lb. So at 44 degrees Fahrenheit we have a specific volume of 0.01602 cubic feet per lb. And the specific volume of the water at higher temperature and higher temperature ambient temperature is 110 degrees Fahrenheit. So move back to our table and chart again. As you can see that there is 110 degrees Fahrenheit and specific volume of the water over here is 0.01617. So we can use this value 0.0167 cubic feet per lb at 110 degrees Fahrenheit. So this is value which I have right over here. So now we have to calculate the high pressure, that is 45 psi. How this comes out? P2 is basically our system maximum pressure. System maximum pressure is basically the pump head loss which we have already calculated. If you have seen my previous videos related to chilled water pump head calculation, you can calculate the pump head and you can use that value over here to calculate your expansion tank size. So let's say the pump head which we have calculated over here is 70 feet. So we need to convert this into PSI. In order to convert this into PSI, you need to multiply this chilled water pump head with 0.433. And you need to add 14.7 in order to convert this absolute to the gauge pressure. So total formula is this pump head into 0.433 plus 14.7. So P2 is the higher pressure we got over here is 45.01 psi. So now we have everything except system volume we will calculate now. So now we have V2, V1, we have alpha value for the material, that is black carbon steel 0.000065, and we know the pressure P1, minimum pressure of our system is 20 psi and the high pressure is 45 psi. So only thing remaining over here is volume of the system, Vs. So let's move back to our second tab in order to calculate the volume of water in system. I have divided this into two parts. First part is related to the pipes, all of the pipes which we used in our project, and second part is related to the equipment side, water content. So first part, so let's say that this is all of the pipes which I have used in my project. I have to write over here. I need to mention the lengths which I have used in my system. Let's say that I have write everything, and the third tab is related to weight of water in pipe, that is lb per feet. How much lb per feet is required for that much this pipe size. So let's say we have a 2-inch pipe, and move to the right side. This is the water content table which we are going to use. We can say that 2-inch pipe size, how much lb per feet of the water is required. 2 feet, this is the weight in lb per feet. 2 inches weight per lb per feet, how much weight is required, that is 1.36. so as you can see that 1.36 is required for 2-inch pipe size. And let's say 8-inch, how much weight of the volume is required. 8 inches weight of the lb per feet, that is 21.8. So you have to write everything in the same way I have explained over here, that is lb per feet is required for each and every pipe. And the fourth column is related to water volume in gallons per feet. So let's say we have 3-inch pipe size, how much gallons per feet is required for 3-inch pipe dia. So gallons per feet for 3-inch pipe dia is required 0.367. You can see 0.367. So in the same way, let's say for 10-inch pipe size, how much gallons per feet is required for 10 inches. 10 inches gallons per feet 4.08. So in the same way you have to write gallons per feet for every pipe used in your project. Now next column is related to total volume. As you can see that we have write volume of water in gallons per feet. So now we have 100 feet. 100 feet, we need to multiply this 100 feet with that much volume of water per feet. So we'll get the total volume in that much length. So as you can see, so we need to, as you can see, the formula which I have applied over here is the volume of the water in gallons per feet multiply this length. You will get the total volume in gallons within this pipe and this length. So total volume of the water required for 1/4 pipe size having 100 feet length is 6.4 gallons. So 4-inch pipe size is 73 feet, length requires 47.67 gallons. So in the same way you have to calculate for all. So let's say we have calculated for all of these and we have summed it up over here. So we have summed it up and total volume of the water in the pipes is 1189.54 gallons needed. So this is basically the volume of the water inside the pipes which we have calculated over here. Now the second part is related to the equipment's volume, how much volume of the water will be inside the equipments. So let's say we have we have write everything which we have in our project, 4 air cooled chillers and air handling units, and then FCUs over here. So air cooled chillers we use in project is 4. So water volume in the gallons required per air cooled chiller is 18.5 gallons. You can get this value from the supply directly, so you can write over here 18.5 or whatever the value which you have for your chiller. So one chiller required 18.5, so 4 chillers required 74 gallons. So and now the second we have air handling unit. So now we have air handling unit. So we need to write the water content in kgs and cubic meter, and then we need to convert this into gallons to get the total volume in gallons. So let's say we have air handling unit with a water content of 24.89 kgs. You need to convert this into cubic meter by dividing by 1000. So next is we need to convert this into gallons. You can get this value also from supply, how much content of the water is required for your air handling unit. So water volume in the gallons, in order to convert this into gallons, you need to multiply this cubic meter with 264.172 in order to convert this into, because 1 cubic meter required 264.172 US gallons. So this air handling unit requires 6.58 US gallons. So since we have one air handling unit of this type, so we got total volume is 6.58 gallons. So in the same way you have to calculate for all of the equipments of your project. So in order to get this value, and then you have to sum up all the volume of the system which you have calculated above. So total volume of the equipment over here is 140.94 gallons. So for the, due to the pipe, the volume which we have calculated is 1189.54, and due to the equipment, the volume which we have calculated over here is 140.94 gallons. So total volume of the system is equal to pipe volume plus equipment volume. So pipe volume is equal to 1189 and the equipment volume is 140.94. So this comes out to be 1330 gallons. So now we have to apply safety factor. You can take safety factor 10 to 15%. So now I am going to apply 10% safety factor to our calculation. So 10% safety factor of 1330 will be 133 gallons. So total volume of our system will be now 1400, that is 1330 plus 133, that is equal to 1463.53 gallons. So now what you have to do, you know all the values. You know V2, you know V1, you know alpha, delta T, P1, P2 and Vs. Total volume of the system we have just calculated now, that is 1463.53 gallons. So now we have to put all the values in our formula over here, that is Vs into V2 by V1 minus 1 minus 3 alpha delta T divided by 1 minus T1 by T2. So I have already write the formula over here and put all the values over here. After that I got the value is 24.66 gallons. So round off it will be 25 gallons. So for that much system volume, 1463 gallons volume of the whole system, how much size of the tank it should be? It should be 25 US gallons. So our expansion tank size should be 25 US gallons. So this is how you can calculate the expansion tank size. Or it's very easy to calculate. If you know all these values, you have to put it and then you can get the expansion tank size. And the last thing I want to explain over here is the location related to the expansion tank. So about the location of the expansion tank, since the point of connection of expansion tank to system is point of no pressure change, therefore it is typically located at the suction side of system pumps. As you can see in this drawing, this is our expansion tank and this is our main chilled water return header, and this expansion tank is connected to main chilled water header, and this is further connected to suction side of primary chilled water pump. Therefore our expansion tank is connected to suction side of primary chilled water pumps, and we don't want any air to withdrawn into the system, and we want the pressure everywhere in the system must be above atmospheric pressure. and we don't want any air to drawn into the system. That's why it is located on the suction side of the pumps. So I hope you guys learned something from this video. Now you guys can calculate easily expansion tank size, and for more videos keep watching my channel and don't forget to subscribe. Hello guys, this is Syed Muhammad Wakas. Many people were requesting me to make video regarding chill water pump head calculation. So today I'm going to make video on this topic. So let's start. So before starting this chill water pump head calculation, I'm going to explain you guys the main difference between primary and secondary chill water pumps. As you can see that I have this drawing of the chiller yard. You can see that I have a chillers over here, and then we have secondary chilled water pumps, and then primary chilled water pumps over here. So what is the main purpose of this secondary chilled water pump and the primary chilled water pump? So primary chilled water pump is basically, this primary chilled water pump is basically taking water from the building and push to the chillers, while this secondary chilled water pumps, they are taking water from the chillers and push to the building. So I will explain you over here in this chiller yard drawing. As you can see that this is our primary chilled water pumps and these are the chillers. So secondary chilled water pump basically taking water from chiller and push to the building. So this is the supply side of the chiller. As you can see that from this arrow, it is supplying water from the chillers. It's coming from here like this, and it is going into the secondary chilled water pumps. After secondary chilled water pumps, it is circulating over here through this line, and then it supplies to the building over here. And primary chilled water pump is taking water from buildings and push to the chillers. As you can see that this is the return. This one is the return from the building. This return is coming from here through this pipe and then going inside the primary chilled water pumps. As you can see over here, then it's circulating back from this pipe like this, and it is coming back from here into the chillers. So this is the main function of this primary pumps and secondary chilled water pumps. So let's start the pump head calculation. As you can see that I have Excel sheet over here. So I'm going to explain you the pump head calculation for secondary chilled water pumps. As you can see that this is the drawing I have, in which I will show you the pump head calculation. So you can see that we have a chiller over here that is has capacity of 200 tons, and we have a 4 air handling units over here, 1, 2, 3 and 4, each with a capacity of 50 ton. And you can see the supply piping from there going into secondary chilled water pumps, 1, 2, 3, and then it's going into the air handling unit 1, 2 and 3. And we know that we have a chiller of 200 TR and GPM is 480 GPM. As you can see over here, 480 GPM, and the pipe size is 5 inches, and each air handling unit with the 50 ton of refrigeration capacity. And how much is the GPM over here is 120 GPM with a pipe size 3 inches for each air handling unit. So as you can see, the pipe size over here is 5 inches. Flow rate changes to 360 GPM because 120 move over there, again 120 move over there to air handling unit 2. So we are left with 240 GPM 4 inch pipe size, and 120 GPM over here in air handling unit 3, and 120 GPM here to the air handling unit 4. So if you want to know how did we get this GPM and tonnage, you can see my previous tutorials regarding pipe sizing and heat load calculations. As you can see that we have divided the this piping into different sections from A to B, B to C, C to D, and F and G, H, I, J, K, and L up till L. And you can see the section length for secondary chilled water pump over here. A to B 5 feet, B to C 5 feet, and so on up to K to L, that is 16 feet. So we have divided this piping into different sections to calculate the pump head. But before starting the calculation, you need to know one more thing. In order to calculate the pump head, we need to find the most hydraulically remote circuit in our chilled water system. As you can see that this is the supply piping for secondary chilled water pumps from there to point K to L. And we know that K to L 16 feet, and I did not write over here, but from K to air handling unit 4 length is 10 feet. So this is our longest run of piping up till point L. So this is our most hydraulically remote circuit over here up to point L. So let's move back to our Excel sheet to start pump head calculations. As you can see that I have divided the piping into different sections, A to I, I to J, J to K, and then K to L. Why did I write from A to I directly? Because if you see that over here, our GPM and pipe size is constant up till point L, up till point I. So after point I, our GPM and pipe size is changed. So that's why we keep the same from section A to section I. Here we have 480 GPM and 5-inch pipe size. From section A to section I, 5-inch pipe size, 480 GPM. So as you can see over there, we have a pipe size 5 inches. So what we have over here from section A to I, we have a straight pipe, we have a gate valve, we have butterfly valve, strainer, elbow, NRV, and DRV. I will explain you each one of this in detail, how we get these fittings section A to I. So let's start this first one. Pipe, we have a straight pipe, this one up till point I. We have a total length. How much is the total length we have from section A to section I? As you can see that A to B 5 feet, B to C 5 feet, C to D 5 feet, and then up to section I we have that much. So 5, 10, 15, 20, 21, 36, 36 and 20, 56, and then 10, 66. So section A to I we have 66 feet length of the pipe. So move back to our Excel sheet. You can see that the length over here is 66 feet. And if you want to convert this length into meter, you need to multiply this length with 0.3048, you will get in meter. And we know that we have a 5-inch pipe size, 480 GPM is the flow rate. We already checked from there, 480 GPM, 5-inch pipe size. So if you want to convert this into liter per second, you need to multiply it with 0.06208, you will get in liter per second. Now I will tell you how did we get this friction. So in order to show you, I will open this pipe sizer for you. So the pipe which we are using over here is flat steel schedule 40, and you see that pipe size is 5 inches and flow rate is 480 GPM. So flow rate and pipe size is 5 inches and flow rate is 480 GPM. As you can see, the head loss over here is 3.895 feet per 100 feet. So this is how did we get this friction, that is feet per 100 feet in the straight pipe, the flow rate of 480 GPM and pipe size is 5 inches. So move to our next column, that is equivalent length. Since we already got the straight length of the pipe, so there is no equivalent length for this pipe. This is only for the fittings and the valves. So it will be 0, number of fittings 0. If you multiply and if we move to next column, that is total equivalent length in the straight pipe. So how did we get this total equivalent length in the straight pipe? We need to multiply this equivalent length time number of fittings plus the length which we have calculated over here, the linear length of the pipe, that is 66 feet. Since this one is 0, so we have only 66, that's why total equivalent length in a straight pipe is 66 feet. So moving to our next column, that is head loss. How did we get this head loss? We simply need to multiply this our friction, that is feet per 100 feet, that is 3.895, with this total equivalent length in the straight pipe. You will get this head loss. So as you can see that friction over here is 3.895 and equivalent length in a straight pipe is 66. If you divide it by 100, you will get the head loss. With 5-inch pipe size and that much friction rate, we will get the head loss of 2.57 feet. So this is 2.57 feet. Now I will show you the fittings which we have from section A to I. So this from section A to I, what are the fittings we have? So in order to give you a better idea, let me show you in this chiller yard drawing. Since we are working with the secondary chilled water pumps, and we can see that this is the section of the secondary pump. This is the pump header, if you can see over here. And what are the fittings do we have on the suction side and the discharge side of the secondary chilled water pump? As you can see, on the suction side we have this butterfly valve and we have a strainer. On the discharge side we have a swing check valve and a butterfly valve. So we have a one butterfly valve and one strainer, one swing check valve and one butterfly valve. So total 2 butterfly valves, one strainer and one swing check valve. Also we have a one gate valve over here from the supply side of the chiller. As you can see that this is a motorized gate valve over here on the supply side of the chiller. It is supplying from here and going into the secondary chilled water pumps. So we have a one gate valve over here, and other things I have already explained you on suction and discharge side of the chilled water pump, secondary chilled water pumps. That is 2 butterfly valves, one strainer and one check valve. And let's move back to our Excel sheet. You can see that gate valve over here, that is 1, butterfly valve we have 2, strainer 1, NRV, that is non-return valve or swing check valve, that is 1, and elbow, we need to check the elbows. So if we move back to our drawing, from section A to section I, how many elbows we have? 1, 2, 3, 4, 5. So up till section I we have 5 elbows. So elbows we have 5 over there. So only one thing is remaining, that is DRV, double regulating valve. So on the pump side we will have one DRV, that is double regulating valve, to balance the chilled water flow rate across the secondary chilled water pumps. So we will have one DRV from section A to I on the secondary chilled water pump side. So now pipe size is same, that is 5 inches for all these fittings, and linear length for these fittings is 0. We need to get the equivalent length from here. So linear length is 0 for these fittings, and flow rate we know that for 80 GPM for all of them up to section I. If we need to convert this into liter per second, we can convert by this conversion. And now we need to know, the important thing over here is we need to get the equivalent length of this fitting or the valve. The valve over here is gate valve, And how much is the size? 5 inches gate valve over here with 480 GPM. So we need to calculate the equivalent length in a feet. So I will open the table over here to give you the idea how to calculate this equivalent length. Okay, this is the wall over here. As you can see that the gate wall over here, and we have a 5 inches gate wall. So you move to the right side 5 inches gate wall. 5 inches gate valve over here. You see the equivalent length is 6 feet over here. So this is how we get the equivalent length of 6 feet. Number of fittings, we have only one wall over there. If you multiply this equivalent feet with the number of fittings, you will get equivalent length. Again, you need to multiply this equivalent length with number of fittings and add this length. Since this is 0, so we have total equivalent length in the straight pipe is 6 feet. Same way you will get the head loss. You need to multiply this total equivalent length in a straight pipe with this friction. Friction will be same. Already I told you how to calculate this friction by using a pipe sizer. You need to multiply 3.895 with this total equivalent length divided by 100. You will get head loss, that is 0.23 feet head loss across this gate valve. Now move to the butterfly valve. We have 5 inch pipe size, the 5 inch butterfly valve over here. So we need to calculate the equivalent length. Since butterfly valve is not over here, we can go for the gate valve. Same 5 inch pipe size, that is 6. So again 6, but we have 2 butterfly valve over here, as we already checked that on the section of the secondary chilled water pump. We have a 2 butterfly valves. So 6 into 2, that is 12. Same way you get the head loss. So move next, strainer. We have a 1 strainer over here, 5 inch strainer, 480 GPM. So we need to get the equivalent length. How much is the equivalent length for 5 inch strainer? As you can see that we have a Y type strainer over here. We have a 5 inch strainer. If you move over there, we have a flanged end strainer, Y type. How much is the equivalent length? That is 80 feet. 5 inch, 80 feet. So we can use 80 over here. Since we have 1 strainer, so 80 into 1, that is 80. Again, you need to multiply this equivalent length with friction, that is feet per 100 feet, divide by 100, you will get this head loss. So move back to our elbow. We already know we have 5 elbows over here. So we need to calculate the equivalent length in a feet for this elbows, 5 inch elbows. Since we are using long radius elbows over here, depending on the site condition, we can use standard elbows, but we are using long radius elbows, 5 inches. So we need to get this equivalent length. As you can see that we have this one, as you can see that we have long radius elbows over here. This is a standard elbow, this is the long radius elbow, 90 degree. So we have a 5 inch pipe size. You can see that 5 inch pipe size with the long radius elbow, that is 8.2. 8.2 is the equivalent length for 5 inch elbow, 90 degree long radius. You can see over here 8.2. So this is how we got this equivalent length, 8.2, 5 inch pipe size. So since we have 5 elbows, 8.2 into 5, that is 41. Again head loss is 41, that is equivalent length in the straight pipe. Multiply by friction rate, you will get this head loss. This is how you can calculate the head loss to the elbows. Now the next fitting which we have over here is NRV, non-return valve, or the swing check valve, that is 5-inch pipe size. So let's move back to our chart to get the equivalent length for this NRV. As you can see that this swing check valve here, 5-inch pipe size. So move to the right side, 5-inch pipe size with the swing check valve. How much is the equivalent length? That is 50 over here. So we can use this 50. You can see that number of fittings we have 1 and equivalent length is 50. Same way you can get the head loss. So next we have a DRV, that is double regulating valve, 5-inch size. So move back to our chart to get the equivalent length for DRV. This is our DRV, that is double regulating valve. Since we are using 45 degrees DRV, 5-inch pipe size, 45 degrees DRV, we got 58 equivalent length. So DRV, 5-inch pipe size, 480 GPM, got one DRV, that is 58, that we already checked from the chart. So total equivalent length in the straight pipe is 58. Same way you can calculate the head loss. Simply need to multiply this equivalent length in a straight pipe, this friction, you will get the head loss, divide by 100, you will get the head loss. So the next section is I to J. Next section is I to J. I to J, there is no fitting, only straight pipe is there. As you can see that pipe size is same, only the flow rate is changed. So flow rate is 360 GPM and pipe size is 5 inches. 5 inches pipe size and flow rate is 360 GPM. And how much is the length we have over here from I to J? That is 12 feet. From I to J you can see that we have a 12 feet length. So we have a 12 feet, that is equal to 3.66 meters, flow rate 360 GPM, that is 22.71 liter per second. And again we need to calculate the friction, that is feet per 100 feet. How did we get 2.261? Again we go to the pipe sizer tool. We have a 5-inch pipe size with 360 GPM this time. So how much is the head loss? 2.261 feet per 100 feet. You can see that 2.261 feet per 100 feet. So this is the straight pipe. We already calculated the linear length, that is 12 feet. So total equivalent length in the straight pipe will be 12 feet, that is over here. And head loss will be, you need to multiply this total equivalent length in a straight pipe with friction rate divided by 100, that is 2.261 multiplied by 12 divided by 100, that is 0.27 feet. That is 0.27 feet over here. Now if we move to the next section, that is J to K. From J to K you see that we have a straight pipe. Also you notice that from 5 inches to 4 inches, so pipe size is changed. So we will have a reducer over here, 5 to 4, 5 by 4 reducer. And the GPM over here is also changed, that is 240 GPM. Also we have no reducing T over here to the point K, no reducing T at the point K. So we have a 4-inch pipe size, 480 GPM with the straight pipe, reducer, and the no reduction T. So move back to Excel sheet. See that we have a pipe, 4-inch pipe size, 240 GPM, reducer, 4-inch, 240 GPM, no reduction T, 4-inch, 240 GPM. So what is the straight length of the pipe from J to K? Is 14 feet. From J to K, 14 feet. Okay, that is 14 feet, 240 GPM. And we need to calculate the friction rate again with 4-inch pipe size, 240 GPM. 4-inch pipe size, 240 GPM. How much is the head loss? 3.255 feet per 100 feet. 3.255 feet per 100 feet. Since this is a straight pipe, so no equivalent length, no, for it will be 0, and total equivalent length will be same as the linear feet over here, that is 14 feet. Head loss you need to calculate, you need to multiply this with this, divide by 100. Now we have a reducer, 5 inches to 4 inches reducer. For reducer, how did we get this equivalent length? 3.8. So let's move back to our chart. Okay, this is the table we are going to use to calculate the equivalent length for the reducer. As you can see that we have a sudden enlargement, sudden contraction, and two other. So since we are calculating the secondary chilled water pump head, so pipe size is reduced from 5 inches to 4 inches. So we have a sudden contraction because pipe size is reduced. In this case, capital D is representing our big size, small d is representing our small size for pipe dia. So 5 inches is capital D, 4 inches is the small d. These are the different ratios over here, 1/2 and 3/4. So since we have 5 inches and 4 inches reducer, 5/4 reducer, so 4/5, small d by capital D, I already told you, small d by capital D, and ratio is 0.8. 0.8 that is nearly equal to 3/4, that is 0.75. So we can get this ratio 0.75, that is 3/4 over here, and we have a reducer 4 inch size over there. So move to the right side with the 4 inch size, and 3/4 ratio, we got 3.8 is the equivalent length over here, 3.8. So this is how we got the equivalent length, 3.8 for the reducer, 5/4 reducer, 4/5 reducer. Since we have one reducer, so total equivalent length in a straight pipe is 3.8. So head loss, again you need to multiply total equivalent length with the friction rate divided by 100, you will get the head loss. And the last one from section J to K is no reduction T. So move to our chart again to find the equivalent length for no reduction T. So this is the chart we are going to use for no reduction T. As you can see that this is the no reduction T over here, and we have a 4 inch size over here. If we move to the right side and 4 inch no reduction T, we got 6.7 equivalent length. 6.7 over here is the equivalent length. So see, 6.7 is the equivalent length for no reduction T. Only one T is there, so we got the head loss over here is 0.22 feet. So now move to our next section, that is K to L. K to L. To understand K to L section, we have I will open one image for you to get the better understanding. As you can see that this is the supply side of the air handling unit, and this one is the return side of the air handling unit. Since we are calculating the pump head, secondary chilled water pump, that is supplying water from chillers pushed to the building. So this is the supply side we need to consider for secondary chilled water pump. So what are the fittings we have on the air handling unit supply side? This is the gate valve, and this is Y-type strainer. So we have two fittings, and this one is a two-way valve. You can use this for primary chilled water pump head calculation, and this is the DRV double regulating valves. So right now we consider only these two things, that is Y-type strainer and gate valve over here, because we are calculating the secondary chilled water pump head right now. So we have two fittings over here, as I already show you in the image, that is gate valve and the strainer from point K to L. Also notice one thing, the pipe size is reduced from 4 to 3 inches, so we will have a reducer over here also. If we move back to our Excel sheet, you can see over here we have a pipe size 3 inches, gate valve, strainer and reducer. So these are the three things which we have in this K to L: pipe, gate valve, strainer and reducer. So we have a 3-inch pipe size over here and 120 GPM, and equivalent length over here we will calculate now. First, linear feet of this pipe is 16 feet, just confirm from there. K to L 16 feet. Okay, 16 feet which we have used over here for this pipe, 3-inch pipe size. Again we need to calculate this friction for this 3-inch pipe size with 120 GPM. Go to the pipe sizer tool, 3-inch pipe size, 120 GPM. Head loss is 3.433 feet per 100 feet. 3.433 feet per 100 feet. So total equivalent length is 16 feet. You need to multiply with friction rate, divide by 100 to get the head loss. 3.433 multiply by 16 divided by 100, you will get the head loss of 0.55. 0.55 is the head loss. Now the fittings which we have over here is from K to L is gate valve, strainer and reducer. First, gate valve, 3-inch pipe size, same GPM. We need to get the equivalent length of this gate valve, 3-inch gate valve. Okay, we have a gate valve over here and 3-inch gate valve. Move to the right side, we got 3.2 is the equivalent length. So 3.2, only one gate valve, so total equivalent length 3.2 in the straight pipe, and you can calculate the head loss in the same way I have explained. So next fitting which we have over here is strainer, 3-inch strainer. So this is a wire type strainer over here and 3-inch. We move to the right side, and since we are using a flange and strainer over here, so equivalent length is 42 over here for the flange and strainer, 3-inch 42. So 42, and we have one strainer, so total equivalent length is 42, and we can calculate the head loss by multiplying this equivalent length with this friction, divide by 100. So last one is reducer. Same way we'll calculate the equivalent length for the reducer. Since the pipe size is changed from 4 inches to 3 inches, move back to the chart. Okay, again there's a sudden contraction from 4 inches to 3 inches. 3 inches representing small d and 4 inches representing as capital D. If we get the ratio of 3 by 4, we will get 0.75. That is 3 by 4 ratio over here. As you can see over here, sudden contraction 3 by 4. And 3 inches, we move to the right side, we get the equivalent length for this reducer is 2.6 over here. Move back to the Excel sheet. The reducer equivalent length is 2.6 feet, only one reducer, total equivalent length is 2.6. Again you need to multiply this total equivalent length in the straight pipe with this friction rate, that is 3.433 multiply 2.6 divided by 100, you will get 0.09 feet. That is 0.09 feet. So all sections head loss has been calculated. Now what we need to do, we need to sum all of this to get the total head loss in the feet. So 15.45 is the total head loss in the feet, If you want to convert this into meter, you can use a conversion rate. So 15.45 feet is the head loss, and we need to add some safety factor. We will add 15% safety factor doing it, and total head loss after adding this 15% safety factor, 15% safety factor is 2.32 feet. So total head loss in the feet is 17.77 feet. So secondary chilled water pump head loss is 17.77 feet. So if you want to calculate this brake horsepower of this pump, you can calculate by using this formula, that is GPM into head into specific heat of the water into 3960 into efficiency of pump. Efficiency of pump, normally we are taking 85%, and specific heat, that is 1. If you will put all the values and GPM, we know that total 480 GPM. So if you put all these values, 480 GPM, 17.77 feet into 1 into 3960 divided by 3960 into efficiency is 85%, you will get the brake horsepower, that is 2.53. And you can get the horsepower by just multiplying this with 1.15, and if you want to convert this into kilowatt, you need to multiply this horsepower with 0.746. So the pump head loss is 17.77 feet and the kilowatt is 2.17 kilowatt. So this is how you can calculate the secondary chilled water pump head. In the same way you can calculate the primary chilled water pump head. The only difference between primary and secondary chilled water pump head, you will get the sudden enlargement over there. So you guys can do it on your own. If you find any difficulty, you can let me know, I will help you. So I hope you guys learn a lot from this video. It will be useful for you guys. For more videos, keep watching my channel and don't forget to subscribe. Hello guys, this is Sayyid Mohammad Waqas. I'm back with another video. In this video I will tell you guys how to calculate the chemical quantity required for the chilled water system. So let's start. There I have made an Excel sheet for chilled water system volume calculation. Before starting the calculation, I will explain you why chilled water system chemical is required. Why do we need to put the chemicals? So we need to put the chemical because we need to prevent the system from corrosion, scaling, fouling and microbiological growth. We are doing this basically in 3 ways. First, the chemicals react with the pipes to form a protective thin inside layer. Second, the chemical help in maintaining the pH level. And third, the chemical remove the corrosive dissolved oxygen in the water. So we are using the dosing pumps to supply the chemicals in chilled water system. I will show you over here in the drawing. There I have one drawing for the chiller yard. There you can see that we have 4 chillers over here, 1 2 3 4, and this is the chemical dosing pot installed over here. Let me zoom in. So as you can see that this is the chemical dosing pot. We are using automatic and manual chemical dosing pot over here. So basically these dosing pots with the dosing pumps are used to supply the predetermined quantity of the chemicals at regular intervals. So as you can see that is how this chemical dosing pot is connected with the chilled water lines. This is our basically chilled water supply line that is coming from the chillers, a chilled water supply, and this is our bypass line, and this chilled water is basically supplying from the chillers into the secondary chilled water pumps. Here there are 3 secondary chilled water pumps, and then this chilled water is supplying from here to the buildings, and similarly this chilled water is coming back to the chillers from the buildings through these lines, and then going into the primary chilled water pumps, and through this primary chilled water pumps it's returning back to the chillers, and the whole process repeats. So this is our chemical dosing part installed over here, as you can see that. So let's start the calculation over here. So this is the Excel sheet. First you have to write all the piping you have used in your project over here, all the dias from your drawings, and then you can convert this into radius, this one in inches, and this column same radius, and it is in meter. You can use the conversion to convert this in meter. So this is all the piping we have used in our project, that is 1.25 inches to 14 inches. So you have to calculate the area of the pipe for 1.25 inches. Similar, it's like pi r square. You can calculate the area of the pipe for each and every dia. So let's move to the next column, that is pipe length. You can get this pipe length from your drawings. So 1.25 inches dia we have used 130 meter in our project, and 3.5 inches we have used 90 meters, and 8 inches we have used 30 meters, and 14 inches we have used 20 meters. So all of the lengths are given here. So now we have to calculate the volume for this pipe. So we know that area of the pipe is here, length is here. We just need to multiply this column with this column. We'll get the total volume to 1.25 inches dia pipe, which we have used in our project. In the same way you have to use for all of the pipes which you have used in our project. 14 inches, same way you need to multiply area times length, and you will get the volume through 14 inches pipe which you have used in our project with 20 meter length, that is 1.99 cubic meters. So now you have to sum all of these volumes, and you will get 11.89 cubic meter volume that you have used in your project. So the total chilled water volume which we have calculated is 11.89 cubic meter. So now we are going to use some safety factor, that is 20%. So we need to get the 20% of 11.89. So there is 2.37 cubic meter. The total chilled water volume becomes now is 14.7, simply 11.89 plus 2.37, so it is 14.27 cubic meter. Now the chemical which we are using over here is corrosion inhibitor, that is A0029, and the second one is microbiocide A2400. So this is a file from Waterbird Chemical Treatment, is one of the reputed company in UAE. So we are going to use the chemicals provided by this Waterbird Chemical Treatment company. So this is A0029 corrosion inhibitor chemical. As you can see, that's a concentrated liquid blend of corrosion inhibitor designed to control the wetting and corrosion in a closed chilled water system and hot water system. It will protect all commonly found in closed system from corrosive attack. I will send you this file and you can read it yourself. So the main thing, the dosage rate for A0029 system, how much is the dosage rate recommended by Waterbird Chemical Treatment. They are recommending 3 kg per cubic meter of system volume is required for your chilled water system. So A0029 corrosion inhibitor, we needed 3 kg per cubic meter of system volume. As you can see that the chilled water volume which we have calculated over here is 14.27 cubic meter. So 1 cubic meter required 3 kg as per recommendation of Waterbird Chemical Treatment. So how much chemical we need for our system? Because we have 14.27, we simply need to multiply this quantity with this quantity. So we need for our system is 42.81 kg of A0029 corrosion inhibitor chemical. Similarly, we have another chemical we are using over here. This is recommended by Waterbird Chemical Treatment, that is microbiocide A2400, and this is the description and advantages. So the dosage rate recommended by Waterbird Chemical Treatment is 100 ml per cubic meter of system volume. So our system volume is same 14.7. We just need to multiply this 14.7 with 100 because 1 cubic meter requires 100 ml. So 14.27 multiplied by 100 will get the chemical needed for our chilled water system, that is 1427.28 ml of microbiocide A2400 is needed for our system, chilled water system. So this is how you can calculate the quantity of the chemical required for your chilled water system, and we are using these dosing pumps to supply these chemicals into our chilled water system. I hope you guys find this video useful. Please like, comment, share, and don't forget to subscribe my channel. For more videos, keep watching my channel. Hello guys, this is Syed Mohammed Waqas. I'm here with another video. If you saw the last video in which I have told you guys how you can calculate the heat load using HVAC software, in this video I will tell you guys how you can calculate heat load using E20 form. So let's start. Here I have opened this E20 heat load sheet. Here I have to give inputs so that it will automatically give me heat load. So let's start filling up. Start from here. This floor is ground floor, space reference, whatever the name you want to give. Over here, if you will see, we have calculated for master bedroom. So whatever the name you want to give, you can give over here. So master bedroom, so you can change it to master bedroom. Okay, then move down. You have area in a square feet. So if we go over there and see what's the area, it is 18 by 20, that is 360 square feet. And ceiling height, we know that is 12.5 feet. So it will give us the volume because this formula is applied over here, give us the volume. So now we have to give the inputs for thermal conditions of that area. Design condition, we know that in Dubai, if we move back to our HVAC software and go to weather properties, we see that Middle East, UAE and Dubai, the city, we see that DB dry bulb, summer dry bulb is 107 and wet bulb is 75. So we can use over here. Outside dry bulb is 107 and wet bulb is 75. Now we have to use psychrometric chart to find this relative humidity and humidity ratio. So I have a psychrometric chart over here. I will tell you how you can use psychrometric chart. So on x-axis I have dBT, that is dry bulb temperature. On the y-axis I have humidity ratio, that is grains moisture per pounds of dry air. And here you can see this is vertical. These lines are for wet bulbs, and the one in the curve lines, that is for relative humidity, as you can see here. So what are our input? We know that dBT, dry bulb temperature, ambient outside temperature for Dubai is 107. So on x-axis we will see and go over here, that is 105 and 110. So 107 will be here. So if we move up like this and go up to wet bulb, as I told you, these are the wet bulb temperature lines. So I need to go from here dry bulb 107 up to 75 wet bulb. This line is touching over here, it's intersecting over here. So as you can see, what is the humidity ratio over here? It is 80. The humidity ratio over here is 80, as you can see here. This is the humidity ratio 80. So I can use this humidity ratio as 80, and relative humidity I also need to check from the chart. So move back to psychrometric chart. What is the relative humidity? As I told you, these curved lines are for relative humidity over here. So if I will move, this is the point, intersection point. 1 second, 107, move up. So this is the intersection point. At that side I got relative humidity, this is nearer to 25. So this is before 25, so we can use 24% like this, 23 or 24%. relative humidity. So we can use 24 over here. Now we know that indoor design temperature is 75 degree for human comfort, and relative humidity is about 50 to 60% for human comfort. So we are using 50 over here. Now we have to give input this output wet bulb and humidity ratio over there to fill this thermal condition. Okay, move back to psychrometric chart. We know that 75 is the dry bulb and 50% is the relative humidity. These are the relative humidity lines. So you can see this point. These are the relative humidity, 50%. This is the point intersecting over here. So at this point, what is my humidity ratio? If I move over here, I got a humidity ratio is in between 60 and 70, but it's very close to 70, so I can take around 68 like this. Okay, let's take 68 from humidity ratio 68. And wet bulb, similarly we can check from here. These are the wet bulb lines. This is in between 60 and 65, so we can say this is 60 and 65 is in between them, so we can take 63 like this as a wet bulb. Okay, let's take 63. So we have filled this thermal conditions for that area, and we got a difference. Dry bulb like this, and wet bulb 12, relative humidity 26, and humidity ratio 12. So bypass factor, as I told you, it is coming from the supply. Normally it is 0.12, so we are using the same 0.12, and this contact factor should be 1 minus bypass factor. So it will automatically come if you will fill the bypass factor over here. No, now as I told you, here we have to give number of people for the bedroom. We assume 2 number of people for the bedroom. And how much is the CFM per person? If we will go back to our app software and open the space master bedroom and go to this ventilation requirement, what is the CFM per person? 5, and CFM per square feet, that is 0.06. so we can use these values. So number of people we already gave it, and CFM per person is 5, and CFM per square feet we know that 0.06 is from the app software. So okay, up till now we are done. So infiltration, there is no infiltration because the construction we considered over here is very tight construction, so no air will come in like this. So it's a tight construction, doors are properly sealed, windows properly sealed, so there is no infiltration load. So if I will move back over here, this is my first I will fill here for the glass. If we'll move back to my drawing, how many glass we have here? One here window, one here window, and what is in the schedule? If I'll see this window 1 is 5 cross 3, 15 square feet. So how much is the total window area for this bedroom? Is 15 for each window. We have 2 windows, so 15 cross 2, we got 30 square feet. So we can use 30 square feet over here for windows, and this is the transmission load for the windows glass. 30 square feet is the total area, and I told you for glass transmission will be outside ambient temperature, that is 107, that is dBT outside, minus inside design temperature is 75, minus it will be 5 degree less than the outside, so we can use 27 degree over here for floor and for partition. But for glass we have to say 107 outside dBT minus 75 inside design temperature is 32. It's a glass transmission load, we have to use 32 degree Fahrenheit. Okay, and glass U value, as we already know that glass U value, that is 0.30, so we can use 0.30 over here. Okay, now for the partition and for the floor area is same as the area we already described over here, that is 360 square feet. And I told you for floor delta T, that is outside ambient minus inside design minus 5 degree, so 27 it will come over here. And floor U value, we will go over here and check what is the floor value, that is 0.1. 0.1 is the floor value, so we can use 0.1 U value for the floor and for the partition. If we'll go back to our partition, okay, so moving back to the partition area, this is our partition wall and length of this wall is 12 feet. So 12 feet multiplied ceiling height is 12.5, we got 150 square feet is the partition wall area. So we can use 150 square feet partition wall area over here. Okay, and partition wall U value we can see over here, that is 0.5. So we can use 0.5 U value for partition, and so it's done. For the roof, that is same area as the floor area, 360 square feet, and delta T I will tell you. First we will add the U value for the roof from here. What is the U value for the roof? 0.045. So we can use this U value for the roof 0.045 directly, 0.045. Okay, now here this is a transmission load through walls and the roof. So now we have to write delta T for the roof. In order to write delta T for the roof, that is we have to add some correction factor in this one. So I will tell you how you can do that delta T by using a different chart. So let me open this first for you. Okay, here it's for roof. Okay, as you can see that our roof is exposed to sun, and I told you the building weight is average medium weight, that is 80 lb per square feet. So this one we have to use, and we know the peak time for the design is 3 p.m. So 3 p.m. is the peak time for the design, and 80 lb per square feet is the building weight. So over here we'll go and it will intersect over here, and we got a value of 28. So 28 we have to use over here, plus, now remember this figure 28, plus we have to add some correction factor due to the material specification. So we'll add 28 plus some correction. So for the correction, what we have to do is another chart over here, correction to the equivalent temperature in degree Fahrenheit. We know that outside design for the month at 3 p.m. minus room temperature. Outside design dry bulb is 107, and we know that inside design temperature is 75. After subtracting, we got 32 degree Fahrenheit, and we know that daily range for Dubai is 17.5. If I'll go back over here and show you the weather properties, summer daily range is 17.5, that is around 18. Okay, so we can use daily range of 18 because 17.5 is very close to 18. We'll use over here, and here we got outside 107 minus inside 75, 32. So 30 and 35 will move to 35, and 18 we got 21 over here. So this figure should be added into the figure 28 which I calculated before. So what is the delta T value? We got 28 plus 21. Total delta T value is 49. We have to use over here. So move back to our E20 form, and we will use delta T value of 49. So we use 49 delta T over here. Okay, now we know that the wall that is exposed, some walls are exposed to sun, and these walls are north side exposed and this side is west side exposed. So north side exposed, we know that how much is the area, 18 feet is the length, multiplied 12.5 is the ceiling height, 225, and we know that west wall, that is 20 multiplied 12.5, 250 square feet. Move back to E20 form. So north wall got 225 square feet and the west wall got 250 square feet, and we know that U values for wall, that is 0.05. just double check again, U value for the wall, that is 0.05. okay, use that one over here, 0.05, same over here, 0.05. Now we have to use delta T values. In the same way we have calculated for the roof delta T, we will calculate delta T values for the wall. So if I move back to other chart, there it is. This is equivalent temperature difference. As we know that wall average weight is 80 lb per square feet and peak time is 3 p.m. So one of the wall is facing north side. If I move to north side, like this is the north side, and we know that building weight is 80 lb per square feet. So 60 and 100, it will be in between them, and we know that 3 p.m. is the peak time for the design. So this is the 3 p.m. as you can see over here, 3, and move over here in between 60 and 100. 60 and 100 got 8 and 3. My value should be in between them, that is 60 and 100. 80 should be in between them, is the average of 2. So what I will do, I will add 8 plus 3 divided by 2. I will get the value for 80 lb per square feet. So 8 plus 3 divided by 2, I got 5.5. So after, remember this figure 5.5. In this figure I will add the correction temperature, and this correction temperature is same as we calculated before. Let's move back to the other again. I will show you once again. Here this is the correction. It is same because outside temperature is 107, inside is 75. So we got 32 over here, and daily range I told you that is 18. So 21 need to be added into 5.5 plus 21 is the correction for material specification. So we got 26.5 degrees Fahrenheit delta T. So move back to our E20 form. For the north side we got 26.5 delta T. As you can see, load is calculated to 98. Okay, now move back to our, and one of the wall is facing west side. As you can see, north side is done and another wall is facing west side. So we have to check for the west side also. West side. Okay, here is the west, and we know that the building weight is 80. Average building weight is 80 lb per square feet. It should be in between them. So if I move over there, and 3 p.m. is the peak time, for 3 p.m. peak time we will move up and west side 60 and 100, 80 in between them. So we'll take a mean value for this one, that is 19 plus 10. 19 plus 10 divided by 2. Mean value is 14.5, plus we will add the same correction factor, that is 21 we use for the north wall and the roof. So we got 35.5 delta T for the west wall. So we'll use 35.5 for the west wall. Okay, 35.5 for the west wall. Now load is calculated over here. Now let's move to radiation load for the glass. We know that total glass, okay, north facing glass, one window is facing north, one window is facing west. This facing north, this facing west. And how much is the area? Window 1, 15 square feet. We can do 15 square feet on our E20 form. So north facing 15 square feet and west facing 15 square feet. And we know that delta T for the glass 0.30, yeah, 0.30. We can use this one over here. Delta T is 0.30. Same we can use delta T 0.30 over here. So now we have to check delta T for the glass. Before checking delta T for the glass, let us check one more thing in the weather properties. 30 degree north latitude. Okay. As we know that in Dubai, this latitude is 30 degree north latitude. So if we move back to our chart over here, yeah, this one, this is for 30 degree north latitude. This is a solar heat gain through ordinary glass. So as we know that the maximum load is occurring during July and the May. So we'll select this one, 21st May to 23rd July. and we know that the peak time is 3 p.m. So, and we know that one of the glass is facing north and one is facing west. So at 3 p.m. north, how much we got over here at 3 p.m.? That is 13. So for the north side we have to use 13 value, and for the west side we have to use at 3 p.m. that is 145. So north side 13 and west side 145. Here the delta T values. North side 13 and west side 145. So here is the load calculated for the north side and for the west side. So all of the inputs are done, almost. Some of the inputs remaining that are over here. As we know that if we'll go back to our app software and open the space and go to internal, we know that sensible heat per person is 230 and latent is 120 for the people seated at rest. So we can use 230 and 120. 230 and 120. Okay, this is the sensible, that is 230, and number of people we know that 2. And lightning, as I told you, general rule is 1 watt per square feet, and we know that the total square feet is 360. And for the equipment, we have assumed that 200 watts. Only one equipment is there, so we can add one equipment over here. And 2 people, and the latent we already checked from the half, that is 130. Latent from the half is 120. 120 we can use over here. 120 get used per square feet. Okay, now everything is done. Infiltration, I told you there's a tight construction of this building, so there's no infiltration, no outside air will come inside. Okay. It's done. Okay, now what we have to do next is one more thing. As we have seen that effective room sensible heat factor is 0.97. Move back to one more chart. So here, okay, we know that dBT inside design temperature is 75 and relative humidity is 50%. So this is dry bulb temperature 75 inside and design temperature 75, and this is relative humidity 50, and we know that this is effective sensible heat factor is 0.97. So if I'll go over here, 75 inside design temperature, 50 relative humidity, and 0.97 is the effective sensible heat factor. So our ADP will comes out to be in between them. So it will be around maybe 54 is here, 55.2 is here. So it will be around 54.7 like this, 54.7. So we can write 54.7 over here, or 54.6, 54.7, whatever. Okay, now if you see that this is the calculated CFM, that is 478 effective room sensible heat, and CFM is 478, and tonnage is 0.92 TR, and load is 11 MBH, and TSMBH is 10,198, and TS kilowatt is 2,957. If we'll go back to our app and we'll compare the result, let me generate the report again and say preview for the report. Here how much we got, total tonnage is 0.9 ton. Here we got 0.92 ton. See, approx it's almost near. So if we move back to our app again, and how much is the coil load, that is 10.6 MBH over here, and how much is the coil load is 11 MBH over here, TMBH is here. Okay, this is also near. And if we move back to here again and see the CFM, that is 427 CFM, and how much we got over here is 478 CFM. So it's not big difference for our calculation. So this is how you can calculate heat load by using E20 form. And for the HAP I already told you in my previous video. So I hope you guys learned something from this video. Please like, comment, share, and don't forget to subscribe my channel. Thanks. Bye bye. Hello guys, this is Syed Muhammad Waqas. I'm here with another video. In this video I will tell you guys how you can calculate the heat load. So here I have drawing open. In this video I will tell you how you can calculate heat load for master bedroom. In the same way you can calculate heat load for store, living room and kitchen area. So before starting the heat load, you must know the local codes followed by that region. For example, I am going to work in UAE, so I must know the U values and the local codes followed by that region. So as you can see that the window schedule is also there, that is window 1, it's over here, window 1 and window 1, and you have window 2 schedule used over here, here, here and here, window 2. So and the U values are also given over here. U value for the wall is 0.05, for roof is 0.045, for floor is 0.1, for glass 0.30, and shading coefficient for the glass is 0.29, and the U value for the partition wall is 0.5, and the average ceiling height in this area is 12.5 feet. So let me show you the U value which you're going to use in UAE Dubai. So open this Chrome factor and move down over here. As you can see, for the warehouse structure non-conditioned space, external wall U values is this and roof is this. For conditioned space U value is this, roof this and floor this. And for the office structure and residential area, what is the external wall U value? That is 0.05, and for the roof 0.045, and for the floor 0.1, and for the glass penetration U value is 0.30, and the shading coefficient maximum is 0.29. As you can see, this is the same values which I am using right now, because the area or the region in which I am working right now, it's Dubai. So these are the local codes which I need to follow in order to calculate the heat load for the particular area. So let's start this heat load calculation for the master bedroom in the HAP software. So let me open this app for you. So new installation standard 2010, energy 2010. Okay. So first of all we have to give some inputs. We have to give wall U values, roof U values and window U values. So let's go to wall U values. Default wall. Here in HAP you will not find, you cannot give direct U values for the wall. So in order to give the U value for the wall, as you can see over here, is that is 0.05. I need to give over here. So let me make this 0.05 by selecting different layers. So if I will go over here, default wall assembly, and let me select face width of 14, board insulation, that's 8-inch high weight concrete block. Okay, now if you will play with these layers, you as you can see U value is 0.056, so I am near to 0.05. So let me change this layers in order to make it 0.05. So if I will move it, okay, now 0.053 were more nearer. So let me move this one also 8 inch. Lightweight concrete 0.051. Okay, R14 board insulation okay, and 4-inch face brick will change this to common brick. As you can see, overall U value is 0.05. So this value we can use to calculate the heat load. So we just select OK over here, and then now we'll move to roof. Same thing we'll do over here. As you cannot, what is the U value over here for the roof? That is 0.045. So we have to make this value as 0.045. Let me change this one to fall shingle plus plywood R22 Duct. Okay, as you can see 0.040, we have to make it 0.045. So 3 plywood, if I will select 3 inch plywood, okay, then R19, that insulation is very near to 0.045, then airspace, then half-inch plywood or half-inch with some plaster 0.045. so we got our value 0.045. so we can use this U value of the roof in our heat load calculation. That's okay. Now go to window, new window, give it a name like window 1, and give it height and the width. As if we move to our drawing, and from the window schedule, 5 feet by 3 feet. 5 feet is the height, 3 feet is the width, so we can use over here 5 by 3. As you can see here, we have window 1 in the master bedroom, both sides, window 1, window 1. So we have to use this dimension of the window, that is 5 feet by 3 feet. 5 feet is the height and 3 feet is the width. It's already there, no need to change. And over here you will find U value for the glass is 0.30 and shading coefficient for the glass is 0.29. We can use these values, 0.30 U value and 0.29 shading coefficient. So select OK. Then we have to move to the space, default new space, but before that we have to select this region in which we are working right now. This is very important. So just select this one and change the region which you are working right now. For example, the region which I am working right now, it's Middle East, and the location it's United Arab Emirates, and city is Dubai. So all of the values are here, latitude, longitude, elevation, summer dryburgh, and daily range, everything is there. And just select OK, and then move to spaces. From the space, select default new space. What is the name of that area? You can give over here. It's a master bedroom. What is the floor area? As you can see over here, it's 18 by 20 feet. So how much is the area? 18 by 20. You will get 360 square feet area. 360 square feet area. And average ceiling height, as I already told you, 12.5 feet. And building weight is medium, and medium weight is 80 lb per square feet. What is the usage of that space? This is for ventilation purpose. So if I'll move down, I need to select this bedroom. You can see hotel bedroom and living room. You can select this one. So CFM per person is 5 and CFM per square feet is 0.06. Then move to next tab, internal. Here you find light fixtures, that is recessed, unvented. As per general rule, if you don't have any data from electrical first it's better you will get data from electrical engineer, so you can use that wattage over here. If you don't know, then you can use by default 1 watt per square feet. This is a general rule. Over blast multiplier you have to use, that is 1.07. And then you have to give a schedule over here. Just give it a name, that is light. Select OK. Then move down, task lightning, no need. Then electrical equipment. if you can get this electrical equipment bought from the electrical data, that's better. If not, then you have to use your general rule or predefined rule, that is 8 watt per square feet needed. If you don't know, so let me use, it's a bedroom, it's not too much, so we can use 200 watts. That would be enough for the bedroom. It's okay. So how many people occupied in this room? 2 people. So we can give over here, it's our activity level is seated at rest, and then over here you also give schedule, that is like, so here also you have to give a schedule, name of electrical equipment, for example it's this one. So occupancy of the people, there's 2 people in the bedroom. Okay, what's the activity level? They are seated at rest. Okay, then same way you have to select a schedule for this one, people. Okay, then move to walls, windows and doors. If we move back to our drawing area, you will see this wall, we should know the orientation of the building. So this wall that is facing north side, and this wall that is facing west side, and this wall, what's the dimension? It's 18 foot. So, and we know the ceiling height is 12.5. so what's the gross wall area? Is 225 square feet. And how many windows over here? Only one window, that is window 1. So 225 square feet is the wall gross area facing north side. So move back to have north exposure, and 225 is the wall gross area, and window quantity is window 1 quantity is 1. And if you will move back over there, and you will see another wall that is exposed to sun, and its dimension is 20 feet is the length. So 20 feet multiplied 12.5 is the ceiling height. We got 250 square feet is the gross area of that wall, and it's facing west side. You see over here, west side, and only one window over here. So move back to have, give this as a west side exposure, and 250 square feet is the gross area, and window quantity in window 1 is 1. Window 1 is already selected here. So go back to roof, its exposure is horizontal, and gross area is the same as the floor area. Then infiltration, no need for this one. Residential, okay. And go to floor. If you will go to floor, there are 4 types over there: floor above condition, unconditioned, slab floor on grade, slab floor below grade. In this example, we have this on the ground floor, so we have this floor above unconditioned space. If it's on the first floor, our ground floor is conditioned, then we have to select this floor above conditioned space. As we are on the ground floor and it's a floor above unconditioned, so we have to select this one. Floor area is the same. U value we already see over here, that's floor U value is 0.1, it's already there. So unconditioned space maximum temperature, ambient at space maximum. As you know, ambient at space maximum, we are working in Dubai, so ambient at Dubai is 107, and this unconditioned space maximum will be 5 degree less than ambient space. So 107 minus 5 degree, you will get 102, and the unconditioned space minimum is 53.6 here in Dubai, so 53.6. So now move back to our partition. So we have wall partition over here. Let me see. Yes, we have wall partition over here. As you can see, master bedroom is our conditioned space. This master bath is non-conditioned space. So whenever you have a conditioned space and non-conditioned space adjacent together, that wall will be your partition wall. So this is your partition wall, and what's the length of that partition wall is, that is 12 feet. 6 feet wide and 12 feet is the length. So 12 feet is the length of that wall, multiply ceiling height is 12.5. So 12 multiplied 12.5 ceiling height, we got 150 square feet is the gross wall area. So go over here, select wall partition, 150 square feet. U value for the partition, we already know that it's 0.5 value, 0.5 U. Okay, we select over here, and same ambient at space maximum is 107 in Dubai, and this will be 5 degree less than the ambient, that is 102.0, and this is 53.6. and 53.6. So everything is done, so just select OK, then move to system and go to over here, new default system. So give this system your name. This is master bedroom AC1. Okay, equipment type, or if we're going to use split air handling unit over here, okay, split air handling unit. And system air type, it's a single zone, so we have constant air volume single zone. Then move to ventilation. Everything's just as selected, constant airflow, and ventilation sizing method is sum of space outdoor airflows, and unoccupied damper position is closed. Okay, then move to central cooling. Supply temperature want 55 degrees, and bypass factor normally we're getting from supplier, and it's normally 0.12, so we just select 0.12. And if we move back to heating, we don't need heating in this one, so we just uncheck it, and we move to duct system. Okay, then move to zone components. Zone components, you just need to select this space and then add into your zone like this. Then move back to your thermostats. It's okay, everything, yeah, throttling right. Move to supply terminals. Okay, and go to your sizing data. One thing more, over here in system, zone components, thermostats, you have to give a schedule name over here for thermostat, like any name, whatever you want, you can give it thermostat. Okay, then go to sizing data. Sizing data, you will find cooling. We have to give some safety factor over here. For sensible we will give 15%, and for latent we will give 5%. The reason why I'm giving 15% for sensible is 10% due to the motor heat of that equipment, and 5% due to the safety for sensible, and 5% here for the latent is the safety factor we need to add over here. So just select OK over here. Now if I will go over here, master bedroom, right click and print view design result, it will give me the load calculations. So just click it, and whatever you want in your report you can add it. So what I need over here is psychrometric system properties. Okay, system load calculation. Okay, let me select this one for you, and space load is also you want to select over here, or if you want hourly air system load you can get it over here from January to December. Same, you can get the graph over here, then select preview in order to get the result. So it will generate the report for you. Just wait a bit, it will generate the report. So as you can see, app has generated the report. As you can see, location is Dubai, United Arab Emirates, and floor area 360 square feet. The master bedroom, calculation from January to December. You can see total coil load is 0.9 tons, and sensible heat load is 10 mph, and coil CFM is 427. So we got everything over here. We got the CFM, we got tonnage, we got mph. So, and you can see that load occurs at July 15, so July 3 p.m. we got a maximum load. And over here you see relative humidity is 47%, and bypass factor we already gave. Coil ADP is 53.8 degree Fahrenheit. This is operator's dew point, and outdoor ventilation required for that room is 32 CFM. So this is how you can generate report in the app. Here you can see it is a design cooling, and all of the load is calculated over here for the windows, roof, wall, partition, ceiling separately, and then calculated over here total. So this is how you can calculate the heat load in the app software. In my next video I will tell you guys the same heat load calculation but by using E20 form. E20 form, and then we will compare the result of E20 form and the HAP. I hope you guys learned something from this video. Please like, comment, share, and don't forget to subscribe my channel. In this video I will tell you guys how to use Psychrometric chart to get the relative humidity, dry bulb, wet bulb, temperature values. Because when we are calculating the heat load, this is very important parameters that need to be input. So here you can see that I have a train psychrometric chart software open over here. So before starting I want to show you the basics about this chart. So let me zoom in. As you can see that this is the x-axis, where there we have a dry bulb temperature in degrees Fahrenheit, and then y-axis we have a humidity ratio in grains per lb, and these curved lines is 10%, 20%, 30%, 40%. These are the relative humidity lines, and last one is the wet bulb temperature line. As you can see that this line, this is a wet bulb temperature lines. So if you remember that in my tutorial number 16 and 17 where I was calculating the heat load, so there I have the E20 sheet, same E20 sheet. So as you can see over here, we need to input the design conditions, outside design and indoor design. Let's say this is the building located in Dubai, and outdoor design condition of Dubai dry bulb temperature is 107 degrees Fahrenheit and wet bulb is 75 degrees Fahrenheit. These values you can get from local authorities in your location. This is provided by Dubai municipality, so you can get in your location from the local authorities. So as we know that outdoor design temperature for Dubai is dry bulb 107 degrees Fahrenheit and wet bulb is 75 degrees Fahrenheit. So we need to get the relative humidity and humidity ratio from psychrometric chart. So let's move back to our psychrometric chart. Let me zoom out this one. Okay, if we go to chart and go to set points and then add points. As we know that outside design dry bulb temperature for Dubai is 107 degrees Fahrenheit and wet bulb is 75 degrees Fahrenheit. As you can see that the other parameters are also calculated over here. So we our concern is about humidity ratio and relative humidity. So if we have a dry bulb 107, wet bulb is 75, then our relative humidity is 22.4%, and humidity ratio, this W is representing the humidity ratio. So humidity ratio is 79.5 grains per lb. So as you can see in our Excel sheet E20 form, we have input our relative humidity as per psychrometric chart is 22.4% and humidity ratio is 79.5 grains per lb. So now for indoor design conditions, for the most comfort system, we know that for human comfort system, indoor design temperature is from 75 to 78.5 degrees Fahrenheit. So we have selected 75 degrees Fahrenheit indoor design temperature. And for most comfortable system, indoor design relative humidity is about 50 to 60%. That's why we have selected 50% relative humidity. So we know that indoor design dry bulb temperature is 75 and relative humidity is 50%. So now we get the wet bulb temperature and humidity ratio from psychrometric chart. So let's move back to our psychrometric chart. So we know that indoor design dry bulb temperature is 75 degrees Fahrenheit and we know the relative humidity, indoor design relative humidity is 50%. So as you can see that we have these two parameters. So the wet bulb is 62.5 degrees Fahrenheit and humidity ratio calculated over here is 64.9 grains per lb. So as you can see that we have used the same values over here, humidity ratio and wet bulb temperature. 62.5 is the wet bulb and 64.9 is the humidity ratio. So this is how you can get the parameters from the psychrometric chart while designing your HVAC system. So this software is fairly easy to use. You can get the accurate values. So I hope you guys learned something from this video. And so for more videos, keep watching my channel and don't forget to subscribe. Thank you. Bye bye. Hello guys, this is Syed Mohammad Waqas. I'm back with another video. In this video I will tell you guys how to calculate the overall heat transfer coefficient U value for the wall, for outer wall and for the inner wall or partition walls. So let's start. Let's say we have a building where outside wall composition is given as this. That building consists of combination of different layers, that is 230 mm common brick plus air space plus 230 mm common brick and 26 mm, that is 13 mm both sides sand cement plaster. So as you can see in this figure, if you will see, this K1 is basically representing as our brick 230 mm. This H0 is over here representing as the outside film coefficient. Then we have a KA, that is the air space over here or air gap over here, and then we have K2 representing the second brick over here, that is 230 mm. Then HI is the inside film coefficient. So this is the general formula which we basically use to calculate the overall heat transfer coefficient U value. So as you know the composition of the wall, so this is the thermal conductance values which are given over here. These values you can find most probably in ASHRAE Fundamental 1997 or any version. You can find the thermal conductance values. So you just need to pick these values and then calculate the overall heat transfer coefficient. So let's say we have this building composition, outer wall combination. Then thermal conductivity of the brick is given as K brick 0.77, thermal conductivity of plaster is given as 8.65, and thermal conductance of the air gap is given as 5.8. Outside film coefficient is given as 23, inside film coefficient is given as 8.5. And this X1 and X2 values, X1 is basically 13 mm over here. As you can see, 13 mm is the sand cement plaster on both sides of the brick. So in order to convert this into meter, you need to divide by 1000, you will get 0.013. So X2 is basically the thickness of this brick, that is 230 mm. In order to convert this into meter, you need to divide by 1000, so you will get 0.23. So these are the thickness of the plaster. X1 is the thickness of plaster, X2 is the thickness of the brick. So as you see, this is the formula which we are going to use. This is general formula, 1 divided by 1 by H0 plus X1 divided by K1 plus 1 divided by K plus X2 divided by K2, so on up till 1 divided by HI. You know that this H0 and HI are the outside and inside film coefficients. And this X1 and X2 already explained you, these are the thickness of the plaster and brick. So if you have any insulation material or anything is added in your wall, you need to add these values to get the overall heat transfer coefficient. So this is the formula, 1 divided by H0. So if we are going to put the values over here, so 1 divided by 1 by H0, H0 is given as outside film coefficient is 23, so we have used 1 divided by H0 is 23 plus this the second. If you see this is the wall composition over here, then we have sand cement plaster over here, then we have brick. So sand cement plaster over here this side, and sand cement plaster, its thickness is 0.013, so 0.013 divided by its thermal conductance value. Plaster conductance value is 8.65, so 13 divided by 8.65, 13 convert this into meter, 0.013 divided by 8.65. Then the next one we have this after plaster we have the brick over here, and brick thickness is 230 mm, that is 0.23. So 0.23 divided by thermal conductance of the brick, that is 0.77. So 0.23 divided by 0.77, and then we have the air gap over here, that is Ka. So 1 divided by Ka in this formula. So 1 divided by Ka. Ka value is 5.5. You can see the thermal conductance of the air gap is 5.8. And then we have this, again we have a brick over here, then sand, cement, plaster, and then inside film coefficient here. So brick first, 230 mm. 230 mm divided by 1000 divided is equal to 0.23 meters the thickness, divided by thermal conductance of the brick is 0.77, plus then we, after brick we have this cement over here, and cement thickness is 0.013 meter, divided by thermal conductance of the plaster is 8.65, plus 1 divided by Hi. Hi is the inside film coefficient and its value is 8.5. So 1 divided by 8.5. So we have applied all the values over here. So after putting all the values, U overall heat transfer coefficient U of the wall is calculated as 1.07 watt per square meter Kelvin. As you can see, if I double click, I already applied the formula here. So this is how you can calculate the overall heat transfer coefficient U value of the wall, and this is for outside wall. So next is, I will show you, it is the same procedure, but still I will show you the inner wall, partition wall U value calculation. So as you can see that our interior or partition wall consists of 230 mm common brick with 26 mm, 13 mm sand, cement, plaster on both sides. So in this case there is no air gap, we have just outside film coefficient, then sand, cement, plaster, then brick, and then sand, cement, plaster, and then we have this inside film coefficient. So this, there will be no there's only one brick over here. You can consider this part only, like outside film coefficient, sand, cement, plaster, then the brick, and then sand, cement, plaster, and then we have this Hi inside film coefficient. This is not here. So same formula which we are going to use over here. So 1 divided by 1 by H0, outside film coefficient value 1 divided by H0, that is 8.5. you can see over here outside film coefficient. Outside film coefficient is over here, that is 23. Sorry, this is 23. One divided by 23. So plus we have cement thickness over here, that is x divided by k1. Cement thickness is 13 mm on this side, one side, and 13 mm on the other side. So 13 mm, convert this into meter, you will get is 0.013 meter, divided by thermal conductance of the plaster, that is 8.65. So inside film coefficient is outside film coefficient is done, then we have sand, cement, plaster is done, then we have a brick, and then sand, cement, plaster layer. So brick thickness is 230 mm, just one brick, so 230 divided by 1000, that is 0.23 meter, divided by thermal conductance of this brick is 0.77. you can see 0.77 thermal conductance of the brick, plus cement on the other side, that is 13 mm, divided by thermal conductance of cement is same 8.65, plus 1 divided by Hi inside film coefficient. Inside film coefficient is 8.5, so 8.5 over here. So this is how you have to put all the values, and you will get the inside wall U value or partition wall U value overall heat transfer coefficient. So as you can see that this is the formula I have already applied here. So after adding all the values in here, you will get the overall heat transfer coefficient U value of the inner or partition wall is 1.86 watt per square meter Kelvin. So this is how you can calculate the overall heat transfer coefficient U values. In the same way, you can calculate, if you know the material for the roof, floors, doors, you can calculate the U values for every single material, because these values, U values, overall heat transfer coefficient, these are the things we are going to use in our HVAC system design. While we are designing our system, this is very important parameter that needs to be calculated first to calculate the heat transfer, to calculate your heat loads. So in the last video I told you about psychrometric chart, and in this video I told you about the overall heat transfer coefficient U values. So these things we are going to use in next videos to calculate our heat load for some particular project. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Thank you. Bye. Hello guys, this is Syed Muhammad Waqas. I'm back with another video. In this video I will tell you guys about equipment selection as per your calculated heat load. So this is the sheet I'm going to use over here. If you have seen my previous tutorial number 16 and 17, in which I have already explained how to calculate the heat load using E20 form and HAP software, so I will continue by following the same procedure from there. So let's move. So first you have seen there I have 4 different rooms over here. I'm going to select the AC machine as per this calculated heat load. So there I have a catalog by Jock. So I'm going to select a machine from this sheet. So first we have a recreation room, and in the recreation room, as you can see that we have already calculated the heat load, and TMBH over here is 18.13 and T kilowatt is 5.26, TSMBH is 16.9 and TS kilowatt is 4.9. so and CFM is 826 and 388.5 liter per second is the airflow rate. So all of the values I have already put here. The first one is in TMBH and the second one 5.26 is in the T kilowatt. Same in this column, same in this column, that is CFM. First one is the CFM 827 and second one is 389 liters per second, that is the airflow rate. So I have already put all the values over here. So I'm gonna show you how to select the machine. So let's move to this catalog. First focus on this CFM airflow rate, that is CFM or liter per second. I'm going to select the machine as per 389 liters per second. So if I move to this chart 389, okay, if we go to this airflow column in liters per second, 389, it's exactly not there, so we will select the nearest one, that is 442 is the nearest one. Or we can do one more thing, we can select 2 FCUs. This is FCU2 198 liter per second and FCU3 198 liters per second. So 198, 2 FCUs, if we will select, it will be 396 liters per second. And how much is over there? 389. So it's okay, we can select this one with 396 liters per second. So we are going to select 2 FCUs for recreation room, that is 198 liter per second and 198 liters per second. So it will be 396 liters per second. In this column I will put only liters per second. Okay, so how much is the TS kilowatt or T kilowatt? We will also see over there. This column is for kilowatt. There is total duty kilowatt and other is sensible duty kilowatt. So it will be 3.88 because we are selecting 2, so it is 7.76 total duty kilowatt, 7.76. And TS kilowatt, how much? That is sensible duty. It is 2.68, 2 times, because we are selecting 2 FCUs over here. It is 5.36 sensible kilowatt, 5.36. So this is how you can select the machine. So 389 liter per second is our calculated, and obviously we have to go for the higher, we will not go for lower. That's why we have selected 396 liters per second. Okay, in the same way we are going to select the machine for showroom 1, showroom 2 and Majlis sitting area. So what we have over here is 1406 liters per second is the airflow rate. So let's move to the catalog again. 1406 liters per second. As you can see that maximum over here is 938 liters per second. Okay, we will select 938 liters per second. 1406 is the total. So we are left with 468 liters per second. 468. So 468 is not there, 442 is there, and higher number after 442 is 518. So we are going to select 2 machines for showroom 1, that is 938 liters per second and 518 liters per second. That is 938 plus 518. So total 1456 liters per second. Okay, so what is the TMBH and TS kilowatt? Same we can check over there. For 938 T kilowatt is 15 point, that is total duty kilowatt is 15.36, and 518 liters per second machine it's 9.85. So total 25.2 total duty kilowatt, 25.21. And then TS kilowatt, that is sensible duty kilowatt, how much? For 938 liter per second, that is FCU2 and that is FCU5. So FCU2 it's 11.48 and FCU5, that is 518 liter per second, is 6.91. So 18.40. 18.40. And so you can see that calculated heat load is that much, and the airflow rate for that machine is 1406, that is calculated, and from the catalog we have selected 1456, that is 1456 liters per second. As I told you, we will select machine on the higher side, we will not go for the lower side for safety. In the same way we will select showroom 2. As you see that 1624 liters per second, that is the calculated airflow rate. So let's move to the catalog again. 1624. As I told you, 938 liter per second is the maximum available there. So we will select 2 or 3 machines. So 938, 1624. So one machine if we select for 938 liters per second, so we are left with 686 liters per second. So 686 liters per second. 628 is there. Okay, if we will select two more machines of 371 liters per second, how much it will be? 686. It will be 742 minus 686. So okay, so we are on the higher side, so let's select this machine. 2 FCU number 1 quantity 2, that is 371 liters per second, plus one machine FCU 2, that is 938 liters per second, so 1680 liters per second. So three machines we have selected for this area. 1680 liters per second. And same way we'll go and check TMBH and TSMBH, or T kilowatt or TS kilowatt. So as we have seen that 938, that is FCU2, total duty is 15.36 plus, and we have selected FCU1 two quantities, that is 371 liters per second, and its total duty is 6.53. Two times we have selected two machines, so total 28.4 total duty kilowatt, 28.42. And then we have to check TS kilowatt. So FCU2 938 liter per second, sensible duty is 11.48, and FCU number 1 we have select two quantity, that is 371 liter per second, and sensible duty is 4.82. So total sensible duty is 21.1. So as you have seen that the calculated airflow rate is 1624 liter per second, and we have selected 1680 liters per second. So we have to use 3 FCUs over here to fulfill this requirement of 1624 liters per second. So this is how you can select your machines as per your calculated heat load. I hope you guys like this video. Keep watching my channel and don't forget to subscribe. Bye bye. Hello guys, it's Syed Mohammad Waqas. Let's continue from VRF System Design and Selection Part 3. Up till now I have discussed two parts with you guys. So today I'm gonna discuss VRF System Designing and Selection Part 3 using Excel sheet. So we'll cover this topic today. So before starting this topic, I want to apologize for uploading this video late. I was a bit busy, so I was not able to upload this video. So today we're gonna finish this topic, so let's start. So there I have prepared an Excel sheet in which I will show you guys how you can select your indoor units and outdoor unit based on your air conditioning load, whether it is cooling or heating load. So we'll see how we will select indoor and outdoor units. So there are different steps which we have to follow in order to finish the selection, and in the end we will check whether the machines which we have selected over here justify our heating and cooling load or not. So let's start. We'll start with one example. As you can see, this is the system I'm going to discuss with you guys. So let's suppose we have 11 zones over here in our system on the ground floor. As you can see, the spaces over here, office, meeting room, locker room, and different spaces over here, and the load which we have calculated over here is also given. You know that how to calculate the load using HAP software and using E20 sheet. So using this process you can calculate the heating and cooling load. So let's say this is the cooling load which we have calculated, and heating load for our spaces. So total cooling load is 51.4 kilowatt for all the spaces, and total heating load is 52 kilowatt for all the spaces. So we are going to select the indoor unit for each space. So before starting the selection of indoor unit, we need to know the indoor design conditions. So when cooling, indoor temperature is 27 degrees centigrade dry bulb, and wet bulb is 19 degree Celsius. And when heating, indoor temperature will be 20 degree dry bulb. And outdoor temperature conditions, let's suppose we are working on the location where outdoor temperature when cooling is required is 35 degree dry bulb, and in the same place when heating is required, the outdoor temperature of that location is 6 degree dry bulb when heating is required, and 3 degree wet bulb. And two more things which we have to use over here as input. Let's suppose the equivalent length of the piping is, refrigerant piping is 46 meter we have used over here, because we have to use this in our selection and calculation. And the height of the outdoor unit, so the height of the outdoor unit to indoor unit is we have used 20 meter over here. We will gonna use this height also in our selection and calculation. So these are just input parameters. We know the location, so according to the location we have selected the outdoor temperature, that is 35 degree dry bulb, and for when cooling is required, when heating is required, this is the temperature. So first step, you have to select the standard capacity based on your air conditioning loads. So this standard capacity which we are going to select over here, I want to tell you one thing. This is a preliminary selection, not a final selection of the indoor units. Final selection we will do over here. This is the corrected capacity of all indoor units, cooling or heating. This is our final selection. So this is just a preliminary selection of indoor units. So we are going to select the machine for this office space, having a cooling load of 6 kilowatt and heating load of 6.2 kilowatt. So let's move to indoor unit models over here. We have a 6 kilowatt for cooling and 6.2 kilowatt for heating over here. So this is all the indoor unit models over here. Let's say I'm going to use 4-way air discharge cassette type. So our loads are 6.0 for cooling and 6.2 for heating. So 6.0 for cooling and 6.2 for heating. So if we are going to select this one, this will satisfy the heating capacity, but this machine will not gonna satisfy the cooling capacity, so we cannot select this machine. So we are going for this machine with the cooling capacity 7.1 and heating capacity 8. So this is the model of this unit, MMU AP0242H. This capacity which we are going to select for the machine should be higher than our air conditioning loads for both heating and cooling. So as you can see that 7.1 is greater than 6 and 8 is greater than 6.2. So we are going to select this A24 type MMU AP0242H. So this machine we have used over here. As you know that the cooling which we have selected over here is 7.1 and heating is 8 kilowatt. So 7.1 and 8 kilowatt which we have selected over here. So in the same way you have to select for all the rooms over here. Let me give you another example. Say for restroom, our cooling load is 4.6 and heating load is 4.8. 4.6 and 4.8. As you can see over here again, heating load capacity it's okay, but cooling is not okay. So we cannot select this machine. We have to go for higher load. Our standard capacity of the machine should be higher than our calculated heating and cooling load. So we are going to select this machine because 5.6 is higher than 4.6 and 4.8 for heating. So we are going to select this machine MMU AP0182H. that is 18 type. 18 type means 18,000 BTUs. This is the capacity rank. I already explained you about the capacity code and capacity rank in my second video, part 2. Capacity code is basically the horsepower of this machine, and capacity rank is BTUs, 18,000 BTUs. So we are going to select MMU AP0182H. So this is the machine which we have selected, and the load of this machine is 5.6 for cooling, 6.3 for heating. So in the same way you have to calculate for all rooms cooling and heating loads, and then you have to sum over here for all the loads for cooling and for heating also. So now we will calculate the corrected capacity A for each space. So how you will gonna calculate this corrected capacity A? There is a formula which we have to use. Corrected capacity A is equal to standard capacity of this space for cooling, because we are here working on cooling over here. So this standard capacity for cooling into temperature correction for the cooling, that is 1. So now I'm gonna show you or tell you how did I get this temperature correction factor for cooling and heating 1. So we are going to use this factor over here to calculate the corrected capacity A. So I'm gonna move to this PDF file, and there we have some tables and charts which we have to use to calculate the temperature correction factors. So this is for the cooling capacity calculation. In the same way we have a charts and tables for heating capacity calculation. So first I'm going to show you for cooling capacity calculation, this correction chart which we are going to use. In the beginning we have assumed that the indoor condition which we have used is 27 degree dry bulb and 19 degree wet bulb. So we are going to use this when cooling is required. So we are going to use this indoor temperature condition when cooling is required, 19 degree wet bulb. So as you can see over there, x-axis we have indoor wet bulb temperature for cooling, and y-axis we have a capacity correction value. So as you see that for cooling, our wet bulb temperature for indoor design condition is 19 degree wet bulb. So 19 degree wet bulb, this is 15, 16, 17, 18, 19. This will be 19. So all the way up over here, when it touch over here, go to the left side. So what is the correction factor over here for this capacity is 1. So that's how I got this 1. If you have a different temperature, like if you have a 16 or 17, let's say 17, so go over here, 15, 16, 17. 17 touch over here, then it will be around 0.94, something like this. So in our case we have 19 degree wet bulb for indoor design conditions. So all the way up 19, and then move to the left side, we have 1 degree. Our correction temperature is 1. So that's how I got this 1 over here for cooling. So I'm gonna show you for heating also how did I get 1. So move to our heating chart, heating capacity. Yeah, over here, as you can see over here, this is our correction chart for the heating capacity calculation. So over here you can see that when heating is required, our indoor design temperature condition is 20 degree dry bulbs. So we have to use this one in the chart, 20 degree dry bulb when heating is required. As you can see that x-axis we have indoor dry bulb temperature, and y-axis we have capacity correction. So we have a 20 degree dry bulb, indoor dry bulb. So all the way up here and move to the left side, 1. So again you can see over here we have temperature correction factor for heating capacity calculation is 1. So that's how I got 1 over here for heating conditions. So this is how we got this temperature correction. So using this temperature correction in our Excel sheet, as I told you about the formula, For calculating the corrected capacity A, you just need to multiply the standard capacity with this temperature correction. So in the same way you can calculate the corrected capacity A for heating conditions. Same formula which we have used over here, but for heating of this standard capacity. So heating of this standard capacity of this particular space, multiply this heating factor which we have calculated over here, that is 1. So this is how you can calculate the corrected capacity A for indoor units. So in the end you have to sum up for cooling over here and you have to sum up for heating over here. And why we have sum up of here? Because on this basis we have to select our outdoor unit. So now we are going to select our outdoor unit, and there's a note again, this is a preliminary selection of outdoor unit which we are going to do over here. Final selection we will do later. So this is just a preliminary, just like the indoor unit. So as you know that the load which we have calculated for corrected capacity A, the sum which we have calculated here is 61.3 kilowatt, and for heating it is 68.9 kilowatt. So preliminary selection of outdoor unit, it is basically the standard capacity no less than the total value of the corrected capacity A for heating and for cooling. At the same time we have to check both connectable indoor unit numbers and outdoor unit diversity. So we are going to select this outdoor unit based on over this corrected capacity sum for cooling and heating. So let's say we have calculated over 61.3 kilowatt for cooling and 68.9 kilowatt for heating. So move to our outdoor unit models over here. How much we have calculated here? 61.3 and 68.9. As you can see over here, 22 horsepower unit, which is a combined unit of two models, that is 2214HT8 and 2214T8, that is 10 horsepower and 12 horsepower, two outdoor units. So it's a combination of two outdoor units. So as you can see, the cooling capacity for this model is 61.5 and heating is 69 kilowatt. So our calculated corrected capacity is 61.3 for cooling, and here is 61.5. so 61.5 is greater than 61.3, so we are safe. And for heating, as you can see, for the same unit, heating is 69 kilowatt, and one which we have calculated here is 68.9 kilowatt. So both are greater, both heating and cooling for this unit is greater, the one which we have selected. So model is this one, MMY AP 2214HT8. So this model which we have selected over here, the standard model of 22 horsepower. As you can see, this is 22 horsepower model with cooling 61.5 and heating 69. So this is how we did the preliminary selection of outdoor unit with cooling 61.5 kilowatt and heating 69 kilowatt. So this is how we did the selection. Now we move to another step, that is corrected capacity B for cooling and heating. Same way we will calculate for cooling and heating. So as you remember, for corrected capacity A we have used this indoor correction temperature for cooling and heating for corrected capacity A, but in corrected capacity B we are going to use this piping correction factors for both cooling and heating. As you can see the formula over here, corrected capacity B is equal to corrected capacity A for cooling multiplied by this piping correction factor for cooling. In the same way, corrected capacity B for heating will be corrected capacity A for heating for that particular space multiplied by this heating piping correction factor. So now I'm gonna tell you how did I get this 0.92 piping correction factor for cooling and 0.97 piping correction factor for heating. So if you know these piping correction factors, it's easy, just need to multiply and you will get this corrected capacity B for each indoor unit. So let's go back to our charts over here. This is for cooling. As you see over here, for cooling the piping correction factor is 0.92. And this is all the charts for cooling capacity calculation. So as you know that the outdoor unit model which we have selected here is 22 horsepower outdoor unit model. So 22 horsepower model will be here, and the standard model we have selected for this one. So according to this outdoor unit model, which graph we have to use for the piping correction, that is A2. So these are the graphs. This is A1 for outdoor unit model, this is A2 for outdoor unit model, and this is for cooling capacity correction. So we are going to use this A2 graph. So according to this A2 graph, which we have on the x-axis, we have a piping length, equivalent length in meter on the x-axis. Y-axis we have the height of the outdoor unit. As you know that we already know the equivalent pipe length of our project is 46 meter, and height of the outdoor unit, that is from our indoor unit to the outdoor unit, height is 20 meters. So length 46 and height 20. And chart, we already know that we have to use A2 chart across this 22 horsepower outdoor unit standard model. So 46 is our equivalent length. Over here, must be somewhere here, go over here, and 20 is the height. 20 is the height, so it will be somewhere in between 90 and 92. So this is how we have used this correction factor 92 for cooling, 0.92, that is 92%. Over here on the x-axis, that is 46 meter, go up, and 20 is the height, so it will cross somewhere here, so it will be like 92%, so it's 0.92. So this is how we have calculated this piping correction factor for cooling, that is 0.92. Now we are going to calculate this piping correction factor for heating. So go to our heating capacity calculation charts, and this is the graph which we have to use. As you see that for heating there is only one graph. Yeah, there is only one graph which we have to use for all the outdoor units from 8 to 48 horsepower. This is only one graph. So same condition, equivalent length is 46 meter, height of the outdoor unit to the indoor unit is 20 meter, between indoor unit and outdoor unit height is 20 meter, so 46 and 20. So as you can, and this is the equivalent length, as you can see over here, to the furthest indoor unit, outdoor unit to the furthest indoor unit, it's like this, and the height you can see over here. So this is the graph we are going to use. 46 must be somewhere here, go up all the way here till 20, so it's gonna touch somewhere here 97%, so it will be 0.97. So this is how we have used 0.97 piping correction factor for heating. So this is how you have to calculate these correction factors depending on your piping equivalent length and the height between outdoor and indoor unit. So you just need to multiply this cooling capacity corrected A with this correction factor for cooling to get this corrected capacity B for this particular space. Same way you have to calculate the corrected capacity B, you need to multiply this corrected capacity A with this heating piping correction factor 0.97. So in the end you have to sum up corrected capacity B over here, and for cooling and for heating also you have to sum up over here, and make sure that the corrected capacity B which you have calculated over here for cooling and heating, that should be greater than your air conditioning load for each space. It should be greater than your air conditioning load for each space. So if it is not like this, any one of this is less than your air conditioning load for heating and cooling, what you have to do, you need to increase the indoor unit capacity. So standard capacity you have to increase again, and then you have to calculate again. So make sure that these values should be higher than this air conditioning load. And one more thing which I should have told you when I was doing the preliminary selection of outdoor unit. When you are doing the preliminary selection of outdoor unit, at the same time you have to check few more factors. So one of the factor is, as you can see, this is the example which we are working. So you can see that 11 units over here, indoor units, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, and the unit, outdoor unit which we have selected is of 22 horsepower system, and this is based on two outdoor units, one with 12 horsepower and second is 10 horsepower, as we already see over here. 22 horsepower is subdivided as two units, that is 12 horsepower and 10 horsepower. And the number of, so thing which I should have told you before is the number of connectable indoor units. This should be checked at the same time when you are doing the preliminary selection of outdoor unit. As you can see, for this model, maximum number of connectable indoor units are 37, and in our system we have total 11. You see over here we have total number of indoor units are 11, and the capacity code over here, this is 12.5 for these 5 units, and this 6 unit is 9.5, so total is 21.95. so total capacity is 21.95 and number of indoor units are 11. So as you see that the number of indoor units in our system over here should be less than this model which we have selected over here. So this is 37 and in our system is 11, so we are good. So if it is more, then you cannot select this system, you have to go for another unit. Also one more thing, I have to tell you about the outdoor unit diversity. So as you or I will discuss it later when we do the selection of outdoor and indoor unit. As you know that we did the preliminary selection over here. Now over here we will do the actual selection of our outdoor units and indoor units. So same time I'm gonna discuss this outdoor unit diversity factor, and one of the friend, he asked me what is diversity, outdoor unit diversity, so I'm gonna explain it over here. So now we are going to calculate the corrected capacity of the outdoor units and indoor units, or the actual capacity, corrected capacity of outdoor units. So the formula which we are going to use over here is, as you can see, that there is a corrected capacity of the outdoor unit for heating and for cooling and heating. So as you can see that this is the final corrected capacity of the outdoor unit for cooling and for heating. Formula which we are going to use for cooling is, we need to, as you know that the preliminary selection of the outdoor unit, cooling which we have calculated is 61.5, and the heating of the outdoor unit preliminary selection is 69. So this is the same value which we have used, as this is the standard capacity of the outdoor unit or with the preliminary selection. So these four factors which we have to use to calculate the corrected capacity of the outdoor unit: indoor temperature correction factor, outdoor temperature correction factor, connecting piping largest length and the largest length and the longest height. which we have to use over here. This is and outdoor unit diversity. So we need to multiply these four factors with the standard capacity to get the corrected capacity of the outdoor unit for cooling. In the same way, we need to multiply these four factors with corrected capacity, preliminary selection corrected capacity for heating of the outdoor unit, standard capacity, with these four factors to get the final corrected capacity of our outdoor unit for heating. So standard capacity, you know that for outdoor unit 61.5 and 69 preliminary selection, and temperature correction factors. As you know that I already told you about the temperature correction factors, and these are indoor temperature correction factors. We have used over here 1 and 1. We already calculated it before. So that's how I write cooling 1, heating 1. And outdoor temperature I will tell you later. First let me tell you about this connecting piping length and the lift factors. So this is also, we know that equivalent piping length, largest piping length is 46 meter in our system, 46 meter largest length, and the height from outdoor unit to indoor unit is 20 meter. So this is length, and the lift, length is 46 and the lift is 20. We already write over here. So the correction factors for piping correction for cooling, we already calculated when we use this one in our corrected capacity. We know that for cooling it's 0.92, for heating it's 0.97. So we already write over here 0.92 for cooling, 0.97 for heating. So now I'm going to tell you about the outdoor temperature correction factors for cooling and heating. How did we get 1 and how did we get 0.95? So let's focus on cooling first. Outdoor temperature correction for cooling. As you know that outdoor temperature correction of the location on which we are working on is 35 degree dry bulb. So move back to our chart. You know that this is the capacity correction charts, and our outdoor temperature is 35 degree dry bulb when cooling is required. So this is the chart we are going to use. Outdoor air dry bulb temperature versus capacity correction for cooling. So x-axis we have dry bulb, outdoor dry bulb, and y-axis we have capacity correction values. So our outdoor dry bulb is 35, you can see over here. So 35, go up, move to the left side, when it touches this line, move to the left side, 1. So our capacity correction factor is 1 for cooling due to the outdoor air dry bulb temperature. So you see, this is how we got outdoor air dry bulb temperature correction factor is 1 for cooling. Now for heating, how did we get 0.95? This one also I will tell you. Go for heating, yeah, this one, correction chart for heating capacity calculation. As you know that for the location in which we are working, when heating is required, 6 degree dry bulb and 3 degree wet bulb. So 3 degree wet bulb temperature is for 35 degree outdoor dry bulb temperature cooling. So now for heating we have wet bulb temperature, outdoor wet bulb temperature for heating will be 3 degree wet bulb temperature, wet bulb. So this is our outdoor air wet bulb temperature on x-axis. Y-axis we have capacity correction. So this is a outdoor air wet bulb versus capacity correction. So our outdoor air wet bulb is 3 degree wet bulb. So this is we have to use. This is -5, this is 0, this is 5. So 3 will be somewhere here. Go up over here, touch over here, and move to the left side, somewhere between 0.9 and 1. So it will be around 0.95. So capacity correction for heating due to the outdoor air wet bulb temperature is 0.95. So this is how we got this 0.95 over here. This is the correction for heating. So the only thing left over here now is outdoor unit diversity. So what is outdoor unit diversity? Outdoor unit diversity is basically it is the ratio of connected indoor unit to the outdoor unit horsepower. As you can see in our example, we have connected indoor units. This is the sum of these 5 indoor units, that is 12.5, and this is the sum of these 6 indoor units. So how much it is? That is 12.45 plus 9.45. So indoor unit horsepower is around 21.9. That's we already write over here. That is 21.95 for indoor unit, and the outdoor unit which we have selected over here is 22 horsepower. So it is basically the ratio of horsepower, indoor unit to the outdoor unit horsepower. So this 21.9 divided by 22, that is 99.5, is approximately 100%. So move back to our chart. This is the outdoor unit diversity. As you can see that this is x-axis, we have a standard capacity ratio, indoor units total capacity ratio, and this is the correction factors. In our case it is 100%, and this chart is for cooling. So 100% go up to the left side, you have 1, so correction is 1. And for if you go for heating, you can see this is for heating, it will be same. So standard capacity on x-axis ratio for indoor to outdoor unit is 100%, which we already see in our example. So 100% go up, again it's 1. So this is how we have used this outdoor unit diversity, 1 for cooling and 1 for heating. So outdoor unit diversity is basically the ratio of connected indoor unit to the outdoor unit percentage. So in our case it is 21.95 divided by 22, that is almost 100%. That's why we have used one correction factors. So as we know all of these factors for cooling and for heating, we just need to multiply these correction factors with preliminary selection of the standard capacity of the outdoor unit for cooling and for heating. So this is how we get this corrected capacity of the outdoor unit, that is 56 kilowatt. This is the corrected capacity of outdoor unit for cooling, and for heating we got 63.58 kilowatt. So now we have to calculate the corrected capacity C for all indoor unit. Before that it was a preliminary selection, now this is the final selection or corrected capacity C. Outdoor unit we already calculate corrected capacity, so now we are going to do for indoor units based on our outdoor unit corrected capacity. So how we are going to calculate this corrected capacity C? Corrected capacity C, as you can see from this formula, corrected capacity C for this space is corrected capacity of the outdoor unit, that is 56.58 into F7, and this is F7 divided into standard capacity of this indoor unit divided by total standard capacity of all the indoor units. So this is how you can calculate the corrected capacity C of indoor unit for cooling, and for heating in the same way you can calculate. You can see the corrected capacity of this outdoor unit which we have calculated is 63.58 kilowatt. So corrected capacity C for this space for heating is this F37. This is F37, that is 63.58. So this corrected capacity C for heating, this sum into this is standard capacity for this space divided by total capacity of all the spaces. So this is how you can calculate the corrected capacity C. All the formulas are applied here. So this is how you can calculate the corrected capacity C of all indoor units. So in the end, what you have to do, this is your air conditioning load, same as above, and these are all the models which we have used for indoor units, and this is the same corrected capacity C for cooling and for heating. So these are the same values which we have to write over here, and this is the sum of corrected capacity C and for cooling and for heating, and this is same as this one which we have calculated for corrected capacity of the outdoor unit. So this is our final selection or corrected capacity for the outdoor unit. So we have to select this model with corrected capacity of the outdoor unit for cooling is 56.6. So we are going to select the machine with the cooling capacity required is 56.6 and heating capacity required is 63.6 for heating for the outdoor unit model, and this is the individual indoor unit models for all the spaces. And make sure that the corrected capacity C which we have calculated here for cooling and for heating, this should be greater than your calculated air conditioning load. If this condition is satisfied, then I applied the formula here. If this condition is satisfied, then it will be okay for each unit for heating and cooling. If this condition is not satisfied and your either heating or cooling load for corrected capacity C of each indoor unit is less than your air conditioning load, then it will not be okay. Let's say I'm gonna decrease to show you one example. Let's say this is 2.8. As you see over here, the air conditioning load is 3, but corrected capacity is 2.8. That's why it's not okay. If it is like this, you need to increase the outdoor unit capacity, and then you have to calculate again the corrected capacity of this indoor unit to satisfy this condition. So make sure that your heating and cooling loads which you have calculated air capacity C should be greater than your air conditioning load for each room. So this is how you can select your outdoor and indoor unit model based on your air conditioning load for heating and cooling. So it depends on your outdoor temperature condition on your location in which you are working. So according to that you have to write these temperature conditions, and you have to calculate these correction factors for heating, cooling. So I hope you guys learned something from this video, and in my next video I'm gonna explain this VRF system designing and selection using software, and in the last video we're going to use the calculation for refrigerant charge calculation, additional refrigerant calculation. So thanks for watching, and for more videos keep watching my channel and don't forget to... Hello guys, this is Syed Mohammad Waqas. We'll continue our VRF system design basics topic, and today I'm gonna discuss part 4, that is related to VRF system designing and selection using VRF selection tool software. So there I have the main screen of the VRF system selection tool software, and here in the Excel sheet, as you can see that we are going to use these loads to design our VRF system. This is the cooling load and this is the heating load for all the spaces mentioned over here. So total cooling load is 51.4 kilowatt and total heating load is 52 kilowatt, and these are the outdoor design conditions which we are going to use when we design our system. So let's move back to our VRF selection tool software. But before starting this VRF selection tool software, let me show you one thing over here. This is the flow chart of the selection tool software which you have to understand over here. Basically we start to create the project first and then we select the method. Basically two types of methods are available here in this VRF selection tool software. One is a wizard type selection, that is detailed design method, and the other one is drag and drop drawing method. So in wizard type selection we select and set indoor. After adding this outdoor temperature information, we will select or set indoor units in the wizard type selection. So after selecting our indoor units, we will move to the next tab that is related to selection of outdoor units. So when you finish the selection of outdoor unit, you will link them, indoor and outdoor unit, you have to link them, and then you have to create, the piping will be created automatically depending on your indoor and outdoor unit capacity. But in drag and drop drawing method, you will create the refrigerant piping first, and then you will select or set your indoor units, and then you will move to the next tab and select your outdoor units. So in the end you will select the central control device, and then you will create the output project of your data. So only difference between these two methods is here you will select first indoor unit, outdoor unit, then link them, and then piping diagram will be automatically created. But in drag and drop drawing, first piping diagram, refrigerant piping diagram you have to create, then set your indoor and outdoor units. So today I'm going to discuss this drag and drop drawing method to create our system. Later we will discuss about this wizard type selection. So let's move back to our selection tool software over here. So as you can see that this is the main screen of our VRF selection tool software, and the different options available over here. First you have to create the project. So in order to create the project, you can either click here, that is create project, or you can go to edit, this option here, that is create project. So we'll create project first, and this screen will appear, and then you have to give the information over here. So let's say I'm going the project number as 111, and project name, whatever the project name you have to specify here, and customer name maybe like CC, and make sure that all the entries with the star, it's necessary to fill up. Other entries, it's up to you whether you want to fill or not, it's up to you, but when you start your project you have to fill all of them. So and then you can also give the address, you can specify the installer, whoever the installer, you can specify the name or company name, you can specify the installation date, let's say it's 31st or 28 February, and commissioning date, let's say it's 28 March, whatever the date you can select over here. So after selecting everything, you just have to save here. And if you want to edit your project data again, so you just select your project over here and then go over here, this is the edit project, or you can go over here edit and then edit project. So you can edit the entries once again once this window is open. So once this step is finished, creating your project or editing is finished, you can either double click this one, just select the project and double click to move to the next step, or you can select from here also, this is the next step, or go edit and go to the next step. So I'm going to the next step by double clicking. Once you double click this one, it will ask you about the method, which method you want to use. You know that the method which I told you, one is a wizard type selection, other is a drag and drop drawing method. First one is a wizard type selection, second is drag and drop. Today I'm going to discuss drag and drop drawing. So I'm going to select this one, and then I will select this next button, or you can go to edit and next button. So I'm going to select this next step. Once you select the next step, then this new window will appear. Here you have to give the outdoor information, outdoor temperature information over here. Remember that I talked to you about the location in which I'm working right now. The outdoor design temperature conditions are this one for cooling and for heating. So move back to our software and I will click outdoor temperature information. So in our location, outdoor cooling dry bulb temperature is 107. So I'm gonna select 107 cooling dry bulb temperature, and heating wet bulb temperature is 37.7. So 37.7. So once you select these temperatures, cooling dry bulb and heating wet bulb, you can save it and then exit here. So after selecting your outdoor temperatures, you have to go to here, that's new. New means you will create a new refrigerant piping diagram over here, or you can go here also in the edit tab and you can select new. So I'm going to select new to create a new refrigerant piping diagram. So I will select here new. Once you select new, this window will appear. As you can see on the left side, all different types of indoor units are available in this software which we are going to use, and branches are also available. Whether we want to use a Y-shaped branching joint, we want to use 4 branching header, we want to use 8 branching header. So there are different types of indoor units are available here, and outdoor model, as you can select from here also, or when you will double click this outdoor unit, then you can select your outdoor unit. As you can see, this is our outdoor unit in the refrigerant piping diagram, and this is our indoor units, but these are dummy units. We will have to select the indoor units from here and then drag into the dummy units. But before starting this refrigerant piping diagram, let's move back to our Excel sheet. So as you can see that based on our Excel sheet load calculation, heating and cooling, we'll select our indoor units. So first I'm gonna draw the piping diagram first. As you can see that we have a total 11 indoor units here in our system. So I have to use 11 indoor units over here. So let me create this piping diagram first. So I'm gonna use this Y-shaped branching joint and 4 branching header combination in my refrigerant piping diagram. So I have to use 11 indoor units first. So let me create this Y branching here also. When you click this dummy unit and right click on this one, there's option insert. You can insert Y-shaped branching joint, 4 branching header, or 8 branching header. So I'm gonna use Y branching header here, 1. So now I have 3 indoor unit, depending on what type of configuration you are going to use. So according to your you can select a Y-shaped branching header, or you can select 4 branching header or 8 branching header. So I'm gonna use one more Y branching joint here and one more here, and then again I'm gonna use Y branching joint here, and one more Y branching here, one more Y branching here, and then I will use 4 branching header here. So how many indoor units I have now? 1 2 3 4 5 6 7 8 9 10 11. So now I have created my refrigerant piping diagram, and I have 11 indoor units available here in my refrigerant piping diagram system, VRF system. So now I'm going to use the indoor units based on my load calculation, cooling and heating load. So first move back to our software. Let's suppose I'm gonna use this for this office, which has 6 kilowatt cooling load and 6.2 kilowatt heating load. Office 1. I'm gonna use this 4-way air discharge cassette type unit. You just need to select and drag over here and then leave it. So your indoor machine will automatically come over here. As you can see that there are different models available here. You can select from them also, like slim duct type, concealed duct, high static pressure type, or 1-way air discharge, high wall 2 series, 4 series. So whatever you want, you can select the indoor unit from here. So I'm gonna use this 4-way air discharge cassette type unit, and the indoor unit name which I'm going to use here is VRF 1, and space name, as you can see, the office 1. So I'm gonna name it office 1. And floor, we have a ground floor there, so it's GF. And there you have one option, that is indoor unit selection method. If you will select this auto, then it will gonna select your capacity rank of the machine, which is basically the horsepower of the machine based on our calculated load. If you will uncheck this one, you can select the machine from all the models available over here. So I'm gonna use this auto method over here, and the indoor design condition which I'm gonna use over here, indoor cooling dry bulb, I'm gonna use is 75. That's okay, that is 23.8 degrees Celsius. And indoor wet bulb temperature, that is automatically calculated when I will give the humidity value. The humidity value which I'm going to use here is 50% for design. For indoor design comfort, it is recommended to have 50% relative humidity. As you see that if I change this to 40, our cooling wet bulb temperature will be changed. So I'm gonna use this 50 as per design recommendation. So I'm gonna use 50. So wet bulb over here is 62.6 degrees Fahrenheit, and the indoor heating dry bulb temperature I'm gonna use over here is 70 degrees Fahrenheit. And now I have to mention my cooling and heating load. So cooling load I'm gonna mention over here now, that is 6 kilowatt. So I'm gonna use 6 kilowatt here. And sensible, let's say our sensible is 4.6. And what is our heating load over here? That is 6.2 kilowatt for office 1. So I'm going to use 6.2 kilowatt here. So as you can see that based on our these loads 6 and 6.2, this machine is automatically selected based on our heating and cooling loads. So now I have to give the piping length from the joint equivalent. So from this joint to the machine I have to mention the pipe length. So let's suppose we have this length is, we have to mention equivalent and actual length. Let's say our equivalent length is 2.8 meters and actual length is 2.5 meters. And we have to mention the height difference between indoor and outdoor units also. Let's say our outdoor unit is installed at the roof, and the height difference between our roof and the ground floor ceiling is 4.5 meter. Whatever the height is, you have to mention here. Let's say it's 4.5. So I will mention 4.5 meter here. So this fan speed I'm gonna select is high. Okay, I don't want to use any heater here. Or okay, so all input are done. So once you select the machine and all inputs are done, so you just need to save it. If any input is missing, it will give you some error, so you need to specify that input. So I'm gonna close this one, and now I'm gonna select the second machine over here. So this time I'm gonna use, what is the space here, meeting room. So meeting room, now I'm gonna use this duct, concealed duct standard type unit. I'm going to use over here, indoor unit. So just drag and drop here. Once it's done, in the same way you have to fill this or give all the inputs. This is our meeting room, and room name is this is VRF 2, and room name is meeting room, and floor is ground floor. I'm gonna select auto again. These conditions are same, only this I'm going to change. So this one, you remember that I have used the same condition for the first indoor unit, same I'm going to use for the second indoor unit. And the loads for the meeting room are 4.6 kilowatt for cooling and 5 for heating. 4.6 and 5. So 4.6 for cooling and 5 for heating. Let's say its sensible load is 3.9 and heating is 5. So now I have to specify the piping length from the joint equivalent. So from this joint to the machine I have to specify the length. Let's say I'm gonna use equivalent is 2.8 and actual 2.5 meter, and height difference between indoor and outdoor units same 4.5 meter, and then save it and then close it. So now I'm going to use I'm going to specify the third indoor unit for third space, that is office 2. So this time I'm gonna use the same 4-way cassette type unit. So instead of again drag and drop here, I'm gonna copy the same data. If you will just right click on this machine and copy, and then here right click again and then paste. So same data will be pasted here, so I'm just gonna modify it. Just double click this machine. I'm gonna select here VRF 3, office space 2, ground floor, auto selection, and this 70, okay. And what is our load here? As you can see, for office, cooling 3.8, heating 3.3, 3.8, 3.3. So 3.8 kilowatt cooling. Let's say this is 3, and heating how much? 3.3. 3.3. So we have specified our heating and cooling loads, and now we have to specify the length again. Let's say it's same 2.8 from here to here, it's 2.8 equivalent we are going to use, and 2.5 is the actual we are going to use, and height with same, that is 4.5 meter. So save this one and then close it. So now I have to specify the fourth indoor unit for number 4 space, that is locker room. So this time I'm gonna use this high wall type unit over here, 3 series or 7 series. So I just have to drag and drop here into the dummy indoor unit, and then I'm gonna use its name as VRF 4. Room name is locker room, and floor is ground floor, and I'm gonna use the auto selection method over here. Same everything except this last one I'm gonna change to 70, heating, variable temperature, and now I have to specify the load. Locker room 1 it's cooling 3 and heating 3.1. 3 and 3.1. 3, let's say the sensible is 2.4 and 3.1 is the heating load. So 3 and 3.1 we have specified here, and now we have to specify this length again. So let's say I'm gonna use same 2.5, 2.8 equivalent and 2.5 actual length. And height difference again I'm gonna use same between indoor outdoor unit is 4.5 meter, because this one is on the ground floor and our outdoor unit was on the first floor, and this is locker room 1. Here locker room 1. Then after specifying all the inputs, then save it and close it. So now I'm gonna select one more indoor unit for our next phase, that is meeting room 2. So let's say I'm gonna select the same unit which I have used here, standard duct type, for meeting room 2. This is for meeting room 1. We should mention this one as meeting room 1. Save this one. So instead of drag and drop another, I want to copy the same data, just edit this one. So right click this one, copy this machine data and right click, paste. So now I'm gonna edit the data for this meeting room 2. So this VRF is 5. This is our VRF 5 and meeting room 2. Same ground floor, auto method. This is all okay. And now we have to specify our loads. Let's say our cooling load is 11.8 kilowatt and heating is 12. 11.8 kilowatt is cooling, and let's say our sensible is 10.2, and our heating load, that is 12 kilowatt. 12 kilowatt. So I'm gonna use the same length from the joint to the machine, that is 2.8 meter equivalent and actual 2.5, and this is 4.5 height between indoor and outdoor unit. So just save it, then close this tab. So now I will input the data for another space, that is locker room 2. So first locker room I have used this 3 series high side wall. So I'm gonna copy the data from here and then paste here on this dummy indoor unit, and then I will double click to modify the data. This is our VRF 6 and locker room 2, ground floor, auto selection method. And now I have to add the cooling and heating load. So cooling load is 3 and heating load is 3, both are 3 kilowatt. So 3, let's say this is 2.4 and this is also 3. So cooling is 3 kilowatt, heating is 2 kilowatt, and same piping length I'm gonna use from this joint to this machine, equivalent and same actual. And height between indoor and outdoor unit, it's same 4.5. I'm gonna use, save, and then close this one. So one more indoor unit for next space, that is our restroom. So for restroom I'm gonna use this 4-way cassette type. I will copy the data and then I will paste here. Then double click this one to edit the data, and this would be our VRF 7, and its room is restroom. So on the ground floor, auto selection method we are going to use, and its cooling load is 4.6, heating is 4.8. 4.6, 4.8, and let's say our sensible is 3.6 here, it's 5. So this is our cooling 4.6 and heating is 4.8. Okay, so the length, pipe length from the joint, from this joint to this machine is 2.8 equivalent and 2.5 actual. So we can save this one and then close it. So there are 4 more indoor units which we have to add over here. So what is our next space? That is smoking room. So I'm gonna use cassette type here again. Copy data and paste on this dummy unit. Then double click to edit the data. This is our VRF 8, that's okay, and this is our smoking room, same ground floor, auto selection method, and we have to specify the loads, 3 for heating and 3 for cooling and 3.1 for heating, 3 and 3.1. so 3.1, and let's say sensible is 2.4. so we have specified, and length, so the length which I'm gonna use now from this header, 4 branching header till this machine is 2.8 equivalent and 2.5 actual, and height is same because this is on the ground floor and our outdoor is on the roof, so it's 4.5 meter. So I'm gonna save it and then close it. Again I'm gonna, so next space is reception room. So I'm gonna copy this data, paste on this dummy unit, double click this indoor unit and edit your data. This VRF 9 and this is our reception room. So I'm gonna change this name to reception room. Reception room, it's on the ground floor, and these conditions are same. Now I have to specify the loads. Let's say our cooling we have calculated is 3.8, heating is 3.9, 3.8 and 3.9. so this is 3.8 and this is 3.9, and let's say our sensible is 3. So now I have to specify the length from the joint. So let's say the length from this joint to this machine is 5.8 equivalent and 5.5 actual. So I'm gonna use 5.8 equivalent and 5.5 actual. So this height is same, and save the data. Then close it. Then move to the next space, that is office 3 space. With the cooling load is 4.8 and heating load is 4.5. So I'm gonna copy this data from office 2 over here, paste, and double click the indoor unit. This will be our VRF 10, and this is our office 3 ground floor, and then we have to specify the cooling and heating loads. Cooling is 4.8, heating is 4.5, and heating is 4.5. Let's say our sensible is 3, sensible cooling load is 3.8. So now I have to specify the piping length from the joint. So let's say from this joint to this machine, the equivalent piping length is 8.8 meters, and actual is 8.5 meters. And then save it, and close this one. So now the last page is here, that is reception area. So I'm gonna use standard duct type here for reception area. So I'm gonna copy this data and paste over here. Then I'm gonna double click this indoor unit and modify the data. This is VRF 11, and this is for reception area. It's on the ground floor, auto selection method. So capacity for cooling is 3 and heating is 3.1. So it is 3 for cooling, 3.1 for heating. So sensible cooling I'm gonna use, let's say it's 2.45, and again I have to specify the piping length from the joint equivalent and the actual. So let's say the length of this piping from our A4 branching header to this machine is 11.8 equivalent, and the actual I'm gonna use here is 11.5, and this is 4.5 meter. Then save this machine data and then close it. So now all the indoor units data has been specified. Now we're gonna move to our outdoor units. As you can see that since we have specified all the capacities for our indoor units, so based on our indoor units capacities, outdoor unit is automatically selected over here. Now the unit which is selected here is MMY AP2416 HT8P, that is 24 horsepower system is selected based on our load calculation for all indoor units. So if you wanna modify the data or edit the data, you just double click outdoor unit. So the unit type which I'm gonna select over here is SMMSE. There are different series available here in Toshiba. So I'm gonna select this SMMSE. Since I have checked this auto, that's why this machine is selected based on my indoor unit capacities or load calculation. So and the maximum selection percentage which I have selected here is 100% based on my indoor and outdoor unit capacity ratios. So there are few more things I have to specify here, that is the main piping length. As you can see that this is 0 right now, so I have to specify this main piping length. If you remember my first video, I have told you about the main piping of the refrigerant VRF system. The main piping length is from this T connection to the first branching section. This is our main piping length over here, as you can see. So I have to specify this main piping length actual and equivalent. So let's say my main piping length actual is 6 meter and equivalent is 6.5 meter. so I have used this length over here. Now I have to specify the T-shape outdoor unit distance LA and LB. As you see, this is our outdoor units here. This is first one and this is the second one. So LA is the distance from outdoor unit till this pipe, and LB is the distance from here to this main pipe. So this is LA and this is LB. We have to specify these lengths. So let's say the LA actual which I have used here is let's say it is 2.7 for LA, and LB is also 2.7, and equivalent, let's say it is 3 for LA and 3 for LB. And one more thing we have to specify here is the height difference between these two outdoor units. Since I want both of them on the same floor, same level, so I'm gonna use 0 meter here. If you have height difference between them, then you can specify that difference in a meter over here also. So since I'm gonna use both of them on the same floor, so I have specified 0. There's no height difference between these two outdoor units. So after editing this data, you just save it. And then exit this one. So as you can see that we have specified this main piping length, but there are few more entries which we have to add over here. So as you know that we have added this pipe length, refrigerant piping length, from this Y branching joint to the machine, but we did not add the length from branching joint to the branching joint. As you can see, it is 0 here, 0. It is 0. It is 0. So we have specified this length, but we did not specify this length. So now I'm gonna specify the length between the joints, Y-shaped branching joints. So I'm gonna select this branching joint to specify the length between this joint and this joint. So just double click this Y branching joint, and its name is Y2. So now I'm gonna mention the actual length and equivalent length. Let's say our actual length is 2.7 meter here and equivalent length is 3 meter. So okay, so as you can see that the lengths are mentioned here, 2.7 and 3. So now I'm gonna specifying this length between two joints. So I'm gonna select this joint, and let's say the length which I'm used here is 3.2 meter actual and 3.5 meter equivalent. So it will come here. Now I have to specify between this joint and this joint. So let's say same, I'm gonna use 3.2 and equivalent is 3.5. So whatever your lengths are here, you have to specify here in your project. And if you don't select these lengths, then you will get an error. Why will you will check your system information. So let's say I will go over there. As you can see that this is an error, so we need to fix that one. Total pipe actual length is not mentioned. It's 0 meter pipe length exist. So when I specify all the lengths over there, so this error will be gone. So we need to specify all the lengths over here. So now I have to specify the length between this joint and this joint. Right now it's 0. So I'll select this one. Let's say the actual length is 6.2 and equivalent is 6.5 for this Y5 joint. So this length will appear here, and now I will specify this length from this joint to this joint. just double click this joint Y6 and mention the length. Let's say actual is 2.7 and equivalent is 3. Okay, now between these two joints, same, I'll suppose this is 2.7 and this one is 3. So now I have to specify the length between this Y branching joint and this 4 branching header. So I have to specify the length. So let's say it's 2.7 actual length and equivalent is 3. So it will appear here. Okay, so all other lengths I have already specified there. So this is how you have to specify all the refrigerant piping length. So as you can see that we have put all the information in our project, and we have designed our VRF system based on our load calculations. And you can see this dia is automatically calculated both for liquid and the gas piping based on our load calculations. As you can see that by specifying the length between the joints, that is Y-shaped branching joint and all the joints, we have specified the length. Before that, the outdoor unit capacity was 24, but now it is 26 horsepower. As you can see over here, one outdoor unit 14 and the other one is 12, so total 26 horsepower. So all these factors matter a lot while selecting your indoor and outdoor units. We specified the length over here between the joints. So this is 26 horsepower system of the outdoor unit, that is divided into 14 horsepower and 12 horsepower. And this one is header and this one is follower. If you remember, I told you about the header and the follower. Header is that unit that is nearest to the first branching section, that's why this is called header, and the other is called follower. And they should be arranged in the capacity according to their capacity. 14 horsepower should come first and 12 horsepower should come second, sorry. So this one comes first, this is second, this is header, this is follower. And if you want to study these piping diameters and lengths, you can see the piping legend over here. The first one is for the gas pipe diameter, second liquid pipe diameter, third is actual length, fourth is equivalent length. So this first one is gas pipe, that is 7 by 8 inches, second is liquid pipe diameter, that is half inches, and 2.7 meters the actual length and 3 meters the equivalent length. So this is how you can study the legend for piping. In the same way, legends are mentioned here for outdoor units and indoor units. So this is how you can design your VRF system based on your load calculation. You have to specify your load calculation for indoor units, and using auto selection method you can select your select your outdoor units based on your indoor load calculations and selection. So in the last but before that I will click this system information. So if I click the system information, you can see that this is the specification column and this one is a design column and this is the result column. So make sure that all of them should be tick in the end. If it is not tick, then you need to correct that error. So as you can see, this is the design column, and in our project this is basically the limit from the supplier, this SPEC specs or specification from the supplier. This is the limit from the supplier, so we need to our design should be less than this specified limit, because this is the limit. So for example, total piping length actual allowed by supplier is 300 meters. In our case it's 80.3, so 80.3 is less than 300, that's why it's ticked. Same over here, maximum equivalent length of the outdoor unit connecting pipe is 10 is allowed maximum, and we have 3 over here, so we are good. So as additional refrigerant charge amount that's automatically calculated for our whole system is 14.76 additional refrigerant amount is required to charge, and outdoor unit capacity is 26. As you see over here, there is 26 horsepower, and 2 outdoor units we have used, one 14 and the other 12, and indoor units are 11 we have used. Indoor unit capacity is 24.45 is the total capacity of the indoor units, and indoor unit to the outdoor unit capacity ratio, that is outdoor unit diversity, is 94%, because indoor unit is 24.5 and outdoor unit is 26, so 24.5 divided by 26, outdoor unit diversity will be 94%. So 94, this is the design, this is the allowed limit, that is 50, it should be between 50 to 135%, and our is 94%, so that's why it's good. And for this pipe equivalent length actual that is allowed from the supplier is 180 meters, and in our case, our project, that is 34.5 meters, so we are in the safe range. So this is how you have to compare your design with the limitations from the supplier. So in the end, we will generate an output from our project. So you just need to click this output over here, or you can go to edit and you can generate an output data. Also you will get the electrical results also here. When we generate the report, we will get the detailed design of this electrical. So let's go to the output tab and select this one. So whatever the things you need, you can select and you can generate the output. You can generate report, table, piping, wiring, and price list, everything. So whatever you need, you just select this one. If you need Excel, you can, for all this you can select Excel. If you need CAD, you can select the CAD. If you need PDF, you can select PDF. So right now I'm gonna select only PDF. So now I'm gonna save these reports, tables, and piping and wiring diagrams, and we'll discuss the results. Let's say I'm gonna save here. Okay, just wait a moment, it will take maybe 1 minute. Once everything is saved there, I will discuss the results related to the VRF system design. We will discuss the report, table, piping and wiring diagrams, and the price list also. Just wait a little. So in my next video, I will discuss with you guys about the additional refrigerant charge calculation, and we'll also use the other method for refrigerant piping design over here for the VRF system, that is wizard type selection, later in another video. Just wait a moment. Okay, it's done. So move here. Okay, these are all the PDF files which we have selected over there. So I'm gonna open this first one, the piping diagram, refrigerant piping diagram for the VRF system, which we have designed there. So as you can see that this is the refrigerant piping diagram which we have created over there. So you can take a print of this refrigerant piping diagram because everything is mentioned here, all inputs are there, load is mentioned there, and machine size is also mentioned there, pipe sizes are mentioned, liquid gas pipe size mentioned, their lengths are mentioned, what are the accessories used here, Y-shaped branching joints, and their types are also mentioned. For example, this is RBMBY105E and this is RBMBY205E. So let's go to piping and wiring diagram in the combined state. So as you can see that this is our outdoor unit which we have selected for our system, that is 26 horsepower system. As you can see, this is blue one is the refrigerant piping over here, and this red one is the electrical cabling here for from outdoor unit to the indoor units. So as you can see that we have all the indoor units over here, total 11 indoor units, and you can see that their gas and liquid pipe sizing are mentioned there, and the lengths are also mentioned there from this joint to this machine, then this joint to this machine, all lengths are mentioned there, and these lengths are also mentioned from joint to joint lengths, and refrigerant piping dias are also mentioned for liquid and gas pipe. And as you can see that electrical wiring for the cables, their sizing is also available here. So if you go over there, you can see the outdoor unit name and its capacity, that's horsepower, and indoor unit total capacity, outdoor unit capacity, everything is mentioned here, and how much is the additional refrigerant charge calculation is required for our project is 14.76. so this much additional refrigerant is required for our project. And if you go over there, you can find the indoor and outdoor units and the accessories, Y-shaped joints, header, whatever we use in our project is mentioned here, and their quantities are also mentioned here. And this is the wiring size and length for the electrical data. Over here you can see what kind of wire we can use, it's mentioned here for the outdoor unit, for the indoor units, and for remote controls, everything is mentioned here. Their wiring, labeling, polarity, their size, length, everything is mentioned here in our report. And you can see the price list also here, our project name, everything is mentioned here. Then outdoor unit, only one we have used, and indoor units, there are different types of indoor units and their quantities available, whatever the price you can mention here. And outdoor unit connection kit which we have used is this model, only one quantity. Then Y-shaped branching joints, we have used these types, this quantity, and then header and then accessories. So this is the pricing list which you can use, and it's easy for you to order the equipments and accessories for your VRF system. So also you have a equipment list, and you have a report drawing. So this is the same thing which we already discussed before. The electrical wiring is there and refrigerant piping is there, and you have a equipment catalog for indoor units and outdoor units. So this is how you can generate your report after finish your design of the VRF system. So it will be easy for you to interpret the results later after your design. If you have these reports, you can easily proceed for installation of the machines and everything. So I hope you guys learned something from this video. In my next video, I'm gonna discuss about additional refrigerant charge calculation. In this software, it's all automatically calculated, but I will show you the calculation behind refrigerant charge. So I will let you know how we have to calculate additional refrigerant. So for more videos, keep watching my channel and don't forget to subscribe. Hello guys, this is Syed Mohammad Waqas. Today I'm gonna continue the VRF topic, designing and selection. If you remember, last time I discussed regarding VRF system designing and selection using software. and today I'm going to discuss VRF system additional refrigerant charge calculation. So there I have prepared an Excel sheet to show you the calculation for additional refrigerant needed for your system. If you remember that last time I have used this software VRF selection tool to design and draw our system, and we have made the PDF file also in the form of results. So our machines like outdoor units and indoor units, these indoor units and outdoor units are pre-charged from the factory, so their refrigerant is already calculated there, but we want to calculate the additional refrigerant due to the piping which we have draw over here. So right now I'm going to calculate the additional refrigerant due to this piping, because indoor units, outdoor units already pre-charged from the factory. So let's start the calculation. Here I have an Excel sheet. So there I'm gonna use two tables for refrigerant charge calculation, and here is the formula which I already applied here to calculate the additional refrigerant. So this first table is you can see over there, dia is mentioned 6.4, 9.5, 12.7, 15.9, 19 and 22 mm. So, and this is the additional refrigerant needed per meter length due to 6.4 mm dia. So 0.025 kg additional refrigerant is needed per meter length of the pipe due to 6.4 mm dia. So all of these lengths are mentioned per meter. Per meter we need 0.055 kg additional refrigerant due to 9.5 mm dia. So in the same way 0.35 kg refrigerant is needed per meter of dia 22.2 mm. So this is the formula which I'm gonna use to calculate additional refrigerant, that is L1 into this additional refrigerant 0.025, because this is due to dia 6.4, and then L2, this is L2, and L2 into additional refrigerant needed is 0.055. so this is the values which I will give over here: L1, L2, L3, L4, L5 and L6. These are the real lengths. As you can see over here, real total length of the pipe dia 6.4 mm, real length of the pipe dia 9.5 mm, and till L6, that is real total length of liquid pipe dia 22 mm. So these are the calculation we have to perform for liquid side, not for the gas side. So that's why it's written that real total length of liquid pipe dia 22 mm, L6 length. So all of the lengths we will provide over here, whatever the lengths which we have used over here, real lengths in our software. So I'm gonna use these lengths over here. So L1, which we will provide over here, into 0.025 kg of the additional refrigerant needed per meter. So in the same way, that is L5, this is our L5, L1, L2, L3, L4 and L5. So L5, how much refrigerant do we need over here? That is 0.25 kg per meter due to dia 19 mm. So, and one more thing in this formula is we need to add additional refrigerant to the system compensation, system horsepower compensation. As you can see over here, this formula, as you already understand. And second thing, you have to add the compensation by system horsepower. So this value will take from these tables. This is the compensation due to the horsepower of the system outdoor unit which we have selected. This is for the standard efficiency models, and this is for the high efficiency models. So whatever the value of your outdoor unit horsepower, let's say our outdoor unit horsepower is 14, and additional refrigerant needed due to the 14 horsepower outdoor unit is 8.5 kg. So we need to add this one also here. So let's move back to our software, and if you remember that I have made PDF files in my last video to interpret the data. So I'm gonna open this table. So as you can see that when we were making our VRF system design in my last video, I have created a PDF file from our design. So we know that the outdoor unit capacity which we have calculated over here is 26 horsepower, and we use two outdoor unit. As you can see over here, there are two outdoor unit. One is 14 horsepower and the second is 12 horsepower, total 26 horsepower. And as you can see that through the software we have calculated 14.7 kg additional refrigerant. So I will compare this value with the value in my Excel sheet. So I'm gonna, let's go back here, and you can see that this is all the diameters which we have used in our project. And you have to know one thing. This first one is for gas. These are the real lengths in meter, and the first one is for the gas pipe and second one is for the liquid. Same, first one for the gas, second for liquid. First for gas, second for liquid, and this is the total length for 3/8 including gas and liquid size, that is 27.4. half inches for gas and liquid both, that is 38. So we are going to use the liquid side length. So first we have dia 14. 14 dia is nothing but it's 6.4 mm. So this is our length L1. So what is the length L1? 1/4 is 6.4 mm. So liquid size, as you can see that 32 meter is the length, this length in meter. So 32 meter is the length which we have used here. So I'm gonna give 32 meter length here. And now second is 9.5 mm. As you can see, 3/8 inches is 9.5 mm. If you convert this in inches to mm, it will be 9.5 mm. So how as you can see, the length which we have gas side is 7.5. Since we are using the liquid side, so it's 19.9 mm, 19.9 meter, sorry, not mm, 19.9 meter due to 9.5 mm diameter. How much length? 19.9 meter. So 19.9 meter. Now I'm going to take the third length, that is half inches. Half inch is nothing but it's 12.7 mm, as you can see over here, and here it's half inches. And first one is for the gas, second is for liquid. So liquid size, how much is the length? That is 13.5 meter due to half inches, that is 12.7 mm dia, 13.5 meter length. And now go to L4. L4 is due to the dia 15.9 mm. 15.9 mm is same as 5/8 inches. If you convert this in mm, it will be 15.9 mm. So 5/8. How much is the length on the liquid size? That is total is 28.8. gas side is 19.9 meter, which we have and you know that these lengths which we have calculated from this project which we have created before in my last video. So every data is in the table form which we have created in last video. So now this is L4 due to the dia 15.9, that is 5/8 inches. So liquid size, liquid side length is 8.9 meters. You can see over here 8.9 meter. So 8.9 meter. and L5 is the length due to the dia 19 mm. 19 mm. 19 mm is nothing but it's 3 by 4 inches. As you can see that gas side there's no length, that is 0. We did not use any dia 3 by 4 for the gas, but for liquid it's 6 meters length we have used for 3 by 4 inches, so 6 meter. And the last one is L6. L6 is due to the diameter 22.2 mm, and if you convert this into inches, 22.2, it will be 7 by 8, and as 7 by 8 inches, 22.2 is 7 by 8 inches. As you can see that gas side we have 10.8 and liquid side is 0, so we did not use any liquid pipe with 7 by 8 inch, so this length is 0 used in our project. So I'm gonna give this one as 0. So as you see that I have provided all the lengths, and I have applied the formula over here, all lengths we have. Let me tell you again, this L1, the formula which we have used here is, that is length L1 due to the dia 6.4, because this is the real length of liquid pipe, dia 6.4. This is 32 meters. As you know that per meter due to the dia 6.4, how much additional refrigerant charge is needed? 0.025 kg. So we have 32 meters, so 32 into 0.025, you will get the additional refrigerant needed due to the dia 6.4 having length 32 meters. So in the same way, length L3, that is 13.5 meter used here, and this is the additional refrigerant needed, 0.105 per meter, 0.105 kg per meter length of dia 12.7. Since we have 13.5 meter used in our project, so 13.5 into 0.105, so this will give you the additional refrigerant charge needed due to the dia 12.7 mm having length 13.5 meters. So all of this you have to add, and then in the last, as I told you, you have to add the compensation by the horsepower of the system. So since we have if you go over there and you will see we have selected 26 horsepower system here. As you can see over here, outdoor unit is 26 horsepower, and it's break down into two outdoor units, that is 14 horsepower and 12 horsepower. And you know that this is the standard efficiency model we have used, not a high efficiency model. So this is the standard efficiency model table, and outdoor unit which we have used over here is 26 horsepower, and you know that it's 14 and 12 break down into two outdoor unit, and you see that compensation by the horsepower is 8.5. so this 8.5 you need to add over here to get the additional refrigerant needed for your piping. As you can see that I have added this G17. G17 is this value due to the system horsepower, 8.5 kg additional refrigerant needed. So you can see over here the additional refrigerant needed is 14.7 kg, which we have calculated over here. And if you go over there from our software, we have calculated here is additional refrigerant is 14.76 kg additional refrigerant, 14.7. so here also 14.7. so we just compared this one with the software result. So this is how you can calculate the additional refrigerant needed for your system. I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Hello guys, this is Saeed Mohammed Wakas and back here with another video. In this video, I will tell you guys how you can calculate the refrigerant line size. So in this example particularly, we will calculate the liquid line size. Also, we will calculate subcooling required at TX valve for proper operation. So let's start. As you can see in the figure, we have a condenser over here, and the evaporator over here that is higher than condenser with a riser of 20 feet. And you can see that this green color is a liquid line, and the liquid line is consist of following components over here. You can see that is 22 feet of piping, 7 long radius elbows, 1 filter dryer, 1 side glass, and 1 globe type isolating wall. How we have 7 long radius elbows? As you can see, this is the 1 elbow, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So we have 7 long radius elbows over here. So let's move back to our Excel sheet over here. So this is our design parameters. Evaporator operated at 40 degree Fahrenheit, condenser operated at 120. Material we are going to use is copper. Refrigerant R410A we are going to use, and the system capacity is 60 tons. And the system capacity we have calculated, we have already calculated using HVAC software, so we know that system capacity is 60 tons. So over here, refrigerant R410A, we have write the components and the number of components used over here. Then before giving this equivalent length for each component, let's move forward and first calculate the estimate pipe size over here for 60 ton capacity. So let's move over here. There we have a refrigerant line size table, R410A refrigerant. So as you can see that this is for suction line, this is for discharge line, and this is for liquid line. And you see over here we have a pipe dia in inches, and over here inside this is the system capacities. So we have to follow this liquid line, and our system capacity is 60 ton. We know it will be in between 45.8 and 79.7. As you can see over here, I have highlighted here. So we will not go for 45.8, we will go for 79.7, higher side, safer side. So for 79.7, as you can see, 1 3/8 is the pipe size, so we can use this 1 3/8 inch pipe size. So let's move back over there and see 1 3/8 inch is the pipe size we are using over here, and actual system capacity, you know that it's 60 ton. And the table capacity is the same. We know that it's 79.7 ton. This is the table capacity we have used over here for 1 3/8 inch. So we have to write this table capacity 79.7. So we have write 79.7, and this table is for 100 feet length. So we have to write this table length also 100 feet over here. Now we'll move to equivalent length now. As you can see over here, down there I told you this 22 feet piping, straight piping length. So we have write 22 feet over here. So long radius elbows we have 7. So what is the equivalent length for each long radius elbow? Let's move back over here. And there you can see equivalent length for the fittings. Smooth elbows 90 degree elbows for 1 3/8 inch. This is the equivalent length 2.3 for 1 3/8 inch. So this one we are going to use 2.3. As you can see 2.3. So for filter dryer, side glass, and solenoid valve we have to check. This is the equivalent length for the valves and other devices. As you can see, 1 3/8 inch, 38 feet is for global solenoid valve. So this is 38 for global solenoid valve. Now go for side glass. For side glass, for filter dryer core it is 35, and side glass it is 2.5 for 1 3/8 inches. So 2.5 for the side glass and 35 for the filter dryer core. As you can see, 35 for filter dryer core and 2.5 for side clamps. So if you multiply this number of items with this equivalent length, you will get fitting equivalent length for each and every component. So simply multiply this with this, you will get to the fitting equivalent length. And if you will sum all of these components equivalent length, you will get total equivalent length in this column, that is 113.6. so up till here it's done. Now table length, it's done. Now table delta T, that is the table delta T. It's 1 degree Fahrenheit. How it comes, I'll tell you. Let's move back over here. As you can see, for the liquid line, we have used this 1 degree Fahrenheit delta T. So we have to write for table delta T, that is 1 degree Fahrenheit. These are the system capacities. So this one we have used over here, 1 degree Fahrenheit. So this one we have to write 1 degree Fahrenheit. Now actual delta T, this is calculated by using a formula. I will show you what's the formula I have used over here to calculate actual delta T. This is the formula I have used over here for calculating the actual delta T. We know the actual capacity, table capacity, we know actual length, we know table length, we know table delta T. So all of these components we know. So by putting the values, we can calculate delta T actual. So this is the formula I have applied over here to calculate delta T, actual delta T. Now we have to calculate the pressure drop from the table. So this is 4.75. How it came, I will tell you. As you can see over here, for 1 degree Fahrenheit, what is delta P? As you can see, that pressure drop, this is a pressure drop, this 4.75. So 1 degree Fahrenheit, what is the pressure drop for R410A refrigerant? That is 4.75 psi. So this one we have to use for the table. Delta P, 4.7 psi. This is the 4.75 psi. Now actual piping pressure drop we have to calculate. This also calculate by using a formula. I'll show you the formula. This is the formula we have used over here for pressure drop actual calculation. So pressure drop for the table, delta T actual divided by delta T table. Actual delta T we have already calculated from this formula. Delta T table, we know that it's 1 degree Fahrenheit, and pressure drop from the table we already checked from the table, that is 4.75 psi. So putting all these values, you will get actual delta P. So this is how you can calculate actual delta P. As we know that riser height, we'll move back to our diagram over here. Riser is also used over here. So what is the riser height used over here? That is 20 feet riser. So we have right 20 feet riser height, refrigerant pressure drop per feet. Again we have to use a table for this one. What is the refrigerant pressure drop per feet? Since we are using R410A refrigerant, so we have to check what is the pressure drop for this refrigerant per feet. So move back over here, go down. There's a one more table, this one, pressure drop in liquid line by refrigerant. As you can see, we're using R410A refrigerant, and there is a pressure drop that is 0.43 psi per foot for R410 refrigerant. So we have to write this one, 0.43 psi. So we have write this 0.43 psi per foot. So if we multiply this refrigerant pressure drop per feet multiply with this riser height, will get the pressure drop from the riser. So multiply these two, will get pressure drop from the riser, 8.6 psi. So multiply 0.43 with 20, will get 8.5. So let's move forward. We have calculated this pressure drop from the riser. Now we have to calculate what will be the total pressure drop in the liquid line. So in order to calculate this total pressure drop, you have to sum this from the riser and actual pressure drop. So you have to add these together, actual piping pressure drop plus pressure drop from the riser. These two add together, you will get total piping pressure drop. So 3.23 plus 8.6, you will get 11.4 psi, 11.84 psi. So move forward. Saturated pressure at 120 degree Fahrenheit. We know that condenser operate at 120 degree Fahrenheit. So this is the saturated pressure at condenser. So we want to calculate now saturated pressure. What will be the saturated pressure at 120 degree Fahrenheit? We can calculate this by using PT chart. So let's move back over there. Here we have a PT chart. We will go for R410 air refrigerant. So this is R410 air refrigerant, as you can see. So this is the temperature in Fahrenheit. So we are going to use 120 degree Fahrenheit. What is the pressure for R410 air refrigerant? As you can see, this is the pressure, 418 psi is the pressure at 120 degrees Fahrenheit. So this is we have to use over here, 418 psi. So we have used 418 psi over here. Now saturated pressure of refrigerant at TX valve. How we'll calculate this one? We have to subtract 418 minus, we have to subtract this 418 minus total pressure. You will get saturated pressure of refrigerant at TX valve. So saturated pressure at 120 degree Fahrenheit minus total pressure, you will get saturated pressure of refrigerant at TX valve. So move forward over there. Now saturation temperature at TX valve. How you will calculate this one? Now we know what is the saturated pressure of refrigerant TX valve, that is 406. So from the PT chart we can calculate the saturation temperature at TX valve. So move back. What is the pressure? 406. 406. As we can see that we have 391 and 418. So we have to perform iteration in between 115 degree Fahrenheit, 120 degree Fahrenheit, 391 psi and 418 psi. I hope you guys know how to perform the iteration. It's quite easy. If you don't know, then let me know. I will tell you how you can perform the iteration to calculate this delta P, that is pressure drop. So this is how you can calculate. Move back. Okay, so after performing the iteration, you will get 117.8 degree Fahrenheit saturation temperature at thermostatic expansion valve by performing the iteration. If you don't know about the iteration, let me know. I will tell you how you can do it. So let's move back over the actual saturation temperature for the condenser is 120 degree Fahrenheit, we know. So this is now we are the final step of calculating the subcooling. Now the subcooling for saturated liquid at thermostatic expansion valve is 2.2. How it comes up? So we have to actual saturation temperature minus saturation temperature at TX valve. You will get subcooling for the liquid at TX valve. So as you notice, this 2.2 degree Fahrenheit is the amount of the subcooling required to have saturated liquid refrigerant at TX valve. If it is less than 2.2, refrigerant will start to flash and TX valve will not operate properly. For TX valve to operate properly and to avoid diaphragm flutterings, there should be an additional 4 degree Fahrenheit of subcooling. So the minimum system requirement we have to add over here. We have to add additional 4 degree Fahrenheit for thermostatic expansion valve to work properly. So the minimum system requirement is 4 degree Fahrenheit. So what is the actual subcooling for the proper operation of TX valve? It will be minimum system requirement plus is subcooling for saturated liquid at TX valve. So this is 6.2 degree Fahrenheit is the subcooling required for proper operation of thermostatic expansion valve, so that refrigerant will not flash. So this is how you can calculate this liquid line size and subcooling. I hope you guys like this video. Please like, comment, share, and don't forget to subscribe my channel. Thank you. Hello guys, this is Syed Mohammad Waqar and back with another video. In this video I will tell you guys about the fresh air CFM calculation. So there I have opened the drawing for the school project. I will show you our different areas for fresh air CFM calculation. So let's start. So first I will calculate the fresh air CFM for this chemistry and bio lab. So in order to calculate the fresh air CFM, I have made this Excel sheet as you can see over here. What we need over here is the room area, CFM per square feet, number of persons, and CFM per person. And total fresh air will be the sum of CFM1 plus CFM2. So let's start for chemistry and bio lab. As you can see, the area of this chemistry and bio lab from here, this much is the width. 10.9 meter is the width of this lab, and 13.2 meter is the length of this lab. So area will be 8.4 times 13.2. That is 110.88 square meters. Also this area is also included, so this is 300, that is 3 meter by 1.6 meter is this area, plus 1.5 meter into 1.4 meter is this area. So that total area will also be added in the chemistry and lab, because this is the part of this chemistry and bio lab area. So let us add this area, that is 3 meter by 1.6 meter, that is 4.8 square meters, plus 1.5 into 1.4 meters, 4.8, 1.5 into 1.4 plus 4.8, that is 6.9 square meters. 6.9 square meters, plus we have already calculated that area, 8.4 into 13.2, 8.4 into 13.2, 110.88 plus 6.9. So the total area is 117.78 square meters, but we have to put that area over here in the square feet. So in order to convert that square meters into square feet, we will multiply it by 10.76. so 1267 square feet is the area of this lab. 1268. Okay, now go for computer lab and classroom. So I will show you one more over here, that is computer lab. As you can see, the length of the room is 1.2 meter, 12 meters sorry, and width is about 8 meter. So total area will be 8 meter by 12 meter, that is 96 square meters. But we need to convert this into square feet, so multiply it by 10.76. so we'll get 1033 square feet. 1033 square feet. Now I will calculate one of the classroom also. As you can see, this is the classroom, and its length is 12 meters and width is 8 meters, so it's same as computer lab. So area will be same as computer lab. So let's move to the next column, that is CFM per square feet. For this I have opened this HAP software. If you will go to the spaces and then go to new default space, from here we can select the ventilation requirement as per AHU standard 62.1. so what we have over here is science lab, that is chemistry bio lab. So if we'll scroll down over here, as you can see, education science lab, that is chemistry bio lab. So we can select this over here, and you can see the CFM per person over here is 10 as per AHU standard, and CFM per square feet required for science chemistry lab is 0.18. so 10 CFM per person and 0.18 CFM per square feet. So 10 CFM per person and how much? 0.18? Yeah, 0.18 CFM per square feet. 0.18 CFM per square feet. As I have already applied this formula, this room area into CFM per square feet will get first CFM. You can see over here, this and this will get the CFM1, that is 228. Now how to get the number of persons? Usually from the architecture you can get the number of persons, how many persons will occupy this chemistry and bio lab and computer lab and classroom. So let's assume the number of persons in chemistry bio lab will be 15. So this CFM2 will be calculated as follow: this number of persons into CFM, you will get this CFM2. So total CFM, how you get this total CFM? Total CFM will be the sum of this first CFM, room area into CFM per square feet, plus number of persons into CFM per person. So total CFM will be CFM1, that is 228, plus CFM2 150. So total is 378 CFM for chemistry and bio lab. In the same way you can calculate the computer lab and classroom. So I will show you again. Let's go for computer lab. In the education, so there it is, education computer lab, you can select from here. So CFM per person is 10 and outdoor air requirement is CFM per square feet is 0.12. so this is 0.12 and 10 CFM per person, and we use the same number of persons here also. So again this CFM area of this lab into CFM per square feet will get CFM1, and number of persons multiplied by CFM per person will get CFM2, and total CFM for computer lab will be the sum of this CFM1 and CFM2, that is 273.96, 274 CFM. So let's calculate for classroom also. So this is the education classroom for grade 6 students. So let's go for classroom age 9 plus, and the CFM per person is 10 and CFM per square feet for classroom is 0.12. so this again 0.12 and this one is 10 CFM per person, and number of person will take same, or we can check from architecture. So total CFM required for classroom is again 274. So if you need to calculate the total CFM for these three areas, chemistry bio lab, computer lab and the classroom, it will be the sum of these three CFM, that is calculated over here is the sum. So this is how you can calculate the fresh air CFM for each and every room. So in the same way you can find the CFM for other classrooms. I hope you guys like this video. Please keep watching my channel and don't forget to subscribe. Hello guys, this is Syed Mohammad Wakas. I'm back with another video. In this video I will tell you guys how you can do AHU room sizing. So let's start. There's simple step which we have to follow. First step which we have to follow is we have to find dehumidified CFM through heat load using HAP software or E20 form. So after using the HAP software, let's say we got 9000 CFM through heat load calculation. So we have to add 5% safety factor into this one to keep safe side. So in order to add this 5% safety factor, multiply 9000 with 1.05, you will get 9450 CFM. So for this CFM we'll select AHU. There I have a catalog for air handling unit. It's a double skin modular air handling units provided by this MEP air conditioning. So let's move down and select our air handling unit for that CFM. So let's say we are going to select this horizontal typical configuration air handling unit. Okay, as you can see that this is the liter per second, so you can convert this into CFM. This is our flow rate, and this is the height of the machine, this is the width of the machine, and this representing as length. So if you notice over here for this diagram, here A is representing as fan motor compartment, B is representing as coil compartment, and this C is representing the filter compartment for primary and secondary. And this is you can see that this is the returns duct area, this is the fresh air duct area, and this is the supply duct area. And you can see that E is representing the whole length of this air handling unit. So as we know that how much is the CFM, we got 9450 CFM. If I want to convert this CFM to liters per second, I will get 4459 liters per second. That's around 4460 liters per second. So move back to our catalog. Over here we got 4026 liter per second and 4598 liters per second. So we'll go for the higher side, will not go for the lower side. As you see that CFM liter per second we got is 4460, and over here we got 4598 liters per second. So this one is closer, so it's like this one 4598. So for this liters per second we got height of machine is 1.4 meter, that is 1400 mm, and width is 1900 mm, that is 1.9 meter. And as I told you, E is representing the whole length of this machine. So if we scroll down over here, this is the E, and how much we got over here is 3.9 meter. So this is our AHU dimensions. Length is 3.9 meter, width is 1.9 meter, and height is 1.4 meter. So move back over here. As you can see, AHU which we already selected from the approved supply data sheet for our calculated CFM of 9450 CFM. So width we got 1.4, height we got 1.9, and length we got 3.9 from the supply data sheet. So if we will add 1.5 meter in all dimensions of air handling unit, we will get the room size for this air handling unit. As you can see that I have added 1.5 meter in the width, and 1.5 meter in the height, and 1.5 meter in the length. So total AHU room size will be 2.9 meter is the width, 3.4 meter is the height, and 5.4 meter is the length. So this is how you can do AHU room sizing. I hope you guys learned something from this video. Please like, comment, share, and don't forget to subscribe my channel. Thanks. Hello guys, this is Syed Muhammad Abbas. I'm here with another video. In this video I will tell you guys how you can calculate duct size using a duct sizer program. So there I have opened a duct sizer program provided by the MEP. So for the duct sizing, you must give this input like flow rate and the head loss in order to get your duct size. So for example, from the heat load calculation, I have calculated CFM 600, like 600 CFM for the particular room, and I want to calculate what will the duct size that is coming out from the machine. So for this purpose of 600 CFM from the supply data sheets, let's say we have selected a ceiling ducted fan coil unit FCU. So if we will go and give our CFM of 600 over there, and we move to the head loss of second input, just keep in mind that for the head loss for the fan coil unit, it should be less than equal to 0.05 inches of water column per 100 feet. So this is your design value for the head loss. Head loss should not exceed 0.05 inches of water column per 100 feet, so that you will not get noise issues in your duct. Okay, we give this input of head loss 0.05 inches of water column per 100 feet. Now let's move to this duct size, and if we'll say 1 over here, and it will give the value for the other. For example, this is the width and this is the height. If I will change this one to 10, let's say 10 is the width and 15 is the height. So one thing you need to remember, that for the duct size you always need to get even numbers in the duct size. You will never see the odd number in the duct size like 13 inches by 15 inches or 9 inches by 15 inches, because this is a standard. So you always have to use even numbers in the duct. And second thing you have to keep in mind, aspect ratio during duct sizing. What is the aspect ratio? Aspect ratio is basically width to the height of the duct. And what is the best aspect ratio? Best aspect ratio is 1:1. Let's say our duct width is 400 and duct height is 250. So I told you aspect ratio is width to the height of the duct. So width is 400, height is 250. Let's say 400 divided by 250. So what's the aspect ratio? 1.6. So that's not bad, that's good. And what is the maximum allowable aspect ratio? Maximum allowable aspect ratio is 4:1. Don't exceed this more than 4, because if you will exceed more than if you exceed 4, then what will happen? You will get noise issues and more friction losses inside your duct. So maximum allowable aspect ratio is 4:1. So let's move and change this size to 12. As you can see, 12 by 12 we are getting the 1:1 aspect ratio. But one thing more we need to see over here, this is the calculated head loss, that is 0.05 inches of water column per 100 feet. And what is our specified? 0.05. So just keep in mind, this calculated head loss should be less than our specified head loss. So we still need to change the duct size over here. So what we will do, we'll change this to 14. Let's say 14 by 10. 0.05 is still more than this, so we'll change this to 16 by 9. So we don't want an odd number, as I told you before. Standard we have to give even number. So let's change this one to 10 inches. So this is the 600 105. Let's change this one to 10. So as you can see, the head loss calculated over here is 0.04, that is less than our specified head loss, 0.05 inches of water column per 100 feet. So this duct size is perfect to use over there. So what would be 16 inches by 10 inches? 16 inches, that is 400 mm, and 10 inches is 250 mm. So what would be the aspect ratio in that case? 400 divided by 250, that is 1.6. So aspect ratio is good, no problem. But sometimes you have to play with this aspect ratio because of the ceiling height issues. Sometimes ceiling height is very less. For let's say the ceiling height is 500 mm. So you will keep your duct height maybe restricted to 200 mm or 250 mm, because you need to give space for the other services to pass through. Like if any sprinkler pipe is passing over there or any chill water pipe passing over there, you need to give space to that service too. So, and from here you can change the units too, from metric to IPS units. So this is how you have to you can calculate duct size using a duct sizer program. I hope you guys like this video. Please like, comment, share, and don't forget to subscribe my channel. Thanks. Bye bye. Hello guys, it's Sayyid Muhammad Waqas. I'm here back with another video. In this video I will tell you guys how you can calculate this diffuser size, and you can select diffuser from the supply data sheets. So let's start. Let's take an example of this FCU 3FC L1. As you can see that we have got 3 diffusers over here, 3 supply and 3 return, 3 supply and then 3 return, 2, and this is a third return. So I will tell you how you have got 9 by 9 inches for that diffuser. As you can see, the machine CFM is about 199 multiplied by 3, it's 597 CFM. So if you want to check the size of the diffuser for 199 CFM, because machine CFM is 597 and 597 divided by 3 we got 199. So we have got 3 supply return diffusers 9 by 9 inches, 199 CFM each. So this is the formula we are going to use to calculate this diffuser or air terminal size. What the CFM we got over here is 199. So CFM divided by 400 multiplied by 144, and if you will take the square root of this one, you will get the diffuser size in inches. So how much we got over here is 8.46 inches. And if you know the standard size for the industry, it's 6 inches, 9 inches, 12 inches, and 15 by 15 inches, 18 by 18 inches, like this. So the diffuser which we can use over here is in between 6 inches and 9 inches. If you will go for 6 inches, it will be undersized. So we'll go for the higher side, so 8.5 inches. So we'll go for 9 inches. So this is how this diffuser size is coming. So 8.46 inches we are going to use, 9 inches, 9 by 9 inches supply return diffuser we are going to use over here. So let's move to another FCU to do the same exercise once again. As you can see that here we use 5 diffusers, 179 CFM each, 9 by 9 inches. So let's check this one also. CFM divided by 400 multiplied by 144 and take a square root of this one, we got 8.02 inches. As I told you, standard size is 6 inches by 6 inches, 9 inches by 9 inches. So we'll go for 9 inches by 9 inches for this one. So as you can see that we have used 9 inches by 9 inches over here. So let's move to the supply data sheet, how you can select diffuser from the supply data sheet. As you know, the different type of diffusers we can use: ceiling diffusers, 1-way, 2-way, 3-way, or perforated ceiling diffusers like this, and different decorative type ceiling diffusers we can use. As you can see that this supply air ceiling diffuser 4-way is here, and this is the size in mm. 9 inches equivalent to about 225 by 225. So we'll go over here and let me zoom this one, and as you can see that this is the velocity in meters per second, this is the flow rate in meters per second, this is the velocity in meter per second, this is the pressure drop in the pascals, and this NC is the noise criteria in decibels. So we will have to go for 225 by 225, and we know that's flow rate for this one. If we want to convert this, as you know in the drawing, how much it says 199 CFM. So let's convert 199 CFM to liters per second. It will be 94 liters per second around. So if we'll go over there for 225, the 94 liters per second, it will be in between 92 and 104. So this is how you can select diffuser from supply data sheet, and noise criteria will be, if you will go for it will be less than 15 decibels. So between 92 and 104 it will come somewhere here. So you can also get the noise criteria in decibels, and you can also get the pressure drop in a pascals in between 9 and 11. It will be like 10 pascals. So it will also be helpful for you to calculate the fan ESP later on. So this is how you can do the diffuser sizing, and you can select diffusers from supply data sheet. I hope you guys learned something from this video. Please like, comment, share, and don't forget to subscribe my channel. Thanks. Hello guys, this is Saeed Mohammad Waqas. The topic which I am going to discuss today is related to the air distribution system design, that is grill sizing and selection. If you have seen my previous video regarding air distribution system design, in which I have explained about the air diffuser sizing and selection, so in this video I'm going to talk about the grill sizing and selection. So as you can see here, I have a spreadsheet over here which I'm gonna use for this purpose, and these are the tables for flat ceiling wall outlets which I'm gonna use, and this is for the beam ceiling. So let's start. So let's say we have a space. This is the space, and this is the small store in here. As you can see, the dimension of the store, length is 32 feet and width is 23 feet as mentioned in here, and the height of the store is, ceiling height is 16 feet. So the next thing we have to check here is the load equally distributed. So the load in this store is equally distributed. What does it mean, equally distributed? Equally distributed means there is no source of heat coming from the outside, or there is no extra source of heat inside the room, because sometimes you have a door that is frequently open. So in that case you have some outside air entering inside the room, and load will not equally distribute, or you have some equipment inside, the extra equipment inside the store. So in that case you have load that is not equally distributed, but in our case we have a load that is equally distributed. Now the ceiling type which we set over here, the ceiling is the flat ceiling, because we have two types of table. One is for the flat ceiling and other is for the beamed ceiling. So we have ceiling, flat ceiling, and the air quantity, dehumidified air quantity, which we have calculated for this store. So you know that how to calculate the dehumidified air quantity. I have explained in my previous videos. Like you can use HAP software or E20 spreadsheet to calculate the dehumidified air quantity. So the dehumidified air quantity which we calculated for this space is 2000 CFM. Now the next thing is the temperature difference. We have to calculate the temperature difference which is necessary for the grill sizing. So temperature difference, how we will calculate, that is room temperature minus supply air temperature. Room temperature which we maintain inside the store is 75, and the supply air from the machine is 55. So if we get the difference, temperature difference will be 75 minus 25, that is 20 degrees Fahrenheit. So next important thing is recommended velocity. How much is the recommended velocity for this space? Because each application has their own recommended velocities. So you can see table 20, recommended outlet velocities, you can see it here for the residence apartments, church, hotel bedroom. So in our case we have a store. We said that store is the application which we have used in here. So for the store upper floor, the recommended velocity is 1500 fpm. So we have used recommended velocity 1500 fpm based on table 20. So now important thing is we have to calculate the number of grills, how many grills required to place in this store, and what will be the size of each grill and each grill air quantity. So this is what we have to calculate. So before, and this is the interpolation tables I'm gonna use as well. So before proceeding towards the grill sizing, I want to talk about the channel membership. If you guys can join the channel membership, you can get access to different perks. So all you need to do is just click this join button. So there are different levels you can see here: MEP Excel sheet, softwares, career book, plumbing design books, and complete MEP material. So you can select whatever material you need. So let's say if you select this MEP drawings career book, there are 3 perks given in this one. You can click this about more perks and you can see the details, what material you will get in this perk. So if you want to see the details of the spreadsheets and everything, so you can see in here. So there are total 25 spreadsheets, as you can see in here, which are available. And list of the softwares, you can just send an email on this email address mentioned below, sayedmohammadw@gmail.com. So even after taking the membership, you can send an email on this address to get access to the required material. So let's move back to our spreadsheet. So there are 2 important things that needs to be calculated for grill sizing and selection. That is minimum blow and the K factor. So first we will calculate the minimum blow. So how do we get the minimum blow? So basic rule for the minimum blow is 75% of the room width is your minimum blow. So in our, for this equally distributed load condition, so you must have equally distributed load condition, then you can use this rule, that is 3/4, that's 75% of the room width. If you have not equally distributed load, then you can take the maximum blow, that is equal to room width, 1 times of the room width. So in our case, the heat load is equally distributed, so we have to take 75% of the room width as a minimum blow. So you can see the width is 23. So 23% if 75% of 23 will be 17.3 feet. So minimum blow in our case is 17.3 feet. Now the second thing we have to calculate here is the K factor, that is air movement factor. How do you get the air movement factor? By using this formula: dehumidified air quantity divided by air outlet opposite wall area. So dehumidified air quantity, we know that that is 2000 CFM, and the air outlet wall opposite area. So we are going to place the outlets on this wall, 32 feet, and the height is 16 feet. So opposite wall area is also the same, 32 feet is the length and height is 16 feet. So if you put the values in here, you can get the K movement factor, that is 3.91 CFM per square feet. So now you know the minimum blow and the K factor values. Now you can easily check the grill size and how many grills needed and what is the CFM for each grill. So let's go to the table and select the grill. So before do the grill selection on this table, I just want to know you how to read this table. So on the top you can see the velocities, then this is for the flat ceiling, 250, 375, 500 and 750 fpm. And here you can see the grill sizes. You can see 30/4, 8/6, 16/6, 24/6, 30/6. These are grill sizes. And this is the air quantity column you can see in CFM, and this is the blow column which we already calculated, and this is the temperature difference which I mentioned earlier, that is room temperature minus supply air temperature. And this is the minimum ceiling height you can see here. So all these are same, and on the bottom of the table you can see the K factor. This is the range of the K factor, that is 8.7 to 29, 5.7 to 19. Similarly in this table you can see that this is the range, that is 1.4 is the minimum and the maximum blow is 4.8. Minimum blow is 2.2, maximum is 7.2. So how much is the blow we have calculated? That is 17.3 feet is the blow which we have calculated, and the K movement factor is 3.91. So let's check the K movement factor first and then the blow. K movement factor is 3.91. 3.91 is falling in which range? So you can see that 3.91 is falling in this range, minimum and the maximum below, that is 2.9 and 9.6. so 3.91 is falling in this range. So you can see here, and the below, if you check here, this is the below column. Below, if you check here, is 17, 34, 33. So we will select the below now. This is 17, this is 17, and this is 18. So let's say if we check the below is 17 here, and calculated below is 17.3. so 17 below here, and if you see the grill size is 24 by 6 inches, and the CFM is 486 CFM. 486 CFM. So since this is not the exact blow and the CFM, so what we do, we will use the interpolation formula. So 17th blow here, and if you move to the right side and you see 24 by 6 inches grill with 648 CFM, having a blow of minimum blow is 24 in here, you can see 24, and at 486 blow is 17. So our blow is 17.3. so just interpolate the table and get the exact value of the CFM. So blow is 17, and the calculated blow is 17.3, and if you see here at 648 CFM, blow is 24. Now we have to check the flow. How much is the flow at 17.3 blow? So 17 feet blow, how much is the flow? At 17 feet, how much is the flow? 486 CFM. 486 CFM. So this we need to calculate. And at 24, how much is the flow? At 24 blow, how much is the CFM? 648 for the same grill size. 648. So how much is the flow calculated at 17 point? How much is the flow calculated at 17.3 feet blow? That is 493 CFM. So this is the minimum blow which we use in here. That means we can select blow not less than 17.3 feet. So our total flow is 2000 CFM. Right. So 2000 CFM divided by 493. Sorry. 2000 divided by 493. So that means 4 grills we need to place. 4 grills we need to place. Even if we change this to 17.5, let's change it to 17.5, and the flow is 498, that is almost 500 CFM. So 500 CFM cross 4 grills, that means we need to place 4 grills, each with a CFM of 500. So 4 grills we need to place. Size of each grill, what we said here, size of each grill will be 24 by 6 inches. This is the size of the grill we selected, 24 inches by 6 inches. And the CFM of each grill, since we said 4, so 2000 divided by 4 equal to 500 CFM each grill. So next thing is we have to verify the velocities as well, that it should be less than 1500 FPM. Obviously it is less than 1500 FPM. If you see, the here is 750 FPM, and the interpolation on this side is 1000 FPM. Let's check the exact velocity. So at this point we have 750 FPM, here we have 1000 FPM. 750, and here we have 1000, and the flow which we said that 486, and the other one is 648, this one, and the flow which we calculated here at this blow, is 500 CFM. So 500 CFM, how much is the velocity? So you can see the velocity of 752 fpm calculated here is less than our recommended velocity 1500 fpm. That means our selection is fine. Now the last thing which we have to check before proceeding towards the final selection of this grill is to check the ceiling height as well. So we know the blow is 17 and calculated is 17.3 or 17.5, it's okay, and the other one is 24. Now we need to check the minimum ceiling height should be less than this height, then our selection will be okay to check all these items. So at 17 feet, what is the minimum ceiling height? 17 feet blow. So you know that this is the minimum ceiling height, and minimum ceiling height we need to check at temperature difference of 20 degrees Fahrenheit, as I already mentioned in the beginning. Supply temperature, room temperature minus supply temperature, it is 20 degrees Fahrenheit. So we need to check this column. So 486 CFM with 17 feet below, what is the minimum ceiling height? That is 8.5 at 486 CFM. 8.5. We need to check the minimum ceiling height at 17.5 feet below. Now what is the minimum ceiling height at 24 feet below? So you can see in here again 20 degree Fahrenheit we need to follow temperature difference and check the ceiling height. At 24 by 6 grill size, 648 CFM, and 24 feet below, minimum ceiling height is 9.5 feet. You can see here 9.5. So by putting these values you get the exact minimum ceiling height required at 17.5 feet below. So this ceiling height of 8.57 is far less than 16 feet. So everything which we calculated here is in the range. So the selection of the grill, number of grills 4, and each size is 24 inches by 6 inches is satisfactory. So we can use 4 grills, each size 24 inches by 6 inches, having air quantity or CFM is 500 CFM. So this is how you can do the grill sizing, air distribution system sizing and selection. I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Saeed Muhammad Vikas. I'm back with another video. In this video I will discuss about Plenum Box Sizing. So before start calculation for Plenum Box Sizing, I want to tell you what is Plenum Box and why we need to install the Plenum Box and where we have to install the Plenum Box. So what is Plenum Box? Plenum Box is a wide but short length duct that is used to properly or uniformly distribute the air throughout the system. Also, why we need to install the Plenum Box? There are many reasons that we need to install the Plenum Box. First, to ensure the air is uniformly distributed throughout the system. Second, to reduce the velocity of discharging air. And third is also to reduce the hissing sound created by discharging air just by dropping the velocity pressure. And also this Plenum Box also facilitates the fresh and return air mixing when system is designed for the return air circulation. So now the question arises where we need to install the Plenum Box. We need to install this Plenum Box before air terminals, could be supply diffusers, or linear slotted air diffusers. So we need to install before this supply diffusers or linear slotted air diffusers. These plenum boxes need to be installed before them. Also we need to install these plenum boxes at the suction side, at the suction end of the air side equipments like air handling units and fan coil units for the return and the fresh air. Also at the discharge and or the mouth side of the air side equipments. So we need to install these plenum boxes to air side equipments, also at the suction side of the exhaust air fans. So let's start the calculation of the plenum box. So what's the size required for the air handling unit? So here you see the procedure. Over here we are going to use the simple equation, that is Q is equal to VA. Here Q is the flow rate, that is in cubic feet per minute, and V is the velocity, that is feet per minute, and A is the area of the plenum box, that is in square feet. So this simple equation we are going to use to size the plenum box. So as per AHU standard, the velocity required for the air handling unit plenum box sizing is 800 fpm, feet per minute. So we are going to use this velocity to size our plenum box. So let's say we have calculate the heat load, and according to our heat load the tonnage which we got is 8 TR. If you want to know how we have to calculate the heat load, you can check my tutorial number 16 and 17, in which I have explained how you can calculate the heat load using HAP software and E20 form. So we are going to use our rule of thumb here, that is 1 TR required 400 CFM. So we have a 8 TR system, so how much is the CFM we needed over here for 8 TR system? That is 8 into 400, that is 3200 CFM that we needed over here. So according to this equation, Q is equal to VA. Now we have flow rate 3200 CFM, and we know the velocity required for plenum box sizing of the air handling unit is 800 fpm. So as per this equation, Q is equal to VA, we know Q and we know V, so we can calculate the area by A is equal to Q divided by V. Q is the flow rate, that is 3200 CFM, and V is the velocity, that is 800. So 3200 divided by 800, we got the area 4 square feet. So area of the plenum box that needed over here is 4 square feet. So before moving to this equation number 2, the area of the plenum box, that is width into height, I'll show you one figure over here. This is the figure. So let's say this is the plenum box of the air handling unit. As you can see that this is the width, this is the height, and this is the depth of the plenum box, and this is the opening that will be connected to the air handling unit side, suction side. So this is the width, this is the height, and this is the depth. So we need to calculate these parameters, width, height and depth of the plenum box. So let's move back to our equation 2. So area of plenum box is given as width into height. So now we have to assume the height as per site condition. We need to assume the height. So let's say we have a space above ceiling and below slab is 2.5 feet or something. Let's suppose we have 2.5 feet space between the ceiling and the slab. So according to this, we need to assume the height of the plenum box. So let's say we are assuming the height of the plenum box is 1.6 feet. So this is the height we have assumed over here. So as we know the area of the plenum box, that's already calculated, 4 square feet, and height we assumed over here is 1.6 feet. So using equation 2, we know the width, we know the height, and we know the area. So we are going to calculate the width of plenum box, that is given as A by H. So width of the plenum box is area divided by height of plenum box. Area is 4 square feet and height is 1.6. So width of the plenum box is calculated as 2.5 feet, that is 4 divided by 1.6. So now we have width of plenum box, that is 2.5 feet, and we have height, that is 1.6 feet. Now we have to calculate this depth of this plenum box. So depth of the plenum box is given by this equation, that is 2.5 times d. Now what is d over here? D is basically a diameter of the fan blower of the air handling unit. So let's say we have a air handling unit of 3200 CFM with the diameter of the fan blower is 12 inches, and this in this formula d equal to 2.5 into 3, it could be 3 times d. So 2.5 to 3 you can use over here. So we are going to use 2.5 over here, and we assume that diameter of the fan blower is 12 inches. So by using this value in equation 3, so depth of the plenum box is 2.5 times 12, that is 30 inches. If you want to convert this in a feet, divide by 12 and you will get the depth of the plenum box 2.5 feet. So now we have calculated width, height and depth. So depth is 2.5 feet, width is 2.5 feet, and the height which we have assumed is 1.6 feet. So this is how we can do the plenum box sizing for air handling unit. So if you want to do the plenum box sizing for the fan coil unit FCU, so you can do that also. The only thing over here is velocity, that is limited to 500 feet per minute, 500 fpm. So the whole procedure is same except the velocity, that is 500 feet per minute. So by using this velocity 500 feet per minute, you can do the plenum box sizing for the fan coil units. So this is how you can do the plenum box sizing. So a plenum box we need to install for properly or uniformly distribution of the air throughout the system. So this is how you can do the plenum box sizing of the fan coil unit and air handling units. So if you want to do the plenum box sizing of supply diffusers or linear supply diffusers, you can do in the same way. The phase velocity required for supply diffusers or linear slot supply diffusers, it is 2.5 meters per second, that is equivalent to 500 feet per minute. So you can use the same procedure above as explained above here in order to do the plenum box sizing of supply diffusers and linear slotted diffusers. I hope you guys learned something from this video. Please like, share, subscribe, and don't forget to press the bell icon so that whenever I upload the new video you will be notified. Thank you. Bye bye. Hello guys, this is Syed Muhammad Waqas. I'm back with another video. In this video I will tell you guys about exhaust CFM calculation. So there I have a drawing in which I will show you for one of the toilet. As you can see that this toilet, its length is 200 centimeter and width about 130 centimeter. So it's 2 meter by 1.3 meter. This is the area of this toilet. So for exhaust CFM calculation, we know that the area of this toilet is 2 into 1.3. So it will be 2 into 1.3 2.6 square meters. So as per architectural drawing, we can see the height of the toilet wall is about 3 meters, so it's 3 meters. So in order to calculate the volume, that would be area into the height of the toilet. So as we know that area is 2.6 and height is 3. So 2.6 into 3 will get 7.8 cubic meter is the volume of that toilet. So in order to calculate the exhaust CFM, we have to use this formula, volume into air changes per hour divided by 60. But this volume, it should be in cubic feet. So in order to convert that volume into cubic feet from cubic meter, we need to multiply it by 35.28 conversion factor. So 7.8 into 35.28 will get 275.18 cubic feet. So as per AHU standard for toilet, pantry, kitchen, we are taking air changes per hour is about 8 to 12. So this ACH is basically air changes per hour. So as I told you about the from the AHU standard, toilet, pantry and the kitchen, it's about 8 to 12. So we are going to take air changes per hour over here is 10. So this is the volume which we have calculated above. So we have to use this volume over here, that is 275.18 into air changes per hour, that is 10 for the toilet divided by 60. So how much we will get into 10 divided by 60, that is 45.86 CFM. So this is the CFM, exhaust CFM required for 2.6 square meters area of the toilet. So if you have seen my previous videos regarding duct sizing calculation, I can show you over here again by using this duct sizer program. So the flow rate, you know that 45.86, we will use around 46 CFM, and head loss, as I told you, 0.06 inches of water column per 100 feet. If you have seen the previous videos, I have explained it over there. So as you can see that we have put this two parameters, flow rate and head loss. We can get the duct size over here. Let's say 6 by 8 by 3, no, 6 by 3, no, 4 by 6, yeah. If we change this one to 4, because we have to keep this in even numbers. So 6 by 4 inches is the good size for this duct, or if you go for round, it will be 4.9 inches. Oops, sorry, 46 CFM 136. So it will be around 5 inches. So 5 inches will be round out, will be round off, and it will get 6 inches. So you will use 6 inches over here for that much CFM. So this is how you can calculate the exhaust CFM for the toilets. In my next video, I will tell you guys about fresh air CFM calculation. For more videos, keep watching my channel and don't forget to subscribe. Bye bye. Hello guys, this is Saeed Mohammed Wakas. I'm back with another video. In this video, I will tell you guys how you can calculate GPM for fan coil unit or air handling unit. So let's start. They have open drawing. As you can see that there I have a schedule for fan coil units. This is a schedule provided by carrier company. So as you can see that this is the unit description, this is the area served by the unit, the type of the unit, quantity, model, total capacity in MVH, airflow in CFM, water flow in GPM, ESP, that is external static pressure, motor power, and unit dimensions. So this is a summary or performance sheet for every block I have over here. This is for third floor and the fourth floor I'm showing you. So let me show you how we got this 2.43 GPM for this FCU. So before showing that, I want to tell you something over here. If you can see, in a case of district cooling, you can see that we are normally maintaining delta T of 16 degrees, and by using this formula 1 TR is equal to 24 GPM divided by delta T, we got 1 TR is equal to 1.5 GPM in a case of district cooling. And in a case of chillers, we are normally maintaining 9 to 10 degrees. So in a case of chiller, we got how much 1 TR equal to 2.4 GPM. So let's move back to our drawing. Just keep this thing in our case. We are using water from district cooling, so we are going to use this formula 1 TR is equal to 1.5 GPM. Okay, as you can see that how much is the MBH over here for this machine, that is 19.47. So 19.47, if you divide this by 12, you will get the tonnage. So how much tonnage you got over here is 1.6225. As I told you, 1 TR is equal to 1.5 GPM in a case of district cooling. So this is the tonnage we got. Multiply this by 1.5, you will get GPM. So how much GPM we got? 2.43. As you can see that 2.43 is the GPM over here. So let's move to another FCU. This is another FCU with getting MBH of 49.32 MBH. So 49.32 MBH, 49.32 divided by 12, you got the tonnage. Multiply by 1.5, you will get the GPM. So how much GPM we got here? 6.165, that is 6.17. As you can see, 6.17 GPM over here. So in the same way you can do for air handling units and all of the FCUs over here in the same way. So this is how you can calculate a GPM for fan coil unit or air handling units. I hope you guys learned something from this video. Please like, comment, share, and don't forget to subscribe my channel. Thanks. Hello guys, this is Syed Muhammad Waqas. I'm back with another video. In this video I will tell you guys how to calculate the chill water pipe size. So let's start. But before starting, I want to show you something over here. I already explained this thing in the previous tutorial, but I will explain you again. In a case of district cooling, we are using 1 TR is equal to 1.5 GPM, and how this comes by using this formula. TR is equal to 24 GPM divided by delta T. So in a case of district cooling, we are normally maintaining delta T of 16. So if we are going to use delta T 16 over here in this formula, so we will get 1 TR is equal to 1.5 GPM. That's the case of district cooling. So same formula we are using over here. If we are using chillers, so delta T will be 9 to 10 degrees. So by using this 10 degrees over here in this formula, 24 GPM divided by 10, you will get 1 TR is equal to 2.4 GPM in a case of chillers. So let's start this pipe sizing over here. There I have an HVAC drawing. I'm going to do the pipe sizing for few pipe segments over here. So before doing that, I will show you a schedule over here for all the FCUs. As you can see that this is total capacity in MBH, airflow in CFM, water flow GPM, fan ESP in Pascals, and motor power unit dimension, everything. So let's start with this machine, corridor machine. As you can see that its serial number is 3FBL2. It's a corridor machine, ducted unit, and its MBH is 29.39, and CFM is 1049, and GPM is 3.67. So let me show you how this GPM comes out before start the pipe sizing. As you can see that 29.39 MBH is the heat load for this corridor machine of 3FBL2. So 29.39 MBH is the heat load. If we divide it by 12, we will get the tonnage. So 2.44 ton for this machine. So if we are going to calculate this GPM, how this comes out, as I already explained you over here, we are using a district cooling system over here. So how much GPM is required for 1 TR? It is 1.5 GPM is required for 1 TR, and we have a machine of 2.449 TR. So we need to multiply this tonnage with 1.5, so we'll get the GPM. As you can see that the GPM is required for this machine is 3.67 GPM. You can see that 3.67 GPM. This is how you can calculate the GPM for each and every machine. In the same way you can do for other machines like a guest room 19 with 19.47 GPM. 19.47 is the MBH load. Divide by 12, you will get the tonnage, and if you multiply it with 1.5, you will get the GPM. That is 2.43 GPM is required for this machine. Over here you can see that 2.43 GPM. So let's move to the pipe sizing now. So I'm going to do for this corridor machine 3FBL2 corridor machine. Over here you can see that this machine is 3FBL2 corridor machine, the one I was talking in the schedule. So you can see that we already calculated the GPM for this machine, and the GPM required is 3.7 GPM for our calculated heat load. GPM required is 3.7 for this machine by district cooling system. So now we are going to see how this 3 by 4 inch pipe size is coming for this 3.7 GPM. So let me open this pipe sizer tool. So I have opened this pipe sizer. As you can see that we are using a black schedule 40 pipe over here. So we have already selected over here, and the fluid is at 50 degrees Fahrenheit water. So now we are going to check the pipe size required for 3.7 GPM. So if you can see that, but before starting this, I want to show you one thing, a design document, because we are going to do this as per our design document. So let me open this design document, general mechanical notes. These are the general mechanical notes. You have to open this and see what is the pipe sizing criteria mentioned over here. As you can see that for pipe sizes up to 50 mm, velocity of the water should not exceed 1.22 meters per second, and pressure drop not exceed 600 pascals per meter. And for pipe sizes 50 mm up to 200 mm, pressure drop should not exceed 400 pascals per meter, and velocity not to exceed 2.4 meters per second. So this is our limitation for do the water pipe sizing. We have seen this on our general mechanical notes. So we are going to do the pipe sizing as per this limitation. So whenever you are doing the pipe sizing, you have to keep this thing in mind. So let's move to our drawing. As you know, this machine has 3.7 GPM. So let's move to this pipe sizer. If we are using this half inches pipe size, and with the we are getting 1.4 US GPM over here. So if we are using our GPM, that is 3.7 GPM. As you can see, the fluid velocity is 3.91 feet per second. This is the calculated fluid velocity, and the head loss is 15 feet per 100 feet. As I already told you, our design document from the general mechanical note, it says if pipe size is less than 50 mm, velocity should not exceed 1.22 meter per second. If you convert this velocity in a feet per second, it will be 4 feet per second, and a pressure drop will be 4 feet per 100 feet. So if we move over there, fluid velocity is almost in the border, that is 3.91. Actually it is less than 4 feet, but head loss is too much, that is 15.039. That is not acceptable. So we are going to check 3-4 inch pipe size. If we use 3-4 inch pipe size and our GPM is 3.7, so we are going to use 3.7 GPM over here. As you can see, the fluid velocity now 2.23 feet per second. That is less than our specified fluid velocity, that is 4 feet per second from our this general mechanical notes. So fluid velocity is okay. Now move to the head loss. If we go for head loss, it is 3.757 feet per 100 feet. As I told you from design document, it is, if you convert this, it will be 4 feet per 100 feet. So head loss should be less than 4 feet per 100 feet. As you can see that this is 3.757 feet per 100 feet. So the pipe size which we have selected, 3-4 inches for 3.7 GPM, it is in the safe range. So we are good to go with 3-4 inch pipe size. You can also use this friction loss chart for closed piping system to check your friction loss. Let's say our GPM was 3.7 GPM over here. This is the flow rate, this is the head loss, and these are the pipe sizes over here. So our flow rate is 3.7 GPM, that will be below 4 GPM over here. And if we move to 3-4 inch pipe size, if this 3.7 GPM cross over here 3-4 inch pipe size, it will fall somewhere, it will fall over here just before 4, that may be 3.8 feet per 100 feet. So as you can see that we already checked over here, and the pipe size head loss is 3.757 feet per 100 feet, that is less than 4 feet per 100 feet. So we can use this pipe size 3-4 inch for 3.7 GPM. So let me show you one more over here. Okay, let's do a pipe sizing for these two pipe segments with the 22.9 GPM. Okay, go to the pipe sizer. If I select 1 inch 1/4 pipe size, and I am going to use 22.9 GPM, you can see that fluid velocity is 4.91 feet per second. That is more than 4 feet per second. 4 feet per second is our design limit. So, and also head loss 8.33 feet per 100 feet, that is more than 4 feet per 100 feet. So we are not going to select this pipe size for 22.9 GPM. Let's move to the higher side, that is 1.5 inches, and give our GPM 22.9 GPM. As you can see that fluid velocity is 3.61 feet per second and head loss is 3.874 feet per 100 feet. You can see that fluid velocity 3.61 is less than our specified fluid velocity, that is 4 feet per second, and head loss of 3.874 per 100 feet is less than our 4 feet per 100 feet. So we are good to go with this pipe size of 1.5 inches for 22.9 GPM. So if in the same way you can do the pipe sizing for other pipe segments, and you can use pipe sizer tool to calculate the pipe size. I hope you guys like this video and you guys learned something from this video. Please like, comment, share, and don't forget to subscribe my channel for more videos. Keep watching my channel. Bye bye. Hello guys, this is Sayyid Mohammad Waqas. I'm back with another video. In this video I will tell you guys about the Stairwell Pressurization Calculation or Stairwell Pressurization System Design. So there I have prepared an Excel sheet, as you can see over there. So by using this Excel sheet I will let you know guys how you can design stairwell system. But before start designing, you need to understand what is stairwell pressurization system. So stairwell pressurization system is basically intended to prevent smoke leakage through doors into the stairs by injecting a clean air into the stairwell and the purpose is to provide the highest pressure in this stairwell area with respect to this adjacent space, so that we can provide a safe escape path to occupants and for firefighters, because in a case of fire, this area will be positively pressurized. There will be air sucked from the fans and it will be thrown into that area, and this area will be positively pressurized with respect to that area. So this area needs to be positively pressurized all the time in case of fire, so that no smoke will enter from these doors into the stairwell. So let's start the designing of the system. So first of all, you need to understand the design limitations. There I have prepared the design limitations that you need to understand. So stairwell pressurization system basically have the following design criteria. Delta P, minimum pressure difference between the staircase and adjacent space. As per NEP standard, it is 0.18 inches of water gauge, and the maximum pressure between the stairwell and the adjacent space, it should be 0.37 inches of water gauge. So this is the minimum pressure this pressure difference and the maximum pressure difference with respect to the adjacent space. And the air, this is as per IBC, that is International Building Codes, and NEP standard 92A. So, and the airflow velocity should not exceed 200 fpm as per International Building Code. When the doors are open, airflow velocity should not exceed 200 fpm, and the maximum force required to open any door handle shall not exceed 30 lbs or 133 newton. So we need to keep these limitations in mind while designing the stairwell pressurization system. So there you can see the tables and formulas over here, which we are going to use to design the stairwell pressurization system. So let's take an example. So as you can see that this is the stairwell shown in this drawing. So there we have an office stairwell that runs 5 floors. Each floor has height of 17 feet. So total floor we have 5, and each floor has a height of 17 feet, and the width is 28 feet and length is 48 feet. So width is 28 feet and length is 48 feet. And we have as you can see there, two single leaf doors, that is A2 and A3, and a one double leaf door that is 6 feet by 7 feet. This is a double leaf door, and single leaf door are 3 by 7 feet. So assume that the doors are open and maximum differential pressure to maintain between the stairwell and the office is, this is the office space and this is the stairwell. So maximum pressure difference is 0.037, as I already told you over here. As per International Building Code IBC, maximum pressure difference between staircase and office space is 0.37, that is adjacent space is 0.37 inches of water gauge. So this is the formula which we are going to use to calculate the volumetric flow rate, that is Q1 plus Q2 plus Q3. So what is Q1, Q2 and Q3? Q1 is 2610 into A into leakage area. A is the basically leakage area of the building construction. It is the leakage area due to the walls and due to the floor. So this is the leakage area of the building construction, and delta P is the pressure difference which we have to use over here, as we already know that this is 0.037. So we have to use table 4 for the leakage area, and same formula we have over here, but this is due to the door, this is due to the building construction material, and this is due to the doors. When the doors are closed, then we need to calculate the flow rate through this equation, but table will be table 5 we are going to use. So this is table, this value will get by using table 4, and this value will get by using table 5. And Q3 is equal to V into A. This is simple formula. Q is equal to VA. Here A is the flow area in square feet, and delta P is the pressure difference in inches of water gauge, and V is the air velocity across open door. So as I already told you about, this velocity shall not exceed 200 fpm as per International Building Code IBC. This is the velocity we are going to use in this Q3. So let's move to our calculation. So first of all, we need to calculate the leakage area due to the building construction, that is due to the wall and due to the floor, that is Q1. And then we have to calculate the leakage area due to the closed doors. When the doors are closed, then we need to calculate the leakage area. So that is Q2, this is Q1, this is Q2, and Q3 will calculate later over. So first we'll calculate Q1 leakage area. First of all, we know that the height of the floor is that height of each floor is 17 feet. We have total 5 floors and length is 48, width is 28. So first we will calculate the area. First we calculate the perimeter over here, perimeter of the walls. As you can see that this side is 48, this is 28, this 48 and this is 28. So perimeter of this stairwell area will be 48 plus 28 plus 48 plus 28. So perimeter of the stairwell walls will be 28 plus 48, 2 times, that is 152 feet. And we know that the height of each floor is 17 feet. So area will be 152 into 17, that is 2584 square feet. But we need to subtract the door area from the wall because we are going to calculate separately for the doors. So we need to subtract the door area. Door area is 84 square feet. How did we get this 84 square feet? Since we have 3 doors here, this is a double leaf, this is single leaf. 2 single leaf, that is 3 by 7, 21 square feet, 21 square feet. And the double leaf door is 6 by 7, that is 42 square feet. So 42 plus 42, that is 84. So door area will be 84. So 2584 minus 84, the door area, we will get 2500 square feet wall area. So now we have to get the average leakage ratio, that is AL by A. How we will get this value? This value we get from the table 4. As you can see that this table is basically from NAFA 92 2012 book, table 4.6.1. Since the construction of our wall or the whole building, it's average construction. You can see that tight construction we need to use this value, average is this, loose is this. This is for exterior walls, this is for stairwell walls, this is for elevator shafts, and this is for the floors. So first we are going to calculate for the walls. So stairwell walls, average construction area ratio is 0.11 into 10 power minus 3. So same we have used over here, that is average ratio 0.11 into 10 power minus 3. So total leakage area will be calculated as, you need to multiply this average leakage ratio with the area of the wall which we calculated over here for the stairwell walls. So 0.11 into 10 power minus 3 into 2500 square feet. So total leakage area will be 0.28 square feet of the wall, stairwell walls. Now second, for the floor area, we know that it's 28 by 48. So floor area is 1344 square feet, and the average leakage ratio for the floor from table 4. So this is for the floors, and we know that this is average construction. So 0.52 into 10 power minus 4. So 0.52 into 10 power minus 4. So you just need to multiply area with this average leakage ratio. You will get the total leakage area due to the floor, that is 0.07 square feet. Now Q1 is done. Now we proceed for Q2, that is leakage area leakage when the doors are closed, that is Q2. Since we know that height of single double leaf door is 7 and width is 6, and 2 single leaf doors we have, that is height 7 and width 3. So area calculations, this 33 is the, you can get this from table 5 here. 33 is basically the crack length. So this 33 feet is the crack length for the double leaf door from the table 5. So this is from the AHU Handbook. You can find these values in the AHU Handbook. There are a lot of doors are given in there. So according to the door size, you have to get the crack length, and then you have to use it in your calculations. So single leaf door crack length is 20 and the gap is 0.006. For double leaf door size 6x7, crack length is 33 feet and the gap is 0.006. So this is the crack length for double leaf door 33 and the gap is 0.006, and crack length for single leaf door, that is 20 and the gap is 0.006. We got these values from table 4 over here, table 5 over here. So how to get the leakage area when the doors are closed? You just need to multiply this crack length with the gap. So crack length into gap you will get for double leaf door, that is 0.20, and then for single leaf door, that is 20 crack length into gap 0.06, that will be 0.12. Since we have two doors over here, that is A2 and A3, two single leaf doors, so that's why we multiplied this with 2 to get the total leakage area when the doors are closed. So total leakage area, so what is the total leakage area? It will be the sum of all of these, that is due to the wall, floor, door. It will be 0.78 square feet. 0.78 square feet. So next, we already calculated this value area. So it, as I told you, this is Q1 and this is Q2, and this is the formula which we are going to use for Q1 and Q2. We already calculated, so we are going to sum this up. So we are going to use this same formula, 2610 into A, that is the total leakage area, into delta P power 1/2. So this is the constant value 2610, and the area we already calculated 0.78 over here, and delta P is the maximum pressure difference. As per International Building Code IBC, it is given as 0.37. So we are going to use this value. So after using these values, Q is calculated as 1243 CFM. This is for one floor only. So we know that we have 5 floors in this building. So total volumetric flow rate will be 5 into 1243, that is 6215 CFM. So total volumetric flow rate is 6215. But now we have to calculate Q3 also. Only then we will be able to calculate the total volumetric flow rate. So Q3 is given by area into V max. So A is the area of the door and the effective open area. So we know that we have 3 doors. A1 is the double leaf, A2 and A3 are the single leaf doors. So A1 is the double leaf, 7 into 6 feet, that is 42 square feet, and A2 and A3, that is 3 by 7, that is 21 square feet. So for doors situated in parallel around the pressurized space, the effective leakage area is given by this formula. Basically we have two formulas. When the doors are situated in parallel, we use this formula. When the doors are situated in series, then we use another formula. So I will show you over here. As you can see over here, we have two scenarios over here. First, leakage path in series, leakage path in parallel. So this is positively pressurized with respect to these adjacent spaces. So if it is positively pressurized, that means the air will flow from high pressure side to the low pressure side. So air will flow from here to here like this. So in order to, so it will not let any smoke to enter into the stairwell area. So this is the path in series. So if you have a situation like this, if your flow is in series, then you have to use this formula. A effective area is equal to 1 by A1 square plus 1 by A2 square plus 1 by A3 square. So it depends on number of doors. According to that you have to use the formula. if you have leakage path in series. So this one, as you can see, that stairwell is positively pressurized. Air will flow from high pressure side to the low pressure sides, that is A2, A3, A4, A3. So it will continuously pressurize this area and it will not let any smoke enter into that area, lift lobby and stairwell area. So as you can see that this is the path, leakage path in the parallel, and we have the same situation or same scenario in our case. So we are going to use this leakage path in parallel. So leakage path in parallel, you have to use this formula, that is effective area is equal to A1 plus A2 plus A3 plus A4. So since we have this condition, that's leakage path in parallel, so we are going to use this formula, A equal to A1 plus A2 plus A3. So that's why we have used this formula, A equal to A1 plus A2 plus A3. So effective open area across doors is 84 square feet, that is the sum of these three doors area. Now the flow rate is given by Q3 is equal to V max into AE, that is Q is equal to VA formula. It's very simple and basic formula. So as I already explained you this thing in the beginning, that maximum velocity that needs to be considered when the door is open is 200 fpm. It should not exceed 200 fpm as per International Building Code section 909.7.2. so we are going to use Vmax 200. So we know that velocity, we know the area, so Q flow rate to the open door is given as Q is equal to V into A. So V we have here is 200 fpm and the area is 84. So total flow rate to the open doors will be 16,800 CFM. So now we will get the total air for pressurization system, that is leakage to the gaps in the building construction plus leakage around the door gaps plus leakage through the open doors, that is Q1 plus Q2 plus Q3. So we already calculate Q1 plus Q2, that is 6,215 and Q3 is 16,800. So total flow rate, volumetric flow rate required for stairwell pressurization system is 23,000 CFM. So this is the total flow rate we required for 5 floors. If we want to calculate for each floor how much is required, 23,015 divided by 5 floors, so 4,600 is the flow rate required for each floor. 4,603 CFM is required for each floor. So if you want to calculate the so we know that the volumetric flow rate for each floor is 4,603 CFM. So if you want to calculate the grill size, you can also calculate the grill size, because we need to place the grill on each stairwell area. Each stairwell area we will have a grill over here through which air will be thrown into that stairwell area to keep it positively pressurized. So we will have some grill over here. So fan will be at the top of the roof through which air will be induced or injected into that area with the help of a grill over here. We will have a grill over here like a supply grill. So if you want to do the sizing of this grill also, you can do that too. So velocity which we normally consider for grill sizing is 500 to 600 fpm. 500 to 600 fpm. So by using the same formula, Q is equal to VA. If you want to calculate the area is equal to Q divided by V. So Q we already know that for each floor, that is 4,603 divided by velocity we are going to consider is 600. So total area is 7.67 square feet. Grill area is 7.67 square feet, will be approximately 8 square feet. So 8 square feet, that means it will be like we can say that 4 feet by 2 feet, or 4 feet means 48 inches by 24 inches.
So the grill size which we need to place on each floor will be 48 inches by 24 inches size. So this is how you have to design your stairwell pressurization system. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Thank you, and don't forget to press the bell icon.
Hello guys, this is Saeed Mohammad Waqas. Today I am going to explain you guys the duct traverse topic, like how to perform the duct traverse to get the accurate velocity reading and then calculate the actual volume flow rate across the duct to compare it with the design airflow rate, and this we are doing for air balancing purpose. So let's start. As you can see that we have this duct, and if we want to perform a traverse on this duct, we need to make holes to get the flow rate, and the instrument which we are going to use to perform this traverse is the velocity probe or pitted tube. When you are using the pitted tube, it will give you the velocity pressure. Then the individual velocity pressure must be calculated for each velocity pressure reading and then averaged together to measure the velocity pressure and then convert it into velocity in feet per minute. So as you can see that this is the duct which we have, and we have inserted the pitted tube inside to get the velocity pressure. As you can see that pitted tube basically measures the total pressure and the static pressure to determine the velocity pressure. So you can see that this is the manometer, and the positive port of the manometer is connected to the total pressure port. This is our total pressure, and this one is connected to the positive pressure port of this manometer, and the negative is connected to the static pressure. And when you insert the pitted tube inside, it basically senses the total and static pressure, and the manometer over here, and it measures the velocity pressure. That is the difference between total and static pressure. When you insert the pitted tube inside the duct, make sure that this tip must be pointed directly in, and it should be parallel to the airflow rate. This is the airflow rate and this is the pitted tube. Make sure that it is parallel with the airflow rate. If you put the pitted tube accurately, then velocity pressure indications will be at its maximum. So when you are using pitted tube inside the duct, you will get the velocity pressure reading on this manometer. Then you need to convert this velocity pressure reading into the velocity, and then using Q is equal to V, a formula, you can get the actual flow rate. And so this is the table which we are going to use for duct traverse of rectangular ducts. As you can see that this is the whole quantity required, and this is the interval C, interval B, and this A is representing as the duct dimension. That is 10 inches, 12 inches, 14 inches. And this table, the duct size is applicable if duct size is less than 48 inches. And for this table we need to refer to figure 1. This is the figure 1, and the interval which I have explained above, that is B and C, you can check from here in this figure. This is the dimension of the duct represented as A, as you can see over here. If we have 10 inches duct size, then A will be 10 inches. Then we need to check how much is the interval B and interval C, and how many holes required for duct traverse. 4 holes required, and B is 1.25 and C is 2.5. So the B is a distance from the inner wall of the duct to the center of the first hole, that is 1.25 for 10 inches duct, and then C is from center of first hole to the center of second hole, that is 2.5 for 10 inch duct size, and the whole quantity is 4, we already know. So we have 4 holes, 1, 2, 3, 4. So it depends on your duct dimension. If you have 30 inch duct size over there, then you need to make 5 holes. with the interval B and C as B as 3 inches and C as 6 inches. And this table is applicable if duct size is less than 48 inches. If you have a duct size more than 48 inches, you still need to make 8 holes to perform the duct travels. But the interval B and C, if you need to calculate the intervals, that is hole to hole distances, and from the inner wall to the first hole and then from inner wall to the last hole distance, you need to get these distances from this figure. So as I already explained you, we can use either velocity probe or the fitted tube to perform this duct traverse. If you perform duct traverse with the velocity probe, you can get directly the velocity, but if you perform this with the fitted tube, you will get the velocity pressure, and then you need to convert this velocity pressure into the velocity by using this formula. That is, velocity is equal to 1096.7 into square root of hv divided by d, where v is the velocity in the feet per minute and hv is the velocity pressure in inches of water from the measuring device, and the measuring device which we use in the fitted tube, that is manometer, and d is the density of the air in pounds per cubic feet. If we are using this velocity probe, we can get directly the velocity readings like over here. So let's take an example. We have 48 inches by 40 inch rectangular duct, and we need to perform a duct traverse on this duct to get the actual flow rate and compare it with the design flow rate. So if you go for 48 inch duct size by 40 inch duct size, so let's take one dimension of this duct is 48 inches and move back to our table over here. So as per ASHRAE and SMACNA standards, for 48 inches duct size, hole quantity is required is 8, and the interval B and C is required as 3 and 6 inches. So number of holes required are 8. And for the second dimension, that is 40 inches over here, number of holes required are 7, and interval B is required as 2.85 and interval C is 5.71 inches. You can refer to this figure to calculate the intervals, that is B and C, for 40 inches and 48 inches duct dimension. So since the number of holes required for 48 inch duct dimension is 8 and 40 inch duct dimension is 7, so we need to make a matrix of 8 by 7, that is 56 number of points. We need to make a matrix of 56 points. As you can see that this is the position from A to H. We have total 8 points, that is representing as 48 inch duct dimension, and it is from 1 to 7, that is representing the duct dimension of 40 inches. So this is how we have created 56 number of points, that is 8 by 7 matrix. If you have 42 inches by 30 inch duct size, then you need to make a matrix of 7 by 5. So since we have 48 inches, the example which we are considering right now is 48 inches by 40 inches. That's why we have created 56 number of points, or 8 by 7 matrix. So after creating the holes, we need to insert that fitted tube inside to get the velocity pressure reading at the manometer. Let's say this is 48 inch dimension and the other is 40 inch duct dimension, and we have 8 holes over here and the 7 holes on the other side. So we need to insert the fitted tube at the first point here that is called point A, and the other one is point 1. So if we put the pitted tube inside at point A1, we will get the velocity pressure reading at point A1, and then from A1 to next A2, then A3, then A4, then A5, then A6, and then A7. If we move to this point, this will be B point at 48 inch duct dimension. So we need to put that pitted tube inside at point B1. This is called B1. If you move inside more, it will be B2, then B3, then B4, and so on and so forth. We need to put the pitted tube one by one, and we need to get the velocity pressure readings at different points. So this is our matrix, and we need to put the reading whatever we got from pitted tube, but make sure that the reading which we got from pitted tube, it's in from the reading which we got from manometer, it will be in the velocity pressure. It will be the velocity pressure. So we need to convert this velocity pressure into the velocity by using this formula. So after using this formula, we will get the velocity in FPM. So let's say we got the velocity at point A1 is 885. This is just an example. You need to go to the site and you need to use this pitted tube to get the velocity pressure, and then you need to convert the velocity pressure into the velocity, and then you need to put that reading over here at point A1. So let's say at point B5 we got this reading over here, and then you need to write each and every reading over here, and after writing all the readings, you need to sum at the point 1 and point 2, 3, 4, 5, 6, 7. So this is the duct traverse for 48 inches by 40 inch duct. So the number of points which we have taken for the reading are total 56. That is 8 by 7, and total number of points are 656. So we need to write number of points, reading points, that is 56. And now we need to calculate the average velocity. So we need to write the average velocity over here. So first we need to sum up all of these velocities. So the velocity which we have over here is 7244, and other point is 7442.9 and 7464, then 7263 and 6889.75, and then 6594.48, then 6437. So total velocity is this much, but we need to calculate the average velocity. Since we have taken 56 points reading, so we need to divide this with 56. So 881 feet per minute is the average velocity. So this is the average velocity across 48 inches by 40 inch duct. So let's say in the drawing we have a design airflow rate is 11,700 CFM. Now we need to calculate the actual flow rate across this duct by using this duct traverse method. So by using this equation, Q is equal to VA. Here Q is the actual flow rate that we need to calculate, and V average is the velocity which we have already calculated over here, that is 881 feet per minute, and A is the area of the duct, and V average, it is in feet per minute. We already calculated above, that is 881 feet per minute, and A is the area of the duct. So as we know that it is 48 inches by 40 inch duct. I will convert this into feet. 48 inches in the feet, it will be 4 inches, and the other one will be 3.33 feet. So 4 feet by 3.33 feet. So how much area we will have? That is 3.33 multiply by 4, you will get 13.33 square feet area. So now we know the average velocity across 48 by 40 inch duct, that is 881 feet per minute, and the area which we already calculated here, that is 13.33 square feet. So we need to put the values in this equation, the average into area, that is 881 cross 13.33 square feet. So we'll get the actual CFM, 13.33 multiplied 881, so we got 11,746 CFM. 11,746 CFM. So the actual CFM which we got across this duct, 48 inches by 40 inch duct, is 11,746 CFM, and the design flow rate which was in the drawing is 11,700 CFM. This is just an example to show you how to perform the duct traverse. So this is how you can perform a duct traverse to get the velocity pressure from the pitted tube, and then convert this velocity pressure into the velocity, and you need to get the area of this duct, and using this average velocity in this equation you can calculate the actual flow rate across that duct and then compare it with the design flow rate. So this is how you can perform the duct traverse. For more videos, keep watching my channel and don't forget to subscribe.